Welcome to Simplilearn's YouTube channel. We live in a world where data is generated every second, from online transaction and social media interaction to mobile application, IoT devices, and even business operations. However, raw data by itself has a little value. The real value comes from extracting insights, identifying patterns, and making informed decisions based on the data. This is where data science courses come into picture. Data science is one of the fast-growing and most sought-after fields in technology today. It combines programming, statistics, mathematics, data analysis, and machine learning to solve real-world business problems using data. From predicting customer behavior and detecting fraud to powering recommendation engines and forecasting business trends, data science is driving innovation across industries such as healthcare, finance, retail, manufacturing, and technology. In this complete data science course, you will learn how to work with data throughout the entire life cycle. We will start with the fundamentals of data science and gradually move into data collection, cleaning, analysis, visualization, statistics, and machine learning. By the end of this course, you will have a strong understanding of data science concepts, analytical techniques, and machine learning fundamentals, along with practical skills required to begin your journey as a data scientist. Having said that, let's take a look at the agenda for this course. We will start off with Module 1, which is Introduction to Data Science and Analytics Lifecycle. Module 2 is Python Programming for Data Science. Module 3 is Mathematics for Data Science. Module 4 is Statistics and Probability Fundamentals. Module 5 is Data Collection and Data Wrangling. Module 6 is Data Cleaning and Processing Techniques. Module 7 is Exploratory Data Analysis. Module 8 is Data Visualization with Python. Module 9 is SQL for Data Science. Module 10 is Feature Engineering and Data Preparation. Module 11 is Machine Learning Fundamentals. Module 12 is Supervised and Unsupervised Learning Algorithms. Module 13 is Model Evaluation and Performance Optimization. Module 14 is Real-World Data Science Project and Case Studies. Module 15 is Data Science Interview Questions and Answers. Hope I made myself clear with that agenda. That's it. If these are the type of videos you'd like to watch, then hit that subscribe button with the bell icon to get notified whenever we host. Also, just so that you know, if you want to upskill yourself, master data science and data analytics skills, and land your dream job or even grow in your career, then you must explore Simplilearn's cohort of various data science and data analytics programs. Simplilearn offers a variety of master's, certification, and postgraduate programs in collaboration with some of the world's leading universities. Through our courses, you will gain knowledge and work-ready expertise in skills like Python, Tableau, Power BI, Generative AI, and over a dozen others. And that's not all. You'll also get the opportunity to work on multiple projects led by industry experts working in top-tier data and product companies. After completing these courses, thousands of learners have transitioned into a data science or data analytics role as a fresher or moved on to a higher paying job and profile. If you're passionate about making your career in this field, then make sure to check out the link in the pinned comments and in the description box to find the data science and data analytics program that fits your experience and areas of interest. So let's get started with our data science full course with a small quiz. What does EDA stand for? Is it External Data Analysis, Exploratory Data Analysis, Enterprise Data Architecture, Efficient Data Algorithm? Please let us know your answers in the comment section below. Now over to our training experts. Start with the first module, which starts with Introduction to Data Science. Let's begin by understanding what data science really is. Can you observe the visual? It shows data science at the center, formed by overlap of three major areas: mathematics, computer science, and domain expertise. Around that overlap, we also see machine learning, statistic research, and also data processing, which tells us that data science is not just one skill or one tool. It is a combination of logical thinking, computing power, subject knowledge, and also analytical methods working together. That is why data science is much more than simply writing code or building models. It brings together different disciplines to understanding data, discovering patterns, and solve practical problems. A simple way to define it is this: data science is exact intersection where vast information meets modern computing to derive meaningful information, find unseen patterns, or even to solve real-world problems. So if someone asks you what data science is, the best answer is that it is a field that turns raw information into useful insight by combining math, technology, and domain understanding. This gives us the right starting point for the rest of the module. The main idea here is simple. Data is useless in its raw form. It must cultivate through a religious transformation pipeline to yield actionable insights. In other words, raw data by itself does not help much until it properly collected, managed, analyzed, and presented in a meaningful way. That is why a life cycle is divided into 5 important stages: capture, maintain, process, analyze, and communicate. Capture is where data is collected. Maintain is where it is stored and organized. Process is where it is prepared for analysis. Analyze is where patterns and insights are discovered. And finally, communicate is where the final findings are shared in a useful form. This flow shows that data science is not just a single activity but a complete journey. Every stage adds value and each one dependently on previous stages being done correctly. Once this life cycle is clear, it becomes easier to understand the people and the roles involved in making the entire process work. Now let's move into foundation of data life cycle because everything that comes later depends on how well this part is handled. The first stage here is capture. Capture is defined as gathering raw, structured, and unstructured information from diverse sources. The key activities include data acquisition, data entry, signal reception, and also data extraction. So, this is the point where data first enters the systems from different sources and in different formats. The second stage is maintain. Maintain is defined as transforming raw inputs into usable, stable architecture for future modeling. The key activities include data warehousing, data cleansing, data stacking, and also data architecture. This is where the collected data is cleaned, organized, and stored in a way that makes future analysis possible. Together, capture and maintain form the base of the entire data science workflow. If this foundation is weak, every later stage becomes weaker too. Now let's move into the analytical engine of data lifecycle where data starts turning into insights. This part of the life cycle is where the real analytical work begins. The third stage is process. Process is defined as examining the prepared data for patterns, ranges, and biases to determine modeling utility. The key activities include data mining, clustering, and classification, and even data modeling. This stage helps us understand the structure and quality of the data so we can know how it can be used for deeper analysis. The fourth stage is analyze. Analyze is defined as the real meat of the life cycle, predicting futures, testing hypotheses, and finding answers. The key activities include exploratory or even confirmatory data analysis, predictive modeling, regression, and even text mining. This is a stage where data starts answering questions, revealing patterns, and supporting predictions. So, process prepares the data for analytical use, and analyze turns the prepared data into actual insights. Once those insights are ready, the next step is to present them in a way people can understand and use. Now come the final stage of data lifecycle, and that is communicate. Communicate is defined as translating mathematical complexity in human clarity. It also explains that this final step synthesizes the information into readable formats to drive immediate business action. That means the work is not complete when the analysis is done. The real value is created only when the findings are presented in a way that decision makers, teams, and stakeholders can easily understand. The key activities involved here is data reporting, data visualization, business intelligence or BI, and executive decision making. These are the methods through which insights are shared and turned into actions. So this final stage closes the full life cycle by converting analysis into business value. And that is what makes data science practical in real world. Not just finding answer, but making those answers understandable and usable. Now that we have understood the stages of data life cycle, the next question is who actually carries out all this work? That is where the idea of human capital comes in. Data science is too broad, too complex to be managed by a single individual from start to finish. It requires an ecosystem of specialized talent working together in precise harmony. That is where four major important roles are introduced here: data engineer, machine learning engineer, data scientist, and data analyst. Each one plays a different part in a larger data science workflow. The data engineer is responsible for building and managing the data foundation. The machine learning engineer focuses on developing and scaling machine learning systems. The data scientist works on extracting patterns, building models, and solving deeper analytical problems. The data analyst focuses on interpreting data and turning it into business understanding. So, this slide makes one thing very clear: data science is not just a job role, it is a collaborative ecosystem of specialized professions, each contributing to a differently but equally important way. And once these roles are clear, the next step is to see exactly how they map across the data lifecycle. Now let's look at these roles more closely and understand what each one actually does in data science ecosystem. This comparison helps separate roles that are often confused with one another, especially by beginners. Even though all of them work with data, their focus, tools, and final outputs are quite different. The data engineer focuses on infrastructure, scalable big data ecosystems, ETL pipelines. The tools associated with this role include Hadoop, MongoDB, Hive, C++, Java, and the output is clean, accessible, stable data systems. The data analysts focus on data interpretation, mugging, and historical reports. Common tools here include SQL, R, SAS, Excel, and Tableau, and the output is visualizations, dashboard, and business reports. The ML engineer focuses on researching and designing scalable machine learning algorithms. The tools listed include Python, Java, REST APIs, and also A/B testing, and the output is automated, production-ready AI systems. The data scientists focus on predictive modeling, deep learning, and strategic problem solving on unstructured data. The tools include Python, R, deep learning, and SQL, and the output is actionable forecast and advanced insights. So this is clear that the role boundary is much clearer and shows how each one contributes in a different way. Now that the different roles are clear, the next step is to see where each one fits across the data lifecycle. This visual maps the data engineer, ML engineer, data scientist, and data analyst against the main stages of the workflow, which is capture, maintain, process, and analyze, and also communicate. The blue bars make it easy to see that every role has a different area of strength within the pipeline. The data engineer is positioned mainly around capture and maintain, which makes sense because this role is focused on bringing data into the system and building a reliable data foundation. The ML engineer stretches from maintain into process and analyze, showing responsibilities for developing scalable machine learning systems that depend on prepared and structured data. The data scientist is strongly aligned with process, analyze, and even a part of communicate because this role works on extracting patterns, building models, and generating insights. The data analyst is connected around analyze and communicate, reflecting a stronger role in interpretation, reporting, and also presenting findings to support decision making. So the big idea here is simple. Collaboration remains constant, but each role has its own center of gravity within the pipeline. That is what makes the full life cycle work efficiently as a team effort rather than as a single person job. Let's start with a simple situation. Imagine you're running an online business and every weekend you have to decide how much stock to keep ready. If you order too little, you lose customers because products go out of stock. If you order too much, you waste money on unsold inventory. Now, the big question is how do you make the right decision when you do not know exactly what will happen next? This is where probability and statistics enter the picture. Statistics helps us look at the past sales, identify patterns, summarize behavior, and understand variation in demand. Probability helps us deal with uncertainty by asking what is likely to happen, what could go wrong, and how confident we can be in a decision. Together, they help us move from guessing to reasoning. And that is why this topic matters so much in data science. Every time we forecast sales, interpret a survey, evaluate a model, run a A/B testing, or even make a business decisions from sample tests, we are relying on probability and statistics. They help us organize raw data, understand uncertainty, compare outcomes, and also make decisions based on evidence rather than instincts alone. So as we go through this module, the goal is not just to learn formulas, but also to understand how data can guide confident decisions in uncertain world. Now that we have seen why probability and statistics matter, let's understand the journey this module is going to take us through. Everything in this topic can be organized into three connected parts: the known, the transition layer, and the unknown. And that is exactly what this roadmap is showing. We will begin with the known, which is descriptive. This part focuses on raw data that we already have in front of us. The question here is very practical. what happened in our specific data set. In other words, when we collect a sample, descriptive statistics help us summarize it, organize it, and understand its basic patterns. This is where concepts like averages, speeds, and simple summaries begin. From there, we move on to the translation layer, which is the probability. This is where we stop looking at what happened and start asking how data behaves in nature. Probability helps us connect observed data with uncertainty, patterns, and likelihood. It acts like a bridge between the sample we can see and the broader reality we are trying to understand. Finally, we move into the unknown, which is inferential. Here, the question becomes deeper. What truths can be uncovered about the whole? That means we use the sample to make conclusion about large population. So the full journey is very logical. First, we describe what we know, then we understand the uncertainty through probability, and then finally we infer something bigger than the sample itself. This roadmap is important because it gives structure to the entire module and shows how every topic connects to the next one. Let's start with descriptive statistics. Let's understand the difference between descriptive statistics and also inferential statistics. Let's start with descriptive statistics. The goal here is to summarize and organize existing data. Its scope is limited to specific sample in front of you. That means descriptive statistic does not try to go beyond and data you currently have. It simply helps you understand it more clearly. The key tools listed here are mean, median, mode, and variance and standard deviation. And the output is exact numerical facts such as maximum height, an average score, or a measured spread within the sample. Now compare that with inferential statistics. The goal here is to generalize and make predictions. Its scope is much broader because it is connected with entire unobserved population, not just the sample we currently hold. In other words, inferential statistics uses sample data as evidence to say something about the bigger group. The key tools here include hypothesis tests such as t-test, ANOVA, and also chi-square. And the output is not just a summary but the probability and the confidence intervals, which helps us measure uncertainty and make reasoned conclusions. So difference is simple but powerful. Descriptive statistics tells us what the sample looks like, while inferential statistics helps us move from the sample to the population. One explains what we have observed and other helps us make conclusion beyond that we directly observe. That distinction is going to guide everything that follows in this module. Now let's get to know what is descriptive statistics in detail. It is a part of statistics connected with understanding the sample we already have. Before we try to make predictions or draw conclusion about a larger population, we first need to make sense of the data in front of us. And that is exactly what descriptive statistics helps us do. A raw data often looks like chaos. It may contain dozens, hundreds, or even thousands of values, and when we look at it, it is unorganized form. It is difficult to immediately understand what is going on. That is why the first step in statistics is not prediction but summarization. We take raw data and convert it into something structured, readable, and meaningful. This process helps us extract two fundamental truths about the dataset. The first is central tendency, which tells us where the data gathers. In simple terms, this helps us identify the center of the dataset, the point around which many observations are clusters. The second is spread, which tells us how widely the data varies. This helps us understand whether the values stay close together or are scattered far apart. That visual movement from chaos to raw data to ordered, summarized data captures the real purpose of descriptive statistics. We are not changing the data itself, we are changing our ability to understand it. Instead of getting lost in individual observation, we begin to see patterns, shapes, balance, and variation. This is what makes the sample interpretable. And these two ideas, which is central tendency and speed, will guide us the next few slides. First, we'll look at how to locate the center, which is mean, medium, and mode. Then we will measure how much the data varies using variance and standard deviation. Now that we have descriptive statistics help us summarize a sample, the first major question is, where is the center of the data? In other words, if we want one value that represents the data set, what should the value be? This is where the three most common measures of central tendency comes in, which is the mode, median, and mean. The first one is the mode. which is the most frequent observation. This tells us which value appears the most often in the dataset. It is especially useful when repetition matters, such as identifying the most common product size, the most repeated survey answer, and also the most frequent category. The mode focuses on popularity rather than balance. Next comes in median, which is exactly in the middle value, and it is described here as an anchored and robust. That word robust is important because the median is less affected by extreme values. The median still stays centered on the middle position. This makes it very useful in skewed distributions such as income data or even house prices. Finally, we have the mean, which is a mathematical average. It is calculated by adding all the values and dividing by total number of observations. The mean uses every value in the dataset, which makes it very informative but also sensitive to the leverage of extreme outliers. This is why in visual, the mean is pulled in the direction of those extreme points. So even though all three describe the center, they do not always give the same answer. Mode shows what occurs most often, median shows the middle, and also the mean shows the average balance point. Choosing the right one depends on the shape of the data and the presence of the outliers. Once we understand the center, the next step is to understand the other half of the story, not just where the data sits, but also how widely it spreads. Once we know where the center of the data lies, the next question is just as important. How far do the values spread around the center? Two datasets can have the same mean or the same median yet behave very differently if one is tightly grouped and the other is widely dispersed. That is why descriptive statistics is not complete until we also measure variation. This slide introduces two important measures of spread, which is variance and standard deviation. Variance is defined here as an average of all squared deviation from the mean. That means we begin by looking at how far each data point is from the average. Then square those difference and then take their average. Squaring is useful because it prevents position and negative derivation from cancelling each other out, and it also gives more weight to values that are far from the mean. Standard deviation is square foot of the variance. That step is very important because variance is measured in square units but which can be harder to interpret directly. By taking the square root, we return the measurement to the original units of the dataset. That is why standard deviation is often more intuitive and easier to explain. So far, we are focused on what has already happened in the data, which is descriptive statistics. But at this stage, we are still looking backward. We are describing observation that already exists. The next step is to ask deeper question. How do we move from observed data to understanding uncertainty, patterns, and future outcomes? This is where probability enters. Probability acts as a transition layer between data and real world. Descriptive statistics summarizes what has already happened because probability helps us understand the underlying rules that generated those outcomes. In other words, if it is not about just recording results, it's about reasoning from those results. If descriptive statistics tells us a story of a sample, probability helps us understand the logic behind the story. That is why probability is such a powerful concept in data science. So far, we are focused on what already has happened in the data. Descriptive statistics help us summarize the sample, identify the center, and also measure its spread. But at this stage, we are still looking backward. We are describing observation that already exists. The next step is to ask a deeper question. How do we move from observed data to understanding uncertainty, patterns, and future outcomes? This is where probability comes in. Probability acts as a transition layer between data and real world. Descriptive statistics summarizes what has already happened, but probability helps us understand the underlying rules that generate those outcomes. In other words, it is not just about recording results, it's about reasoning from those results. If descriptive statistics tells us a story and a sample, probability helps us understand the logic behind the story. That is why probability is such a powerful concept in data science. It allows us to model uncertainty instead of ignoring it. It helps us ask questions like, how likely is this event? How unusual is this outcome? And what should we expect next if the same process continues? Once we begin thinking in probabilities, we stop treating observation as an isolated facts and start seeing them as outcomes generating by patterns, randomness, and structure. This is also what makes predictions possible. By understanding nature's rules, we can make informed guesses about what may happen next, not perfect certainly, but reason expectation. And that is a major shift in thinking. We move from describing the past to preparing for the future. So, probability is not separated from statistics. It connects descriptive statistics to the inferential statistics. It is a bridge between what we observed in the sample and what we want to say about the larger process behind it. And the next slide introduces one of the most important patterns of probability, which is Gaussian or normal distribution. Now we arrive at one of the most important ideas in all of the probability and statistics, the Gaussian distribution, also known as the normal distribution or the bell curve. A normal distribution is symmetric around its center. Most observations cluster near the center. The values become less frequent as we move away from either the direction. This is why the curve rises in the middle and tapers off towards both ends. One of its most important properties is visible in the diagram. The mean, medium, and the mode all meet at the center in a perfectly normal distribution. That tells us something powerful. When data is balanced with no strong skew, the most of the common value, the middle value, and the average value all line up. This makes the normal distribution a very useful reference model for understanding how real world data behaves. The idea that Gaussian distribution appears in many natural settings is also central to why it matters so much. Many measured phenomena tend to cluster around a central value with relatively fewer extreme observations, and this bell shaped behavior appears across many statistics applications. In practice, not every dataset is perfectly normal, but the normal distribution gives us a powerful starting point for modeling uncertainty and understanding the variation. After understanding the normal distribution, the next important question is this: how do we measure where a specific observation lies within the distribution? That is exactly what z-score helps us do. A z-score tells us derivations a value is above or below the mean of the distribution. In other words, it converts raw distance into standardized statistical distance. The formula here is x minus mu divided by sigma. This means we take an observation, extract the mean, and divide by standard deviation. Once we do that, the value is no longer tied to the original units of the dataset. Instead, it is expressed in terms of standard deviation from the mean. That is why z-score are so powerful. They standardize any datasets and tells us exactly how far a point is from the center, regardless of whether the original units are marks, heights, salaries, or responsive time. A z-score of 0 means the observation is exactly at the mean. A positive z-score means it is above the mean, and a negative z-score means it is below the mean. So a z-score is not just a number, it is common language for comparison across different datasets. This concept becomes incredibly useful in statistics because it converts individual observation to a larger distribution. It helps us identify unusual values, compare scores fairly, and eventually compute probabilities under the normal curve. And that brings us to the next major shift in the module. We are ready to move into inferential statistics, where we use sample evidence to say something about a larger population. So far, everything we have done has prepared us for this shift. We started by summarizing the sample, then measured center, and then spread, and then used probability to normal distribution to understand uncertainty and the distance. Now we take the next major step, which is we move from data we process to the truths we cannot directly observe. And that is the core idea behind inferential statistics. Inferential statistics uses sample data to draw conclusions about a large population whose truly parameters are usually unknown. This slide captures that moment very clearly. On one side, we have sample statistics, which represents the data we actually have in hand. On the other side, we have population parameters, which represents the larger unobserved truth we want to understand. In most real-world situations, measuring the entire population is impractical or impossible, so we rely on representative sample and use it as evidence. But that immediate creates an important question. If we see pattern in sample, Is it real signal about population or is it random variation? If we see a pattern in the sample, it is real signal about the population or is it just a random variation? That is exactly the problem in inferential statistics is designed to solve. It helps us decide whether what we observe is likely reflect of a broader truth or whether it might simply be a statistical fluke. This is where inferential statistics is probability based. Because samples vary, we never know which complete certainty how closely a sample matches the population. Instead, we make decisions using evidence, probability, and formal testing methods. And that leads directly to the next concept, which is hypothesis testing, where we begin to test claims about the unknown population using the sample we observe. Now we come to the heart of hypothesis testing, the null hypothesis and the p-value. This is a point where inferential statistics become a decision-making process. We are no longer just describing data. We are now asking whether the evidence is our sample is strong enough to challenge the existing assumption. We begin with the null hypothesis or HO. This is where baseline assumptions are default position that says that there is no real effect, no meaningful difference, or no relationship. In hypothesis testing, the null hypothesis acts as a starting point that we assume to true until the data provides enough evidence against it. It is not a claim we can try to prove forever. It is simply the position we test against. Then comes in the p-value. The p-value is the probability of obtaining results at least as extreme as the ones we observe, assuming the null hypothesis is true. So the p-value does not just tell us whether the null hypothesis is true or false directly. Instead, it tells us how surprising our observed data would be if the null hypothesis were actually correct. That is why the slide uses the image of a scale. On one side is null hypothesis, the assumed innocent baseline, and the other side is a weight of a new evidence which is represented through the p-value. If the p-value is very small, typically less than 0.05, then observed data will be quite unlikely under the null hypothesis and we reject the HO in favor of the alternative hypothesis, which is the H1. If the p-value is larger, we do not reject the null hypothesis because the evidence is not strong enough. So in simple terms, hypothesis testing is a disciplined way of weighing evidence. The smaller the p-value, the heavier evidence against the null. Now that we have understood the null hypothesis and the p-value, the next practical question is which hypothesis test should we use? In statistics, choosing the right test is not random. It depends on the kind of question that we are asking and the structure of the data we are comparing. This slides focus on common situation, which is comparing groups to find significant difference. If the answer is yes, then the next question becomes how many groups are you comparing? That single decision point is extremely important because it guides us towards the right test. If we are comparing exactly to two groups such as men versus women, treatment versus control, or before versus after, we are typically using a t-test. A t-test is designed to compare the means of two groups and determine whether the difference between them is statistically significant. If we are comparing three or more groups such as East, West, North, South, then we move on to ANOVA, which stands for Analysis of Variance. ANOVA is used when we want to compare means across three or more groups at the same time. This is important because running many separated t-tests increases the chance of false positives, while ANOVA handles all the comparison in one overall framework. Note, these parametric test makes assumptions about the underlying distribution of the data. Essentially, that is approximately normal along with the assumptions like independence and often similar variance across the groups. So this slide gives us a practical decision rule. Two groups used led by t-test and three or more groups led by ANOVA. Next, we'll look at the idea from the previous one and turn it to one more structured comparison. Instead of only asking which test to use, we now look at why each test is used, what variables is expected, and what null hypothesis is tested, and what kind of a real-world question it makes. This makes the distribution between the t-test and the ANOVA much more practical. Let's begin with the use case. A t-test is used for comparing means between exactly two sets of data if you only have two groups. This is usually the direct and appropriate choice. In contrast, ANOVA is also used for comparing means across 3 or more groups. So the number of groups is the first major deciding factor. Next, look at the variables. In both cases, the setup involves one categorically independent variable and one quantitative dependent variable. The difference is that the t-test is categorical variable has 2 categories, while in ANOVA it has 3 or more categories. Now consider the null hypothesis. For the t-test and the null hypothesis is a group. One mean is equal to group of 2 mean. For ANOVA, the null hypothesis is that all the group means are equal to, such as group 1 mean is equal to group 2 mean is equal to group 3 mean. That is a very important distinction between ANOVA test for an overall difference. Somewhere among the groups, not just between one pair. A t-test might ask whether a new drug lowers blood sugar more than an existing drug. ANOVA might ask which region, which is north, south, east or west, spends the most on shopping. So this slide acts like a quick diagnostic chart. 2 groups suggested a t-test, 3 or more groups suggested ANOVA. And since ANOVA is now introduced, the next slide will break down about it. So in this slide, we'll explain the core logic behind ANOVA in the simplest possible way. ANOVA does not just compare group names or look casual at averages. Instead, it compares 2 kinds of variations: within group variance and between group variance. Understanding this key difference is a key to understanding how ANOVA decides whether a result is meaningful. First, look into the within group variance. This is a natural spread or noise inside each individual group. In the visual, each colored cluster has points scattered around its own center, and that spread represents the normal variability within that group. Even when the group are truly similar, there always be some random variation inside them. Now look at between group variance. This refers to how far apart the group means are from one another. In the diagram, the cluster of east, west, north are separated in spaces, and that distance represents between group variation. If the group centers are far apart, it suggests the group may genuinely differ, which is essentially the ratio of between group variance to within group variance. If the distance between the groups is much larger than the noise inside the group, the F value becomes large, and that gives stronger evidence that the group means are not all equal. But if the variation within the group is large and the group means are not very far apart, then we are observe the difference may simple and due to the chance. So the message of this slide is beautifully simple. ANOVA asks whether the signal between 2 groups are stronger than the noise within the groups. If yes, the difference is literally real and not statistical fluke. Next slide brings the full hypothesis testing process together into one connected flow. Instead of treating each concept separately, it shows how descriptive statistics, probability, and inferential decision making work as one engine. That is why this slide is such an important transition point. It helps learners see statistics not as an isolated formula, but as a sequence that turns raw data into validated decisions. The process begins with extracting descriptive statistics. As the slide indicates, the first we calculate measure like mean and standard deviation from the sample. This gives a summary of what the data looks like before and formal testing begins. Next, we move into probability by translating those values into a Z probability distribution where the observed result is standardized into the Z score. A Z-score tells us how far the observed value lies from the expected mean in standard deviation units. And that lets us connect the observation to probability under a known distribution. Once the Z-score is obtained, we use it to derive a p-value. That p-value tells us how likely the observed result would be if the null hypothesis were true. Typically below 0.05, we reject the null hypothesis. If not, we fail to reject it. We do not do the math for its own sake. We use the engine of statistics to transform messy human data into decisions that are more confident, more defensible, and also more evidence-based. So let's see how to code with SQL. SQL follows a specific syntax consisting of keywords, clauses, and operators. We begin with data definition language or DDL to define the structure of the database. We use the create table command to build a brand new table with defined column names and data types. So here I'm using any online compiler. For now, I'm using Programmis. So here there are predefined columns as well. Let me just erase all those. So for creating a new table, the code will be create table followed by the name of the table. So let's say employees. And if you want to add the exact integer and also the heading, you just type in what the column names are. I'll give ID and space. You have to mention what kind of data will be initiated, which is int, suppose, and then comma followed by the next one, which is name, followed by again what kind of characters will be there. It should be var character, and let's give 255 and close the brackets. Next, if any other thing, let's add salary to it. Salary, what's the type? It will be int. So salary int. So salary, it will be an integer. Let's also add department ID. So department ID followed by the type, which is integer. Let's close this and run it. This will create a table with column names as ID, name, salary, and department ID, which has a specific values, which is set. The name character will be absolutely a varchar, and then the ID will be integer, and salary again will be integer, and also department ID will be integer. So let's run this. So as you can see the output, the table employees already exists. So there's already a table called employees. So let's just change this name. So let's say employees table, and let's just run the code. As you can see, we have a SQL query successfully executed. However, obviously we are not printing any query as of now to show the table. Once the structure is defined, we moved on to a data manipulation language or DML. DML is used to manipulate the data stored in the database. We use the insert into command to add our new rows of the data into the table. Now, how do you add values into this table? So here the code will be insert into followed by the table name. I've given it as employees table. And then how do you add values here? So employees space values, and then you can add the value. So here the first one is that we have to enter is ID. So here you can see we have the employees table. So according to that, we can add it. So let's give the first value as one comma, where is employees table here? Then we have to give the name. So suppose the name is Ramesh, and then we have the salary. Let's say 30,000, and then followed by the department ID. Let the department ID be 10. So let's add the values. It's Ramesh and the salary will be 30K, and then followed by department ID, which is 10. So let's just close this up. And then if you want to enter any other values, just copy this, paste this here, and you can just change these values and you will have it. So just you can Control C, enter. And then here you can just change the numbers and name. Let's just change the department ID. Let's keep it 12 and run the sequence. So here's a small correction as well. The var character, which is the name that you have entered, it should be in single quotes. So that's the error. So let's just fix that and run the sequence. So here you can see SQL query successfully executed. However, the result is empty, so we are not going to print the table. To retrieve specific data from tables, we use the select command. We can write queries that domain a where clause to limit the output received based on a specific condition. We can also use order by clause to sort out the output in descending or an ascending order. So let's see an example of that. We are going to select name, salary, from which table? From employees. I've changed the name of the employees table to employees. Where? Again use caps in thing. Where salary should be greater than 15,000. And then you can order by salary in descending order. So if you run this SQL code, employees, so the spelling here is wrong. So let's just run it after sorting that out. So as you can see, we have John Smith and Jane Dan, which is both are having 75 and 80,000, and it is having a descending order, which is 80,000 and 75,000. Often data has missing values. SQL provides single row functions that execute once for each row in a dataset. For example, the NVL function provides a mechanism to convert null values into more arithmetic friendly data values, like converting a bank salary into 0. Now let's take an example of that. So again, we have to select name. So first, since that is already done, we have select name and we have B and enclose it by salary and make it into 0. And then from which table? Again, from employees. Close it up and run the SQL. So NVL is a pre-owned library. You have to install it. So whenever you're using the environment, make sure to install it. We can use aggregation function in select statements to produce meaningful reports. By using the group by clause, we divide the data into groups and calculate aggregated metrics such as an average salary per department. We can also exclude entire groups of data from our results by using the having clause. So let's see an example of that. So firstly, let's select department ID and also average of the salary. From which table? From employees. And then you can group by department ID having average salary greater than 50,000. So we have group, let's put that in caps since it is a code, group by department ID which is having salary more than average salary. Average salary greater than 50,000. So it should give me the department which is having an average salary of more than 50,000 rupees. So again, if I run this, you can see department ID 10 is having an average salary of 75,000. Department ID of 20 is having 80,000. In relational databases, data is naturally spread across multiple tables. We write the select statements and with join clause to access and combine data from more than one table, linking them together based on matching condition. So let's see how this works. First, we have select space e dot name and then space d dot department. And then we have from which table? From employees. Then we are joining these two back. So we have e dot join. Let's put that back. E dot join. Repeat. Department D on E department ID. So on the basis of departments, we are going to merge the department ID as well. So just let's run this. There is a syntax error. Let's just see. So basically you can join two different tables based on one common column and then figure it out the rest. Finally, we use subqueries to solve more complex problems. A subquery is simple, a query nested inside another query. In this example, the subquery dynamically calculates the overall average salary and the main query uses that result to retrieve employees who earn above that average. So let's see how that is done. So we have select name from which column? Which table? Employees, where salary, which is the column that we have given, is greater than select AVG average salary from, again it's from the same table. So let's close it and run the SQL. So let me just close it and run the SQL. And here you can see the name is John Smith, which is having more than an average salary. Now, if you come to the coding languages used in data science, there are two major ones that are used, which is Python and SQL. So let's introduce you to Python. Let's start with variables and string. String can be defined by single, double, or even triple quotes. Since Python strings are immutable, we cannot change the part of a string, but we can easily manipulate the output using built-in methods like lower to make everything in lowercase. So here I'm going to use Google Colab. You can use any other interface as required. And then if you want to initiate a string, we can just say my string and is equal to anything under double quote is considered a string. Hello data science. So I've given a string here. First, let me print this as it is. So here is the running code and let's say print. Just give the name of my string. So that's done. And here you can see it is hello data science. Now if you want to convert into lowercase, we can just add dot lower and then execute it. Now as you can see, the caps have changed to a normal lower class. There are so many inbuilt methods in Python. Make sure to use and explore everything one by one. In Python, data structures form a crust of the language. First, we have list defined by square brackets, and then list which are mutable, meaning we can change the individual element after we create them. Next are tuples defined by parameters. Tuples are immutable, meaning they cannot be changed. Because they are locked in places, they process much faster than list. Then we have dictionaries which are defined by curly braces, which hold unordered key value pairs. Finally, we have sets which are used to store unique, unordered elements. Now let's take a look at everything at one time. So first, let's start with creating a list. Let's say my list, which is 2, 4. List can be mutable, that means they can be changed, but when it comes to tuple, we cannot change. List can be changed, but the values in the tuple cannot be changed. So how do we assign a tuple? We have the name is equal to, instead of square braces, just circle braces and enter the value. Next, we have dictionary. So we have my dictionary where it can store a lot of different values. It doesn't actually have to be a string, it can be a number also. So just give it in curly braces, it works. So I can give name, and also I can give age. I can give number also, like 30. This also works. Now what about sets? Now again, it's the same procedure. Let's give a set also, which is equal to curly braces and then 1, 2, 3, 4. There is no single quote which will convert that to a dictionary. Now coming to conditional statements, which are used to execute code fragments based on a condition. The most commonly used construct is if-else, which allows us to check if a condition, such as determining if a number is even or odd, or even execute the corresponding block of the code. So let's take an example of this. So here I'm just going to give a random number first to start off with. Then I'm going to start with a if condition. I'm checking if this number is even or odd. So if I divide this number with 2, the answer, if it is 0, that means if the remainder is 0, then let's print. What should we print? It is even. Now what else? Else print odd. Now make sure that if and else are in the same format or same space, and then shift enter. Now can you see it is already displaying that it is even. Now change the number to 7 and execute it again. You can see it is changed to odd. This is a simple if statement. Python also features looping construct for iteration. Like most languages, Python has a for loop, which is most widely used method iteration, allowing us seamless cycle through items in list, tuples, or any other advanced data structures. So let's see an example of that. So a simplest example for that is for I. In, let's say, my list, I've already initiated the list, so I don't need to do it again. Print I. I'm just printing I until the condition or the for loop is executed. So let's enter this and it will show an error because I have also not initiated I. For I have missed out on in and shift enter. As you can see, 2, 4, it is printing the list. What is the list here? 2, 4, and it is printing the list here. So this again is the smallest example for a for loop used in Python. As your code grows, you will want to avoid repeating yourself. You can create functions to make reusable blocks of code. We will be using def keyword to define a function, pass a parameter, and return a compute result. For example, if you create a block on calculator or to calculate area, let's create it. Def. Let's say the block is calculated area. Let's keep it small. And what are the parameters that I need to calculate the area, which is length and width. Now a function is ready. Now what happens inside of functions when you have the length and width? let's return the value, which is the area, which is basically length into width. Now, instead of writing the code again from scratch whenever you want this, you can just call this function. Now the coding block is ready. Now how do you call this function? It's basically very easy. Just mention the calculated area, which is the function name which you have mentioned, and pass the parameters, which is the length. Let's say 10 and 5. The area should be 50. So just run it. So here I can see there's a spelling error. Let's find that. And so as you can see, we can get the answer as 50. Now, instead of writing the formula of length into width again and again, you can just give calculated area and your length and the width, and your answer will be there. Again, there is one more point. Instead of writing complex code from scratch, we import libraries. Libraries such as Pandas, which is one of the most useful data analysis libraries in Python and is essential for structured data operations. Using the read.csv function, we can instantly load a static CSV file into the data frame, which is similar to Excel workbook, and view the top rows with the head function. Now let's see how to import this. It's very easy. Import just the name Pandas. Now if you have any CSV or Excel file, just you can upload it or import it from here itself. So what is the definition for that? We have df is equal to pd dot read CSV. If it is an Excel file, just replace the CSV with Excel and give the name, let's say train.csv. If it is Excel, again it will be .csv in single quotes, and this is done. This you are importing the entire CSV or even Excel file. Now it will throw an error because here in Google Colab we need to upload the file before executing any kind of read comment. And also if you want to get the first few of the headers or few of the values of that, just print df.head and you'll be able to get the first initial values of the Excel or CSV file. Real world data is messy, so we must perform data mugging. We use methods like isNull.sum to check the number if the null is missing values in each column. Most modules don't want to work with missing data, so identifying them in the first step before estimating and filling those values wisely. So suppose you already have a table and you want to find the null values or the empty values in the entire columns. So just df dot function and then just give sum so that it counts the number of null values in each column. So if you execute this, you will get a null values list as well. Python is considered one of the most widely used language. Why? Because it has inbuilt functions for everything you require. So make sure to explore every single part of it. This was just a basics of Python, but there is a lot more to it. Now let's talk about data preprocessing and exploratory data analysis from the bridge between the raw data and useful insights. In real-world projects, data rarely comes in a clean and analysis-ready format. It may contain missing values, duplicated records, inconsistent formats, errors, or even unnecessary noise. If this raw data is used directly, the results can become misleading. That is why preprocessing is the first important step. It provides the quality of a data set and makes it suitable for further analysis. Once the data has been cleaned, exploratory data analysis helps uncover the meaningful structure hidden inside it. EDA focuses on understanding distribution, spotting unusual values, identifying patterns, and also observing relationships between variables. This helps us understand what kind of data we have, what problems exist in it, and also what direction the analysis should take. Together, preprocessing and EDA helps separate useful signals from random noise. One prepares the data and the other helps interpret it. These steps create a strong foundation for accurate modeling, reliable insights, and better decision making in the rest of the data science process. Data preprocessing and also exploratory data analysis do not happen in a straight line. They work as a continuous loop where each step improves the other. In practice, data scientists rarely clean the entire data set once and move forward permanently. Instead, they process the data, explore it, discover the issues or even patterns, and then return to cleaning and again with better understanding. Preprocessing focuses on removing noise and improving data quality. This includes handling missing values, correcting inconsistencies, removing duplicates, fixing formats, and even preparing variables for analysis. Once that is done, exploratory analysis begins to reveal the real structure of the data. It helps identify distribution, trends, and even unusual values and relationships between features. That exploration often exposes new problems that were not obvious at first, such as hidden outliers, skewed variables, and also categorical that need to be regrouped. Because of this, preprocessing and exploration feed into each other repeatedly. One pass through the data is often not enough. The dataset becomes more reliable with each cycle, and only when the data stabilizes does it become a valid input for machine learning. This is why data science is described as iterative rather than linear. Data diagnoses are the first step to ensuring analytical quality. Before any modeling can happen, we must identify and resolve the common issue that prevents algorithms from functioning correctly or even lead to biased results. One of the most frequent problems is the presence of missing values or NANs. These represent incomplete records where data is missing entirely. They break statistical functions and algorithms, which generally require a complete set of inputs to perform calculations, making the identification and handling of missing data crucial first task. Another issue involves outliers, which are extreme values that fall far away from the rest of the data. For instance, if you have a dataset of human ages and one entry is recorded as 250, the outlier does not reflect a real biological possibility. Instead, it is an extreme deviation that mathematically skews averages and also variance, leading to an incorrect representation of the truth. Identifying these requires statistical checking or even visual inspection. Finally, there is the problem of dimensional imbalance. This occurs when features in the datasets are recorded or vastly different scales. For example, trying to compare an annual income of 50,000 with a value of 1.5 years of experience in mathematical problematic, as large scale will dominate the analysis. Addressing these issues through techniques like normalizations or scaling ensures fair mathematical comparison across all variables. Handling missing data is one of the most important decisions in preprocessing because it directly affects both quality and dataset size. Missing values, often represented as NAN, cannot simply be ignored. They must be first identified and then handled using method that fits the amount and also importance of the missing information. One option is to drop a missing data. This approach preserves the original truth of the available records because no artificial values are added. It is usually reasonable when the data loss is very small, such as less than 5%, or when the entire column is mostly empty and contributes very little. The trade-off here is that dropping data reduces volume, which may weaken the dataset if too many records are removed. The second option is to impute, which means estimating and filling the missing values. This preserves dataset size but introduces a statistical assumption, so the method must be chosen carefully. For systematically numeric data, the mean is often used. For skewed numerical data, the median is more reliable because it is less affected by extreme values. For categorical data, the mode is commonly used since it fills the gap with the most frequent category. The right choice depends on how much the missing variable matters to the analysis. Dropping the data preserves pure truth but sacrifices volume. Imputing data preserves volume but introduces a statistical assumption. Choose the weight of the missing variable. Now, coming to outliers, outliers are values that lie far beyond the normal behavior of the data and need careful treatment because they can distort the result of analysis. A single extreme value can shift the mean, increase the variance, and create a misleading pattern that do not represent the majority of the dataset. That is why outlier treatment is an important pre-processing step. The first step is to define a threshold that separates normal observation from extreme ones. Once a value crossed that boundary, it is considered a candidate outlier. However, not every outlier is automatically an error. Some unusual values are caused by data entry problems such as recording age as 250, while others may represent rare but legitimate events. This is why domain knowledge is essential. A machine cannot always tell whether an anomaly is a mistake or a meaningful exception. After identifying the outlier, two common solutions are used. One approach is to trim it, which means deleting the record entirely. This is useful when value is clearly invalid. The other approach is to cap it, which means limiting it to maximum or minimum acceptable threshold instead of removing it. This keeps the record but reduces the mathematical impact. The correct choice depends on whether the extreme value is false data or an important but fair observation. Next, we have data transformation. Data transformation becomes necessary when features are recorded on different scale. If one variable is measured in very large numbers and other in very small numbers, algorithms may treat the larger scale feature as more important simply because of its size. Transformation fixes this by bringing feature into a comparable mathematical range. One of the common methods is min-max normalization. This technique maps raw values into fixed range, usually between 0 to 1. It is useful when algorithms requires hard boundaries when the data does not naturally follow a Gaussian or a bell-shaped distribution. The advantages is that every value is compressed into the same interval, which makes comparison easier across variables. However, min-max scaling is sensitive to outliers because extreme values can stretch the range and compress the rest of the data. The second method is Z-square or Z standardization. Instead of mapping values into fixed bounds, it centers the data around a mean of 0 and measures each value in units of standard deviation. This method is often preferred when the data contains outliers and that would distort min-max scaling. Standardization preserves the relative distance of values from the mean, and it's especially useful in models that assume centered or even normal distributed input. The choice between normalization and standardization depends on the data distribution and the algorithm being used. Now, coming to histograms, which is one of the major ways how data is represented. Histograms are one of the most powerful tools for visualizing the distribution and frequency of a single continuous variable. Instead of looking at individual data points, a histogram sorts all observation into discrete intervals or bins. The vertical axis then measures the raw count of increase that fall within each bin, creating a visual representation of how frequently different values occur. This shape is highly informative. It instantly reveals whether the data is skewed, meaning it leans heavily on one side, or whether it follows a symmetric pattern. It also identifies extreme trails where very few observations occur, which is often the point to the presence of outliers. Beyond just visualizing shape, histograms help inform technical decisions during the preprocessing. For example, the shape of the distribution dictates whether you should use the mean or the median to impute missing values. If the data is symmetric, the mean is often a good choice. If the data is skewed, the mean may be pulled towards the tail, making the median a much more accurate and robust estimate for filling in the gaps. By summarization, the entire distribution in one chart, histogram provides a quick, intuitive diagnostic that guides a cleaning process. Now let's get into another visualization tool, which is a box plot. A box plot is a standardized diagnostic tool that provides a 5-number summary of a dataset spread. The minimum, the first quartile, which is the Q1, the median, the third quartile, which is the Q3, and the maximum. This summary gives us an immediate snapshot of the data's central tendency and its variability without needing to look at every individual data point. The central part of the box plot, known as the box, represents the interquartile range, which covers the middle 50% of the data. This range is defined as the distance between the upper quartile, which is Q3, and the lower quartile, which is Q1. By visualizing this middle section, we can easily see how tightly or loosely the majority of the data is clustered around the median. Beyond the summary, the box plot provides an immediate visual threshold for outlier detection. By convention, any data points that fall more than 1.5 times of the IQR distance away from the edges of the box are flagged as potential outliers, represented in a plot as isolated circles. This makes the box plot an incredibly efficient diagnostic for identifying extremes. Furthermore, because it provides such a compact summary, it is a perfect tool for comparing data distributions across different categories side by side. Now let's talk about scatterplot. A scatter plot is used to visualize the relationship between two continuous variables. In this chart, each dot represents a single observation placed along two-dimensional axis where one variable appears in horizontal axis and the other in a vertical axis. In the example shown here, age is plotted against the estimated salary. So every point captures one combined observation of those two values. This type of plot is especially useful because it helps us see whether the two variables move together in a meaningful way. If the point follows an upward pattern, it suggests a positive relationship, meaning as one variable increases, the other trends to increase as well. If they slope downwards, it suggests a negative relationship. And if the points appear randomly scattered with no visible pattern, the relationship may be weak or simply noise. Scatterplot reveals covariance and correlation in a very intuitive form. They help answer an important analytical question: when feature X increases, does feature Y consistently rise, fall, or even remain unrelated? This makes scatterplot essential during exploratory data analysis because they allow us to quickly detect trends, spot unusual points, and even judge whether a relationship is strong enough to be useful for modeling. Preprocessing and exploratory data analysis are not optional steps, but the baseline for predictive truth. The visual moves from raw to refined to understand, which clearly shows the journey of data must go through before it becomes useful for machine learning. Raw data from the real world is usually noisy, incomplete, and also chaotic. It contains errors, irregularities, and also patterns that are not immediately ready for algorithms to interpret correctly. Here we understood that algorithms are mathematically blind. They assume that all the input data is the truth. That means if we feed messy or misleading data into a model, the model does not question it. It simply learns from it and builds patterns based on whatever it receives. That is why pre-processing of EDA are so critical. These steps translate chaotic real-world events into signals that are valid, understandable, and structured enough for the machine to actually learn from it. Preprocessing removes noise, repairs gaps, and also aligns the data, while exploratory analysis helps us understand whether the patterns we see are meaningful. Only after this refinement can the data move from being raw information to becoming understood input that supports trustworthy prediction. Now let's actually see how data preprocessing happens in real world. So for this you need a data set. So you can go to Kaggle and search for whatever data set you require and download it and use that as a data set. So here I'm going with loan prediction. You can go with anything, that's fine. And you can just download anything. So I'll just go with this. So when you open a loan prediction copy of this, you will see notebook, input, output logs. Now, how do you actually download the data? You can go to input and here you can see view the data set. So open the view data set and here you will see an option of download. So just download this and you will get a loan data set.csv. So we can use this data set and run the code. Now again, for running the code, there are two ways any Python would work, any Python ecosystem would work. So either go with Jupyter Python, which is very efficient, and also here I am taking Google Colab since it's easy for me and also it has Gemini integrated in it. So the first part is to upload the file here. So just go here, files. As of now, no file is created. As you can see, we can upload a file to it, upload the same dataset that we have downloaded, which is loan, and it will show you a warning, it's fine. Now, why I'm choosing Google Colab? Because it is an excellent cloud-based Jupyter Notebook environment for data science. Before running this script, make sure to download the loan prediction dataset from Kaggle or even upload the CSV file directly into the Google Colab file directly so that the read CSV command can locate it. So starting as usual for any Python program, we have to import the required libraries. So import the required libraries. What are the required libraries I would require here? Sorry. Here I would be requiring pandas. So import pandas as PD. And then what are the other things? NumPy also is required. Import NumPy as NP. And also for visualization, as it's suggesting, we have import matplotlib.plot as PLT. Now I think these are the basic imported libraries that is required. The next step is to load the data set that we have uploaded here. Now how are you going to do that? Let's see. So the second step is to load the data set. And how are we going to do that? With the help of the pandas. Make sure that the file which has to be loaded is already uploaded in Colab. So here for uploading we need df is equal to pd.read and which kind of file. It is a CSV file here. If it is Excel, go with Excel, and the name of the data, which is loan data.csv, and close the columns, and that's it. You can load your data. Now how do you actually see if it's loaded? Just type in df.head and semicolon, and there you go, it is printed. This is the data that we are having, which includes loan ID, gender, married or not, dependents, educational, self-employment, and loan status. Loan status is at the last, whether yes or no. Now after uploading the data, what is the next step? Second is we'll do a basic EDA, which is exploratory data analysis. So this is the above things are very basic. So let's add a text. Here it is EDA basics, very basics. So the first step in EDA basics is to generate a statistical summary of all numerical columns. So we should have an idea of all the numerical columns, whether which is the highest, which is the lowest, what is the mean, median, standard deviation, minimum, quartiles, and also maximum. So how do you do that? It's very simple. You have only one statement to print, which is df.describe. If you run this, you can see here we have count, mean, standard deviation, minimum 25%, which is Q1. We have Q3 and maximum value of the columns which are numerical data sets. So you can see here income of a person count is, we have around 6,14,000, 6,014,000, and then the average mean is 5,403, standard deviation is 6,109, minimum is 150, maximum is 3,000, sorry, maximum is 81,000, and we have co-applicant income also, loan amount, whatever the loan amount is taken, we have an mean value of 146.412162. So we'll get an idea of what kind of numbers are there, what is the maximum minimum of each column, etc. Now after this is visualizing, which is distribution and outliers. We have to identify the outliers in order to start it. For that, first we are going to plot histogram. Let's say we are plotting a histogram with 50 pins to view the distribution of applicant income. So as you can see, we have applicant income. So let's plot a histogram against this number. So for that, df call the column name. What is the column name? Applicant income without any gap. Dot HIS, which represents histogram, and bin let's give 50, and just run this. There's an error. Let's take a look at it. Sorry, this is histogram, so HIST, and just run it now. As you can see, we have the histogram ready. So as you can see, the income mostly ranges between 0 to 20,000 range here, and many people's range from 0 to 10,000 as well. Very few are there above 30,000, here and there dots. So we can identify the outliers. You can consider these as the outliers and concentrate on this graph, which is majority of the people. Now, what if I have to give a name for this histogram? So just plt.title and give the title name. Let's say distribution of applicants' income. And in some cases, the graph may not come. So for that, just you need to add one more statement, which is plt.show. Here it's coming, but usually in Jupyter Notebook, you need to add the command for the graph to appear. So when you execute this, as you can see, the title is already added, which is distribution of applicants' income. Now let's go with the box plot. Now here let's plot a box plot to visually identify extreme values or outliers in the income data. Now we want to spot the outliers in the income data, which is, let's go up and check income. So applicant's income, this is the section that we are going to see for a outlier. So let's start. Again, it's box plot. So we have df dot box plot, and we have column is equal to applicants income. Make sure the name of the column is similar, or obviously it should be the same. And again, let's give a title to it. So plt dot title box plot of applicants income. Close it, and again, if there is no graph appearing, just add plt dot show. Let's execute this, and as you can see, there is one outlier in 8,000, another one between 6,000, 5,000. Also it is an outlier, and most of them belongs to 10 to 20,000. So I can consider at least these three as an outlier. So you can either remove these values, clean these values, etc. Now let's check. That is the next part. So next part is called data mugging, which is cleaning the missing values. First, you need to check the exact number of missing values, which is the null values in every single column. So for that, there is a statement which is df.isNull.sum. So execute this, and here you can see what are the empty spaces in the entire data set. So we have 13 gender, in the gender column, 13 of the values are null, which is empty. In the married section, we have 3, dependents we have 15, self-employed we have 32, loan amount we have 22, and credit history we have 50 of them missing. Now we know that if we have an outlier, we can either remove it or replace it with mean, median, or mode depending on the type of data. Similarly, if there is missing value, depending on the column which is more important to the loan status, you can identify that and see if you can replace it with mean, median, mode, or if the column is not that really informative, you can go and remove it off. Now, the second option is to fill in, which is impute. So let's say loan amount, we have 22 of them missing, right? So let's fill it up with either mean, medium, or mode. For here is, since it is amount, I feel mean would be more appropriate for it. So how do you fill those values? We have df, again column name. Which column do we want to fill? Loan amount. There is no space, so we are not going to give space. Now fill NA, which is NA in values, with df dot, we have to calculate the mean, right? So call the column, loan amount dot mean of the entire column, and close it, and also keep the in place as true. So let's execute this. There's some error. Let's take a look. Your name true is not defined. The T should be capital, and then run it. So I think it has done the job. So as you can see, before loan amount was 22 of the null values. Now let's see how many are remaining. It should be 0. Let's see. So as you can see, loan amount, everything was replaced by the mean of the column. Similarly, for every column, there should be 0 null values and 0 outliers for more precise machine learning models. The next step is data transformation, which is to apply a mathematical log transformation to the loan amount to nullify the effect of extreme outliers. Now here's how you deal with actual outliers. So again, I'm going to consider loan amount itself. So for that, in a mathematical way, we are going to take the log of the same column. So let's say df and loan amount log value, right? So let's name it log. This is a new column that I'm creating, which will be equal to np.log of the column. What is the column? This is the column. Now this calculates the log of the entire column. Now let's just run this, and it's done. Now it normalizes everything. Not too many outliers will be there. It will be between a certain amount, and it will be like ratio kind of a format. Now let's plot a new histogram to verify that the transformed data now resembles a normal distribution. Now we have already taken a histogram. So let's do the same for the loan amount. Sorry, it's not loan amount, it's loan amount log. This is the new column, right? So let's replace it, and let's say normalization. It should be equal to the Gaussian that we just talked about. Normalizing data. And let's run it. So as you can see, it has a wave to it. It is a normalized data. Let's change the number of bins and see the results also. So as you can see, it is resembling a Gaussian representation, which is equal to a good data values. Now this is all about data preprocessing and EDA. Please check out other data sets, work with that, play with them and understand your data before even going to the next step, which is modeling. Try to replace your none values and also outliers with mean, medium, mode, whichever suits the best. Now, regarding correlation graphs, one of the most important parts of knowing if the column is actually valid or not, you can plot a correlation graph. I forgot it. Now, how do you plot a correlation graph? It is very simple. You just need to do df.corr. df is the data set that we have loaded in. So, I'm just going to get the correlation. So, just type in and execute it. There's an error. Let's see what the error is. Since Colab also has Gemini, it's easy for us to identify the errors and validate it, and also it will get it corrected itself. Okay, so it's showing me to use this, and there is an option of accept and run. So just accept and run. As you can see, there is a correlation. So you have to consider for log amount, credit history. So before that, I forgot to tell you one more thing. We have categorical data, right, in the data set. Suppose here we have yes, no, yes, no. This should be replaced by ones or zeros depending on whichever suits you. And then here you will get the correlation of that as well. So you can see which table is actually useful. And then there is another option called heat map. For that, let's just import Seaborn, since that is the library that is having this heat map. And then we have data, which is df, and then a not true and vigorous. So let's just enter it. There's again an error in it, and let's just ask Gemini to help us. So as you can see, we have column name and the numbers here. It's a little bit scattered. Maybe we can reduce the range or something. So the colors are mostly violet, so it is between 0 to 10,000 itself maximum. So like this, you keep on analyzing your entire data set. You will have an idea of which column is important and which is not. So for the columns where this is not important, you can either drop the entire column, or just the null values, you can drop it down. If the column is very important, just replace the null values with either mean, median, mode, depending on the exact numbers that you want, or you can replace it with whichever number you are comfortable with according to the data that you are preprocessing it. Welcome to this module on machine learning and predictive modeling. As the subtitle says, this module is about paradigms, processes, and also core algorithms, which means we are now moving from data preparation to the stages where machines begin to learn patterns from data and even use those patterns to make predictions. In the previous module, we focused on preparing data properly through preprocessing and exploratory analysis. That step was essential because machine learning does not start with algorithms alone. It starts with clean structure and meaningful input. Now in this module, we will build the foundation and ask a few new questions. Once the data is ready, how can machine use it to identify relationships, detect patterns, and even predict the future outcomes? This is exactly what machine learning is designed to do. It gives systems the ability to learn from examples rather than being explicitly programmed for every possible rule. Predictive modeling then takes that learning and applies it to all further or unseen data. So in this module, we will explore the major learning paradigms, understanding how models are trained, and look at core algorithms that power modern intelligence systems. The next step is to clearly define what machine learning is actually and why it matters. So let's get started. Now we'll talk about the basic taxonomy of machine learning by dividing the field into three major paradigms, which is supervised learning, unsupervised learning, and reinforcement learning. This classification is very important because before we study algorithms, we need to understand the kind of learning problem we are trying to solve. Different machine learning methods are designed for different data types, objectives, and also feedback mechanism, and this slide gives you a high-level map. The first category is supervised learning, which defines as learning from labeled data. In this paradigm, the model is given input data along with the correct output, so it learns a mapping between features and target values. This is commonly used for a task like classification and regression, where the goal is to predict a known label or number of new data. The second category is unsupervised learning, which focuses on discovering hidden patterns. Here, the data has no labels, so the model explores structure on its own, often through clustering, grouping, or even dimensionality reduction. The third category is reinforcement learning, which is like a reward based trial and error. In this approach, an agent learns by interacting with the environment and improving its behavior based on rewards and penalties. So, this slide gives us a full landscape, and the next step is usually to begin with supervised learning, since it is important to direct and widely used starting point in predictive modeling. Let's take a brief look at what is the difference between supervised learning and unsupervised learning. This will help us understand how these two paradigms differ from each of data, goal, algorithm, focus, and real world use. While both belong to machine learning, they solve very different problems. Understanding this distinction is essential because choosing the wrong learning type can lead to a wrong modeling approach altogether. On the left is supervised learning, which is described as method based on labeled data, where inputs are mapped to no outputs. Its core goal is to predict a specific target variable, and its main algorithmic focuses on classification and regression. The example on the other side is predicting a coin currency based its specific weight, which is clear feature to label mapping. This means the model learns from examples where the answers is already known, then applies that learned relationship to a new case. Next, we have unsupervised learning, which works with unlabeled data, meaning there is no predefined output. Its goal is to discover underlying structures and groupings, and the main algorithmic focus is clustering and association. The example given is grouping cricket players into batsmen and bowlers based on patterns in runs and wickets without prior labels. So the key difference is simple. Supervised learning predicts known outcomes while unsupervised learning discovers hidden structure. Now let's talk about one of the most important ideas in machine learning, which is the train test split. We should never mix training and test data because a model must be evaluated on unseen data to prove that it has actually learned patterns, not just memorized the examples it gives. The distinction is critical because the true goal of machine learning is generalization, which means performing well on new data, not just on historical records used during training. Usually, the standard split is 80 to 20 split pipeline is considered, where historical data is divided into two parts: the training set, which is 80% of the data, which is used to establish the mathematical rules of the model. In other words, this is the portions where the algorithm studies patterns, relationships, and also structures in order to build a predictive function. The testing set, which is remaining 20%, is kept separate and used later to verify accuracy on unseen data. This gives us more honest measures of performance because the model has never seen those examples before. So the key takeaway is simple. Training teaches the model, but testing validates whether the learning is real. The next question that would arise would be, why do we need to split the data at all? The reason is written clear. If a machine sees the test data during training, it begins to memorize the noise instead of learning the underlying signal. That is one of the biggest dangers in machine learning because a model may appear highly accurate during the development while actually being weak on new real world data. The first one is memorization, also called as overfitting. In this case, model learns the tiny fluctuations, irregular jumps, and random noise in the training data instead of true pattern. That is why the slide repeat. An overfit model performs very well on the data it has already seen, but poorly performs on unseen data because it has not captured the general structure. The next problem would be generalization, which is the correct objective. Here, the model captures the smooth underlying pattern instead of just chasing every random point. That is why it is a right fit which is robust and pattern based. So that the purpose of the split is not just technical separation, it is safeguard that helps us tell the difference between a model that truly understands the data and one that has only memorized it. Now let's talk about the idea that regression forms the mathematical bedrock of predictive modeling. In other words, before we study many advanced machine learning methods, we first need to understand regression because it provides one of the most fundamental ways a model learns relationship from the data. Now there are two core forms. One is linear and logistic, which represents two essential predictive approaches. Linear regression is used when the output we want to predict is continuous, such as salary, sales, temperature, or even price. Its goal is to find a mathematical relationship between input variables and a numerical outcome, usually by fitting a line that best represents the trend in the data. This makes it one of the simplest and most interpretable predictive models. It helps us understand how changes in one or more feature influence a continuous result. Logistic regression, despite its name, is used for classification problem rather than continuous prediction. It is typically applied when the output belongs to categories such as yes or no, spam or not, pass or fail, etc. Now let's dive into linear regression, one of the most fundamental algorithms in machine learning and predictive modeling. Linear regression finds the straight line that best fits the relationship between the variables in order to predict a numerical output. That makes it especially useful when the target we want to predict is continuous, such as price, temperature, demand, or even income. The equation shown on the slide, which is y is equal to b0 plus b1x, or y is equal to mx plus c. Now, this represents the straight line relationship. Here, x is the input variable, y is predicted output. The slope determines how much the value of y is. Y changes when x changes, and the intercept shows where the line begins. The visual on the right also highlights residual, which are vertical gaps between the actual data points and the regression line. The goal of the model here is to minimize these residuals so that the line represents the overall pattern as accurately as possible. Now, some of the use cases include forecasting stock prices, predicting temperatures, or even estimating a diamond's price based on carat weight. These examples show why linear regression is so important. It transfers patterns in historical data into numeric prediction for unseen cases. Once we understand linear regression, the next logical step is to move to logistic regression when predictions shift from numbers to categories. Now let's dive deep into logistic regression, which is used when a goal is not just to predict a continuous number, but to decide which category an input belongs to. Logistic regression predicts the probability that an input belongs to a primary class and then uses a threshold to convert that probability into a strict category. That is why it is widely used for binary classification problems. The key here is mechanism behind logistic regression is sigmoid function shown as in the graph on the right. The S-shaped curve maps any input a value between 0 to 1, which can be interpreted as probability. The dashed line at 0.5 in the diagram represents the decision boundary or threshold, meaning the values above that point may be classified as class A, while the values below it may be classified as class B. This is how a model turns probability into a final decision. Some of the use cases are spam versus not spam, whether it's a cat versus dog, etc. In each of these examples, the answer is not a number but category. So logistic regression becomes a natural choice. Now let's have a direct comparison between linear regression and logistic regression, helping learners clearly understand when to use each one. Here on the linear regression side, the output type is continuous, meaning it's a model predicts numbers. Its visual shape is a straight line, and the mathematical goal is best fit, usually by minimizing mean squared error. That is why the practical question of linear regression is how much or how many. This makes it suitable for tasks like predicting salary, house price, temperature, or even sales. On the logistic regression side, the output type is categorical, usually binary class labels. Its visual shape is a S-curved or sigmoid, and the mathematical goal is estimate probability and then apply the same threshold between 0 and 1. That is why the practical question here becomes which category, or yes or no. So the type of algorithms which you want to choose depends on the type of answers that you actually want from machine learning. Algorithm's choice is dictated entirely by shape of the target data. In simple terms, the kind of output you need to predict determines which algorithm is appropriate. First, let's take a recap of what the data pre-processing looks like, and then we'll move on to the machine learning algorithms. So as we all know, I've imported all the necessary libraries here. Then we have read the data, installed the data, and we have calculated the null numbers in each of the columns. So as you can see, we have gender, married, and 15 people. Columns are there which are having null values. Now here for loan ID, since this is irrelevant data, loan ID doesn't gives us any useful information. So I'm going to drop that entire column. Next, to replace the null values in gender, I'm going to replace it with the most repeated one, which is the mode value of the entire column. For married, I'm going to again replace it with the most repetitive values. For dependents, again going to consider mode. Self-employed, again mode is replaced. Credit history is also by mode. I've used everything as mode. Here even the loan amount term is replaced by the mode. Coming down here, if you look at loan amount, I'm not going with the mode because we cannot consider it as the mode value since each will have a different value. Here I'm filling it with the mean value, which is the average. Then we come here, we are going to remove the outliers, which is away from the natural data. I have calculated the numeric DF, Q1, Q3, IQR, and then here as you can see, I am replacing the outlier condition as well. So we have a clean data. Next, we are using square root transformation to normalize the distribution. Now, what is normalization of the distribution is basically converting huge amount of numbers into minimum value, which will be in pointwise. So even if the numbers are in lakhs, we'll get it in points. So it's easier for us to compare the values. So here I have used square root transformation. We can use any other model, or we have transformers as well. You can just fit the model and it will give you a normalized table. Next, here I've shown you how to convert the categorical data into the numeric format. As you can see, we have education, self-employed, applicant, not applicant, but we have property area and loan status as the categorical data, which is a group which is, suppose consider education, we have graduate or not graduate. When it is self-employed, it is yes or no. When it is loan status, yes or no. Property area is urban or rural, etc. There are maximum 2 to 3 values. Now, how do you convert these values into numerical format? Either we can go with fitting a model, or you can do that manually. Manually will take a lot of time. So what I've done is I've considered ordinal encoder, where it converts the categorical into the numerical as zeros and ones. So here you can see all the 6 of the columns are here, and this is the code where select the column encoder.fit transform df is equal to the column name, and then before that we have to have scikit-learn and then import the ordinal encoder and then give the encoder as ordinal encoder in brackets. Now if you run this, these values which we earlier saw as categorical value will be converted into numerical value. There you go. Gender as zeros and ones, and education is zeros and ones, self-employed as zeros and one, and finally the loan status as zeros and ones. So this is a normal cleaning and getting our data ready for our next step. Now next step is to define our independent variables, which is x, and dependent target, which is labeled as y. Now here let's consider a minimum amount. Let's consider only 3 column as x, which is the input. So we have x is equal to df. What are the columns that we are going to consider? Let's consider most important one, which is income, applicant, income, and then the next, I think it's loan amount log. I think I don't have the loan amount log, but I have loan amount. So I'll use loan amount, or else you can just go ahead and just calculate the log amount also, that's fine. And then let's consider credit history. credit history, and this will be your X. So let's just run it, and now we need, sorry, let's just run it, and now we need, there's an error. Okay, I think spelling error or something like that. Okay, here I've left a gap. Let's cover that up, and that's fine. Now we have to know our target variable. Now what is our target variable? You all know that it is status, loan status. So we'll just give y is equal to df and loan status and shift enter, and it will be running. Now we have our x and y values. Okay, so the next important step is to test train split the entire data, that which is x and y data. So for that, firstly we have to install the library which is required, which I have already done, which is from sklearn.model selection import train test split. Now after giving this, it's time to split the entire data in 80:20 ratio. Now we have x train, we need to divide it into 4 parts: x train, x test, y train and y test. So let's say x train, x test, and then we have y train and y test is equal to train test, give the x and y values, x comma y comma. Here you have to mention the test size. Here the test size will be 0.20, which is equal to 80:20 ka split. Test size will be equal to 0.20. If it is 70:30, it will be 0.30. After the test size, we need to give a random state. We cannot pick which data will go into the x train, x test. It's a random state. So let's give a random state. Let's say 42, that's fine. And let's run it. So it's done. Our data is separated 80% and 20%. Let's just calculate the length of x train and see. So length of x train, we have 142. Now what is the length of x test? As you can see, it is 36, which is 20% of the data. Now the next part is training the model. Now which kind of model? Is it logistic or is it linear? Firstly, we all know that the categorical data that we are having as y, so we are going to prefer logistic regression. If it was numerical, we would have preferred it to linear regression model. Okay, now how do we fit this model to a linear regression or logistic regression? As per this data, logistic regression is the right way to go by. So before that, we need to again have a library of logistic regression. So as you can see, I've already installed from sklearn.linear model import logistic regression is the thing. And then let's fit this model to the test train split that we have created. So first we have model is equal to logistic regression. And then now we are training the model using the dot fit function. Now how do you fit the model? Here we have model, which is the logistic model which we have given. Dot fit, we have first x train. We are just training the model with x train and y train, comma y train, which is 80% of the data. Now let's execute this. There's an error. Let's see what that is. So here I've given model as logistic regression and then fit the data. So as you can see, the error was basically I had converted the entire loan status into one categorical value. I changed that up to zeros and ones depending on yes or no values. Now the next step is to just make predictions and evaluating, which is confusion matrix. So for that we need specific type of libraries from sklearn. So we have from sklearn metrics, import, accuracy, score, and also confusion matrix. Now let's just run it, and it's already there. Now we'll ask the train model to predict the outcomes for the rest of the 20% unseen test data. Those are predictions basically. So for that, let's just clear this. Okay, anyways, leave it. So for that, it is predictions is equal to model. We are fitting the model again, dot predict, and then we are giving the x test. These were kept aside so that we can test the data. So again, if you press enter, it's done. Now let's calculate and print the accuracy score. Now we are comparing the actual y to the y predict. So we have accuracy is equal to accuracy score in terms of y test and prediction. So if you type in enter, there is a small error, prediction does not exist. So this is predictions. Now the value here is, let's just print accuracy. Here the accuracy is 0.8%. That means we have predicted 80% of the y test data towards the predicted y test values of the machine learning generated outputs. Now at the last step, we are going to print the confusion matrix. Now how do you actually put the confusion matrix? It's confusion. Let's print it first. We have confusion matrix. We are placing it against y test and prediction. Now if you print this, we have 18:33 and 4:130. So here this grid represents the true positives, true negatives, false positives and false negative. So our accuracy is pretty much good enough. 80% is good enough accuracy to proceed with the model. Let's start with the fifth module, which is data visualization and communication. At its core, data visualization and communications are about translating mathematical complexity into human clarity. Data by itself can often feel overwhelming. Large spreadsheets, calculation metrics, and raw numbers may contain valuable insight, but if people cannot understand them easily, the information becomes difficult to use effectively. This is where visualization becomes so powerful. Human beings naturally process visuals much faster than raw numeric data. We recognize patterns, trends, comparisons, and changes more quickly, even though charts and visuals, than through row of numbers. A good visualization helps simply complex information so people can understand what's happening without spending too much time analyzing the data manually. But creating charts alone is not enough. Communication is equally important. The purpose of visualization is not just to display data, but to explain the meaning. A chart should help the audience understand what matters, why it matters, and what actions or insights should come from it. If a visualization looks effective but creates confusion, then communication has failed. This is because especially important in real world environments where people from different backgrounds work with data. Business leaders, managers, analysts, and clients may all look at the same information differently. Effective communications help bridge that gap by making technical insights easier for everyone to understand. In many ways, data visualization is the form of storytelling. It turns abstract numbers into something meaningful, memorable, and actionable. When done correctly, it helps people much faster and more confident decision using the data. One of the most important ideas is data work is understanding that data is useless in its raw form unless it can actually drive business actions. Collecting data alone does not create value. Organizations capture massive amounts of information every day, but the real impact comes from how the information is transformed into understanding and decision making. The data lifecycle usually moves through several stages. First, the data is captured from different sources. Then it is maintained and stored properly so it remains reliable and accessible. After that, the data is processed and prepared for analysis. Once the analysis is completed, insights begin to emerge. But even after all that work, there is still one critical step left, which is communication. This stage is often called the final mile. It's the point where technical analysis must be translated into something people can understand and act upon. If insights remain inside notebooks, dashboards, or technical reports that nobody understands, then the work loses much of its value. A data professional is not only expected to analyze information accurately, but also to explain findings clearly. Stakeholders, managers, and decision makers may not have technical background, so communication becomes the bridge between analysis and action. The ability to simplify complex insights into clear narratives is what makes data truly useful in the real world. This is why communication is considered such an essential skill in analytics and business intelligence. The success of the project is not just measured by only one quality of analysis, but also by whether people understand the results as well enough to make informed decisions from them. Good data visualization is not just about making charts look attractive, it's about making information easier to understand accurately and quickly. Strong visual communication follows a few important design standards that help reduce confusion and improve clarity. The first standard is readability. A chart should be easily to interpret without unnecessary distraction. This is where the idea of maximizing the data to ink ratio becomes important. In simple terms, most of the visual space should focus on the actual data, not the decorative elements. Too many borders, shadow colors, labels, or even extra graphics create chart junk, which makes the audience work harder to understand the message. Clean and simple visuals actually make communication much more effective than overloaded designs. Second is standard clarity. Visualization should represent data accurately and maintain correct mathematical proportions. If scales are manipulated or values are displayed inconsistently, viewers may misunderstand the information completely. Even small design mistakes can change how people interpret trends, growth, or even comparisons. A good visualization helps the audience trust the data because the presentation remains precise and honest. The third is being unambiguous. The audience should not struggle to figure out what is the chart trying to communicate. This is why unnecessary 3D layouts, distorted perspectives, and unusual visual effects are often discouraged in professional reporting. While they may look visually interesting, they can distort perceptions and also make values harder to compare accurately. Ultimately, the purpose of design in data visualization is not decoration, it is communication. Every design choice should help the audience focus on the insight instead of struggling to decode the visual itself. Clean, accurate, and straightforward visuals almost always lead to better understanding and better decisions. One of the biggest goals in data visualization is eradicating ambiguity. A viewer should never struggle to understand what the data is saying. If a chart creates confusion, focus extra interpretation, or distorts value, then the visualization is no longer helping communication. A common example of ambiguity comes from using exclusive visual effect like 3D charts. While these charts may appear visually impressive at first, they often make comparison much harder. Depths, angles, and perspective can distort the actual values being presented. A bar is placed in the background may appear a smaller simply because of the perspective, not because of the data itself is smaller. This creates unnecessary cognitive effort for the audience. In contrast, simple 2D charts are usually much more effective because they prioritize clarity over decoration. When bars shares align baseline, viewers can compare values quickly and accurately. The human eye naturally interprets length more effectively when everything begins from the same reference point. This is why professional dashboards and reports typically avoid unnecessary visual complexity. Direct labeling also improves understanding. Labels placed close to the data reduces confusion and speeds up interpretation. Small design improvements like this can make a huge difference in how quickly information is understood. The broader lesson here is good visualization removes obstacles between the audience and the insight. Every unnecessary effect, distortions, or even decorative feature increases the chance of misunderstanding. Simplicity is not about making visuals boring, it's about making communication precise, effective, and also trustworthy. In professional environments, people rely on charts to make decisions. That's why clarity and accuracy should always matter more than a visual decoration. Effective data visualization always begins with purpose. Before seeing any chart or visual, it's important to clearly define the precise analytical intent of the data. In other words, we first need to understand what questions we are trying to answer. Without that clarity, it becomes very easy to choose visuals that look good but fail to communicate the right insight. Different analytical goals require different visualization approach. One of the common goal is comparison. Here the objective is to evaluate the difference between categories, values, or even groups. For example, comparing sales across regions or performance across teams. In these situations, visuals that emphasize length and align baseline usually work best because they make difference easier to interpret. Another important goal is understanding relationships. Sometimes we want to know whether two variables are connected in some way, or does customer satisfaction improve retention. Relationship based visuals help identify correlation clusters and trends between variables that may not be obvious in raw data. We also visualize to explain proportions. This focus on showing how individual parts contribute to a whole market share, budget allocation, or even population distributions are common examples. The audience is not just comparing values independently, they are trying to understand the composition and contribution within a total. Finally, some visualizations are designed to reveal patterns. These help us uncover trends, cycles, spikes, anomalies, or even changes over time. Pattern focused visuals are especially useful in forecasting, monitoring, and decision making because they help people recognize behavior that may otherwise remain hidden. The important idea is that forms follows function. The chart type should always support the analytical purpose of the data rather than being chosen purely for appearance. An important skill in data visualization is knowing the difference between comparisons and proportions. Even though both involve numeric data, they answer completely different analytical questions and each require a different visual approach. Comparison are used when a goal is to identify the difference between entities. For example, comparing revenue by region, sales by product category, or even performance across departments. In these cases, the audience want to quickly understand which value are higher, lower, or even closer together. Visuals designed for comparisons work best when they use shared baselines and variable length. This is why bar charts are so effective. The aligned starting point allows human eye to compare values accurately and quickly. Proportions focus on something different. Instead of comparing independent categories, they reveal parts of a whole. A common example is market share, where each segment contributes to total percentage. Here, the audience is trying to understand compensations rather than ranking alone. The relationship between the parts becomes more important because every segment contributes to the complete whole. This distinction matters because using the wrong chart can weaken communication. If the goal is comparison, proportion focused visuals may hide important difference between values. On the other hand, if the goal is to explain composition, a simple comparison chart may fail to show how the total is distributed. Good visualization starts by understanding the analytical intent behind the data, that we are trying to compare categories or are we trying to explain how something is divided. Once that question is answered, clearly choosing the right visualization becomes much easier and far more effective. Another important distinction is data visualization is understanding the difference between relationships and also patterns. While both help us explore data more deeply, they focus on different types of analytical insights. Relationships are used to show dependencies between variables. The goal here is to understand whether changes is one of the variable are connected to the changes of others. For example, we may want to study the relationship between age and income, advertisement speed and sales, or even study hours and exam performance. In these situations, the visualization helps reveal whether variables move together, move independently, or show some form of correlation. Charts designed for relationship usually focus on plotting multiple data points across coordinate systems. This allows viewers to observe direction, strength, and clustering with the data. Sometimes the relationship may appear strongly positive, sometimes negative, and sometimes there may not be any meaningful relationship at all. These visuals are especially useful in analytics because they help us uncover hidden connections that are difficult to notice in raw tables of the numbers. On the other hand, patterns focus on something slightly different. Instead of studying dependency between variables, pattern based visualizations help us understand frequency and distribution with the data itself. They reveal the overall shape of the data and help spread peaks, gaps, and even unusual behavior. Histogram and density plots are commonly used for this purpose because they help display how values are distributed. This becomes extremely useful when identifying trends, detecting anomalies, or also understanding whether the data follows accepted behavior. In many real world situations, recognizing patterns is essential before building models or making business decisions. The important idea is that relationship helps explain connections between variables while pattern help explain the structure and distribution of the data itself. As organization grow, the way they communicate data also becomes more structured. Different business situations require different level of detail, speed, decision making and support. This is why visual reporting is commonly scaled across reports, scoreboards, and dashboards, with each of them serving a different purpose. Reports are designed for deep context and detail. They are usually sequential, meaning information is presented step by step in a structured flow. Reports are best suited for comprehensive and historical analysis where users need explanation, breakdowns, trends, and also supporting information. They are often used by analytics managers and leaders and leadership teams when detailed understanding is more important than speed. Scorecards focus primarily on KPI tracking. Their purpose is to measure performance against goals and targets. Unlike reports, scorecards are more performance oriented and structured from a top down perspective. They commonly combine lagging indicators while measure post results with leading indicators, which helps predict future performance. This allows organizations to monitor whether they are moving in the right direction strategically. Dashboards are designed differently. Their primary goal is high level orchestration and immediate operational insights. Dashboards are usually more constrained because they prioritize speed, visibility, and quick interception. Instead of deep analysis, dashboards help us monitor current conditions, identify issues quickly, and support fast decision making in day to day operations. Understanding the difference between these formats is important because each serves a unique business need. Report provides depth and scorecard provides performance measurement and dashboard provide rapid operational awareness. Choosing the right reporting medium help organization communicate insights more effective and support better decision making at every level. One of the biggest challenges in dashboard design is managing cognitive load. When users are presented with too many charts, matrices, and visual elements at the same time, the dashboard becomes difficult to interpret. Instead of helping decision making, it creates confusion and slows the understanding. This is where the dashboard rule of 7 becomes important. The idea behind this rule is that the dashboard should contain a maximum of around 7 major visual objects or focus areas. Human attention is limited and people can only process a certain amount of information effectively at one time. When too many elements compete for attention, users struggle to identify what matters most. A good dashboard creates hierarchy. The most critical lagging indicators should appear on the top because they usually represent the most important business outcomes. This placement naturally guides users' attention towards the highest priority information first. Supporting visuals and operational details can then be organized into separate zones below. Another important principle is consistency. Each zone should use purpose driven chart selection based on the type of insights being communicated. Trends are easy to understand through line charts, bar charts, and also summary metrics through KPI indicators. When visuals are chosen internationally, users can interpret information faster with less mental effort. Dashboard should also separate information logically instead of placing everything together randomly. Organizing matrices into clear sections improves readability and helps users navigate information more naturally. An effective dashboard is not just the one with most data. It is the one that communicates the right information quickly, clearly, and without overwhelming the audience. Simplicity, hierarchy, and focus design are what makes the dashboard useful in real world businesses environment. This is module 4 demo. In module 4, our model generated a raw text based confusion matrix. Handling a raw grid of numbers to a business executive usually causes confusion. Today, we are going to translate those mathematical complexities into professional, easy to read, executive visual using Seaborn. Now, the first step is to visualize the confusion matrix as heat map. So, let's just see if heat map is already there. Seaborn is already there, so I don't need to import it again. So, if not, just import the Seaborn. Seaborn is a powerful Python data visualization library built on top of Matplotlib that makes graphics look higher professional for business stakeholders. Next, we'll import the Matplotlib, which is this one. Now, this is to control the size and display of our visual figures. Next, from Scikit-learn, we need to import the metrics import. So, let's do that. So, here we can import the Scikit-learn. So, from sklearn, import confusion matrix, and let's just run it, and it's imported. Now, why do we import this confusion matrix? We use it because function to evaluate where our classification model made correct predictions versus errors is identified using this. Now let's just import that. We have cm, which is equal to confusion matrix, and then give your y test and predictions, and let's just run it. We calculated the confusion matrix by comparing the actual holdout test with data, which is the y test, against the predictions our model just made. Now let's plot this up. For that, you just need to type in plt.figure, and in the braces just give the fig size, which is whichever size you prefer, which is equal to, let's say for me 6,4 is fine, and let's just run it. We set the size of our visual figure to 6 by 4 inches to ensure it is readable. Now, how to plot SNS heat map? So let's say we have SNS, right? So SNS dot heat map, and give the access to that, which is confusion matrix, comma, and note is equal to true, comma, FMT is equal to D, and comma, CMAP is equal to, let's say, blues, and execute this step. So as you can see here, it has given us a confusion matrix. This is the core visualization step. We generated a two-dimensional heat map, which is a note is equal to true and FMT is equal to D, which ensures the actual whole numbers are printed inside the squares. The C map is equal to blues. Oriented applies color variations where dark blue separates instantly draw the executive's eyes to our success zones, which is true positives and true negatives, while the lighter squares represent errors. Now let's just name the title as, let's say, plt.title, known prediction, and confusion matrix. So let's just press enter after this. And as you can see, there will be a title which is loan prediction. There was an error in spelling. It says fix that. And there you go. You have a heat map to display to the people. We added a clear title as well to our chat so stakeholders know exactly what they're looking at. Now let's say we have to add an X label. So for that, enter PLT. Now what is the name? We can give predicted as well. Predicted. And then let's say PLT dot Y label and print actual. And then if required, we'll just print show. PLT.show. Now let's execute this. There's an error. Now can you see we have an X label as actual and predicted as a Y label. So the graph is more clearer which is predicted and which is actually the values that is printed. Finally, we display the rendered heat map to the screen. Now step 2 is visualizing feature importance as a bar chart. For that, let's start with importance is equal to model coefficient, COEF, and bar. We grab the exact names of our columns, which is applicant income, loan amount, and also credit history, so we can label our chart. So again, we'll start with plt.figure and fig size. I'll give it a little bit bigger so you can see the difference. Let's say 8,5. Now here we have to create a new slightly wider figure for our next visual. Next we have SNS dot bar, and then we are introducing features in that. So we have X is equal to feature, and then Y is equal to importance. And then also let's give a palette also. Palette is equal to, let's say, viridis. Now, when you want to illustrate comparisons between different categories, a bar chart is an absolute best choice. We pass our features into the x-axis and their extracted weights to the y-axis using professional color palette. So after this, the next step is to put on y label and x label. So we have plt.y label and let's say importance.
and in brackets coefficient, which is coefficient and weight. This should be my y label. Next, let's plot the x label as well. Now, what should be the x label? Let's just say fetus. And then finally, it is plt dot. And now let's execute it. There are some errors in fixed size. So just explain error. So as you can see, the bar graph, we have a x-axis, y-axis, and we have a title as well. So here, can you see the differentiation of the palette as well? So step 3 is going to be the execution role play, which is the conclusion. Clear the code cells from the screen so that only the heat map and the bar charts are visible side by side. For the final part of this course, we are going to role play. You are lead data scientist presenting your findings to the bank's board of directors. You would point to the screen and say, executives of our goal was to automate loan approval safely. As you can see from the dark blue zones of the heat map, our predictive models automates this process with high accuracy. Furthermore, looking at our bar chart, the model reveals that we should prioritize marketing to applications with existing credit history. And with that, the executives approve your model for deployment.
Let's move on to Module 6, which focuses on model deployment and operationalization. Building a machine learning model is only a part of the overall life cycle. In many real world projects, creating the model is actually not the hardest part. The bigger challenge is talking about the model and making it usable in practical environments where real users, applications, and even business systems can benefit from it consistently and reliably. This is where deployment becomes important. Model deployment is an important process of moving a trained machine learning model into a production environment so it can start making predictions on real world data. Instead of remaining inside a notebook or experimental setup, the model becomes part of an actual working system. Operationalization goes even further. It focuses on maintaining, monitoring, scaling, and managing the model after deployment. A model may perform well during deployment, but real world conditions consistently change. Data distribution shift, user behavior evolves, and even system requirements grow over time. Because of this, deployed models need continuous monitoring and updates to remain accurate and useful. This module explores how machine learning systems move experimentation into production ready solution. It becomes concepts like serving models through APIs, integrating models into applications, managing infrastructure, tracking performance, and also handling issues such as latency, scalability, and also reliability. In modern AI systems, success is not measured by only how accurate a model is during a training period. A successful model is the one which can operate efficient in real environments, deliver prediction consistently, and continue creating value over time. That is why deployment and operationalizations have become essential skills in machine learning and AI engineering. One of the most important mindset shift in machine learning happens when moving from a notebook to the real world. During development, models are usually built and tested in controlled environments. The data is clean, static, and historical. Everything runs locally, experiments are repeatable, and achieving high testing accuracy often becomes the primary focus. Inside a notebook, the workflow feels predictable, data is already available, dependencies are controlled, and model only needs to perform well under expectational conditions. But it does not fully represent real production system. The real world is very different. Instead of static historic data sets, production systems deal with continuous live data streams. Data arrive constantly, often with inconsistency, missing values, noise, or even unexpected patterns. Models must operate inside complex software ecosystems where multiple services, databases, APIs, and applications interact together. Another major difference is accessibility. A model may achieve excellent accuracy during training, but if it uses or systems cannot actually access it, then it creates zero business value. This is why deployment is so critical. Deployment is the act of freeing the model from the notebook environment and making it available for real world use. Once deployed, the model becomes a part of an operational system. Applications can send requests, receive predictions, and use those predictions to support decisions, automations, recommendations, or even business processes. At that point, machine learning stops being just an experiment and starts becoming a functional product. Understanding this difference is essential because real world AI is not about building accurate models. It's about building systems that are accessible, reliable, scalable, and also capable of delivering value continuously outside the deployment environment. Model deployment introduced a major paradigmic shift in how machine learning systems are designed and evaluated. During development, most machine learning work happens inside a local Jupyter notebooks. These environments are ideal for experimentation because they allow data scientists to test models, visualize results, and also iterate quickly. But production systems operate very differently. In development environments, models are usually trained using static CSV batches or historic datasets. The data is fixed, predictable, and already available before training begins. In production, however, systems often process real-time JSON streams where data arrives continuously from applications, users, sensors, and extreme services. This means the model must handle income requests dynamically instead of working with preloaded files. Evaluating those also changes significantly. In notebooks, success is often measured using static accuracy scores such as predictions, recall, and overall testing accuracy. While these metrics are important, they are not enough in production systems. Real world models require continuous health monitoring because performance can degrade over time. Factors like data drift, changing user behavior, or even infrastructure issues can affect how well the model performs after deployment. Even the overall goal changes. During experimentation, the focus is usually on finding historical patterns in the data and improving model accuracy. But once deployed, the priority shifts towards serving real time users' requests reliably and efficiently. A production model must respond quickly, remain available under heavy usage, and integrate smoothly with other software systems. This shift is important because production machine learning is no longer just a research program. It becomes an engineering problem as well. Success depends not only on building intelligent models but also on creating systems that can operate continuously, scale effectively, and also deliver predictions reliably in real world environments. Deployment is a process of integrating a machine learning model into a live production environment so it can receive real time inputs and also return actionable prediction. This is the stage where models moves beyond experimentation and becomes part of an actual working applications or even business system. A deployed model must be able to interact with real users, applications, or even services continuous. Instead of manually testing predictions inside the notebook, the system now receives requests automatically and generate outputs in real time. This allows machine learning models to support recommendation systems, fraud detections, forecasting automation, and many other real world use cases. One important concept is deployment is containerization. Containerization involves encapsulating the module and its dependencies into secure and uniform operating environments. Tools like Docker are commonly used for this purpose. Containers help ensure that the model behaves consistently across deployment, development, testing, and production system. With containerization, difference in software version and environments can create unexpected failures during deployment. Another critical component is web frameworks. A deployed model is often wrapped inside a server architecture that listens for incoming requests and returns predictions. Web frameworks help explore the model through APIs so external systems can communicate with it effectively. This allows applications, websites, or mobile platforms to send data to the model and receive responses instantly. Next, we have scalability, which is strategies are also essential in production environments. As usage increases, the deployment systems must handle larger volumes of requests without slowing down or falling apart. Model deployment architecture are designed to support scaling and redundancies so services remain available even during heavy traffic or system interpretations. Deployment transfers machine learning from an isolated experiment into a reliable operation services capable of creating real business value. One of the most important components in model deployment is the API bridge. APIs or application programming interfaces act as a communication layer between the user's application and the machine learning model. Without the bridge, most real world systems would have no practical way to interact with deployed models. The process usually begins with user interface. This could be a website, mobile application, dashboards, or even another software systems where users provide input for a request prediction. For example, a customer may upload an image, type the message, or even submit the transaction details. The application then needs a way to send this information to the machine learning model. This is where the API becomes essential. The API acts as a messenger between the application and the model. It receives requests from the web application, translates the data into format the model understands, and forwards it to the machine learning system for processing. The model then performs its task using the trained algorithm. Depending on the use case, it may classify data, generate predictions, determine anomalies, and also recommend product or even perform some other intelligent operations. Once the prediction is generated, the result is sent back through the API to the application. Finally, the user interface displays the actionable answer to the user in a simple and understandable way. From the user's perspective, the process feels almost instant, even though multiple systems are working together behind the scenes. The API bridge is critical because it allows machine learning models to become accessible and usable within the real applications. It connects software systems with AI functionality and enables machine learning to operate as a part of scalable real world products and services. Now, operationalizing a machine learning model means turning it into a usable service that can handle real world requests automatically. One of the most common way to do this in Python is by using Flask, which is a lightweight web framework often used for deploying machine learning models through the APIs. The first step is loading the model. After training is complete, the model is usually saved as a file so it can be reused later without retraining every time the application starts. When the Flask application runs, the pre-trained algorithm is loaded into the memory and becomes ready to generate predictions. The next step is setting the endpoint. An endpoint is essential a URL where external system often can send requests. Flask allows developers to create routes that listen for incoming data. In machine learning applications, these endpoints are commonly designed to receive post requests because users or applications are sending data to the server for predictions. Once the request reaches the servers, the application extracts the data. Most modern applications exchange information using JSON format because it is lightweight and easy to process. Flask retrieves the income JSON data and converts it to a structure the machine learning model can understand. After pre-processing the input, the model executes its prediction logic. Depending on the application, this could involve classification, regression, recommendation, and any other machine learning tasks. The generated prediction is then prepared for delivery back to the user or application. Finally, Flask returns the results as a response, usually in JSON format. This response travels back through the API and becomes available to application interface most instantly. This workflow is important because it transforms machine learning models into accessible services that can support real-time applications, automation systems, and scalable business solutions. One of the biggest misconceptions in machine learning is believing that deployment is the finish line. In reality, deployment is only the beginning of model's real-world lifecycle. Once a model enters production, it immediately starts facing conditions that are different from the historical data it was originally trained on. Machine learning models are built using past data. During training, the models learns patterns, behaviors, and relationships that excited at the point in the time. But the real world is constantly changing. Customer behavior shifts, market conditions evolve, business processes change, and also external events introduce new patterns that may not exist in the original training data. As these changes occur, the model's predictive accuracy naturally begins to degrade. This problem is commonly known as the model drift or data drift. A model that performed extremely well during the testing may slowly become less reliable over the time because the environment it operates is no longer matches the environment it learned from. This is why production machine learning requires continuous monitoring. Teams must track performance matrices, monitoring prediction quality, identifying usual behavior, and retain models when necessary. Without monitoring, organizing may continue using models that are slightly making increasingly inaccurate decisions. Operational machine learning is therefore not one time task. It becomes an ongoing life cycle involving maintenance, evaluating, updates, and improvement. Successful AI systems are not simply deployed and forgotten. They are actively managed to ensure they remain accurate, relevant, and also reliable as conditions evolve. Understanding this reality is essential because real world AI systems must adapt continuously if they are expected to deliver long term business value. Model deployment does not end with making predictions available to the users. Once the model is running in production, it must be continuously maintained and monitored to ensure it remains reliable, accurate, and stable over the time. This is a critical part of operational machine learning. One of the most important areas of monitoring is tracking. Technologies such as ELK stack, including Elasticsearch, Longstash, and even Kibana, are commonly used to collect logs and diagnose production issues effectively. Another major focus is monitoring prediction, accuracy, and latency. Accuracy monitoring helps determine whether the model is still generating reliable prediction in real world conditions. Latency monitoring measures how quickly the system responds to requests. Even highly accurate models can accurate poor user experience of the predictions take too long to return. Production systems must therefore balance both intelligence and performance. Model maintenance also involves comparing prediction outcomes against actual real world results. This is one of the most effective ways to detect model drift. Over the time, the relationship between the input data and real outcomes may change, causing prediction quality to decline. By continuously evaluating prediction against reality, teams can identify when the retaining or updating the model becomes necessary. Operational AI systems require ongoing attention because real world environments are dynamic. Successful machine learning systems are not static deployments. They are actively monitored, maintained, and improved so they can continue delivering consistent business value even as conditions change over the time. Machine learning models are not meant to remain unchanged forever. As real world conditions evolve, models must also evolve to maintain accuracy and reliability. Repeat. As real world conditions evolve, models must also evolve to maintain the accuracy and reliability. This ongoing improvement process is commonly known as retaining the loop. The cycle usually begins with monitoring performance. Teams continuously track prediction, accuracy, and system behavior using dashboards and monitoring tools. The goal is to identify performance drops, unusual trends, or even signs of model drift as early as possible. Since production environments change over time, monitoring becomes essential for maintaining trust in models' predictions. The next stage involves assessing new data. Production systems constantly generate fresh real-world data from users, applications, and business processes. This new data often contains patterns that were not present during the original training phase. Collecting and analyzing updated dataset helps teams understand how the environment is changing and whether the model is still reflects current conditions accurately. Once enough updated data is available, the model can be retained and fine-tuned. During this process, the machine learning algorithms are rebuilt using the newer datasets so the model can learn more recent patterns and behaviors. Fine tuning may also involve just hyperparameters, improving pre-processing steps, or refining feature engineering techniques to improve overall performances. After retraining, the updated model must be validated and redeployed carefully. Teams need confirm that the newer version actually performs better than the previous one before replacing it in the production. This helps to avoid introducing unstable or lower performing models into the live system. The retraining loop highlights an important reality of operational AI. Machine learning is not a one time project, it is a continuous life cycle of monitoring, learning, and improving, and also adapting to changing real world environments. The operational life cycle of machine learning system goes far beyond simply training a model. In real world AI system, deployment is not just a destination, it is beginning of continuous operational life cycle that requires monitoring, maintenance, and consistent improvement. The process usually starts with training the model inside a notebook environment during this stage. Data scientists prepare datasets, build algorithms, evaluate performance, and optimize accuracy. This is where the foundational intelligence of the system is created. Once the model is ready, it is wrapped inside the API using frameworks such as Flask. The API acts as a communication layer that allows applications and extreme systems to send requests and receive predictions. This step transforms the model from a research artifact into a usable service. After that, the model is deployed into production environments, often using technologies like Docker containers. Deployment ensures the model can operate consistently across systems and support real world applications reliably. At this stage, the system begins serving user requests using real time JSON data or other live inputs. But the lifecycle does not stop after deployment. Production system must continuously monitor health and performance. Teams track predictions, quality, latency, uptime, and also system behavior to ensure everything remains stable and accurate. Over the time, models begin experimenting drift because real world conditions evolve. When drift is detected, new production data is collected and used to retain the model. The updated model is then redeployed into the production, restarting the cycle once again. This continuous loop is what makes operational machine learning different from traditional software systems. AI systems must learn and adapt continuously to remain effective. Successful deployment is not just about launching a model once. It is about maintaining a living system that allows alongside the environment it operates in.
A machine learning model is only valuable if it can be accessed in the real world. Now let's train the model to save and deploy its live web application programming interface, which is an API using Python's Pickle and Flask libraries. So the first step here is to freeze and save the model. Now what is the code for that? Follow as well. First things first is to import Pickle, and next is to save the trained logistic regression model to a file. So we have with open, let's say loan model dot pkl. This is the pickling model, and then followed by wb, which is a file. Next we'll dump it. So we have pick dot dump model comma file. And next, if this is successfully there, we'll just print done. So let's execute this. So there is a error. So let's fix it. And there is one thing I'm missing. So let's fix that. And here we go. Still there is an error. Let's check what is an error. You can use Gemini also to figure out what the error is. So there was a space here, and let's just accept the mistake and run it. And the model is pickled. As you can see, you will see this loan model pkl. Just download this file to the app file, which you can create a new folder and you can just download it. Now it's downloaded in my downloads. I'll just copy this and paste it in my app folder. So I have an app folder where I have a file which already has the code, which I'll be explaining it soon, and paste it over that. Before we leave our notebook, we must save our trained model so that we do not have to retrain it from scratch every single time a new customer applies for a loan. To do this, we use Python's pickle model. This process of freezes our trained logistic regression model and saves it in a file. In this case, loan model PKL is that can be easily loaded into our web application. So the next step is to building the Flask and web API. So firstly, you need to create a notebook or Python IDE or any kind of blank text editor like VS Code or PyCharm to create a new script named AppPy. Now, what is the code inside that? Let's take a look at that. So firstly, here we are starting out with importing Pickle and NumPy, which are like the required libraries here. Then we are creating a Flask app, which is AAP is equal to Flask name. Then we are loading the pre-trained model here, which is model is equal to pickle.load, pen, and the model name. Next, the step 3 is to create prediction API, which is a router API and the prediction function. Next, we have df predict. Now here you can see we are extracting features from JSON post request where data is equal to request.getJSON post is equal to true. Next, we are organizing the data again here, and also adding the features, which is the application income, loan amount, and also the credit history. And the final features, we have put it in an array. And the last step, we are making the prediction using the loaded model. Now, what is a loaded model? It's pickle. So we know that. And then we have the last, which is prediction is equal to model.predict, the final feature. Next, we are convert prediction in human reliable JSON response. So here we are giving a command of approved if prediction is equal to 1, else denied. And then we are returning the loan status output. And lastly, we are run the live application, which is if name is equal to main, run the app. So let's just run this model and see what are the issues or if its system is running or not. So how do you run this? Again, command prompt and just check the location, copy it and cd location, enter, and then you have to give Python and the app.py. So it will take some time to execute. There's a warning, but Flask app debug It's fine. It's just a warning. So finally, what happens here is it'll ask the loan amount to be approved, your name and other details. So the model will calculate if your loan is approved or denied based on the information that you have provided to the model. And with that, the final deployment, we have successfully taken raw, messy data and turned it into a automated, intelligent business application.
So let's start by understanding what exactly is data science. Well, data science is a blend of statistics, programming, and domain expertise. It's about extracting insights from the data to help solve complex problems. Think of it like a detective story, but instead of solving crimes, you're solving business problems using that particular data. You take raw data, clean it, analyze it, and present the findings to make informed decisions. So now you must be thinking, why is data science so important today, especially in year 2026? Here, data science is not just an option, it's the necessity. From AI to big data, companies are using data to predict trends, automate decisions, and personalize customer experiences. Whether it's improving healthcare with predictive models or increasing sales using targeted recommendation, data science is the engine behind it all. So here is a quick question. Can you think of any app or website that rely on data science to work? If yes, drop your thoughts in the comment section below. Now, let's look at some real-world applications of data science. Data science is used in several sectors, like healthcare, where it helps doctors predict diseases, personalize treatments. Second, it is often used in finance, where it is used for fraud detection and risk management. And last but not the least, it is often used in retail sectors, where companies like Amazon and Netflix use data to recommend products based on your preferences. Now that we know what data science is and why it is important, let's talk about the tools you will need. Every data scientist works with tools to clean, analyze, and visualize that data. So let's look at the key ones. And the key tools are Python, Jupyter Notebook, and Anaconda. So first, let's talk about Python. It is the most popular programming language for data science because it's easy to learn and has lots of powerful libraries in it. Next is Jupyter Notebook, where you will write and run your Python code. It allows you to mix the code and documentation, which makes it perfect for data science projects. And last is Anaconda. It is a package manager that simplifies the installation of Python and all the libraries we need for data science, like NumPy, Pandas, and Matplotlib. Have you already installed Python, Anaconda, and Jupyter Notebook in your system? If yes, then it's great. You can easily skip this part, and if not, then don't worry. Just follow along and you will be up and running in no time. So now let's begin by installing Python first. For this, visit your default web browser. Here, type Python. Here you will find the official website of Python, that is www.python.org. Click on this particular website. Here, go on download section and you will find the latest version of Python, that is Python 3.14.3. So click on this. This will particularly download the exe file of the Python. Click on this. Because it is already installed and updated in my device, that is why it is showing this. In your case, it will show install. So click on install and all the required packages will get installed in your file. So just to verify the installation, you need to go here on your command prompt, click on command prompt, and just to verify the installation, you need to type Python --version. And this will give you the correct installed version of Python. And this particular command shows that the Python has been successfully installed in your device. Now, we will learn how to install Anaconda in your system. So for this, go on the official website of Anaconda, click on Anaconda. Here, click on free download option. Here you will be finding get started. So here you need to click on get started button. And here you need to sign up with your email. So just do it accordingly. Here you will find whether you want to download for your Windows, your Mac or Linux. So choose, most probably it is for Windows, so choose Windows, accept your cookies. So here you will find the Windows 64-bit installer. So download. Now it's being downloaded. And check here, one download in progress. Anaconda file is being installing. Just wait for a few seconds. And it's done. Click on this. Once the Anaconda is being successfully installed in your device, the icon will be visible here. See Anaconda Navigator. Click on this. Click Next. I agree. Next. And then the path. See, it will take a bit time to get started. So once it is started, you'll show all the pre-installed libraries here. Here you'll find Jupyter Notebook. See. So from here, we can launch our first Jupyter Notebook. Click on this. Here's the interface of Jupyter Notebook. Here you will find all the files, that Python files and CSV files, all your files. Here, you can click on New, Python 3. A new kernel will open. And here you will begin writing your first Python code. So this is the particular cell we'll write our first code. So the basic and the universal code, which is print hello world. And just to run this particular code, click on this run command. Or you can even press Ctrl plus Enter. So the code is being run properly and the output is being displayed on the screen. Hello world. This is how you can create your first program in Jupyter Notebook. You can even rename this file from here. See. So here you can give the file name as, let's suppose, sample, and .ipynb is the default extension for the Python file. So you can rename it from here. See, it got renamed to sample file. Here you can run your code cell by cell. So this is how you can create your first Python program, and you can even practice more. It will eventually improve your coding skills in Python. So now let's start with coding. Now that we have our environment set up, it's time to get familiar with the basics of Python. Don't worry if you're a complete beginner. I'll walk you through it step by step. First of all, we will talk about basic and one of the most important concepts of Python, that is a variable. A variable is a container for storing data. For example, x is equals to 10. Means that we are storing the number 10 into variable x. Python has different data types in it, such as integers that contains whole numbers, for example, 5 or 100. Then comes float. So floats are the decimal number, for example, 3.14, 9.8 or something like that. It comes under float category. Then comes string. So string is nothing but text which is closed whether into a single quote or a double quote. For example, data science or Python that is enclosed in single quote or double quote, it will come into the category of string. Now comes boolean. Boolean is nothing but a true or false value. So these were some few basic examples of variables in Python. Now let's consider and move forward towards conditional statements and loops. So now let's look at conditional statements. So here, first of all, we will assign the value 11 to the variable x. Then we will give a condition which is if x is greater than 10. If x is greater than 10. Then if it is true, then we will print x is greater than 10. Else x is less than or equal to 10. Equal to 10. So this is a basic coding just to check the conditional statement, if and else. Please check the indentation. It is very important in Python. Now we will run this code by clicking on this icon. And boom, your output is on the screen. X is greater than 10 because we have assigned 11 to the x. So eventually x is greater than 10, so the output has come, which is correct. So this was all about conditional statement. You can practice more. It was just a basic about it. Now we also have loops to repeat the actions. For instance, a for loop runs code multiple times for each item in the list. So now let's look at one of the basic examples of loop in Python. So here we will write for I in range 5 and then we will print I. Please take care of indentation. It is very important in Python or else your code will not run without error. So this is the code to run the program where it will take the numbers from 0 to 4 because in Python or in computer science, index always starts from 0 and the print statement will print the current value of I. So now let's run this code. Let me run it again. And boom, the output is on the screen. So numbers are 0, 1, 2, 3, 4 because we have iterated it from 0 to 5. I mean 1 to 5, so it will take from 0 to 4 because the index always starts from 0. Next we have functions. Functions helps you group code that you will reuse. For example, let's define a function, or I can say a simple function to add two numbers. So let's do it like this. We'll go back to our Python notebook and we'll write the code here. So we will do it like this. Write def add numbers a comma b, and then we will return a plus b, that is the sum of two numbers. Then we will store this result into the result variable. We have passed these two numbers as the argument. You can even take the input, but for now I'm taking the number as direct inputs only. And here we will print. So now let's run this code. I hope it will run without an error. There is a syntactical error. I forgot to put this colon. Now I will run it again and the output is on the screen, which is 8. Means we have passed two numbers, that is 5 and 3, and the sum is 8. Now let me explain this code to you. So here def is used to define the function, and the function name is add numbers. And here a and b are the two input values. And this function is returning the sum of these two numbers. And the output is being stored into the variable called result. And at last we are printing the sum as result. So that's it. So this is how we can perform different operations in Python. Finally, we will learn how to interact with users. So you can ask for the user input using input function and display the information with print function. So I'll show you how you can do this. So now we will check the demo of how to take input using this code. So first of all, we'll type name is equals to input. What is your name? And then we will write print hello enclosed in single quotes because it will come as it is on the screen, and then the name which is being entered by the user itself through keyboard. So let's run this code. It's asking us for a name, so I'm giving my name and pressing enter. So it is printing the output as follows: hello Stuti, and there's no space in this, so we will give the space from here. Then we will again run. Again I'm giving the name, and the name is being coming with a space. Now it is more presentable. That is why we have rerun this particular code. Let's get into the exciting part, that is working with data. In data science, we use two amazing tools that are NumPy and Pandas. So let's begin by understanding what is NumPy. So Python is a powerful language, but when it comes to handling large amount of data, normal Python list cannot do it, or it becomes slow. This is why NumPy comes in. NumPy stands for Numerical Python. It is a Python library used for fast and efficient numerical computing. NumPy provides a special data structure called an array, which is faster and uses less memory than a Python list. With NumPy, we can perform mathematical operations like addition, multiplication, finding averages, and matrix operation without using loops. Because of its speed and efficiency, NumPy is widely used in data science, machine learning, and much more. Now let's look at the working of NumPy from here. So first of all, we will install the NumPy library, and the command to do the same is !pip install NumPy. So this command will automatically install NumPy in this. Because I have already installed, it is being showing requirement already satisfied. But in your computer, it will get installed without any hurdle. Now we will import this NumPy library which we have installed. So the command for this is import NumPy as NP. Here NP is just the short form for NumPy. Now we will print the version of NumPy just to check or verify whether it is being installed successfully or not. Print np dot underscore then close. This particular command shows the installed version. So run this particular cell, and then it is showing 2.4.2. It's been successfully installed in our device. Now let's start working with NumPy. So now let's look the basic operations of NumPy, which is array. So again, we are importing import NumPy as np arr, which is the name for our array. np.array is 1, 2, 3, 4. We have predefined our array. So now let's perform the addition of the arrays. So for this, we will create array 1, which is arr1 is equals to np.array 1, 2, 3, and then we are giving second array that store values as np.array 4, 5, and 6. Then we are adding these two arrays and storing the result into the result variable. So we'll do it like this. Result is equals to array 1 plus array 2. And we will print result. Run this following command from here and see. The output has come as 5, 7, and 9. And it has added all the values element wise, which means 1 is added with 4, 2 is added with 5, and 3 is added with 6. So array 1 plus array 2. This is how you can perform different operations using numpy. Why numpy arrays? Because a numpy array stores numbers in a structured way and is faster than Python list. Another reason is you can perform math on the entire array at once. Try doing this with a normal list, and I'll bet on it that it won't work the same way. This is called element-wise operation. You can even try other operations like subtraction of two arrays, that is array 1 minus array 2. You can even try multiplication, which is array 1 multiplied by array 2. More you will practice, more you will learn. So now we will check working with Pandas data frame. Well, numpy is used for numerical calculations, but working with real-world data like tables, rows, and columns can still be difficult. This is where Pandas come in. Pandas is a Python library used for data manipulation and data analysis. It allows us to work easily with structured data such as Excel sheets, CSV files, and databases. Pandas provide two main data structures, that is series and data frame. And in this video, we will be working with Pandas data frame in detail. A data frame is like an Excel table with rows and columns, making data easy to read, clean, and analyze. Using Pandas, we can clean missing data, filter rows, sort values, group data, and perform analysis efficiently. Because of this, Pandas is widely used in data science, machine learning, and analytics. In simple words, Pandas helps us turn raw data into something meaningful information. So now let's look at the working of Pandas itself. We will create a new cell. And then first of all, just as in the case of NumPy, we have installed the NumPy library. Here we will do the same. We will install the Pandas library. So the command for the same is pip install Pandas. And we will run this particular cell because I already have it in my system. That is why it is showing requirement already satisfied. But in your case, it will get installed by this command. If you want to verify that whether it is installed successfully or not, give this command import pandas as pd dot underscore version. Run this particular cell. So this number indicates it is being successfully installed in our device. Now let's start working with Pandas. Here you must be wondering about what is PD. It is nothing, just a short name for Pandas. So now we will enter the database in which we will perform our further operations. So this is the data on which we will perform the operations. It does contain 5 columns which suggest ID, name, age, score, and date. And the values are as follows. And you can see this none value, which means it is null. There is no value in it. This we will use further to remove the duplicate rows. So that is why we have kept some null values in our data set. So this data is a dictionary right now. Now we'll try to convert this dictionary into data frame with this command. The command is as follows. df, which is the short form for data frame, and we will print this data frame. Now we will run this particular cell and see, we have our data in the form of data frame and not dictionary. This is how you can convert your dictionary data into a data frame. And here you can see the indexes, that is 0, 1, 2. It's being included automatically here. This command will make the data look like the Excel table. You can even see on the screen, it's looking like an Excel table. And this table is being visible because of this command, which is print command. Now we will convert this data frame into CSV file, and the command for the same is this. So this command will convert this data frame into a CSV file called students.csv. So let's run this particular cell. And here your data frame will be converted into CSV file. And where we can check it, just give me a second, I'll show you. See here, on our home page, we have a file called students.csv. You can open this file and you can see the file is being stored into the CSV format and it is looking like an Excel table. You must be thinking about what is CSV file. So CSV file is nothing but a file where the columns are being separated by comma itself. You can check the delimiter here. It's comma. It means it is successfully converted into CSV file. See, students.csv. So this is how we can convert our data frame into CSV file. Now we will look at importing from CSV. So to import from CSV, the command is as follows. So from this command, you can import data from CSV file. So this line, which is df.toCSV, it reads data from CSV that is stored in the file called as students.csv. This following command helps us read the data from CSV file, which is students.csv. And this print command will print the data and convert it back into data frame. And the data frame is stored in df.csv. So let's run this particular cell and see the data is back in the form of data frame. So this is how you can import data from CSV file. You can see the head word. So this head shows the first 5 rows of the table. We have already inserted just 5 rows, but if in case there are more rows, then this head will show only first 5 rows by default. So this is the functionality of this head function. Now we will check how we can perform data selection and filtering on this data. So what if you want only few columns from this data set? Let's suppose just we want name and score. We can do it by this following command. So this command will select only 2 columns from your table, that is name and score. And you can give any of the columns according to your own choice. For example, I'm using these 2 columns, name and score. Then when we will run this particular cell, the output is as follows. Just name and score is being displayed on the screen and not the complete data set. So this is the functionality of this particular command. You can select the specific columns as per your requirements. So now we will learn about filtering the data. You must be thinking about what is filtration. So sometimes we need data, some specific data. Let's suppose we want to display the data where the score is greater than 80. So we can perform this particular thing through this code. Just look at it. The command for the same is, let's suppose we want to, for example, we want to filter out the rows where the high score is greater than 80. So we will do it like this. High score is equals to df. Now we will print high scorers. So let me explain this line to you. You must be thinking, what is this df score? So this particular command will sort only the score column from the data set. It means it will only point out to this column, and this greater than 80 will check the condition. And all the data will be printed where the score will be greater than 80. So let's run this particular cell and see. You can check the output where the scores are just 85, 90 and 88, which means they are greater than 80. So all the rows that satisfies the condition are only printed on the screen and other rows are being eliminated. Now we will perform filtering on the rows with missing scores. So the command for the same is missing scores. So this is the command for the same. Here is null, checks for the missing values that are the null values in our data set, which is denoted by NONE, none. So let's run this code. So let's look at the output on the screen. We have got the data where Bob has null score. So it is being showed here and other values are being ignored. Now we will try to filter the duplicate names. For example, we have a duplicate name called David in our data set. Look here. So we will try to remove this duplicate value. So the command for same is, it's df, then df name, where name is equals to David. So now let's run this cell and the output is correct. So here's how we can filter out the duplicate columns. So we have duplicate values as David in our file. So this is how we can get the duplicate values. So it will filter out the rows where name is David. Now we will check another example for filtration so that it will become more clear for you. Here we will filter out the age which is greater than 30. So we will write the command for the same. I'm copy pasting the command. So this particular command shows students whose age is greater than 30. Let's run this code. See, you can check we have only one data where the name is Charlie and his age is greater than 30. This particular row has been come as the output because it does satisfy the condition we have given. So that's all for filtering part. So in nutshell, we can say filtering means showing only the rows that match our given condition. Whatever condition we give in our coding, if it does match, then the output will be displayed according to that condition itself. So now we will see how to handle the missing data. Here we will fill the missing values with 0 and the command to do the same is df.fill NA with 0. Here the null values will get replaced by 0. Run this command and see, wherever we have the null values or the none values, it is being replaced by 0. You can see here on the index 2nd and the last index. Now we will see the command to remove these null values. Here we have replaced it. Now we will see how to delete it or to remove it. This is the command to remove the duplicate values from our data set, and we will be keeping just the unique values. So when we will see the output, see, David is being removed from our data set and only one time David is being printed. So in nutshell, it keeps only the unique records. Now we will see data type conversion. It is also one of the most important thing into Python. So please look into it very carefully. Now we will check how we can convert the data types. So the command to do the same is, here in our database, date is into text format and we have converted it into date time format using this particular command. Which means that this pd.toDateTime will convert our date from text to date type. See, our date which was into text format is now converted into date format. This particular output indicates the same. Now let's talk about scaling and encoding. When we work with real-world data, different columns often have different ranges and some columns contain text instead of numbers. Machine learning models cannot handle this directly, so we use feature scaling and encoding. Feature scaling is used to bring all numerical values to a similar range. For example, in our data, let's suppose the age has small values like 20 or 30, while salary has large values like 20,000 or 80,000. Because of this difference, the model may give more importance to salary just because the numbers are bigger. To solve this, we will use min-max scaling, which converts the values into a range of 0 to 1. The smallest value becomes 0 and the largest becomes 1, and all other values fall in between. This ensures that age and salaries are treated fairly in the model. So now let's understand this with an example. So come back to your Jupyter notebook. Here to perform this feature scaling, we will use the database like this. Remove this part, I'm importing the database. So this is our database where we will see feature scaling and encoding. Here, age and salaries. These two values are far different from each other. Age has some small values and salary will be having some large values. So eventually it will give more importance to salary, but we will solve it using the feature scaling, or we can say min-max scaling. Now we will print this data frame. We will run this code. So this has come into the table format where the data is being stored into the form of rows and columns, or we can say Excel format. Now we will perform min-max scaling on this particular dataset. To perform min-max scaling, first of all, we need to install scikit-learn library. You must be thinking, why scikit-learn? So the reason is simple, because min-max scaler belongs to the scikit-learn library itself, that is sklearn. So let's install it into the system. The command to do the same is pip install scikit-learn. Again, it is already installed in my system. That is why it is being showing requirement already satisfied, but it will get automatically and successfully installed in your system using this particular command, pip install command. Now let's begin the code from sklearn.preprocessing. So this is the command to do the same. This particular command will help us to bring the age and salary into the same range. So let's run this particular code. Okay, we have forgot to print the data frame. So let's do it with this. See, you can see in the output, age and salary are being converted into zeros and ones so that it could come in under the same category and could be treated equally, and none of the values get extra weightage. Age and salary have been scaled. All values are now between 0 and 1. The smallest value becomes 0 and the largest value becomes 1. And the middle value becomes 0.5. So the youngest age is 0, oldest age is 1. That's how it will work. And same logic applies for the salary. This helps the computer treat age and salary equally. So now you must be wondering why city is still in the text format. Because scaling works only on numbers. And city will be converted into numbers using encoding. Now let's understand what is encoding. Machine learning models cannot understand text data like city names. So we convert categorical values into numerical forms. Using one-hot encoding, we create separate columns for each category. For example, the city columns become city underscore Delhi and city underscore Mumbai, where 1 means yes and 0 means no. So let's check this where we can see, you must be wondering where is 1 and 0. So we'll check it here in our Jupyter notebook. Let's get back to the Jupyter notebook. The command for the same is tf is equals to pd dot get underscore dummies. Now this particular command will help us convert the text, which is city, into numbers. And it will also create separate columns for each city. So let's look into the output first. See, whatever we have said, it is being generated the same way. So you must be thinking that city Delhi and city Mumbai, the data is being categorized. It is fine. But their values are coming as true and false and not 0 and 1. So I think you know, by default in computer science, true means 1, that is yes, and false means 0, that is no. Internally, machine learning models treat true as 1 and false as 0. So functionality is same as 0 and 1. It doesn't matter. So now after scaling and encoding, the dataset becomes completely numerical and ready for machine learning. So in simple words, scaling balances numbers and encoding converts text into numbers. Now we are going to talk about data visualization, one of the most exciting and important parts of data science. Wondering why? Because once you analyze your data, the next step is to show insights in a way that it is easy to understand. And that's where visualization comes in. Data visualization means showing data using charts and graphs. When we look at data in tables, it is hard to understand. But when we use graphs, we can understand the data quickly and easily. In Python, data visualization is used to see patterns, trends, and comparisons in data. For example, we can see which value is high, which is low, or how data changes over the time period. Matplotlib and Seaborn are the two Python libraries that allows us to create stunning visuals. In simple words, data visualization turns number into pictures so human can understand it better. Now let's talk about two powerful tools we will be using for data visualization. That is Matplotlib and Seaborn, as we have already discussed. Both of these are Python libraries that allows us to create stunning visuals, but they have their own differences. So let's look at it. Matplotlib is like the Swiss Army knife of data visualization. It is very flexible and can create almost any type of chart you need. But sometimes it can be a bit tricky to make things look really pretty. So here comes Seaborn. So Seaborn is built on the top of Matplotlib and is a bit more user-friendly. It makes it easier to create beautiful complex visualizations with just a few lines of code. So now let me show you the demo, how we can create bar charts, line graphs, scatter plots using Matplotlib and Seaborn libraries. Now let's first start by understanding bar charts. A bar chart is great when you want to compare values for different categories. You can use bar charts for comparing anything like revenue by month, population by country, and much more. So let's look at a basic example in the Python Jupyter notebook. So here we are creating bar chart. For this, first of all, we will need to install. So let's start by installing Matplotlib library, which is one of the most important libraries if you want to create stunning visuals, as we have already discussed. So the command for the same is this. It's exclamatory pip install matplotlib, and we will run this command. Because I've already installed it in my system, so this is showing requirement already satisfied, but in your case it will be successfully installed. No issues in that if you will correctly run this command. Now we will import this Matplotlib library. It's being imported. So this is the data set we will work upon, and using this data set we'll be creating the bar graph. So it does contain students and marks. So in total we are having 5 records. Now we will start plotting the bar chart. Now this particular command will create the bar chart. Now we will label the x-axis and y-axis using this command. Just plt.xlabel students and then plt.ylabel, which is to be marks. Copy pasting this. Now we will give the title to this bar chart, which is as follows: plt.title, and it will be like marks of students. It's done. And then the particular command which will show the bar chart. So it is as follows: plt.show. So simple. Don't forget to put this braces. Now I'm running this particular code and let's see if the chart comes. See, boom. Our bar chart has came on the screen. It does have all the labels where the title of the chart is marks of students, and then the x-axis being labeled as students and y-axis being labeled as marks. This is one of the most appropriate way to create a bar chart. Now we will start with a line graph. So a line graph is used to show the change over time. It helps us to see trends, like whether something is increasing or decreasing. Let's understand it with an example. So let's begin with another cell. Let's again import this Matplotlib command. So this is the database we will be working upon. In this example, we are showing website traffic during the week. So the traffic belongs to different days of the week, whether Monday, Tuesday, Wednesday, Thursday, Friday, and so on. Now let's start plotting the line graph. plt.plot days, traffic. Now we will add the title for this line graph. So this particular command will help us creating and adding title for this line graph, which is plt.title. Now we will be adding the labels. I'm sorry, it has been come without labels. Let us correct it first. Remove this. Actually, remove this. It was run like unknowingly, so remove that. Now we will try to add the labels. So this particular command will add x label and y label, and then we will show, or we can say print, the line graph on the screen. This is the code for the same. So the command for the same is plt.show. And let's run this code now. And hopefully a stunning line graph will be displayed on our screen. So here's how the line graph looks like. Now we have the title of the line graph as website traffic over the week, and the X label and Y labels are being marked efficiently and correctly. So this is one of the best ways to create the line graph. What do you think this graph is showing? So this graph tells us website traffic is increasing each day. The upward line shows positive growth. So in a nutshell, we can say a line graph helps us understand how values change over the time. Now, without wasting any more time, let's talk about scatter plots. So a scatter plot is used to display the relationship between two variables. For example, let's visualize how hours of study affect the exam scores. So to do the same, we will again import this matplotlib file. It will work without importing also because we have imported it once, but it is better to import it again. So it is the data we will be working upon, which does contain hours and scores. Now we will be creating scatter plots. It is a good practice to keep mentioning the comments. So make it a habit to mention the comments after every line. Now let's create the scatter plot, and this is the particular command to do the same. It is plt.scatter hours and scores. Now we will add titles and labels, and the command is plt.title study hours versus exam scores. Now we will be adding label. So this is the command to add labels. X label, which will show hours of study, and Y label, it will show exam scores. Now we will show the plot, and the command for the same is plt.show. See, the scatter plot has been came on the screen. The scatter plot has come on the screen as we have expected it to come. So here, each dot represents one student. You can see these blue dots. So it represents each student. And more study hours indicates more exam scores. So we can say scatter plots help show relationship between two variables. Can you think of something you'd like to visualize using a scatter plot? Maybe how much sleep you get and how your energy levels are? If yes, let us know your thoughts in the comment section below. Now let's move to advanced visualization that helps us understand how different variables are related to each other. One very useful visualization is a correlation heat map. A correlation heat map shows the relationship between numerical variables. It tells us how strongly two variables move together. For example, we may want to understand the relationship between age, height, and weight. A heat map helps us to see whether these values increases, decreases, or are not related to each other. We create the heat map using the Seaborn library. So now let's look at it, how we can do the same. So first of all, for this, we need to install the Seaborn library. So it's pip install Seaborn. Let's run this code. I'm sorry, the spelling of install is wrong. So let's run it again. Same, this command will automatically install Seaborn library in your device. Now let's start with the coding part. Import Pandas as PD. Now import Seaborn as SNS. Now we have imported matplotlib file and an example dataset on which we will be performing our code. So the dataset includes age, height, and weight. And it will convert, this particular line of code will convert the dictionary into a data frame, as we have discussed previously. Now we will create the correlation heat map. So this particular command will create the correlation heat map. Now we can add the title by giving us plt.title correlation heat map, which is our title. And then we will show. Now we are running this code. See, the correlation heat map has been arrived on our screen as we have expected it to come. This is giving you the visual representation of how age, height, and weight are related to each other. Here, number inside boxes. You can see here the number inside boxes. It shows the correlation values. Value that is close to 1, it indicates strong positive relationship. Values that are close to -1 indicate strong negative relationship. And value close to 0 indicates weak or no relationship. So this is how you can basically visualize the data and see how they are related to each other. Finally, let's discuss some best practices for data visualization to ensure your charts are not only clear but also effective in communicating the data. So, the first point is keep it simple. Don't overcrowd your visuals. Focus on one message at a time. Second is label everything. As we have shown in our example, always label your axis and give your charts a title. This will make it easier to understand what the chart is showing. The third one is choose the right type of chart. Use bar charts for comparisons, line graphs for trends over time, and scatter plots for relationship between variables. Avoid misleading scales. Ensure your data scales are consistent and not manipulated to give a false impression. Last but not the least, use color wisely. Colors should enhance your data, not distract from it. Stick to simple color schemes. Remember that visualization isn't just about making things look pretty. It's about making your data clearer and easier to understand. Alright, we have covered a lot already. Now let's dive into statistics. Statistics is the foundation of data science. As a data scientist, understanding the underlying patterns in the data is the key. In this chapter, we will explore some of the most essential statistical concepts you will need to know. Let's start with the basics. So let's start by understanding mean first. This is the average of a set of numbers. To calculate it, we sum all the numbers and divide by how many they are. Let's look at a quick example. So we have the number as 2, 4, 6, 6 and 8. So the mean for the following number will be adding all the numbers, then dividing it by the count of numbers we are having. So we are having 5. So eventually the output will come as 5.2. This is what basically mean means. Now let's talk about median. So median is the middle value when the data is arranged in the proper order. So let's look at the example again. We are using the same set of numbers, which is 2, 4, 6, 6 and 8. So you can see this data is being arranged in a proper order, or we can say ascending order. Now we will find the median as 6 because it is the middle number of this data set. As you can see, 6 is the middle number. So this is what median is all about. Now let's talk about mode. The mode is a number that appears most frequently. So in our data set, you can see 6 has been repeated mostly, or we can say 6 is being repeated twice. So the mode of this data set will be 6. Now let's talk about standard deviation. So this tells us how spread out the numbers are in the data set. If the standard deviation is low, the data points are close to the mean. If it is high, they are spread out. So the standard deviation tells us how spread out the numbers are. The formula of standard deviation is quite complex, but Python can easily calculate it for you by using numpy.std function. So using this numpy.std, you can easily calculate standard deviation. Now let's talk about probability. Probability helps us predict the likelihood of an event occurring. For example, if you toss a fair coin, the probability of its landing heads is up to 50%, and probability of landing it to tails is another 50%. So, probability is essential when building predictive models in data science. Now let's discuss about distributions. A distribution shows how data is spread across different values. So basically, there are two types of distribution, and that are normal distribution, and the second one is binomial distribution. So now let's first understand about normal distribution. So a normal distribution looks like a bell-shaped curve. You can see here on screen, a bell-shaped curve is being visible. So here you can see most values are concentrated around the average and fewer values appear as you move away from the center. It is commonly seen in real-life data such as heights, exam scores, or salaries. Now let's talk about binomial distribution. So a binomial distribution is used when there are only two possible outcomes, such as success or failure, or heads or tails. It helps calculate the probability of getting a certain number of successes in a fixed number of trials, like flipping a coin multiple times. So there are probably two outcomes in it, either heads or tails. Can you think of a real life situation where you would use probability or distribution? Please let us know in the comment section below. Now let's understand about histograms and box plots. A histogram shows how often values fall within a certain ranges. For example, if you plot a histogram of a student marks, you can easily see how many students scored between 60 to 70 or 70 to 80 or so on. This helps you understand patterns like whether most values are high, low or spread out. So now let's understand it with a code. So now let's code it in our Jupyter notebook first. Now let's start by understanding how we can plot this histogram in our Python file. So let's start with the coding part. So first of all, we will import the matplotlib library. So this particular command will import the library. This is the sample data we will be working upon. So it does contain marks. Let's start coding to create histogram. plt.figure, and then this particular command will create the histogram where we have given marks. Bins is equals to 5, h color is equals to black. Now we will add titles and labels to our histogram. So as I told you earlier, make a habit to give the comments to make the code more explanatory. Now we will write plt.title. We will give title as histogram for student marks. Then we will mark labels. So this particular command will mark our x label as marks and y label as frequency. And then we will display our plot. Hashtag display plot. And we will write plt.show function to show the histogram on screen. So let me explain this once. We know each histogram has a bar. So bar used to create the histogram. So each bar represents the frequency, that is count of marks in the specific range or bin. Now you must be thinking about what are bins. You can find here bins is equal to 5. So the bins are the range. So the range is divided into intervals called as bins, and the bin is equal to 5 as we have given into our code. So this parameter means there will be 5 intervals for this data. You can even change the number to adjust the number of bins. And now you can find here frequency. See here. So frequency is the height of each bar, shows how many marks fall within each bin. Now let's run this code. The histogram has been printed on our screen. So this histogram shows the distribution of the student marks. The x-axis represents the interval of the marks. For example, the range between 50 to 60, 60 to 70, 70 to 80, then 80 to 90. And the y-axis represents the frequency of students falling within each interval. You can see here. This is our y-axis and this is our x-axis. So the most frequent marks range is around 90 with 5 students in that particular range. You can see here. The longest bar shows the most students fall into the category of 90 marks. And the fewer students have marks in the lower range, that is 50 to 60. You can see it has the lowest bar. It means the frequency is just 2. The data is skewed towards higher marks, indicating better overall performance in the sample. Now let's understand about box plots. So a box plot shows the overall spread of the data using minimum, maximum, median, and quartiles. For example, with employee salaries, a box plot can quickly show the typical salary range and highlight outliers, such as someone earning much more or much less than others. Let's look at the example code for box plot. So we have imported the same data so that we can create the box plot. Give the comment as now create box plot. It makes the code more explanatory, so it's good to use comments. plt.figure plt.box plot function, which should has marks in it. Now we will be adding title. So plt dot should be like box plot for student marks. Then we will give labels. So here we are marking Y label as marks. There's no need for X label. I'll show you why. And now we will display the plot. Plot.show. Now let's run this code. Hopefully it will run without an error. See, we have just mentioned y-axis and there was no need for x-axis. So this is how the output has come. So now let me explain this output to you. So basically, median, which is Q2. So the orange line inside the box shows the median of the dataset, which is around 75 in this case. This is the middle value of the data, meaning half of the students scored below this marks and half scored above it. Now let's understand what this box indicates. So it is an interquartile range. The box represents the middle 50% of the data, ranging from the first quartile to third quartile. The bottom of the box is Q1, around 65, meaning 25% of the students scored below this marks. The top of the box, that is Q3, around 85, meaning 25% of the students scored above this marks. And you can look at these whiskers. So these lines extending from the box show the range of the data excluding outliners. The lower whisker extends down to the minimum marks, that is around 50, and the upper whisker extends up to the maximum marks, that is around 95. And if I talk about outliners, then there are no outliners in this box plot, as the whiskers cover the entire range of the data. So by looking at this box plot, we can figure it out as the marks are fairly and evenly distributed, with the majority of students scoring between 65 and 85. There is a slight skew in the data since the median 75 is closer to the top of the box, suggesting that the higher portion of students scored in the upper range. The marks seem to fall within a fairly narrow range, indicating consistent performance among the students. So in a nutshell, we can say histogram shows how marks are distributed across ranges, whereas box plot indicates median, spread, and any outliners. So together, histogram and box plots help you clearly understand the structure, variation, and unusual values in your data. Now, the most exciting part, that is machine learning. This is where we take our data and use algorithms to make predictions. Now, let's dive into the basics of machine learning. So first of all, let's understand what machine learning actually is. So machine learning is a subset of artificial intelligence that enables computers to learn from data and make decisions or predictions without being explicitly programmed for each task. Instead of following a set of instructions, a machine learning model learns from patterns in data and improves over time as it is exposed to more data. Now let's look at the key types of machine learning. So there are basically three types of machine learning. First is supervised learning, second is unsupervised learning, and third is reinforcement learning. Let's start by understanding what is supervised learning. So in supervised learning, model is trained with labeled data, means the data where the outcome is known. The model learns to map inputs, example house size, to correct the output, example house price. Now comes unsupervised learning. Here, the model works with unlabeled data and tries to find patterns or groupings on its own. For example, grouping customers based on their purchasing behavior without knowing the categories in advance. And now comes reinforcement learning. Here, the model learns by interacting with an environment, receiving feedbacks, and adjusting its action based on that particular feedback. So this was all about the three types of machine learning. That was supervised, unsupervised, and reinforcement. Now let's talk about machine learning workflow. So this mainly consists of 5 key steps. First step is to collect data, which means gather the data for that particular model. Next is to clean the data. Remove any inconsistencies that are present in your data. Then the third step would be train your model, where you will teach your model using algorithms and you will try to perform different algorithms on your data. Then your next step would be evaluate that model. Check how well it performs with your test data. And last will be deploying that model. Once it works well, now you can deploy the model as it is ready for real world use case. So these are some basic steps of machine learning workflow. Now let's dive into another important concept, that is linear regression. So you must be wondering what linear regression actually is. So a linear regression is a machine learning method used to predict numbers like prices or marks. It learns from the past data where the answers are already known. The model looks at the relationship between input values such as house size and output values such as house price. It assumes that the relationship is straight line based. Using that data, it draws a best fit line that helps in making predictions. So here you can see on the screen, there is a simple linear regression line, which means there is a straight line representing linear regression. So during training, the model compares its predictions with real values and adjusts itself to reduce mistakes. As a result, it becomes better at predicting new data. Linear regression is easy to understand, simple to use, and commonly used in real life for price prediction, sales analysis, and trend forecasting. So let's understand how linear regression actually works in Python. Now let's start by importing the necessary libraries. Import numpy as np. Then we will import pandas. Import pandas as pd. And then we will import matplotlib library. I have imported all the libraries that are needed to code the linear regression line. Now let's look at the sample data. So this is the sample data, and using this command, this df is equals to pd.dataframe, we have converted this dictionary dataset into a data frame. Now we will start creating the linear regression model. Let's give it a name as linear model. So model is equals to linear regression, and then we will train this model. So this is the code to train the model, and then we will draw certain predictions. So the code for the same is predicted price is equals to model.predict, that is this value. This particular line of code will predict the price of the house with size 2200 square feet. Now we will print the predicted price by this line of code. Now we will plot the data points in the regression line. This will be the scatter plot for the data, where we have assigned the color and the label that is equals to data point. And I guess you know the meaning of df now. It means data frame. And we have choose a column as size and price. And then using this particular line of code, we will plot the regression line, which says plt.plot and df size, then model.predict, where the color is assigned to be red and label we have given as regression line. Now we will add titles and labels. So our X label is being designed as size of house, Y label indicates price, and the title we have given is linear regression, where is house size versus price. And now we will show the plot with this particular line of code, plt.show function. Now let's run this code, and boom, the output is on the screen. Now let me explain this output to you. So the plot visualizes the relationship between house size and price. You can see these blue dots. These represent the actual data points, showing the size of each house represented by x-axis and price in dollars represented by y-axis. This red line indicates the linear regression line that represents the best fit for the data, indicating that the size of the house increase, so does the price, showing a positive linear correlation. So here you can see predicted price is 3,20,000. It means the model has predicted that the house with 2200 square feet would cost around $3,20,000 based on the regression line. Please make sure that these prices are in dollars. The plot effectively illustrates how the house size can use to predict its price using linear regression. You can easily see the plot effectively illustrates how the house size can be used to predict its price using linear regression model. So now let's move to a different kind of model, that is decision trees. A decision tree is a machine learning classification model used to predict a category or a class. It works like a flowchart where the model asks a series of yes or no questions based on input features. For example, to predict whether customer will buy a product, the model looks at the feature like age and income. It may ask questions such as, is your age above 30 or is your income above $50,000? Based on the answer, it will finally decide you will buy or not buy. The model starts with all data at the top, splits it step by step using questions, and ends with a final class label. Decision trees are popular because they are easy to understand, simple to explain, and work in a way similar to human decision making. So let me show you how you can implement it in Python. So first of all, we need to import decision tree classifier. So let's do it. From sklearn.tree, import decision tree classifier. Then we will take the example dataset. So this is our example dataset where we have used age and income, and we have converted the dictionary data into data frame using this df is equals to pt.dataframe command. Now we will feature age, income, and target using this particular command. Now we will create the decision tree model. So decision tree model. So where model is equals to decision tree classifier. Now we will train this model by using this particular line of code, that is model.fit x, y. Now we will make predictions. So using this line of code, we will make the prediction whether the customer of age 36 and income 55,000 will be able to buy the product or not. Now with this particular line of code, we will print the prediction, where 0 indicates no and 1 indicates yes. Now let's run this code. So the prediction indicates that according to the trained decision tree, a customer with age 36 and income 55,000 is predicted to buy the product. Because you can see on the screen, the output has came as 1, which internally means yes. So to summarize, supervised learning is when we teach the model using labeled data, and unsupervised learning is when the model looks for patterns in the data without labels. We can use different algorithms like linear regression for predicting continuous values and decision trees for classifying categories. So, these were the core concepts you need to know to kickstart your data science journey in 2026. Congrats, you have made it through all the basics of data science tutorial. Now, let's talk about something super important. That is your career path in data science and some final tips to help you succeed in this exciting field. So you must be wondering what roles you can pursue as data scientist. So let me help you with this. Data science is a growing field with plenty of opportunities. So first, you can become a data scientist. A data scientist analyzes complex data to find patterns and insights that help businesses make better decisions. Next, you can become a machine learning engineer that focuses on building, training, and deploying machine learning models and algorithms. Next, you can become a data analyst who works on extracting insights from data and presenting them through reports and summaries. Next, you can become a data engineer. A data engineer is responsible for creating and maintaining the data infrastructure used for storage and processing. Last but not the least, you can become a BI analyst. A BI analyst designs dashboards and visual reports to help organizations track performance and make informed decisions. Now, let's talk about one of the most important questions that must be on everyone's mind, that is salary expectations. So if I talk about India, in India, as a beginner level with 0 to 2 years of experience, you can easily earn up to 3 to 7 lakhs per annum. At middle level, with 2 to 5 years of experience, you can easily earn up to 8 to 15 lakhs per annum. And at senior level, with 5 plus years of experience, you can easily earn up to 16 to 30 lakhs per annum. Now, let me give you a salary guide for data science roles in USA. So, if you are at a beginner level with 0 to 2 years of experience, then you can easily earn from $70,000 to $100,000 per year. If you are at a mid-level with 2 to 5 years of experience, then in that case, you can easily earn up to $100,000 to $140,000 per year. And if you are at a senior level with 5 plus years of experience, you can easily earn up to $140,000 to $200,000 per year. Now we will apply everything we have learned in this tutorial through this mini project. This project will cover all the important steps from data collection to model evaluation. So let's get started. So our first step would be dataset overview and then cleaning. For our project, we are going to use a simple dataset that contains information about houses. Our goal is to predict the price of the house based on the features like size, number of bedrooms, and age. Let's get started with the coding part. So these are all the libraries we will be needing in this project, such as Pandas, NumPy, Matplotlib, and so on. Please make sure to import all these. Now we will create a sample dataset. So this is how our dataset will look like. Here, we have used a larger sample dataset with all the missing values and duplicate values so that we can see all the steps. This too contains size, bedrooms, age, price, and so on. Using this particular command, we have converted this directory into a data frame, which is pd.dataframe, and the data is being called here. So see, I have created this dataset, intentionally added some missing values and duplicate rows to understand all the steps more clearly. But for your practice, I would recommend you to directly download the databases from Kaggle website and perform the operations on that particular dataset. So now let's start with our second step, that is data cleaning. So now first of all, we will check for all the missing values and handle them by filling with appropriate values. And then we will remove duplicate rows. So let's start with this procedure. See, here we will be checking the missing values. Now we will be printing missing values in each column, and this particular command will print all the missing values. Now we will try to fill missing size with the mean size. And the command to do the same is df size is equals to df size.fillNa and df size.mean. So this particular command will fill the missing size with the mean size. Now we will fill missing age with the median age. Let me show you the command for the same. And guys, please do not forget to use comments because it will make your code more easy and more understandable. It will ultimately help you only. Make this as your habit. Now this particular command, that is df age is equals to df curly braces age, will fill now. Basically we are filling our missing age with the median age here. So this is how we will be handling all the missing values in our dataset. So now let's check again. After performing this command, is our missing values are being handled properly or not? To do the same, we'll write this print missing values after handling. So we have checked for the missing values using this particular command, that is df.isNull function.sum. This will check all the missing values after handling it, if we are still left with any missing value or not. Now let's check for the duplicates. So the command to do the same is, so we'll write print df.duplicated.sub. So this particular line of code will check all the duplicate rows in your dataset. I repeat, now we will remove these duplicates. So let's give the comment as remove duplicates. So it's like df is equals to df.drop duplicates. So here we have identified the duplicate rows, and if there are any duplicate rows, it will be removed using this particular command, that is drop duplicates. This ensures that no row is repeated in our final dataset. So now let's run this particular section of code and check for the output. See, the output is being like this. So we can see size, age, and price are having 1 missing values. And after handling these missing values, we can see there are no missing values in our dataset now. And the duplicate output is being coming as 2. It means there are 2 duplicate rows in our dataset. So it means this works perfectly well. Now let's start with the step 3, which is exploratory data analysis, that is EDA. Now that our data is clean, let's perform some EDA functionality. These steps help us understand the data and its patterns better. So let's start by importing necessary libraries. Let's first import Matplotlib library. So these are the 2 important libraries we need to perform the functionality. It means to perform our third step. Now we will plot the price distribution. So this particular command will plot the price distribution, where we have given the title, we have marked X label and Y label. X label is price and Y is frequency. And this particular line of code will show the price distribution. Now let's plot scatter plot. So this particular section of code will plot scatter plot between size and price. where we have given title as size versus price and marked X label as size and Y label as price. Now here comes correlation heat map. So this particular line of code will print correlation heat map, and let's give this a proper title. Now let's run this particular section of code and check for the output. I hope it runs without any error. So here you can see a histogram for house prices that came on our screen. Let me explain you this histogram. The histogram shows that the house prices are relatively uniformly distributed, and the bar height represents the frequency of houses in each price range, showing how the house prices are spread out. Now let's see at the scatter plot. So the scatter plot shows the relationship between the size of the house and its price. As expected, larger houses tend to have higher prices. So here we can see there is a positive correlation. As the size of the house increases, the price also increases. The plot suggests that larger houses generally have higher prices. Now let's look at the correlation heat map. So this is the correlation heat map. We used a correlation heat map to understand how different features are related to each other. So here we can see size and price have a strong positive correlation, that is 0.88, meaning that larger houses are typically more expensive. Bedrooms and price have a moderate positive correlation, that is 0.83, suggesting that more bedrooms generally led to higher prices, but the relationship is weaker than size and price. Here we can see age has a very weak negative correlation with price minus 0.018, indicating that the age of the house doesn't significantly impact its price in this dataset. Now move on to the fourth step, which is building and evaluating the model. Let's start by building linear regression. So first of all, we will start by importing all these libraries. Now draft input variables and output variables. Features. So this particular line of code will give us input variable and output variable. So here x-axis shows size, bedrooms and age, and y-axis shows price. Now we will try to drop all the null values in both x-axis and y-axis. So here we can do this. So with this particular line of code, that is tf clean pd.concat xy-axis .drop na, this particular function will drop any rows with null values in both x and y. And then we will print the non-null values, means clean dataset. And we will store it in xclean and yclean variables. Now we will split the data into training and testing sets. So this particular line of code will split our data. Now we will create and train our model, that is linear regression model. So this line of code will help us create our linear regression model. And now we will make predictions and evaluate our model. So let's see how we can do this. So this particular line of code will help us make predictions from the model. So here we are predicting the prices for the test case. Now we will calculate mean squared error and R squared. So let's give the comment first. So this particular section of code will calculate mean squared error and R squared. Now let's print both these errors. So here's how we can print both these mean squared error and R squared. Now let's run this particular section of code and see the output. So here we have trained a linear regression model using size, bedrooms and age as a feature and price as the target variable. So now let's evaluate the model performance. So for this, we used mean squared error to measure how far the predicted prices are from the actual prices, and where R squared tells how much of the variation in the house price is explained by the model. And R squared values close to 1 means the model is doing good job. So here we can see on the screen, when we run this particular section of code, we get these two outputs. So here when we see on the screen, the model's prediction deviated from the actual prices by an average of 16065385729. A lower MSC indicates better model performance, where we can see R squared value as 0.631, means that 63.1% of variance in house prices. It suggests the model captures a reasonable amount of variation in the house prices. So comparatively, it is good for our case. Now let's go on to the step 5, that is interpreting results. So now let's interpret the coefficients of the model to understand how much each feature impacts the price. So let's start with the coding part. Let's look for the model coefficients. So by this particular line of code, we can print model coefficients on our screen. And now we will draft a scatter plot of predicted prices versus actual prices. So here's how we can do this. So here plt.scatter takes two arguments, that is ypred and ytest. Then we have given this a title as predicted prices versus actual prices. Here we have marked x label as predicted prices and y label as actual prices. We showed the particular scatter plot with this particular command, that is plt.show function. Now let's run the final section of this code. And boom, the output is on the screen. Don't worry, I'll explain you this output. So first of all, let me explain you what coefficient tells us. So basically, coefficient tells us the impact for each feature. Now first of all, let me explain you what coefficients are. So coefficients tells us the impact of each feature. First of all, size. For each additional square foot of house, the price increases by a certain amount. Now comes bedrooms. For each additional bedroom, the price should increase or decrease based on its coefficients. And then comes age. The coefficient for age tells us how much the price decreases for each additional years of house. So here, after running this particular output, we can see the coefficient for size is approximately 84.59. Meaning that for each additional square foot in house size, the predicted price increases by 84.59. Now comes the bedroom, this part. The coefficient for bedrooms is minus 171.87, meaning that for each additional bedroom, the predicted price decreases by 1711.87. This is unusual, I know, because you might expect a positive relationship, but it could be due to the small data set and how the features are correlated. And if we see the coefficient for age, then it is 6454.06, meaning that for each year increase in the age of the house, the price increases by 6454.06. Again, this might not align with the typical expectations, but in data science, it's completely normal to get strange or unexpected results. In our case, the unusual results might be happening because of the small data set. And that's completely okay. With limited data, models don't always behave perfectly. What truly matters is that our process is correct. So we have followed all the proper steps and we have understood the learning objectives clearly. That matters the most. Now let's look at this predicted versus actual prices plot. Here, the point seems little spread out, which indicates that the model's prediction didn't match that perfectly with the actual prices. Since I told you the data set is small and according to our requirement, so this is expected. A larger data set would likely improve the predictions. So this was our complete mini project. Here we have cleaned the data, explored it, built a model and evaluated how well it performed. Now this is your homework. Try different models and compare the results yourself. Experiment with decision trees, random forest or any other algorithm and see which performs better on the same dataset. Because remember, data science is not about one model. It's about practice, experimentation, and continuous improvement. And don't forget to download the data from Kaggle website for your practice.
Next, we'll talk about the concepts about the data science part. What is data science? What is the process and so on. Again, that's the first page, right, that I have as a part of thing. So a fundamental definition that we go through with it is the use of scientific methods, processes, and algorithms to derive meaningful insights from the data. That is the idea behind it. I will not go through with that, right? I will not talk about this. What I'll try to talk about is to think of a real world scenario. I am giving you guys a scenario. Can you on everybody? I hope so everybody can see my screen. On my screen, can you see there is a bulb? Yes or no? Great. Thank you, Gilbert. Thank you, Preeti. Now that's data for me. I'm giving you this data. This is the data. It's a visual data, right? It's a visual data. Now, think yourself as a person who is a data scientist, right? Who is a data scientist at some bulb manufacturing company, right? Some bulb manufacturing organization, right? You're a data scientist at a bulb manufacturing organization. You're walking out of your house and you saw this bulb. You're walking out of your house, you're going to work. Imagine you're going to work, and this bulb was there into the next house, or maybe somewhere on the road. You found out this particular, or somewhere on the pathway, you found out this particular bulb there. Great. Hypothetical situation, but thinking process. This is the most important part for a data scientist, for an AI engineer. Is the most important part is the thinking process. How do we think about it? Now, think about what you can recommend as data scientist, considering this particular bulb as an input, right? This is the input to you. Think about that. Okay, you may not know what is data scientist roles, but whatever your understanding of data scientist based upon that, right? Or AI engineer course, right? Whatever your course enrolled into. What is your approach towards a business proposition or about this particular information that you have that you can recommend to your, let's say, the to the management over there? Maybe you can tell them, okay, I saw that bulb on the street and I have so many so and so recommendations for you. Anything that you would like to talk about, or let's talk about what you can tell me about this bulb. Let's say, how will you draw insightful information about the data? Can you tell me about this bulb? Just information, no decision making, just about the bulb. Tell me what else information you can give me. I'm okay with that. You say that if the bulb is yellow, that is also an information. It's a screw based bulb, not a click and lock method. Its brightness level, okay. Bulb dimensions, great. What else? See, I'm looking forward towards something. Power consumptions, great. Materials used, wattage, great. Lights when connected power, okay, that should be, a basic property, Preeti, yeah, but it's still good. Anything else? See, I want you guys to observe things. Take your time, observe, because whenever you are saying, let me just try to tell you, I have too many options came up. Like Abhinetri says, brightness level. Is it observable from the given image? The bulb dimension, Gilbert, is it observable? Is it available on the given data? The power consumption, Narendra says that, wattage, or the material used, lights when connected power, how many watts, is that available with the given data? Can you actually find it out from the given information? Ajay Shri, what is that? Sairam is coming up to caution validation required before green. On top, some black dot is there. Yep. What does that implement? E27 bulb holder. Agreed. Devashish. It is an object. It is an object. Okay. Any object. Right. Good. So I tend to, closely follow the observation from Sairam. The kind of inference that you might require to take it up is something that is unusual, right? Something which is unusual, because as a data scientist or as an AI engineer, everybody knows, right? I know, you can see the options coming from 10 different peoples in the chat window as well. Someone is talking about, wattage, powers, luminosity, and so on and so forth, right? But something different, something that makes you unique, something that is no one else is able to observe, and that has some meaning. So Sairam talked about there is a black dot on the top. What do you recommend? What is the reason behind it, or what would be the implication? It's a filament bulb. Great. It's a filament used in the bulb. It's a tungsten bulb. Great. So one observation, which is directly not available, but it is hidden. None of the bulb manufacturer label, that's not available, right, Gilbert? But what I can observe, let me just put it across. What I want to convey to you guys is, right, with this particular image. See here, I can see that there is a black dot on the top, right? It's a black dot on the top. That black dot tells me that whatever the outer covering is, right, of this bulb, that outer covering is getting blackened out. That means the intensity of the power inside the bulb is such high that it is turning out the features outside, or the outer body is black. And if that is happening, that means it has to be usually a tungsten bulb. That's number one. It's a tungsten bulb. Second thing, this does not happen over a day. This does not happen over a day. It happens over a long period of time. That also tells me it's a very old bulb. Isn't it? Do we agree? Thank you. And if it is a very old bulb, as business perspective, I can think of incandescent bulbs, for example. Similarly, it's a very old bulb. Now, I can think of an alternative bulb. I can think of, as a business proposition, I can think of an alternative bulb that does not give the black structure, gives me better, life, or maybe something like that. It's not using tungsten technology, maybe using some other technology like light emitting diodes. Could have been any other solutions, right? Which will offer a better or cheaper options. Make sense? Now, why did I discuss about this bulbs for so long? The only reason I wanted to talk about is not the bulb, but the approach. Make sense? See, I can go on with this theoretical presentation for a long period, not a problem. But the point is, this is not what we're here to learn. You can go through with this presentation 10 number of times. You will have access to this presentation. So I will not concentrate more on to the presentation part, but what we need to do in real world, I'll try to concentrate more on that. Is that okay with everyone? Right? Presentation is something that you guys can read through 10 number of times, right? And most of the slides are self-explanatory on this. So what did you learn from here? That whenever you're getting a data, whenever you're going to work around with the data, you do not look for things which are obvious, right? You need to look for things which are not obvious, isn't it? Now, in order to find out those things, you require certain kind of methodology. Here it was easy for us, right? Because we can see that pictorially. There is a picture available, and I can see that part. I can see that shine. There is a slight little curvature onto that too. I can use that too for some informative purpose. Like it's in a background where there is too much light. That's why I have that shiny part or shiny curve on the top. That means there's a background light reflecting on that particular bulb. Right? So understand this part, that it is not about that what is given already in the data. It's not important because everybody can see that. What is important is what is hidden in the data. Is that okay? Thank you. Hopefully. Thank you, Gilbert. Okay, so moving on. Now I have some basic things to talk about. Very quickly walk you through with that. So the process of data science, it's a kind of process where I would require a lot of information, right? I need to know about the domain. I need to know about the scientific methods and technologies. Three important things, right? Now, domain is something that you may or may not be aware about at any point of time. For example, let's say If I talk about when I started my career as a data scientist, I was coming from a financial background. I was working in State Bank of India prior to that. So I came up from a BFSI background, banking and financial institutions. So my core expertise was on finance. But if you talk about over the period of time, what kind of projects that I've dealt with, I've dealt with the financial, non-financial, pharmaceutical, I've aviation, different kinds of projects that I've dealt with. So subject expertise is not something that you will have in all sections ever. This is something that you will acquire project wise, right? You would have to do the hard work to read about the project, read about the domain, understand the domain, acquire knowledge about the domain. That is what you need to do, right? When it comes to the scientific methodologies, right, that you need to do. So scientific methodologies are the mathematical tools and the scientific tools that we have, right? So I'll talk about that during this course. What are the scientific methodologies that you need to require to be a data scientist or an AI engineer? We'll talk about those mathematical and scientific concepts that are used in the real world. We'll talk about that during this course. As a part of technology, we require a machine and a programming language. Two things, right? A machine and a programming language to implement these things. Good. So I have a programming language like Python. I can use that. There are other languages as well which allow you to do that. Then operating systems, data processing tools. Again, we'll talk about the Python language slightly, data processing tools, the libraries, the application design. We'll talk about all those things during this particular course. So that's your upcoming portion. Are we good? Keep on asking questions. Some of the applications of data science processes is being given up here. One of the data science process application is the biometric sensing of the data, right? You wear up a wristwatch or the what you call it as a smartwatch. It counts up your steps, it counts up your heartbeats, and talks about the real-time information about that. I can use that information and take out some decision-making process and make some conclusive decisions. Let's say suppose my wrist or this particular smartwatch detects that my blood pressure is going beyond 200, right? My blood pressure is going beyond 200. There is no movement in my body. It can be detected. Now, would be possibility that I'm suffering from a cardiac arrest, or I'm suffering from hyper blood pressure. So I might require immediate emergency services help. My Android device or my whatever Apple device or whatsoever it may be, right? My smart device can make up an emergency call to the emergency services and send my location. If it can send my location, emergency services can arrive at me and take necessary care, right? Without any human intervention, we can still deal with these things, right? So useful interactions that can happen. Another example of data science is the search recommendations. So recommendation systems, not in this course, but in the next course, machine learning, we'll talk about that. How does the recommendation system feature works? We'll talk about that. But recommendations that you might have observed on Google platform, you write down typing something and it starts, showing up, okay, this is what people have searched for, or this is what is the possible next word. So next word recommendation, right? Suppose I want to write down, maybe you might have seen in how many have seen that, okay, while you're writing a mail, right, it tells you, if you write on hello, it automatically shows you sir or madam and so on. It asks you to press tab to select that option. Automatic recommendations of certain words, completing a line, completing a paragraph. Seen that before? Expecting yes. Yeah, thank you. So that is coming not from just any kind of software, it's just a data science process, the recommendation systems. Similarly, your loan applications, right? Credit card applications or loan applications, they say that you'll get an approval in 2 minutes. Who is going to look after that application in 2 minutes? No one. It's a backend machine. Looks at your credit report, looks at your history, looks at your application status and everything, and makes up an informed decision based upon that data, right? You'll study about how does the decision making process happens in ML course, machine learning course, right? You'll study about that. But as of now, you can understand that this is an application of data science. There can be a lot of applications, right? Any field that you think of, there is an application. Any particular field you want to put up an example? Any specific field you think that I should put up the example with? I can put that example, no problems. But ask it. Any specific field. For example, let's say you apply on a job portal for a job. You think that my job, that my qualifications are exactly what is being required for a particular job. You still do not get a call. Thank you very much, Abhinitri. See, this was theoretical portion, so I was not expecting too many questions with this part so far. But I just want to follow the process. So this is the entire process that we have, right, in the field of data science, right? Now, in this, there is few things, right? First thing is problem definition. Problem definition is a kind of a problem statement that is given to us, right? A client will come to your organization or to you to tell you that, okay, this is the particular problem that I'm facing particular business, right? Say, for example, I'm a soap manufacturer. I manufacture 10 different kinds of soaps. Out of those, only one particular soap is not getting a high sales, or the sales values are very low for that. Why is that happening? No. You need to answer as a data scientist or an AI engineer what is the problem, what is the possible cause of the problem, and how we can rectify that problem, right? So once we know the problem, based upon that problem, we ask the client to provide the data, right? The data acquisition happens. Now, what is the skill set that is required for data collection? Anybody? I'll only talk about the skill set. As a part of data collection, usually what happens is a client will tell you, okay, these are my database servers. I have kept my entire transactions data or whatever the things that we have. I've kept in particular database. These are the login credentials that you will have. Take out these login credentials and fetch the data from there. Sensible? So we should be aware about how to fetch data from different database servers. Now, as a data science, if you talk about end-to-end process, people will seek those kind of things. If you talk about small or marginal organizations, very small organizations, they think of person who can do end-to-end job. But in bigger organization or mid-level organizations, they have a separate team who does the ETL portion. We call it as extract data and transform and load it back. And then we have a different set of data scientists. But in general, the skill set that is commonly expected is structured query language, SQL. Not a part of this course. We will not talk about SQL at all. That's a separate course altogether. You may have that as an optional topic, but you should know about structured query language, if not in detail, but slightly about it. Are we good? So that is where we collect the data. Either we'll do that through databases or we'll roll out Google Forms. You see that there was a Google form rolled out to you at the beginning of the session, isn't it? What was the purpose behind it? Yeah, there is one purpose that I get to know about you guys, but there is another purpose that is a data collection process that is happening in the background of Simplilearn. They get to know, those or whatever the data scientist team that is working in the background for Simplilearn. They will get to know, okay, what kind of learners are joining in, what they know about, which industries, and so on and so forth. A lot of conclusions can be made out of this. A lot of business decisions can be taken out of that. Are we good? So data collection is not just with the SQL. It can be directly from the from the end users. It can be directly through online resources. You can extract it from web pages. You can just walk through with the web pages, and you can use that. Maybe there is another library that you can use for data collection is BS4, Beautiful Soup. That is a web scraping library. But that's not our objective. We're not going to talk about these two portions, the problem definition and data collection. Why? Because we are going to go with the standard problem statement. There is a standard problem statement that will be given to you, and there is a standard data, right, which is in the format of CSV. It is in the comma separate value format. So what I'm expecting is you will have a data set, you will have a problem statement, and then we'll start working. Are we good? You, yeah, you will get the problem statement. Maybe I'll address it live in the session. The data set, if it is available into your standard practice data sets, it is available into your LMS. Otherwise, if I will use some additional data sets, I will share it with you guys. Okay, if I would require any one of those. So our learning for this particular course will be limited to this part only, the part 2 and part 3. We'll get to know how do we clean the data, how do we explore the data, and how do we perform the feature engineering part. So this is the basic thing that we'll do here, right? In between, there is a lot of things. How do we clean and explore the data? Exploration is the major part, right? Because we need to make a lot of decisions about the data while doing exploration. Some part of model building is also part of this particular thing, right? We'll discuss into that part, but we'll not actually build the model. Maybe if time permits, I'll try to see some one or two models to be built up, right? But this part is not part of your curriculum. Model evaluation and model deployment, we will not discuss that at all. This is a part of your machine learning section, right? Next course, machine learning. These three topics, 5, 6, 7. So essentially, the entire 9 sessions are dedicated to this particular portion only. Now, how important is that? Is you can understand this. Suppose if there is a project, let's say there is a project of data science that talks about a particular problem, and the time span given is 6 months to complete that project, for example. Out of those 6 months, you can imagine at least 4 months will only be spent on this part. At least 4 months. It can go up to 5 as well. This is very, very critical factor, because how good we clean the data and how good we manipulate the data, that makes the next stage, which is the model building, more robust, more efficient. So that is one of the very critical factor in the field of data science or machine learning or artificial intelligence. How is the data being prepared? So data preparation is a really important topic, and that is what we're going to learn through this course. Are we good? Okay. Python for data science, preferred programming language across the industries, have some advantages and disadvantages. We'll not talk about that. What are the important packages? NumPy is one of the important packages. We'll discuss that in detail. Pandas is the second topic. SciPy, we'll discuss that shortly for some period. Then stats model will come into the picture as well. We'll talk about scikit-learn, not too much in detail, but slightly about scikit-learn as well, wherein I'll talk about what is scikit-learn, and some features of scikit-learn will come into the feature engineering course. Matplotlib will discuss in detail. Seaborn will discuss in detail. Plotlib will come with the questions. Okay, with the Plotlib. This is a types of plots with the examples which is given into the presentation. Wherein, what is a line plot? Connect two dots and join them with a straight line, that becomes a line plot. A marker plot, highlight those dots and that becomes a marker plot. So you can see your dot, see that becomes a marker. Then there's a scatter plot, which is typically used for the purpose of analyzing relationship between two data points, right? We'll discuss all these plots in detail. This is just for your reference to know about these words. That's it. Then you have this area plot, that is also called as a stack plot. Area plot and stack plot are same thing, and it talks about cumulative changes between certain data, right? We see why I'm trying to rush through with this is because I need to talk about this, how these are created and what kind of meaning they take up at a later stage as well. So I do not want to put up time here just to talk, if I give you the details right now and then later on again same problem arises. So I need to talk about how they are created and how we will use them. We'll do that. All these graphs that I'm talking about. Bar plots again talks about frequencies of the things, how many things are appearing how many times. Grid plots, drawing of that grids. Histogram, another plot, very important plot that talks about the frequency distribution. Pie chart again talks about the frequency distribution. That's it. What is data exploration? Will we be diving into the specifics in a subsequent session? Yes, definitely. In the data exploration part, we will talk about a lot of things. 3 things. There will be a lot of things as a part of data exploration. Essentially, when I'll try to start working with the Pandas library, right? When I start working with the data Pandas library, I'll tell you how to reach out to particular data, why to reach out to a particular data, what inferences you are going to make out from a particular data, and how will you deal with them. Every kind of possible scenarios, the different sort of data sets, I will try to include that. Whatever the possible situations that you may come up across in a real world scenario, up to a certain limit, right? Because I have limited number of data sets that I can talk about. But yes, I will talk about data exploration. Essentially, that will be the most longest thing that we will have, highest longest thing after the mathematics portion. The maximum time will go on to mathematics, but next thing that will be data exploration. Otherwise, I just need to talk about syntaxes, right? Suppose what is numpy, what is numpy syntaxes, what is an array. So basic concepts, right? So that will be a syntactical thing where I'll talk about syntax and tell you, okay, this is how the things are designed in Python. We need to follow the very strict Pythonic way. That is one thing. I'll tell you this is what is supposed to be done. That is fixed. But when and why is something I'll let you know. Good. All right. So what I will do here is I am currently using Anaconda, tool, which you can do it by this way. You can go on to anaconda.org.download.success. I have shown that link, and you can download your requisite installation. If you're using a Mac machine, just in case if you're using a Mac machine, you can go onto the Mac link and find out the downloader here. Either for Silicon, Intel chip is not available there. Why, I'm not sure. But Apple Silicon graphical, Apple Silicon command line is Intel chip is also should be available, right? So if there is any concern with that, let me know. Otherwise, you can get it from this. This is a local installation. That means that allows you to create files locally on your machine, use your local hardware, and work on the local manner. But typically, you can also use, a cloud-based hardware, and that is what you can use with the Colab. So you can search for colab.research.google.com. Once you go onto that page, that should appear up with something like this if you're already signed into your Google account. If not, it will not appear up that way. But you can click on the new notebook option and you will come across with this kind of scenario. My Office laptop is VS Code install extension of Jupyter. I am okay with that, Sitish. I'm okay with if you do not have to install that extension and you're putting up a path for Python. Kotian, yes, Simplilearn does offer a lab. You can use that, but what will happen is in a later on courses, like when you will use start machine learning or deep learning, some later courses, Simplilearn lab is going to be not available. And I do not recommend people doing the Simplilearn lab. See, I am working for Simplilearn, but I do not recommend it. Why? Because there is a reason behind it. The reason is because some of the libraries in that particular field are not current. They are slightly older one. They're not updated. And hence what happens is certain functionalities will not work in a proper way, or they will work, but they will not offer you this solution that you should expect out of it. Right. So I do not generally recommend people using Simplilearn. That's the final, ultimate thing that I tell people. Okay, if you cannot do anything, go with the labs. Great. I will recommend you to use Colab. Anybody who's not okay with the local installation, come to the Colab page. That's how you will see it. I will just close out this AI companion, and I'll put on one simple code print my name. Very simple thing. I write down that piece of code into my cell block over there, and I can execute that by clicking on that play button. It gets executed. I am not going to use Colab in general. I will be using the locally installed Jupyter Lab environment. So I'll show the same piece of code on the local Jupyter Lab. Here it goes. So I opened up Jupyter Lab and I have clicked on this sheet and I can write down that print, same piece of code. And I'm putting up my name. This is going to be faster for me. Right? It works. Hopefully 1, 2, 3. It does not. Why till now? Taking too long. Something is wrong with my machine. Maybe I'm acquiring too much of it. Done. Great. So anybody and everybody, give that a try. Can you just take out that print statement and see if you're able to execute that? Either in Colab, either in your environment, whichever you're preferring, I'm okay with that. But just make sure that you are able to get the codes executed. Great, Abhinetri. So we'll start talking about the first library, and that will be your first file, which I'm going to rename over there, numpy. And I'll put up that is for your Jan, or rather, this is your EDSP batch for January, EDSP B1, that's batch 1 for Jan 26 or January, that's fine. Rename. Great. So let's start talking about numpy. So what is numpy? So NumPy is essentially a framework or library, one of the very basic or base library that is available in Python, or that's a part of Python, which is used for numerical computation, primarily used for numerical computation. So NumPy is a library of Python which is used, something from Sairam. Yes, Sairam, tell me. Which is NumPy is a library of Python which is used primarily for numerical computation. The word numpy is coming from numerical Python. So numerical, that's fine. Numerical Python. So I've just highlighted those characters in uppercase. Right. So essentially the idea behind the numpy was that I wanted to make sure that I can use the mathematical concepts of Python in an efficient manner. Right. It brings in, what does it brings? It brings the concept of, brings in a new data structure, that is array. Now, do we know what is the data structure? Anybody? Not data types. It is a data structure. Now, data type and a data structure are slightly different in nature, Narendra. Collective data of different types, not even of arrays, not of different types. A data sets are not even a data set either. So when I talk about a data structure actually defines defines the arrangement of data. Defines the arrangement of data in the memory. Let's try to understand that through a conceptual or graphical manner. Very simple thing, but I'll try to put that into a graphical manner. Suppose it's your birthday. Possible? Anybody's having birthday in the month of January? Oh, January is finished. February? In the house? Suppose it's your birthday. Now there is a locality, right? There is a locality where 5 of your friends are living. There are 5 friends of yours. Suppose this is the entry gate of that locality. This is your friend 1's house. This is your friend 2's house. Right? This is your friend 3 house. This is your friend 4 house. And this is your friend 5 house. Now, the problem is that you know where is friend 1. So you can reach out to friend 1, give him the invite. Friend 1 knows where friend 2 lives. Friend 2 knows where friend 3 lives. Friend 3 knows where friend 4 lives. And friend 4 knows where friend 5 lives. Good? Now, if you think about this process, it is going to take up some time for you to go around with all the friends' houses and distribute the invites. Yes or no? As compared to, when I ask you the comparison, if it is the situation like this, that you have a friend 1, you know where is friend 1, but the friend 2, 3, 4, and 5, they are living adjacent. You know that friend 1 lives at a particular place. You will go up to the friend 1, and then you know next house is of friend 2, then 3, then 4, then 5. Now definitely you will take up less time in this scenario, isn't it? Thank you. So that is what array offers. So array is a arrangement of data into the computer's memory in a contiguous manner. Contiguous means in a single chunk. So whenever data is arranged, right? So what is an array? That is what numpy offers. An array, which is referred as ND array. The word that is used in Python is ND array, right? We use the word ND array in Python. So referred as ND array is a contiguous memory allocation of the data of same type. Now, idea is that every information will be of similar nature and it will be arranged in a contiguous manner. Contiguous means that one after the other. It will not be scattered around in the memory, but it will be together in single chunk. Sensible? Not sensible? Yes, no, maybe. So you need to ask questions. Now, every time when I start with NumPy and I say that it is used for numerical computation, people say that Python has its own module for numerical computations like math. Then why do we require NumPy? So that's the next basic question. That is, why NumPy? Why NumPy? So what is the NumPy? Because of the use of the arrays, and its functionalities. Right, its functionalities. NumPy offers much faster execution. That means it is intended to be very, very fast. Good. That is the only reason I require NumPy. Then the core Python. Let's try to look at something. Now, first of all, before I begin with this, how many of you know what is an import statement? Import keyword. Anybody have ever used import keyword before? Yes, no, maybe. Yes, Naresh. Yes, Gilbert. Great. Yes, yeah, for importing. Yes, to use the library. Thank you very much. So almost everybody knows it. Hoping so. Now, considering that, I'm going to import few things now in front of you. Right. I'm going to import a library that is called as import. I'm going to import. Just correct that. It's raw. We get code. Let's import time. One of the library, which is the default library to the Python, which is time library. I'm going to use that library. Why I want to use that library is because I want to showcase something. Great. What I want to show is this. If I just talk about time is a library that I'm using, dot time, and I'll try to print it up. Let's print what is the time function is going to give me. Now it gives me a epoch time. What does it tells me? It prints the epoch time at execution. Right? What is an epoch time? Somebody help me. Present time, no. Unix time, yes. But what essentially that means? Unix time, Narendra. So epoch time, if I talk about, is the time that is elapsed in seconds since January the 1st, Jan 01, 1970. Right? So that is called as an epoch time. Right? Epoch is another word that is used alternatively as Unix time or Linux time. Essentially, that was the period when Unix was introduced and the clocks were reset to be standardized for a standard reference. So it was kind of something of that we follow in the computer science fraternity to keep a hold of time as a fixed things across everyone in the entire globe, because time is something which is varies across the globe. Every geographical location. I am currently right now. It's almost like 11 in the morning or early afternoon. You can say that 11 a.m. is the timeline for me. Some of you would be at different time zones, isn't it? For some of you it might be early evening, for some of you it might be the early afternoon, maybe late afternoon, some of them, right? Isn't it? Depending on the time zones that we follow. So in order to standardize that, we use a particular timeline on the machines, and that is we call as the epoch time or Unix time or Linux time. Great. Now what is the advantage over there? Now, since I have executed this particular statement, right, there is some time elapsed, isn't it? Let me just try to copy the same statement again, paste it back again. Good. And execute. Can you notice that there is a difference in the two outcomes? Right? 17698364891 17698366649, or essentially, if I can say that, between that two executions, right, there was 159.5690 seconds elapsed. This is the difference between the execution time, right? Two statements I have used, and I have tried to showcase the difference between the time of execution. Are we good? Now I'm going to utilize this. For what purpose? The purpose is to tell you why numpy. Good? Great. Yes, no, maybe. Now, I'm going to use out a data structure over there just to showcase this part, which you will learn about in due course in upcoming time, maybe today itself or tomorrow. That is going to come up, right? But I'll start talking about this part, right? And that is a random thing. So I'm going to create an array. The idea is let's create an array of random data. Create an array of random data, right? So how will I do that? Since I am using that, you can use that in syntax for yourself. As of now, do not put into your brain for this. Just think of that as a syntax, okay? And I am expecting everyone is going to do that for me, right? I'm going to create an import library, import numpy as numpy. I'm going to put that as a name np. What it essentially means that I am importing the numpy library with an alias name np. Thank you very much, Narendra. And now I'm going to create up a data. So let's say data is equal to np dot random dot rand, and I'm going to use let's say 1 2 3 4 5 6 7 8 zeros. So what I want to do it is to ask my numpy to generate random values of what nature? Of rand nature. Now rand means random floating point numbers between the range 0 to 1. We'll discuss that rand function later on. I'll do that. But as of now, consider I have a floating point numbers, which are decimal point notation numbers, that will be between the range of 0 to 1. Good. I'll have that many numbers. Good. It generates that data. Good. The data is now generated. Now, if I ask you that I want to calculate the average of this, a very simple thing, right? There are that many number of data points. That's 10, 100,000, 10,000, 100,000, 1 million. So that is approximately 1 billion. Good. 1 billion numbers. If I want to calculate the average of those 1 billion numbers, how will I do that? I need the summation of all those. Agreed? What is an average? Take the sum of all numbers, right? Divide by the count of numbers. Is that okay? That's average. So let's take a sum. Sum is equal to, or let's say, I'll define that average is equal to whatever the data that I have. So I'll take up the summation of that. Sum of AVG, that is going to give me the sum of, not AVG, but DATA. I'm taking that sum divided by the count of, but the count is not available, the length of DATA. Good. Ln of DATA is going to give you the same data. If you just, let me just show you that number, right? Same number. So I will calculate the average over there with this function. Good. Now, I'll try to do what? I'll try to note down the time. So I'll take up a start time that is equal to time.time. So that is going to capture the time that is elapsed since epoch before the execution of this statement. Good. And then I'll copy the same thing and I'll put it down below and I'll put that as a word stop and I'll write down time.time again. So stop is going to capture the time immediately after the execution. Agreed? Thank you. Let's try to display what is the time taken. So can I put a print time taken is equal to, and I'm putting that as the stop time minus the start time. Correct? Everybody okay with this till now? Thank you. I'll execute that for you. It's going to take some time. Let's see how much time it takes up. It is going to be machine dependent. My machine will take some time. Your machine might take some different time, but it takes me 12.69 seconds. The difference that I got is 12.6994. So approximately 13 seconds. You can say that. Good. Now, I'll copy the same piece of code, right? No changes at all, apart from how I am going to calculate the average. I'm changing the process of calculating the average. Instead of using the, the traditional approach, I'm going to use a numpy library approach. I will ask np.mean. That's a numpy function to calculate average of a data. And I can put up that I want an average of this data, which is by the name DATA. Good. And look at the time. Time taken 0.42. Do you notice the difference? Right. Now, some of you guys, I'm not expecting all of you, but some of you are going to tell me how much time on your machine it took up without NumPy and with NumPy. Some of you will tell me. That will confirm that everybody is doing along with me or not. This is just for that purpose, nothing else. Because what I'm expecting is that you guys will do along with me. I have not yet started with NumPy. I'm still trying to, talk about the advantages of NumPy and so on. No one? And no from Asif. I'll wait. I have time. No problems. I'll wait. But I want you guys to practice. And I insist, guys, give that a try. If you're feeling not comfortable with the code, I will, show up whatever maximum possible. Maybe you might require this line as well. Paste up the results, Akshay, the time before it took up and time after. So Rosie, it took up 0.01301 and 0.00. So potentially Rosie is having either a very good machine or she's using Google Colab. She or he is using Google Colab. I'm not pretty much sure. I cannot capture with the first name. Is it a he or a she? Sorry for that. Now that can be pronounced as a Rosie and it can also be pronounced as Rosé. So slight confusion, not a problem. I am not gender biased. Anything, I'm okay with that. But good. Potentially, what I can inference from that is either you have a very good machine or you're using Google Colab servers. If I'm not wrong, can you confirm? Again, data start off with length 10. Preeti has tried to use servers slightly utilize these things, but yeah, you can still notice the difference in the time, isn't it? Right? You have used a small chunk of data, that is why the time taken has not too much of difference, but there is a difference, right? So essentially what happens is because of the numpy functionality, right, I can use or I can perform tasks in a faster manner as compared to the traditional approach, and that is why people prefer using numpy and not using the functions, not using the default or core functions or core Python part. Core Python is good. We need to use certain things from core Python. It's great, but yet you would require libraries to do work with this. Now, does anybody require help installing NumPy onto the machine, especially to the people who are using VS Code and not able to extract NumPy? Anybody not able to execute any of the piece of codes that I have discussed so far? So suggest some system for data science, Akshay. Typically, that's difficult to gather for me. What kind of system that you're looking for? Thank you very much, Narendra. On that part, we've installed NumPy. Minimum requirement. See, there is even if you have a very basic machine, right? You have a basic machine that allows you to browse internet over any period of time. Not a problem. What you want, I want you guys to have a good browser, right? And you can still use Google Colab. I'm not saying that you need to have a locally installed software, not necessarily. You can use the cloud softwares. The point is we need to be a little bit more conscious with them, because they lose out on the data. I need to keep a local copy of those data. So a simple average machine, where any simple average machine, let's say you can have 4 gigabytes of RAM with any simple processor, I'm okay with that. But make sure you have a good internet speed, right? If I talk about my machine right now, I'm working on currently on 200 megabytes, 200 mbps connection right now. And that's the maximum available in my area. If I would have some more options, I would have gone with that. So good internet speed works well, provided you have an average machine, which is good enough to play, videos, watch out anything. I'm okay with that. So nothing specific from my end, a minimum requirement, but yes, something that you can have that allows you to do a proper without lag functionality. I'm okay with that. 2 gigabytes of RAM is also fine with me. I'm okay with that, provided your browser works well. Good. Great. Now comes the first aspect, that is the array. Now, before I move on to the arrays, can someone tell me the list? Anybody heard about the word list before? List in Python? No? Great. Okay. Heard about linked list in other languages? Now, data structure. An ordered mutable collection that stores multiple values in one variable. Thank you, Satish. So essentially, understand the idea. Python offers a data structure. Data structure is an arrangement, right? It offers a data structure which is called as a list. Now, list can contain any type of value, right? I can have an integer value, I can have a floating point value, I can have any sort of, I can have a string, I can have any Boolean type of data. The point is, when the list works, what does it do? It tries to store your data into the memory. Now, it does not store that into a contiguous manner, right? It will try to store integer value somewhere, a floating value somewhere else, or another value somewhere else. Now, whatever the combination, it can be, continuous. It may be continuously together. It may not be together. It varies machine to machine, right? Wherever the memory is available, a list will store all data points accordingly. Now, however, the arrays allows me to store the same information in a contiguous manner. That means that essentially, if I have 4 or 5 or 10 number of values, array will allow me to store the data in a contiguous manner. It's like this. I have 1, 2.4, let's say letter A and true. But there is a catch. The catch is, with list, every individual element, right, of that data structure will keep its data type. That means if something is integer, that will remain integer. If something is floating, that will remain floating. If something is string, it will remain string. And something is a Boolean value, it will remain Boolean. However, with the arrays, the data type changes. That means it is going to be throughout the array, every element is of same data type. Every element of the array is of same data type. Are we good? Thank you. So, what is an array? So, an array, I've given you the definition earlier too. An array is a contiguous arranged data in memory, right? A contiguously arranged data. That's a simple array. NumPy has array by the name on NumPy addresses. Let me just put that up. Addresses arrays as the name, and the name is ND array, which refers to n-dimensional array, What is the idea behind it? So the arrays could be in multiple number of dimensions. When I say dimensions, what does it mean? It means that suppose I have a single line of data. It can be horizontal, it can be vertical, does not make a difference. I call that as 1D, one dimensional. If I have a table like this, I have rows and I have columns, right? Like this. I'll say that as two dimensional. If I have a three-dimensional data, like I have rows and columns like this, behind that I have another layer, like just like you can say that a Rubik's cube, right? You can think of a Rubik's cube or any three-dimensional object, right? So if the data is arranged in that format, I'll say that as a three-dimensional data. Or hypothetically, you can think of 4-dimension, 5-dimension, 5th-dimension. These are not pictorially representable, but imaginary, right? But yeah, we can represent them in terms of machine. Great. So Python offers two ways. There are two ways by which the arrays can be created in Python, right? What is the number one way? Using the array function. There's a function called as an array, and then there is using the built-in array generative function. But there are a lot of many of those, so I will not talk about them in general. I'll try to talk about them one by one. Good. So let's try to create arrays. Let's create arrays. Create ND array rather using array function. Great. Now, the first one that we have in the picture is, let's create a zero-dimensional array. Now, what does zero dimension means? Input stream. What do you mean by zero dimension? When you say the word zero dimension, anything strikes back? Yes, does not exist. No, it does exist, Preeti. A zero dimension does exist. Empty array, no, Rosai, Ravichandran. Empty array, you can say that as zero dimensional, but that indeed does not mean the same thing. Understand what is, do we know what is the difference between a scalar data and a vector data? I will though talk about scalar and vector in detail later on. That's a separate thing. But what is a scalar data and what is a vector data? A scalar is without direction. Great. Thank you very much. Direction means a dimension. Understand it. Suppose if I think about a coordinate system, suppose this is a XY coordinate system, right? And if I put up a point anywhere in this XY coordinate system, right? Let me put up a point. Trying to take a bolder pen. Suppose this is the point. Now, this point, if you do not talk with reference, a single point I've talked about, if you do not talk about this point with reference to any point, right? If I talk about where is this point from this location, right? That is a vector, right? It is a vector. Where I'm talking about the location of a particular data to a reference, right? There is some length and some magnitude. Both things are available. Some magnitude and some kind of direction available to the data. What is talking about positive, negative, northeast, northwest, whatsoever it may be, right? I'm not talking about that. But some direction, then I'll say that is a vector quantity. If it is not vector, right, it is some data, right? Or something that you can think of which is directionless. Think about your height. For example, your height. Suppose I personally talk about myself, I stand 182 centimeters, right? I stand 172 centimeters. Now, if you talk about my height, if you measure it from my head to my toe, if you measure it from head to toe, you put up the scale from head to toe, I'll get 182. If you put it up from toe to head, I'll still get 182. Does it make a difference? That's scalar, right? Direction does not make a difference. How do you measure it? It does not make a difference. Now let's talk about gravity, for example. The gravity on the earth, suppose this is your earth, and the gravitational pull that we have is 9.8 meter per second square, right? I'm talking about very standard basic figures, right? So if something is attracted towards the earth, it is coming at an acceleration speed of 9.8 meter per second square. Agreed? Now, if something is going away from it, then I do not have the acceleration. We call that as the word deceleration, right? But that is nothing but minus 9.8 meter per second square. The direction changed, right? The magnitude remains the same, but the direction changed. Here it was adding up to the things. Here it is retracting from those things. Make sense? So direction changed. Or you can say the force, acceleration, velocity, these kind of entities which are direction wise. These are called as the vector quantities. Are we good? Thank you. So zero dimensions data or zero dimensional data or zero dimensional array are those that do not have any direction, right? And are created using scalar value. Okay. So how will I put it up? Very simple thing. So I'll name that as ARR0D get is equal to, I'll use numpy library dot the array function, as I said that here, using the array function. Good. np.array, and I'll just put up a single scalar value. Let's say put up 5. I put up a single number 5. So I'm asking it to create up a numpy array, which is of 0 dimension. And so what I'm asking it, numpy, please create an array and use this data. This data is in no dimension. I'm just putting up a scalar value. Good. It creates up an array. You might not agree to this. So let's first of all print that value, ARR0D. I'm going to print that data. I'm going to print the data type of this data, print the type of this data. If anybody is not comfortable with any of the function that I'm putting up or using, let me know. If you do not ask it, I will not talk about it, because this is some basic functionalities just coming from the very basics of Python, like type function and print function that I've used. Quickly. Done. You can see 2 results on the screen. Confirm if they're visible and you have questions on them. ARROD, where did I use it? It's not OD, it's a 0D that I've used, and that typically is a variable name that I've taken up. You can take up anything. You can take up your name instead of that. If you do not like that particular part, you can put up your name, Asif. If you want Asif, I will put up Asif over there. If you don't like it, I can put up ASIF. It works well, no problems. It's just a variable name. That is our choice. It has to be a valid name as per the Python documentation. That's it. Great. But I've just kept that as ARR0D so that it becomes, understandable that I'm creating up a 0 dimensional array. That's the idea. That is the only one idea, right? So at a later stage, when you are going to look at the codes, you would get to know that it's a 0 dimensional array. Everybody able to get that as a numpy 0D array? eyes, nose, maybe is ND array. But is it zero dimensional? How will I put it up? I need to know the number of dimensions, isn't it? So how will I know that? Same array, I can use another function. This is a numpy function, so please remember. What is ARR0D? It's a numpy array. It offers me a lot of functionalities. One of the functionalities is to know about the number of dimensions it has, right? So I want to know ARR0D, the number of dimensions, NDIM. That gives me what? The number of dimensions for a particular array. So this is your array, and I want to know the number of dimensions of it. I want to print that up, so I'll just put up a print function before it. Print the number of dimensions. Good. Can you see 0? See, guys, I want you guys to code along with me. If you want me to take a pause, I'll pause it up. If you want me to wait, I'll wait for it. That I am trying to write down the piece of code. I'm fast and not able to go along with me. I will wait, but confirm that you are getting also the same results or similar results. If you're getting any kind of error, if there is any issue, any problems or anything, let me know. I'm here to help you out. No, Asif, I will not do it. I want to look at my screen, type it down, and then do it. There is a deliberate reason behind it, and I'm being very blunt on this because I wanted to make learn and not understand how to do a copy paste. Right? You want me to take a pause? Why we cannot use Rosie Ravichandran np.ndim AR of 0D? See, the idea is slightly, different into that. Do you understand the concept of classes and objects, Ravichandran? Now that was a specific question coming from Ravichandran. Right? Basic understanding. So the idea is that this property, right, ndim, is a class attribute, right? Like when we create up a class, we have an attribute called as ndim. Good. And then if you talk the way you are talking about, you're talking about there is a function, right? You're talking about the way I'm talking about, that I am trying to write down a function called as ndim followed by an argument of the array, right? So that is a method, right? If I have a method by the name ndim, I can call that method passing an argument data, right? So there is a difference between a class attribute and a class method. So here ndim in Python with numpy library is given as a class attribute rather than a method. There are certain things which are methods. I will use them as methods, but there are certain things which are as a class attribute. I need to use them as an attribute. Make sense? Now here you should know what is a class attribute. That's the basic idea. Thank you. Again, team, I'm okay with 2 plus 2 is equal to 4, but ask it. If you do not ask it, I will not get to know. But right, can I move on to the next attribute or next property? Yes, no, maybe quickly. Yeah, thank you. So next property that I want to talk about is the shape. So same thing, I've just copied and pasted back, and I'm writing down the word shape. Now, what does it tell me? Now, listen to that definition very clearly, because this is going to be a very, very important attribute that you will have to use multiple number of times at multiple number of places for multiple number of reasons. Right? So shape is one of the very important attribute, right? Very important attribute. So you need to understand that very clearly. what does it talk about? It tells you the number of elements in each dimension as a tuple, right? Now, can you tell me what can be the expected output from the information given by me? Zero. Preeti says zero. I tend to disagree. Anybody else? The Preeti, your approach is not wrong, but the way you are interpreting the answer is not exactly the way it should have been. Narendra says nothing with a round bracket. Zero itself, Abhinetri. No, it's not going to be zero again. Yeah, you mean an empty tuple? I agree with that. Zero is not an empty tuple, right? Not square brackets, Kunal. Yeah, round brackets. What I want is that it is going to talk about the number of elements in each dimension. Now, how many dimensions do I have? Nothing. So there is no dimensions available, so I cannot count any number of elements in any number of dimensions. Right? So what I'll get is a tuple that is having nothing. A tuple without nothing means an empty tuple. An empty tuple will look like this. Are we good? Sensible? Thank you. Let's talk about the next property. Size. And I'm going to give you the definition for size too. It gives the number of elements, in the array. Now, what should I expect over there? Arrays are denoted by square brackets. See, arrays are denoted using square brackets. Agreed. But the point is, I'm not denoting the array. I'm denoting the shape of that array. If I have to print that array, ARR 0D, the number of square brackets, I'll come to the square brackets concept in a short while. Someone has, let me just scroll back up. It was Kunal. So Kunal, I'll come to the concept of square brackets in terms of Python in a short while, and I'll talk about 1D array. I'm still stuck at 0D. Right. So just hold on. I'll talk about when the square brackets comes into the relevance. What is the purpose of square brackets in terms of arrays? What is the significance does the square brackets hold up? Everything will come up, but I need to put up the right path. So coming back to the size. Now, when I talk about size talks about the total number of elements possible in that array. Now, here I have only one element, so I'll get the answer as 1. Almost everybody was wrong, or everybody was right. Next property I want to talk about is a very basic property. It's called as the D type. Now, what does D type tells you? It talks about the data type of every element in the array. Now, some of you would be getting int 64, some of you would be getting integer 32-bit, 32, right? Let's have a check. I've got int 32 over there. Anybody got int 64? I am expecting that from the Google Colab users. Right? int 64. Now, what is the difference between that? You're using a local Mac. What is the data type that you got? D type. Shishodhya, Narendra, 64. I'm okay with that. Great. Now, what does that mean? Any idea? What does that int32 means? It means that the machine has stored the data as an integer of 32-bit. Interview question team. Let me ask it. What is the default size? What is the memory allocation size? Memory size of integer in, or let's say integer 32-bit in Python. Now you see that I have given up a word. I've said that what is the memory size of integer 32-bit in Python? Now you might say 32-bit, but that's not right. It goes like this, that by default, when it is 32-bit, right? Python takes it at not as 32-bit, but it takes up that as 28 plus 4. That means it is allotting 28 bits to allot the data, and 4 bits are incremental. That means if a number can be accommodated in 28 bits, it will accommodate in that. If it cannot, it will use next 4 bits for this. If it cannot be accommodated into that, it will increase that by 4 bit. Is my screen not visible? Akshay is not able to see it. Rest of the team, you can see. Sairam, thank you. So Python is, kind of a language that, does not allow, or it allows me to avoid data usage or data leakage. Does not happen with that. For example, let's say if I talk about A, let's say I'll put up a number A is equal to 999. 4 times 9 works well. Print A. I can see 999. If I increase that to any number of 9s, I still get that same number. If not okay with that, I will copy that and paste it up multiple number of times. I'll still get the same number. That many long values are not supported in other programming languages, but Python does it. What it says is that I am willing to extend your data structure. Willing to extend it. I'm going to give it a default value. There is a library that I can use, that is a sys library. I'll just show it with that. Let's put up import sys, how much memory it takes up. For example, if I put up here sys dot size of, okay, great, very simple function, sys dot size of. All right, I want to get it up. So get size of, yay, and let's print it up front. Now I want you guys to concentrate on here the number of data points that I'm going to use. Look at this. You will have a great knowledge on this. I'm putting up 9,999. Good. What does it tell me? What is the size here? 28 bits. It is in size in bits. Let me increase one more 9. Still 28. So that many number of data can be accommodated in 28 bits. If I put up another 9, 28. If I put up another 9, still 28. Another 9, still, now it becomes 32. Make sense? Right? So whenever this data cannot be accommodated in 28 bits, it increases that by an incremental value of 4. Make sense? Why by 4? Because my machine is 32-bit. In 32-bit, it is going to increase by 4 bits. In a 64-bit, it is going to increase by 8 bits. And it's going to not start with 28, it's going to start with 56. Make sense? Now, if I just put that number, let's say double it up. I'm just putting the same number, doubling it up. You can say it goes up to 36-bit. Akshay Sharma rejoin, because many all the other learners are able to use and see my screen. So it has to be an issue at your end. Please rejoin. Akshay, then it has to be something at your end. You need to check at your end, please, because it is nothing from my end. Every other learner apart from you is able to see my screen. So something that you might have disabled around, or maybe something that is causing that problem. You might have put up, hide screen or hide whatever. SY's function is size. See, SYS is a library, Asif, that's a default library to Python that is used to know about the system interactions. That means how is the machine interacting, the hardware component part, right? So it's a library. It has multiple number of functions. One of the function that I have is get size of, that talks about the amount of memory or hardware memory that is taken up by particular data. So get size of gets me the memory in terms of bits, which I can see over there. Not in bits, but in bytes. Are we good? Thank you very much. Now, very common question. Now, had that been a 64-bit integer, same thing would have varied. Those who are using 64-bit machine, you would have seen that I have 36 over there, you might have 72. Same example, same data, you would have 64 or 72. Right? No, it is not starting with 28. It starts with 56. Because for 64-bit, it is 56 plus 8. 8 is the incremental term. For 32-bit, it is going to be 28 plus 4. INT 64, I am getting triple line is 36. Not possible. Integer 64-bit does not start with 36 bits. Not possible, Kunal. Data used is 28. For me, it starts with 28. See, that is a separate thing, individual machine-wise. Kunal, hold on. See, it is an individual machine-wise things. You might think it is 32-bit or 64-bit. I'll talk about individual machines if you require, but that's not the point. The idea is that I want to convey is that what your machine is going to be, how it is going to take up the data. Either it is going to be a 32-bit data or a 64-bit data, right? That is the main concern. Does not matter. It does not make an impact at the end of the day, as of now for you. As of now, it will make an impact when you are dealing with, bigger corporate clients where every single bit of data is an important, right? Things you want to, save out on even a single bit of memory. Optimization of the project is a concern. You might require that information at that stage. So I just given that as an additional information to you guys. Good. The size of integer. There is a concern with the size of floating point. There is a concern with the size of the strings. I am not going to talk about that at all because that is going to take me a long time. But what I'm trying to bring in is the perspective where you can, extrapolate your knowledge, how you can utilize your time after today's session, coming up to tomorrow's session, and have multiple more number of questions for me, right? Giving you something new to explore. Hopefully. Are we good? Next thing I'm going to talk about is another property into the same array, the zero-dimensional array, and that is the item size. Give that a look, team. Item size. What is that item size? Talks about the amount of data or space allotted in bytes. So it has given 4 bytes of space. Those who are using 64-bit machine would have had the value as 8. Good. Confirm. Everybody okay with this? So on my machine, size of is 32 and item size is 8. Abhinetri, I need to have a look into the machine because there will be a lot of things to consider. But what I have told you about is the standardization. Either for 64-bit, it should be 8. But if there is a disconnect, then there should have been a clash between your machine operating system size and the Python installation size, right? Maybe your machine is 64-bit and you have installed a 32-bit Python, or the vice versa, right? If there is a disconnect between the version, at times what happens is people install, okay, they think that my machine is 64-bit and they install a 64-bit Python, but at the end of the day their machine is 32-bit only. So there is a clash happens. So some certain things will work on 32-bit, certain things will work on 64-bit. That is going to happen. It is going to happen, right? Nonetheless, let's try to talk about a vector quantity now, because I'm starting with 1D array. Let's talk about a data point. Till now, I've seen a value 5. I've just given a number 5. I did not tell it what it is, in which direction it is, where it is from. Now, in my coordinate system, right, this is your x-axis, this is your y-axis, right? If I have to refer a point, let's say this one, this is 3 on x-axis, let's say 4 on y-axis, okay? So that means that I'm moving by 3 data points on x and I'm moving by 4 data points on y, then I'm reaching to this point. Make sense? From where? From my origin, which is 0, 0. Good? Agreeable? Yes or no? Thank you. Now that means from my origin, that is into some direction and have certain length. Acceptable? Now, if I have to represent this point, can I say that is x, it has a value on x-axis, it has a value on y-axis. That means I have two terms at least. X-axis holds a value 3, y-axis holds a value 4. Correct? Or can I say that this is individually a scalar value, this is also an individually scalar value, but I combined them together to make up a vector value, isn't it? So when I combine multiple scalar terms, it becomes a vector. And that's what I'm going to do over there. For 1D, I'm going to create up a combination of multiple vectors. So let's take up a vector quantity. I'm going to take up a list 1, 2, 3, 4, 5. A simple data, right? A very simple data 1, 2, 3, 4, 5. A simple list that is 1, 2, 3, 4, 5 values, and I'm naming that as ARR1D. And I'm not going to change up anything else apart from the variable name. And I will request everyone. Yes, Akshay, tell me. LSM would be available, but if it is a video issue, you can let me know. I can see some responses coming through. Akshay, you will be getting a call in a short while from a call or connection coming from Anurag. Great. So what I can see here are some responses. Let me just quickly have a look. Okay, here it goes. Sairam got Sairam has 1, 2, 3, 4, 5 class numpy ND array, comma 1, 5, comma 5 integer 32 and 4. Then 5, 4, 3, 2, 1, 4, whatever the number is, that does not make a reference to me. 8 bits, 8 bytes. Okay, 1, 2, 3, 4, 5 class numpy ND array, 5, comma 64. I'm okay with Kunal's. Sairam is okay. I'm okay with that. Again, 14 is okay. I'm okay with that too. So most of you are getting the correct answers as expected. But the idea is to understand or comprehend the results. Number 1, print 1D array. Now look at this. When it was a zero-dimensional array, it was a 0D array, right? How many number of brackets do you see in the output? Square brackets? No brackets. Good. Now, when it becomes 1D, can you tell me how many brackets at the beginning and or at the end? I'm using the word or, not and. Brackets either at the beginning or at the end. Number of brackets. You have 1, right? So for zero-dimensional arrays, in display, you will not get any brackets around it. It's still that is an array. For 1D array, you will have 1 square bracket around that entire data. When it becomes 2D, you will get 2 brackets. When it becomes 3D, you will get 3 brackets. When it becomes 4D, you will get 4 brackets. So if you need to know about the dimensions of the data at all, and if it is an array, you just look at the starting brackets or the ending number of brackets. Whatever is the count of starting number of brackets or the ending number of brackets, you can tell that that is the dimension of that array. Good. Here, it is ARR 1D starting with 1 bracket. So my number of dimensions is 1. How many dimensions do I have? I have 1 dimensional. So for the first dimension, how many elements are there? Essentially means within the first brackets, how many independent individual elements are there? So within the first pair of brackets, this is starting, this is ending. I have 1, 2, 3, 4, 5. So within that first bracket, I have 5 number of elements that is given there. And since it is a tuple, so I can see comma. Size gives me the total count. That's the size. That's the memory size, a D type, and the memory size. Are we good? Anybody? Any questions with this? Yes, no, maybe. Confirm. This is concepts comes from the tuple concepts. What is a tuple? The definition of tuple. Right. Suppose if I make a value, for example, many people say that tuple is a value is within the pair of round brackets. That's wrong, right? Let's say if I make a tuple t1 is equal to, and I want to write down a single value. Let's say if I put a 5 and I put that up within the pair of round brackets. Good. Now what do you think? It should be tuple, isn't it? It is not going to be a tuple. It is not going to be a tuple. I'll tell you why. That why part. But let me just show you. Print the type of T1. It's going to be an integer. Look at this. Observable. Now the moment if I just change that to a comma, right, it becomes a tuple. Now what is the difference? The difference is, try to understand. For tuples, it is not mandatory to use the round brackets. The mandatory condition is it should be a comma separated value, right? I can write down, let's say for example, T2 is equal to 5 comma. Did I put up any bracket? No. Yet if I just ask you to print the type of T2, right, it's a tuple. Good. So brackets does not make a sense. What makes the sense is the comma, right? So if there is only a single value and I still want to represent that as a tuple, right, then I need to put up at least 1 comma. There are multiple values in tuple. Square brackets is must. No, it's not mandatory. If you need to take out multiple values, let's say T3, not mandatory again. T3 is equal to, I can put up 1 comma 2 comma 3 comma 4 comma 5. That still will work as a tuple, not a problem. See, the brackets are not mandatory. These are just notional. In case of tuples, the round brackets are just notional. You do not require round brackets to create a tuple. It's just notional, just to make it separate looking kind of thing from lists and so on. That's the only ideology behind it. Otherwise, you do not require them. To create tuples, you do not require round brackets. See, I have not used round brackets on 1, 2, 3, 4, 5. I still. Yes, with a list, Narendra, yes, you require square brackets because that's the fundamental definition of list. These are comma separate values within square brackets. For tuple, it is not the fundamental definition. The fundamental definition of tuple is comma separated values. That's it. The use of round brackets is promoted by many people, but it's not the truth. Many people say that okay, tuples is values which are enclosed in the round brackets. No, it's not. It is just comma separated values. Anything which is comma separated is by default a tuple. But if there is anybody else questions, 1D array, I have talked about endim shape, size, D type, and item size. Typically, you will not see any difference. Okay, now I cannot comprehend that. The two-dimensional array. Now, when I combine multiple scalar values, I got 1D. So when I combine multiple 1Ds, I'll get 2D. Right? So I'll take this 1, 2, 3, 4, 5 again. I'll copy it, pasting the same thing again, but just changing the values to 11, 12, 13, 14, and 50. And combining them together again as a list. So if you look at this, this is a list of lists, right? I have an outer bracket that is defining that I have two lists in between, list 1 and list 2. And within that interior lists, there are 5 elements here and there are 5 elements here. Are we good? Changing the variable to 2D. We're supposed to reach out to a different place in this current situation. But if you can look at this part and tell me if you are okay with ARR 2D or not. I'm not talking about anything else apart from creating the two-dimensional array from a list. First of all, just look at the starting number of brackets, ending number of brackets. It's a 2D array, hence I've got 2 brackets. Then that is your number of dimensions too. That is why in my tuple I have 2 values. It says in first dimension I have 2 data points. What is your first dimension? First pair of bracket. This is starting over here, ending over here. How many elements? Element number 1, element number 2. Good. So that is why I have 2 over there. Then what is your second dimension? That is your second bracket. It starts over there, ends over here. Number of elements 1, 2, 3, 4, and 5. And I got 5 over there. Make sense? So what I want you to understand is how to read that shape output. Now, in a similar fashion, I can create up a 3D array too, a 3-dimensional NumPy array. Great. When I combined scalar values, it became 1D. When I combined 1D values, it became 2D. So when I combine 2D, it will become 3D. Right? So I'll just put it up. Same thing, copied, pasted below. Good. And I'll put up create a 3-dimensional array. So that would be a rarity that you will be dealing with a 3-dimensional data at the beginner level, but maybe you might be dealing with multiple dimensional data, so you should understand what the dimensions are, right? So I'll take up this 2D data that we already have had. I'll copy the same information, comma, paste it back again, and I'll enclose that another pair of brackets. So this is one 2-dimensional data from here till here. This is another 2-dimensional data from here till here, which is again enclosed as a single unit. So let me just put up as a reference a different numbers 21, 22, 23, 24, 25. Here I'll make it 31, 32, 33, 34, and 35. Just to make the changes, right? And now you get the 3D information. What I want you guys to concentrate on the result of endim, result of shape, result of size. The D type item size is not going to change. It's going to be same thing because I'm using the integer values, right? So not into this part, but look at this. It is an array. Number of dimensions is 3. First dimension I have 2. Second dimension I have 2. Third dimension I have 5. Total number of elements is 20, which is a multiplication factor. 2 into 2 into 5. Get that value. Agreed? Thank you. Now, when it says that I have 2, 2, 5 shape part, look at the outermost bracket. This is the outermost bracket, right? Which closes over there. The number of elements that I have in that bracket is this. I have here till here. This is one element. This is your second element, right? Two elements that I have in the outermost bracket. Good. So hence I have two over there. Then I will look into the second bracket. If you look forward for the second bracket, right up there, this is the second bracket, starts over here, ends over there. Number of elements, 1 and 2. And hence I have the second 2 over there. Good. And then I look at the third bracket. Third bracket starts over there, ends over there. 1, 2, 3, 4, and 5. And I've got 5 over there. Is that sensible? Very critical for me, for you guys to understand the shape parameter. How is the shape calculated? What essentially it means, and how it talks about the real world information. Okay, thank you. Let's think of a data. I'll not take the same example. Suppose there is a cuboid. Good. There is a cuboid that you have, right? A cuboid looks like this. Agreed? I may be bad at drawing, so please pardon me on that. I've drawn up a cuboid. Now, there are 3 dimensions to this. I'll use a different pen. Okay. One is this dimension. The second is this dimension, and third is this dimension. Agreed? Now, can you tell me how many number of layers do you have in this dimension? That is your first dimension. I have 1, I have 2, I have 3, and I have 4. There are 4 layers. Accepted? So that is my first dimension. Second dimension is the one that you have in vertical. Can you tell me how many number of lines do you have in the second dimension? Rows? 3. That is my second dimension. Can you tell me how many number of columns do I have? 2. Thank you very much. That is my third dimension. That is the total shape of my data. Depth, rows, and columns. Make sense? Awesome. Thank you. So 3-dimensional structure will look like a cuboid, or maybe it can be cube as well. Right? If it is equal all around, then it can be cube. But it's kind of cuboid. Are we good? Hopefully that makes sense. So when we look at this data over there, here, so I have, 1, 2. The depth is 2. That means I have 2 different layers of numbers, layer 1 and layer 2. On the layer 1, I have 2 rows and 5 columns. On the layer 2, again, I have 2 rows and 5 columns. They are, sandwiched together. Good? Yes, no, maybe up to 3D. Whatever I've taught up so far, if there is any problems anywhere with any of the things, you need to tell me, okay, I'm not able to understand this. This is way beyond, my level, or something you're talking, hypothetical, you became, kind of, let's say, how in terms of those things are way beyond anything, but ask it, please. So we use first 3 only. Essentially, you might come across Akshay with 4D and 5D data, but when we are going to do the data processing part, right? When we are going to deal with how to manage or manipulate the data, we do not deal in more than 2 dimension. Even 3-dimensional data is not very much comprehensible, not very much processable. So essentially, when you talk about data manipulation, data exploration, data analysis part, we deal in the data with 2D, because that's the best possible way around to deal with the data. If array stores the same data type for data, why will we have to use D type for every element? See, the D type is a function, or it's an identity given, or attribute given to us to know the data structure or data type of every individual element available in it. It's going to be common for every single data element. It just tells us that what is the data type. It's an informative function and of no other use. It will be of use when I will talk about Pandas library. Same attribute D type will become different for you when the data structure changes from array to a list, not a list, but to a series and a data frame. So the idea here is that you need to know what is D type tells you. It talks about the data type of every element into the array or into the data structure. That's the idea behind. Good. In arrays, we know that by fact that every element is going to be of one type. I'll also talk about what is the overriding factors and so on. When is what going to change up? What if it is a mix of type of values? A lot of things will come up into the picture, but not today, tomorrow. Confirm if you are okay with creation of 1D, 2D, 3D, 0D arrays and basic properties. I'm not even looking for D type. Endim, no. Shape and size. And if you do not understand size, I'm okay with that either. Only the shape property. NumPy. Not too many of those. We'll not talk about too many functions today. I'll start talking about very basic functions, to be very precise, and we'll talk about the arrays now. We'll start with the very basic functions of the arrays in terms of how will I put it up. So there are three basic functions that I want to start with, or rather two basic functions of the arrays, or in terms of understanding what NumPy arrays are. So we'll start with some functionalities. Number one is the reshape function. Now, team, please try to understand that you may still not find it relevant in terms of when and why I'm going to use those functions. But as of now, just know them, that these are certain things that you can do. Good. So reshape function, what is the idea behind the reshape function? The reshape function allows me to change the dimension of an array from any shape to any shape. Now, shape does not make a difference, but the idea is that with the constraints in the resultant array, that's the idea behind the reshape. So let's consider an array for an example. Okay, I'm going to put that up array. Let's say ARR is equal to np.array. Good. And I'm putting up certain elements 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's put up 10 too, or 0. Good. Now, can you tell me, what did I miss? Invalid syntax of 2 commas over there. Number of dimensions that I have. Number of dimensions of this array, 1. The shape is a tuple of 10 elements. And the size is 10. When I talk about the reshape functionality, it talks about that the size will remain consistent. That means I will only have 10 elements, but I can modify the shape. If I modify the shape, that means I'm altering the number of dimensions too. Now, suppose if I have 10 values, right? Very simple thing. This is the last thing I'll take up today, right? I'll wind up the session for today. Maybe after these two functions, right? So if I have 10 elements, I can arrange them as a single data line of 10 elements. Or I can do them as 2 rows and 5 columns. I can do them as 5 rows, 2 columns. I can do them as one layer of 2 rows and 5 columns. I can do them as one layer of 5 rows and 2 columns. I can do it as one layer of 2 rows, or rather 1 row, 1 column, and another one thing, right? I can make it into 4 dimension. So it is dependent upon to me what are the number of dimensions that I want. So I will have a given shape and I want to modify that shape to a different form. But the only objective that I'll keep on remembering is that I want to make sure that the number of elements that I have before I reshape and after I change, that remains consistent. Good. Now, here I have 10 elements. How can I reshape them? Let's say I want to put up ARR underscore reshaped, and I'm putting up the reshaped as 2 rows and 2x5. Good. So how can I do that? Same array ARR, and I'll use the numpy function called as array of the reshape. Good. And I want to put up the new shape as 2 rows, 5 columns. Good. Let's have a look. Print, same thing, ARR reshape 2 by 5. And now you can see that those numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, which were linear or one dimensional, now has been changed to 2 dimensional. Just to verify, I can print ARR before the change and after the change. Good. Now before the change, you can see that it starts with 1 bracket, ends with 1 bracket. After the change, it starts with 2 brackets, ends with 2 brackets. Can I make it 3 dimensional? The answer is yes. How? I can let's change it to the shape of 1 layer with 2 rows and 2 columns, or 2 layers. Let's put it up of 1 element, and you can see this now. This is your 3-dimensional thing. Outermost dimension has 2 things, 1 and 2. The second dimension that has only 1 thing, starting from here, that is only 1 thing that I have in second dimension. Third dimension has 5 things. That is 1, 2, 3, 4, 5. Are we good? Eyes, nose, maybes. So the ideology remains that the number of elements should be same. That is the idea behind the reshape function. Now, suppose if I have a 2-dimensional array, let's create a look at the 2D array. I'm going to bring back my example. Next function that I will put up is flatten. What does it do? It converts any dimensional array to 1-dimensional array, 1D array. Right? The role of the flatten function is to convert any dimensional array to a 1-dimensional array. Let's take up an example. Let's take a print ARR 2D. We have created a 2-dimensional array earlier, right? In this particular batch. And that is how it looked like. I have 1, 2, 3, 4, 5, 11, 12, 13, 14, 15. Good. Is it 2D or 1D? 2D. Thank you very much. Now I can directly convert that without using the reshape. I have a choice that I will tell it, okay, I want to convert that into 1D. I can put up, let's say, ARR 2D dot reshape, and I'll tell the number of elements. That's 10, comma, that's the shape. And I get a 1D array, right? Now here, what is the problem? The problem is that I need to know the number of elements, correct? I need to know what is the size of my data. Accordingly, I can use with the reshape to convert it to 1D. But if you do not want to take that into consideration, irrespective of the size, what you can do is you can put up ARR2D dot flatten. Flatten means what? It is supposed to convert anything and everything into 1-dimensional. irrespective it is 2D, irrespective is 3D, irrespective is whatever D it is, right? Number of dimension does not make a difference. But flattened function, without knowing how many number of elements are there, it's going to convert everything into 1D. Right? I give you a block of iron. This is a block of iron, right? What is the dimension of this right now? Suppose it's a sheet, two-dimensional, right? Now, if I ask you to make it a wire, make it a wire. What is the thing that you're doing? Make it in 1D. Right? In order to do this, what you would have to do, you might have to beat it around, molten it up, do whatever you want, right? But you want to make sure that it comes into one dimensional instead of two. If I'm converting this to this form, isn't it? I might have to beat it around, I might have pass it through some kind of tools and gadgets, but I can get it 1 to 1D, isn't it? Same thing is done by the flatten function. The flatten function is going to take up any dimensional data and bring it to one dimension, right? Any dimensional data. It can be 2D, it can be 3D, it can be 100D. Does not make a difference to me. That's the use of flatten. What is the purpose? See, at times, to be very precise, it is very, very complicated to imply certain functions on two-dimensional or multi-dimensional data. When it is a multi-dimensional data, many functionalities I cannot directly implement on them, right? So what we would like to do is, I would like to bring that down to a lower level of dimension. That means one dimensional, apply certain concepts and bring it back to the upper level. So I would be doing those things at a later stage where I'm going down from, let's say, 3-dimension, let's say from 2-dimension, I'll come down to 1-dimension, do some job and bring it back again to 2-dimension. Because applying things in 2-dimension is complicated, but doing the same thing in 1-dimension is easy. For example, if I ask you, now this is coming from little bit of mathematics team. I've not yet talked about mathematics. But suppose if I ask you to multiply this is a two-dimensional data, 1, 2, 3, 4, 5, 6, right? Two-dimensional. I ask you to multiply it by 2. Is that easier or is this easier? This is option 1, this is option 2. Tell me which option is easier. Option 2. Why is it easier? Because this is flattened out. This is one-dimensional, right? This is two-dimensional. So at times, I'm not so talking about only the multiplication process, but in general, there will be a lot of processes that you will deal with in the future prospect, where in dealing with high dimensional data like 2D, 3D, 4D, 5D will be very complicated. But the same thing could have been achieved by a lower dimensional data. So I would like to reduce the dimension of that data, and there flattening or reshape will help us. Make sense? I have taken an example here, which was a small array. Had that been a very, very huge amount of array, because at a later stage, I will introduce you certain kind of arrays where the number of data points would be in millions. I will bring those kind of arrays into your picture. Now, in this scenario, if you try to do it that way, right, it would be a very, very slow and lagging process. You will not love it. Otherwise, it's okay. Yeah, you can take out the length and extract every single element one by one and make it 1D. You can do it. Allowed. Right? But in real life as well, there are a lot of things which are allowed but are not considered as a good practice. Right. So I have a backup question coming up from Asif about to go through with one-dimensional, two-dimensional, and three-dimensional. So I'll start with a very simple example, right? A very simple sort of example, wherein suppose there are 10 dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, as you can see on my screen right now, these are some 10 dots, some 10 different data numbers, data points, data values, something like that. Okay? Now, if I arrange them in a straight order, in a straight line, one line, it means point number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's your one dimensional. Good. If I arrange them, these things, these 10 dots, again, into a two-dimensional space. That means suppose I divide them into, let's say, something like this, two rows, and 1, 2, 3, and let's say put up a fourth line, and I put up dot 1, dot 2, dot 3, dot 4, dot 5, dot 6, 7, 8, 9, and 10. I am putting them into two-dimensional space. So it is only about the arrangement of the data, how you arrange the data in the memory is what makes the difference. When you come across 3D, right? Same information could have been arranged in three-dimensional space. Right? Instead of creating a plane like this, I can create up a three-dimensional object. Think of a three-dimensional, like a cube, like a little thick thing, right? Which contains 1, 2, 3, 4, and 5, like this. And then we have the same thing over there. Make sense? So that's the idea behind 1D, 2D, and 3D arrays. It's all about the data arrangement. How is the data being arranged? Are we good? Asif. Thank you. Now, moving on to the next part, which is very important, very critical for me, and that is the functions that we have been started discussing about, yesterday. We started with some of the functions in NumPy as of yesterday, right? So we talked about one of the important function, which was the reshape function. Good. Then we talked about the flatten function. Everybody okay with the reshape and flatten? Any questions on that? Next function that I have into the pipeline is called as the transpose function. I'll start with the transpose function. The transpose is something I am expecting should be a very common word for everyone. Can someone tell me what is transpose means? It converts the array reversing rows and columns. I'll not say that in that terms. Reversing is not the correct word, but switching would be the correct word, right? Abhinitri. So, or rather, it switches rows to the columns. It switches the array rows as columns, or vice versa. That's the idea behind transpose. Let's understand that through an example. Let's import NumPy. Why I am doing that is because many of the people are not going to use, NumPy would not have been available for you guys. You might want to restart with a new file. I'm using the old file. I could have worked on the old file itself. But let's start with import NumPy as NP. Let's create up an array, a 2D array. So let's create ARR is equal to np.array. And there, let's create up a two-dimensional array. So in the first dimension, I have one element, comma, two element, comma, three elements. So I have three things in the first dimension. In the second dimension, I'm putting three elements again, 1, 2, 3, 4, 5, 6, and 7, 8, 9. Good. Let's have a look at the print ARR, just to look at what ARR looks like. That should look like an array or a two-dimensional structure with three rows and three columns. Everybody okay with this? Now, someone quickly confirm what is the first row data? What is the row data for first row? 1, 2, 3. Thank you. Second row is 4, 5, 6. Third row is 7, 8, 9. Agreed? Thank you. Now, what does the transpose function do? Now, there are two ways to do a transpose, right? One is a numpy method, one is a Poisson method, right? So, numpy way is I will ask my ARR that numpy, please do a transpose. So, numpy dot transpose. Transpose of what? The ARR array. At the moment I do it, let me just print that up. And what you now see here is the first row, that is 1, 2, 3, has now become the first column. Agreed? The second row, 4, 5, 6, has now become the second column. The third row became the third column. Are we good? Yes, no, maybe? Use of transpose? Great. Abhinitri, transpose is essentially not for 2D array. We can use it for 3D array, but practically not useful. So if you talk about transpose functionality, yes, it is possible for 3D, 5D or multi-dimensional. You can go for that. But the practical implementation or the practical usage of transpose would only come across for the two-dimensional arrays. Why it is for two-dimensional array? That's the question, major question. So the idea behind the use of transpose, listen to that very carefully. The idea behind the use of transpose is to solve a set of linear equations. Solve linear equations. Anybody understand what is a linear equation? Yes or no? See, it's a part of mathematics. I'm supposed to take that care of that in the mathematics part. No, I have one no coming from Preeti. Okay, great. Let's Preeti take an example. Right, it's a part of mathematics portion. I will reiterate that in mathematics, but just to give you an idea. For example, suppose a data. I'm putting across a data in front of you that contains like information like this. Good. It has 1, 2, 3. I have apple, bananas, and cherries, and price P. Good. This is day 1. I bought 2 apples, 1 banana, 3 cherries, and I end up paying, let's say, $10. Day 2. I bought up 2 apples, 2 bananas, 1 cherry, and I end up paying, let's say, $12. Day 3, I have paid up, let's say, I have used 1 apple, I have taken up 1 banana, and I have taken up 4 cherries, and I paid up, let's say, $9. Good. This is random numbers that I've chosen. Now, day 4, let's say day 4, I am looking to buy 4 apples, 3 bananas, and 2 cherries. Can you tell me how much money should I carry in my wallet? It's a prediction, right? Isn't it? First of all, do we agree that it is a prediction? It is a prediction. Everybody agreed to that? Thank you. Now, if it is prediction, then I need to have a mechanism to get this in. Right? What can I do? So I can now see here that the apples are being bought at a price X, bananas are being bought at a price Y, and cherries are being bought at a price Z, assuming common prices. Right? Then I can say that in mathematical terms, that if I take apples multiplied with its price plus bananas multiplied with that price plus cherries multiplied with their price, that equals to my p-value. Can I say that relationship? Thank you. Now, if I have to satisfy that relationship, that means I need to know the value of x I need to know the value of y and I need to know the value of z. I do not know it yet. Given data does not tell me what is the price of individual apple, individual banana, individual cherry. But can I extract it? The answer is yes. How? I have three separate equations available. If you look at this very carefully, line 1, day 1 tells me if you take 2 apples plus 1 banana plus 3 cherries, you need to pay $10. The second equation says 2 apples, 2 bananas, and 1 cherry, you are going to pay $12. Third equation says an apple, 1 apple plus 1 banana plus 4 cherries is $9. Now I have an equation of 3 variables, A, B, and C, right? Right. So that should be XYZ. You can say that, right? ABC instead of XYZ, I need to have XYZ there, right? The price list, not an account, because ABC is representing the account. So other way around. But can I get the values from these three equations, the individual price for every single fruit, eyes, nose, maybes? If I solve this set of linear equations, I have a method of substitution, I have a method of replacements, which I can use and solve this. Three variables, three equations, we can solve it, correct? Mathematically. Good. But the problem is that when I'm doing the mathematical solution, as humans, we can solve it easily, right? I can tell it, okay, equation 1 minus equation 2 minus 2 times equation 1, equation 3 will help me out, solving it out, and we can do that. Make sense? But the point is the machine cannot do it. Then we have an alternate methods. Right? In that alternate methods, I solve these set of linear equations using matrix and the concept of matrix, right? In solving that, I will require the use of transpose. I would require to use transpose somewhere because I need to calculate an inverse of a matrix that is called as inverse. The inverse is coming from the transpose of a cofactor matrix. It comes from the transpose of a cofactor matrix. Maybe may not find it very relevant right now because you do not know what is inverse, you do not know what is cofactor, right? You may not know about it. I will come across to these points. What is a cofactor matrix? What is the transpose? And how does it make a difference? How is the inverse calculated? How is the linear equations are solved using matrices? Everything is will follow. But the idea for the reason understanding the transpose concept is, because that's what we're trying to talk about, is to know that what is transpose. So everybody able to understand what is transpose, yes or no? Where and why to be used, there's a lot of things into that. Is that okay, team? Thank you, Abhinitri. Now there is an alternate way, which is called as a Pythonic way to do the transpose, right? A Pythonic way. This was a numpy method that I've used, but I can also take up the transpose of ARR. I can put up ARR dot uppercase T. When I do this, the uppercase T letter is predefined in Python to take a transpose of a two-dimensional data. You can see the same out. Can you see that? 1, 2, 3, 4, 5, 6, 7, 8, 9 as being separate columns. So either you can use the numpy method or you can use the Python method. Now, why did I talk about this part? np.transpose and T both, just because to let you know that there are multiple choices. Good. Thank you. Now I have a question for you guys. Would you like to work on that? I'm sending that data to your screen too. On my screen, can you see something? Read out that question and tell me the answers. If there is anything that you do not know about, well, the data attribute I've not talked, so leave out on data. It's not required. It does not any kind of good information. It's okay. Rest of things. Let me see if someone can send me the outputs quickly. You can see the statement on my screen. That's also available on to your chat window. You have the data available. Give me the answers. And I'm not looking for the outputs. I'm looking for the codes. What you write down. Someone. So in order to solve, I have a given data of the temperatures. I will take that as an input. Temperatures is equal to this. And it says that it has to be a numpy array. Let's say create an array by the name temp is equal to np.array of temperatures. Good. Let's print temperatures. Print temp. Good. I got 1D array. The question says that explore the key attributes of numpy array, including endim, shape, size, dtype, and item size. Can we do that? Something came in. Let me just check. Array dynamic is np.array of that elements. Thank you, Narendra. Dynamic type, array dynamic.endim, array dynamic.shape, size, dtype, and item size. Great. Thank you very much. Good. Anybody else? There was some second part to it too as well, Narendra. I hope so you can do that. So I have 1, 2, 3, 4, 5, 6, 7. Typically reshape is not possible. 7 is a prime number. I cannot reshape it. I can put it 1D, 2D, 3D. That's possible, but that does not make sense. It will still remain the same idea. Flatten does not make a difference. Transpose will not make a difference in this particular data. Should not make a difference. So question number 2 you can avoid if you want. But endim, shape, size, D type, and item size. Everybody okay with that? Confirm? I'm not going to solve it. I'll leave it to you guys. Good? Kunal is getting error in endim. So whenever there is an error, team, paste the last line of your error. Whatever the error output that you're getting, just tell me that. List object has no attribute shape. So you did not convert, Kunal, the temperatures to an array. You need to convert that to an array. Right? You missed out on this statement. Shape is a function or shape is an attribute for an array, not for a list. The temperatures given to me in the information is a list, and this is a array that I've converted into because I want to use shape. Shape is an attribute a property of an array and not of a list. Good. Abhinitri says NM, okay, type of ARR 3, shape, size, D type item says good. I'm happy. Thank you very much, Abhinitri. Transpose is okay, Narendra. But essentially, we will not see that difference in the outcome. Can I move on to the next part? Thank you. Arithmetic and statistical functions. A great coming it from Kunal. Temp, type of temp, temp.shape, temp.size, temp.dtype, temp.nm. Good. Happy. We can have also use end dtype item size as well. I can see the results for dimensions, shape, size, dtype, and item size. Yeah, thank you, Akshay. Looks fine to me. Great. Someone got 8 at the end. Why? 8 byte. Okay, load 64. I'm okay with that too. Thank you. Great. Can I move on to the arithmetic and statistical functions? Thank you. See, very quickly, we want to wrap it up, team. We do not want to waste up too much time onto the things which are not needed for us too much. I just want to make sure that you guys know about those things. Good. Thank you very much. Let's move on. So when I talk about arithmetic and statistical functions, can you tell me what are the different arithmetic operators that are available in Python? Arithmetic operators. Add, good. Like does not complete that. I want everything, Narendra. Kunal has given me addition. You have given me subtraction, multiplication. What are the others? Arithmetic operations. Percentage, that's remainder. Good. I'm still waiting for 3 more. 4 are there into the chat right now. Addition, subtraction, multiplication, and remainder or modulus. Remaining 1, 2, 3. So 3 more left out. Floor division, great. Powers, okay, 1 more left. It's a basic one. Exponential power is same thing, Asif. It's the same thing. Power and exponential. One more left out. Scroll back up into the chat and see what is missed. I can tell it in a flash of a second. Thank you very much, Abhinitri. Division. So we got all 5, all 7 kind of operations. Let's try to implement all these operations using NumPy, because we know as a fact that I can perform that operation using the basic Python operators, right? We have plus, minus, subtract, and so on. So let's try to create 2 arrays. Let us create 2 arrays, 2 numerical data arrays. Create 2 num arrays. Good. So I'm naming them as x is equal to an array with a value, let's say 10, 20, and 30. Good. Let's create another array y is equal to 3, 4, and 5. Good. Let's put up that as np.array of this data. And here too, np.array of this data. Now, essentially what happens here is, I missed out on the comma over there. So essentially here, whenever I'm performing an operation, right? Suppose if I do a mathematical operation like addition, for example, if I perform addition, let's give that a try. I want to print out what happens if I put up x plus y. Can you tell me? X plus y. What should be the result I'm expecting? It adds. Adds what? Asif. So Narendra gets 13, 24, and 35. The numbers. Thank you very much, Asif. Do we agree? I tend to see if everyone agrees to Narendra. Thank you, Asif. Now here what happens is there is a element-wise addition. That means first element of the first array will be now performed operated with the first element of second array. Second element with the second element. The third element with the third element. Good. So every individual element will be matched up together and perform the operations with. Good. Great. What I can see is 13, 24, 35. So 10 plus 3, 20 plus 4, 30 plus 5. Clear? Similar kind of operation. This is done using the basic Python operator, which is plus. Right? This is the basic Python operator plus. But can I do through numpy? The answer is yes. Print numpy dot add. Add what? My array x and array y. The only difference is this plus is common to any kind of things, right? It can be plus with a list, it can be plus with the two numbers, could be anything. NumPy add function is a NumPy function. It's applicable not for everything. Good. Still see the same output. So result wise, you do not see any difference, but there is a processing speed difference and efficiency wise, there is a difference. Good. Difference is in terms of efficiency. Great, everybody? Yes, no, maybe? Confirm. Thank you. Can I do that similar fashion subtraction? Give me the code string. Pythonic way, x minus y. Good. So 10 minus 3, 20 minus 4, 30 minus 5. May I know why the result are repeated twice? Because I have used two different statements. Asif. One is the print statement using the Pythonic way, and another is using the NumPy way. Great. Now, for the subtraction. Length of the array should be same. I will come to that, Satish. So x minus y, and I'm going to replace the word add with the word subtract, not sub. The word is subtract. NP dot subtract. Works well. Good. Again, two outputs because minus operation using Python, minus using operation NumPy. Good. Multiplication. So x multiplied by y and NP dot multiply. Good. Division. I'm putting down all things together now. X divided by y and NP dot divide of x comma y. So divide x by y. Then we have the modulus. Modulus or the remainder, right? You can say that. Modulus. X percent y, or you can put np dot mod mod. And lastly, we have the floor division. Or this is exponential as well, right? So floor division. x /y and np dot floor divide. Name of the func method is floor underscore divide. Objective that I'm trying to achieve is to get you acquainted with the name of the functions that are used in NumPy to perform the arithmetic operations, which are the basic arithmetic operations from the core Python. How can you perform them using NumPy? Sensible? Not sensible? Yes, no, maybe. Thank you. Last option that I want to put up is your exponential. So x operator that we use in Python is double star, x raised to y, or here I can put up np.power. Name of the function is np.power. Done all the executions. Can you check that? Any questions with the results or the outcomes that has been displayed to you? Let me know. Please explain the floor division in power. Good. So floor division, I got these results. Power, I've got these results. Are we good? So floor division, I have 3, 5, 6. Good. Let's have a look. I have 10, 20, and 30 as a part of x, and I have 3, 4, and 5 as a part of y. When I perform a floor divide of x with y, what does essentially that means? Essentially, it means, now I'm not pretty much sure how many of you know about the floor division very correctly. Taking first example, let's say take up the example of 10 and 3. Good. So what I'm trying to say here is with the floor division, that when you're doing a 10, a floor divide by 3, good, essentially it means that I have to perform a division of 10 by 3. Can you tell me what will be the result, Asif, if I divide 10 by 3? It's going to be 3.33, right? Acceptable? Thank you. Now, we look into the number line. In school, you would have studied about the number line that has a 0 at the center. You have minus infinity on the left. You have positive infinity on the right. Right? Good. On to that number line, let's imagine this is 1, this is 2, this is 3, this is 4. Good. If, let's say, on the other side, I have minus 1, minus 2, minus 3, sorry for that mistyping, minus 4, and so on. Good. Now, the division result that I get, what is my division result? 3.33. Where will it lie? On that number line, that's going to be somewhere here. Agreed? That red line. Great. From that red line, the floor division, the concept of floor division says that whatever the division result is, right, in absolute terms, from that point, move towards the negative infinity. I need to move towards negative infinity side. Good. That means from here, I'll move towards negative infinity. That's on to the left. Good. Once I move towards that side, whatever is your first integer value, that is your answer. So floor division is a value coming from the division results moving towards the negative infinity, or rather our integer value, the nearest integer value. Good. So I'll get 3 over there. Make sense? If I talk about 20 and 4, so that come out to be 5. When I divide that is 5. So I do not have to move at all, right? It will remain at 5 somewhere. I do not have to move around because it's already an integer value. 30 by 5 is 6, so I'll already have 6. So 3, 5, 6 should be the answer. Good? Did you understand the ideology behind? Thank you. So can you tell me what will be the output of this? Double slash floor division operator. Can you tell me what is the output of this quickly? Don't execute it. -3, I tend to disagree. Chenna, Keshwara, Kotin, -14, never allowed. That's way different. -3 is not right. -14 is not right. -4 is right. Thank you. How many of you can get to know why it is -4? Because a very common understanding that people think about floor division is rounding off. No, floor division is not rounding off. We need to understand this very clearly. Let's take into consideration a simple example, very simple example. What if I ask you 17 double slash, or let's say 19 double slash 5? What is the result? Think of it. 19 double slash 5, when you will do it, not 19 double slash 5, I'll put it up as 95 double slash 5 or double slash 50. What was the result that I'll get? I would get 1.9, isn't it? Now, if I round off, that should become 2, right? A rounding off should make it 2. But floor division will give me 1. It's not clipping off the decimal point, but from 1.9, if you move towards negative side or to the lower integer value, then 1 will be the integer value, correct? Similarly, if I do -7 double slash 2, let's say for example, this one, the previous example, the division result is going to be -3.5. From -3.5, if you move towards negative infinity, you'll reach to -4. Sensible? Thank you. Coming to the exponential function, Asif, can you tell me what is the value of 10 raised to 3? 1000. What is the value of 20 raised to 4? Whatever that number is. Right? 2 into 2 into 2 into 2. So that's 1000, not 80,000. 10 raised to 4 should 20 raised to 4 should be 2 into 2 is 4, 4 into 2 is 8, 8 raised to 2 is 160. So 160 and 4 numbers, 4 zeros. So that should be 16 million, close to 16 million or 1.6. Let me just check. Yeah, 160,000. 160,000. Good. Similarly, the third one that I have 30 raised to 5, that's 243. So 1, 2, 3, 4, 5, 6. So that's 24 million, 24.3 million. Good. Hopefully good. Exponential, Asif. Exponential means raised to the power. Any questions with the arithmetic operators team quickly? All kind of operations. There are 7 operations that you do in multiplication in terms of mathematics, and I've talked about all of them. Clear? Let's talk about the statistical function. The mathematicians in the house, economists in the house, help me with the statistical functions. Can you list out the names of statistical functions which are prevailing or which are very common in statistics? Got few responses like range, variance, mean, median, mode, standard deviation. Anything else? Apart from this, let me just check. No, nothing else so far. Variance has came in. Okay, good. Variance was there already. So statistically, to talk about, there are many statistical functions which hold the relevance in the field of data analytics, in the field of data science, in the field of machine learning, in the field of artificial intelligence. Many statistical functions are there. Essentially, many of the inferences, many of the conclusions about the data are derived through these statistical norms. We'll discuss those statistical functions and their relevance with respect to the data at a later stage, not now. Why later stage? Because I want to talk about some data first, and then we'll talk about the statistical functionalities of those data and what is the relevance of those statistical values. As of now, our concentration is to understand what are the different statistical functions that we can use and how to use them. Good. For an array. Great, everybody. So we'll talk about statistical functions of the nature. Number one, a mean. Talk about mean. Let's talk about median. Another important, speciality in statistics is mode, which is not available in NumPy, so I'll not talk about mode. Then we have standard deviation. We have variance. What else? We have percentile. Then we have range. Then we have interquartile range. Good. So basic things. There are few more tools like covariance and correlation. I would not like to introduce them right now. We'll talk about them at a later stage. Why later stage? Because it does not make sense right now to talk about them. Good. Let's talk about all these things. How many of you know what is mean? Everybody knows what is mean. So mean is the sum of all number. Forgot Asif. So mean means an average, right? Suppose if I talk about 1, 2, 3, 4, and 5. So the mean would mean that I sum up all those values and divide with the number of values that I have. So add them all. That becomes 5 plus 4, 9 plus 3, 12 plus 2, 1, 14 plus 1 is 15. And I'll divide that with the count of values 1, 2, 3, 4, 5 values. 15 by 5, that equals to 3. So I've got a mean value is 3. Good. Add all, divide by the count. That's your mean. What is the purpose? So mean is the central value. We'll talk about what is the centricity and everything. But mean, how do we calculate that in Python? I'll take an array ARR is equal to any random array. Good. I've taken some values. I can find out print np.mean numpy.mean value of the ARR. That's going to give me the mean value of the array. Good. 74 1 point whatever that number is. It would have added all those numbers and divided by that count. Next comes is the median. What is the median? Anybody? So median is the centrally positioned value when the data is arranged in an order, like ascending order or descending order. So if I talk about in this particular scenario, you can look at this. I have numbers 1, 3, 3, 1, 3, 4, 4, 3, 2, 4, and 572. So that will look like 1. If I arrange that in order, 1 followed by 2, then followed by 3, 3 2 times. So 3. Why it is not typing in? Something was wrong. So let me put up 3, comma 3. Then I add 4, 1, 2, 3 times 4. 1, 2, 3 4s are there. Good. And lastly, I had 572. Correct? That's how the number look like. That is something that I've arranged in an order. Right? Ascending order, descending order does not make a difference. But usually we'll do it in ascending order. Now, once that is done, now I need to look at it centrally positioned. In terms of central position, you can think of, let's say, take 1, 2, 3 numbers from the left, 1, 2, 3 numbers from the right. Good. Now I'm left out with 2 central values. If I take both of them off, I will not be left out with any number. So I need to look for a central value in between them. So that will be the average of those, or mean of those, 3 plus 4 by 2. That is going to be 3.5. And my median is going to be, for this data, a 3.5. Are we good? If there are 2 numbers left at the center, take the mean of them or average of them. If there is a single number, that becomes your median. Good. Same functionality, same methodology, only the name changes from np.mean to np.median. Good. Next comes the standard deviation. With the same data, I'll talk about the standard deviation, STD. Good. We'll talk about standard deviation. Functionality is by np.std. And you can see, look at this value. It says 188.18. Anybody knows how is the standard deviation calculated? I'll give you the formula right now. I will not explain what is the purpose. The formula for standard deviation is, you can note it down on a piece of paper. It is usually represented by a letter sigma, and sigma is equal to, is given as square root of sigma, there is a summation sign, of every value minus the mean, which is usually represented by a letter mu, the whole square, divided by n, where n is number of elements. So I is equal to 1 to n. Okay? That's the standard formula for standard deviation. Are we good? Do you want me to practically solve that for the current data that I've used? How did I read? How has it came in with 188? Okay. Very simple thing. Keep that formula in the mind. So my x has value 1, 3, 4, 4, 3, 2, 572 and 4. Agreed with this? This is my input x. My mean value is 74.125. Good. So 1 minus, so I will try to find out x minus the mean value. That will be minus of 73 point something, right? 73.125. 3 minus this, so that is going to be 71.125 on the minus side. Good. Abhinay 3. And so on for the rest of the list. 4 minus will be 70 point, again 4 minus 70 point, 3 minus 71.2 minus 72 point, 572 minus 74, that will come out at some value, and 4 minus something will come out at some value. Let's take up, for ease of convenience, can I take up some smaller values, simpler values? Calculation purpose. Because 1, 2, 3. Okay, I've taken this. 1, 2, 4, 5, 6. Good. Let's say standard deviation is 1.85 some number. It is easy for me to solve it. So here, my input data is 1, 2, 4, 5, and 6. Good. My mean value is 3.6. Acceptable? So if I talk, if this is your x, can I calculate x minus affecting outliers? I'm not going to talk about that stage at all right now. Outliers and everything will come into the picture later on. X minus the mean value. My mean value is given as 3.6. So 1 minus 3.6 is minus 2.6. 2 minus 3.6 is minus 1.6. 4 minus 3.6 is plus 0.4. Correct? Then I have 5 minus, that will be plus 1.4. 6 will be plus 2.4. Agreed? Now, next I calculate the square of this term. X minus mu the whole square. Calculate the square of this. Everybody help me with 26 square. 2.6 minus 2.6 is just 0.26 square. So that is going to be minus of 2.6 multiplied with minus of 2.6. 6.76. Abhinitri, no, not 5. So I'll have 6.76 here. For 1.6, it is going to be 16 into 16 is 216. No, 256, right? So 2.56. Just to re-verify. 2.56. Then for the third one, 0.4 into 0.4 is going to be 0.08. No, 4 into 4 is 16. 0.16. Good. 1.4 is going to be 1.6. Why? 0.4 into 0.4 is going to be 0.16. 2 decimal places, Mandeep. See, I'm very bad at mathematics, team, but 0.16. Right. Then 1.4 into 1.4. That should be 14 into 14, 1.96, right? 1.96. 2.4 into 2.4, that should be 576. 5.76. Good. Thank you. Someone has given me that answer. So I got these square terms. What did I do? I had the individual data. I subtracted that with the mean, and whatever the subtraction result was, I took up the square of it. Good. Can you sum it up for me quickly? That's going to be 6.76. There is a reason why we do squaring operation. It's not random. It has a logic. Then I have 0.16 plus, then I have 1.96 plus 5.76. So 1, 2, 3, 4, 5. 5 numbers are there. Good. Done. That will be your summation part. It says 17.200 something. And I have 5 numbers. So I'll divide it by the whole result by 5 to take an average. 3.44. But what I need is the square root of this term. Right? So I'll copy this and double star, since I need to take a square root, 0.5. 1.854723699099 My one is rounded off to one place. The result in a manual way and result in the Pythonic way, into NumPy way. Is that same? If that does not help out, what did I do? Listen to that very carefully. I found out first my individual value x, individual value x of I, subtracted that with the mean minus mu. Good. Once I subtracted them, I calculate the square of each one of those and I added up that squared value. Good. Then I divided that squared value summation by the count of values. Once the division is completed, I took the square root of it. Simple, understandable, yes or no? How is the formula created? Now, many people ask me this question, why we have taken up a square, why was there a subtraction from mean and not from any other central value? So there are a lot of things behind it. And there is a reason and logic behind it too. Now, it's not a formula, it's not random, Asif. I will not say Pythagorean theorem says a square is equal to b square plus b square is equal to c square. I'm not saying going to say that to you. If c square is equal to a square plus b square, I will tell you why it is happening, what is the reason. Everything is going to come up. But as I said that, this is not the mathematics class right now, this is a NumPy class. So I am only talking about how to use those features using NumPy. I do not have to do all this manual work, understand the background information right now. I just need to know that I can calculate the standard deviation just by merely using the function called as std. Is that good? Thank you. Again, objective is different. At this juncture, my objective is not to teach you mathematics. My objective is to teach you the syntax. Yeah, I tend to agree with that point, Abhinati. That's what I try to tell you. There is a huge conceptual meaning of standard deviation in terms of data analysis, data science. Huge meaning. But I tend to not use it right now. I do not want to get into that field right now because I have to explain you a lot of things about the data distribution. I have to talk about probabilities. Before I come to that part, what role standard deviation plays? How is the standard deviation such an important factor when you deal with the data? Right? It has a very, very deep meaning for us. Very deep meaning. As data scientist, analyst, or whatsoever profile you think of, similar fields. Good. But as of now, please concentrate on the fact that you know how to calculate the standard deviation using NumPy. I am not asking you to interpret what does it mean. Just understand how to calculate. Good. Thank you. Let's move on to the next property, which is variance. See, variance also talks about the same strategies, same scenarios, what standard deviation talks about. Same thing. Formula wise, there is no such difference. In standard deviation, which was represented by letter sigma, that was equal to the square root of summation sign, individual value minus the mean divided by the total count of values. Good. That was the formula. Good. Now, in variance is nothing but a squaring operation. Square on left side, put up a square onto the right side. Square of the same thing. So essentially what is going to happen? I am going to remove out this square bracket. The square root operation is not done. So essentially 1.85, if I take a square of it, I'll get the variance. Tip of 4. Right? Manually also we got that. Good. Next comes the percentile. What does percentile represent? Anybody? It's a value. See, I've not written down any definition for mean, median, standard deviation, variance, but I'm putting it for percentile. it's a value in the set or in the sorted set of data, that depicts a value which, excluding itself, divides the data in percentage. Now, may not make sense to you. Okay. In order to understand the concept of percentile, try to look at the same data 1, 2, 3, 4, 5, 6. Good. If I write down that in order 1, 2, 4, 5, and 6. If you look at number 4, right? Look at the number 4. If you exclude that number, good. If you exclude that, the remaining data that is left out, 50% is lesser than that value, isn't it? And 50% is more than that value, isn't it? Correct? That means this is the data point that divides the entire data into two equal halves. Right? If you go lesser than that, 50% will be the less number of values, 50% are more than that. And that is what percentile tells you. So if I just give you a simple example, let's put up print np.percentile. Percentile of the ARR, which percentile value? 50th percentile. Good. And you can see the same value coming up. 4. You can also look at some very prominent percentile numbers which are of use. We call them as. So one of the important percentile is called as 25. Another important percentile is 75. Very important percentile numbers. Look at this 25th percentile and 75th percentile. Right. 25th percentile says 2, 75th percentile says 5. Look at your data and then tell me. Same data that we have here. 25th percentile means what? Once you select a value, remaining values that are left out, I have left out with 1, 4, 5, and 6. Good. So the remaining values that are left out with, remaining data that is left out with, 25% of that is less than that value and 75 is more. That is 25th percentile. Similarly, when you took 75th percentile, that will be that 75% of the values are lesser and 25% are more. Sensible? Thank you. Can you tell me what will be the 0 percentile? Is nothing but it's the minimum value, right? And if you talk about the 100 percentile, that is the maximum value. Good. Always remember this. This 25th percentile in statistical terms is also called as Q1 or quartile 1. Good. The 75th percentile is called as quartile 3. 50th percentile is called as quartile 2. Minimum value is also termed as quartile 0. This is considered also as quartile 4, Q4. Now, what is the purpose? Very important purpose. There is a data, right? Starting from this point till this point. Good. That is your minimum value. Agreed. This is your maximum value. When you divide that data into two equal halves, what you will have is a central line. This is called as your median, right? Which is equal to nothing but the 50th percentile, which is equal to nothing but Q2. Why Q2? I'll come to that point. Now, when you divide that entire data into four equal spaces, that means 25%, then 25%, then 25%, and 25%. No, there is no function for mode, right? So, first 25% data lying here, next 25% here, third 25% here, and remaining 25% here, right? So, I'm dividing the data into four quarters, four different sections, right? This first quarter, right, starting from Q0 ends at Q1. So quarter 1 ended over there, quarter 2 ended over there, quarter 3 ended over there, and quarter 4 ended over there. Get endpoints. Essentially, quarter 4 and max are same, quarter 0 and minimum are same. Quarter 1 is your 25th percentile, quarter 3 is your 75th percentile, quarter 2 median and 50th percentile are same. Are we good? Just a nomenclature, team, just to understand. Good. Thank you. Now there is a huge implication of that. Next statistical property that is very prevailing is called as the min and max value. Min and max. So I can find out print np dot minimum of my ARR, that's my array. I can print the maximum np dot ARR the max, np dot max of the ARR. Good. I have an extra p over there. So minimum maximum values printed out. Slight difference that you can notice with the percentile, there is a mathematical calculation with the division operator, and hence I have a floating point answer. But here there is no mathematical calculation, it just directly finds out whichever value is there and gives me that value. So that is why I can see the integer output, because I have the original data as integer. Good, but the value is the same, min and max. From there comes the range functionality. Range. So range is the difference between, see, all these things have a relevance at a later stage. So I want you to make sure that you know the function, the numpy function, not the logic, why and when and how to use them. No, just know that what does it mean and what it tells you. Syntactically, difference between the maximum and minimum value, right? That is called as your range. What it tells, we'll talk about that later. So I can find out print or the range of the data. Let's put up, I'll put up that as print np dot max of ARR, right? Maximum minus np dot min of ARR, right? So maximum minus minimum, we need to do that way. Good. I get my range. That's the value number 5. Or there is something else which is called as the interquartile range. Interquartile range. Interquartile range is the difference between the 75th percentile and 25th percentile. Good. So how can I get this? np dot percentile of ARR, which percentile value? 75th percentile. And again, same thing. Both has a relevance, 25th percentile. Good. So I got the interquartile range as 3. Good. In the outputs that have shown up so far, do you want me to put up some messages, right? Like let me in the output like this formatted string, mean is, and then this thing. Do you want me to format like this? I can do it, but I don't find the relevance again. That's the purpose. Considering there is no input coming through, assuming people want it. Right, rest you can do on your own. Just a piece of writing the text in Python. I'm not teaching Python to you guys. Questions so far, team? Any questions, please let me know. We talked about these statistical functions. Let's talk about the next part, which is the string functions. Do you know about strings? Yes, no, maybe, please confirm. Thank you, great. So if I talk about an array, till now what we have used is an array for numbers only. But when I created array, I used list. So what if I think of an array? Let's say I create up a list here. This is a list that I'm creating up containing first value as Narendra. Good. Next value as Abhinitri. See, that's going into the reverse chronological order. Abhinitri has an extra H. Third one is Akshay. Good. My basic question is it a valid list? First of all, is that a valid list? Great. Now, if this is a valid list, can I create an array out of it? Let's say names is equal to np.array. Earlier also, I have created arrays using valid list. So if I create this, what happens? A valid array is being created. But if you look at this front, names dot d type, if you look at the data type of it, that's going to be type object u10. Can someone tell me why u10? What does that mean? Hopefully someone can. Say no if you cannot, so that we can save on time. Maybe the maximum number of characters. Okay, great. No idea. Thank you. See, the idea is the representation of the array. This is an array. So that means I am representing every element of this array into the memory. My every element is a string here. So whenever there is a string array that contains string elements, right, it allots a space in my memory, right? So if this is a string input, it finds out whichever is the largest string, the longest string, right? So here I have a string that is Abhinitri that contains 10 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 characters. So it thinks that the longest string requires 10 characters. It allows 10 characters for this. Another one also string will get 10 characters. So every character, every individual input will have a space of 10 characters. It may acquire the entire 10 characters or less. Sensible? Great. So that is why U10. The word U stands for Unicode. That means I am representing those string things in numerical format in my memory using the Unicode character format. I'll not talk about what is Unicode character format. Essentially, any character from any language in the entire world. Known languages, right? Unknown languages I cannot promise. But almost like more than 200, 250 languages are, the written and spoken language, not computer language, right? Whatever symbols they have are available in Unicode. Good? Questions, if any, till now? So U stands for the word Unicode and 10 represents the number of the length of the longest character. But that is not my problem. My problem is with the string functions. That is what I want to talk about. Good. Now, what happens is NumPy offers me a separate module, a submodule. We call it as a char module. CHAR. What if I write down? Suppose this is an array. Good. Execute. Now, let's take up another array here. Let's say greet. Let's say Narendra, I want to say Mr. Abhinetri, I want to say Miss. Akshay, I want to say Mr. Okay? Just a simple thing. Now, I want to print out greet plus names. Could not work. See, there are two arrays. I'm trying to add them up. I want to print the greet one-on-one, Mr. plus Narendra, Miss plus Abhinetri, Mr. plus Akshay. Had that been numbers, that would have worked, correct? That would have worked. Or this was not available in the earlier versions of Python, but now, see, with string it can work. I can write down a string, Mr., and I can put up a plus symbol and I can add Narendra to that. That will work. This is going to work, no problems. Narendra. So I can add two strings. Concatenation can happen. But here it is not happening. It's not happening over there. Mr. plus Narendra is not working because we know that addition is supposed to do element-wise things for array, but it's not happening with the list with the string. So how to solve it up? So earlier, if I talk about in historical manners, this was not allowed. In recent versions of Python, this has become allowed. That is, I can write down numpy.add function, the numpy add function, and I will tell it I want to add the greet array with the names array. In recent versions, mine Python version is a little older one, but in recent version, this has started working. You can directly use add. But if you do not get that working, you can also use this character functionality. So NumPy has a char submodule, which I can use, and that works. Can you see this? MR Narendra, MS Abhinetri, MR Akshay. If I missed out on the title parts, team, please pardon me on that. Are we good? Not good? Yes, no, maybe confirm. Great. So again, I will not get into very much elaborative nature of this np.char. Why? Because it is not supposed to be used, in real world scenario. Whenever there is a string kind of situation, we generally do not prefer using numpy. We do not prefer using that. We directly go on to the string methods. But just to showcase, I'll just try to show dir np.char. What is that going to give me? It's going to give me the list of all functionalities which are available in NumPy character submodule. These are the functionalities. If you take out into the picture these underscore things, these are the functions which are available. Give that a read and tell me if there is something new which is different from the basic string functionality. One or two might be different, right? And depending upon the version of Python that you're using, you might have some different options. Good team. So like converting string to lowercase, uppercase, removing the characters from left or right, stripping those things, splitting the string, checking for the alphanumeric thing, and rest on basic functionalities of strings. The same things are available with the Python too, with the NumPy. So we'll not delve into that. Good. Questions? Can you explain again? What part? I can explain anything. Cannot. But which thing? Okay, Kunal. Let's take a simple example. Suppose I write down a name. Let's say a variable name is equal to a simple string. Let's say your name, Kunal. Acceptable input? Good? Great. Now, I want to convert your name to uppercase. How can I do this? First method I can use is name.upper. Good. That gives me your name in uppercase. Agreed. Now here, name is a string. Good. And I'm using a string function called as upper. Acceptable? Thank you. Now, instead of doing this, if I write down np.char.upper of name, the ideology changes that now I am trying to do the same thing. I'm converting a string into an uppercase character string, but instead of using the normal Python, I am now using the NumPy. Sensible? I still get the same result. The difference, the output with the string, I'll get a string. The output with NumPy char module, I'll get an array. Are we good? If not good, tell me. So when I use NumPy, I get the output as an array. When I do not use NumPy, I get the output as string. That's the difference. Otherwise, in terms of functionality, in terms of the results, no such difference. Hope so everybody is okay with that. Great. Thank you very much. Now I'll talk about some NumPy miscellaneous functions. Why I'm putting the word miscellaneous is because these are too many functions. Repeat percentile, okay. Okay, let's take up this 1, 2, 3, 4, 5, 6, 7, 8, and 9. Good. Can you tell me how many numbers are there, Asif? Count of numbers. 9. Great. If I ask you to choose a number that divides the data into 50-50 ratio, can you tell me a number? Number is 5. Why you chose 5? Because the remaining digits are 1, 2, 3, 4, and 6, 7, 8, 9. Correct? So I have 4 numbers onto the left. I have 4 numbers onto the right. Acceptable? 50% lower than that, 50% upper than that. Good. Now, if I ask you to choose a 75th percentile, what does 75th percentile means? That means there will be some number in such a manner that below that there will be 75% of the remaining data, and above that will be 25%, excluding that number. So number is not included. Can you tell me what can be that number? It has to be exact 75-25 difference. Till 7. Why? Tell me the number. Exact number. 75th percentile. Why you said 7? So let's assume you're right. Assume that you're right. Good. I'm not saying you are. So 7 is your 75th percentile. I'm left with 8 values, correct? So 75% of 8 is going to be how many? That is going to be 75 into 2 is 150. 150 into 4 is going to be 6 values. So I have 6 values lower than that and 2 values upper than that. Agree. Good. 7 will be your percentile. 75th percentile. Are we good? Did you understand this? Logically? Right. What if I add another term here? Just for the sake of confusion. Why multiplied by 4? See, I tried to solve my mathematics as if I had to do a multiplication by 8. So I do it multiplied by 2, then multiplied by 4. That was I was trying to look at. That is a calculation process. Let's suppose, what if I have a number 10? Let's suppose I have a 10 over there too at the end. Can you now tell me what is the 75th percentile? Will it change, first of all? Will the median going to change? The 50th percentile? No, it's not going to be 8. Asif. Because if you take 8, you have 7 values lower, you have 2 values upper than this. So out of 9, 7 by 9 is some percentage and 2 by 9 is some percent. That is not definitely 75-25, correct? Not even a 7.5 quotient. It has to be 7.25 if I'm not wrong. Just to showcase. NP dot percentile percentile number is 75. I think so. It's 7.75. Yeah, correct. Not 25, but 7.75. 70% is going to 7.75. That may not be the exact number in the range. It can be something in between them as well. If you look at the 50th percentile, that's also not going to be 5 or 6. It is somewhere in between the 50th percentile. 5.5. Right. Great. So when I take that up, I need to divide this data into such a manner that I need to find out a number, let's say 25th percentile. That means 25% of the value will be lesser than that and 75 would be lesser than that. So if I have altogether 10 numbers, I would require to see a value somewhere. There are 10 numbers. So that means it has to be divided in 25-75 ratio, right? That means I will have a value somewhere here between 2.5 and between 2 and 2.5, such that these values are lesser than and these values are greater than. Right. So first division will come between 2 and 3 for me. Between 2 and 3, I would again require 25-75 ratio. So 25 will come this side, 75 will come this side. 2.25 should be the answer for 25th percentile, or 3.25, right? Somewhere like that. Good. It starts with the 1, not 0. That is why 3.25. Any questions, team? Can I move on? Again, please understand, the objective is not to know how to calculate percentile. That's mathematics. I do not want you to learn that. I want you to know that the relevance of using percentile. The idea is, let's understand first of all, very simple idea. Suppose I give you two numbers, that is 1 and 10. And I want you to tell me that I want to create a data wherein I have the values that starts from 10, which closes at, which starts at 1, closes at 10. 10 is not included. It is not included. Good. And I want to keep a gap of 1 between two values. You will say the numbers will be 1, 2, 3, 4, 5, 6, 7, 8, and 9. Agreed? Thank you. And that is what we do with the arange function. So arange function essentially generates the array of numbers that will be with the equal gap. How is the syntax? The syntax is, I can use numpy dot arange and tell it the number I want to start at. I want to start at 5, comma, the number at which I want to stop at 25. And then I want a gap of 3 between consecutive values. So what I'm telling you here is 3 terms: the start value, a stop value, and a step value. Step value means or a gap. So what did I say here? 5, 25, and 3. So what I want here, start with 5, end with the 25, and keep a gap of 3. So 5 will be my first value, plus 3, 8, plus 3, 11, plus 3, 14, plus 3, 17, plus 3, 20, plus 3, 23. Plus 3 will become 26, which is beyond 25. I can go up to 25, but not 25. Is that okay? If you look at the outcome of this, can you see the same numbers? 5, 8, 11, 14, 17, 20, 23. All right. So there are 3 important things that we need to notice. That we need to tell it where we want to start at, where we want to stop at, and what is the gap that we want to use. Now, I have a variant of this, not in terms of variant, but the choices. I would say that. Friends, what if I do not tell it this thing? See, here I have 3 comma separated values going to the function. What if I just mention friend np.arange and I just tell it 25? I do not tell it any number other than this. What you will notice is that it started with 0, ended with 24, generated 25 numbers with a gap of 1. Essentially, if you look at this statement, I can write down it in elaborated form as np.arange start at 0, comma, stop at 25 with a gap of 1. Eyes, nose, babies. Thank you. Now, So when I mention a single value, it means I will start from 0 and I'll end at the given number and I'll keep a gap of 1. Though I have in control whatever the things that I want, I can control where do I start at, I can control where do I want to stop at, and I can also control the gap between. The gap can also go in a negative factor. For example, what if I mention that I want to start at 10, stop at 0, with a gap of -2. Essentially means that my first number is 10, second number is 10 plus of -2, that is 8. Third number is 8 minus 2, 6. Fourth number is 6 minus 2, 4. Then 2, then 0. But 0 will not be included, it is excluded. Good. 10, 8, 6, 7, 4, 2. Are we good with the arange? Thank you. Next functionality we have is called as linspace. That stands for the word linear spacing. Linear spacing means same idea. This function is used to generate 1D array of numbers within a specified interval with a specified, I had missed the word gap over there, right? With a fixed gap between consecutive values, and there is an AND condition. And the AND condition is that of specified count. When I say specified count, suppose if I ask you a very simple question, let me see how many of you can answer it. Good. Let's take a number 1 and 10. Good, two numbers. I want to start at 1. I wanted to close at 10. Good. That means the first value is 1. The last value is 10. Good. And I tell you to design it in such a manner that there are 5 numbers. So 1 is this, 2 is this, and I need 3 more numbers in between. Can you tell me? The only question is that the gap between two numbers will be equal. Can we say that that is going to be 1? What could be the next number to you? If not, you're not able to calculate mathematically. 4. No, 4 cannot work. 4 plus 3 is 7 plus 3 is 10. That does not work well. 3 cannot work well. 1 plus 3 is 2. No, 2 is not possible. It will be sum in decimal point notation. But how will I put it up? I'll put a print np.linspace, linear spacing. I want to start at 1, close at 10, and I need 5 numbers. So 1, 3.5, 3.25, 5.5, 7.75, and 10. If you look at the gap between these two numbers, or these two numbers, or these two numbers, or these two numbers, is that same? But the numbers of number generated, count of the numbers generated is 5. 1, 2, 3, 4, 5. If I put it up here, I want 10 numbers. It gives me 10 different numbers. If I need 100 numbers, it gives me 100 numbers. Are we good? The only strategy, the only change, the only ideology that we have between the linspace is that the between the given interval, I will have an equal spaced interval values, but the count shall be controlled. In A range, what we control is only the gap. Here, in A range, I control that how much gap will be there between two consecutive values. Here, I'm not controlling the gap. I'm leaving it out. What I'm controlling is the number of values being generated. Sensible? That's linspace. Next, we talk about the random submodule. Very important. You may not find a relevance of A range. I can repeat that, Narendra, not a problem. So linspace is talking about linear spacing. Suppose, Narendra, there is a one number called as 2, another number called as 20. Good. I have told you that this is your starting point, this is your stopping point. This is given. And now I'm asking you to give me 4 values. I want a data that contains 4 values. And the condition is that any 2 consecutive values will have equal gap. So essentially now what I'm looking forward to is a set of 2 values. I need 1 and 2 more values because 2 are already there. I have 2, I have 20. But I need 2 more such values such that the gap between 2 and this, the gap between this and this, and the gap between this and this is same. Sensible? But I have specified that I only need 4 terms, not more than that. So how can I get that? I can give a mathematical solution to do that too. Think about 2 numbers. Let's say I put up here 8 and let's say 16, let's say 15. Now the gap between 2 and 8 is 6. Between 8 and 15, the gap is 7. Between 15 and 20 is 5. So this gap is not equal, though I have 4 numbers only. So I need to alter that gap somehow. It has to be between 6 and 5. Let's make it 6.5. Let's see what happens if I make the gap as 6.5. 2 plus 6.5 is 8.5. 8.5 plus 6.5 is becoming 15, and 15 plus 6.5 is 21 points. So that does not make difference. So I will have some more gapping difference. Exact calculation wise, how will I get to know? I have a starting value 20, ending value 2, starting value 20. I need 4 numbers. That will be ending value minus this value plus 1 divided by the count of numbers that you want. So that is going to be 18, 19 by 4. That will be the gap that I would want. Just the mathematical explanation, 19 by 4 is 4.75. I would require a gap of 4.75. So 2 plus 4.75 is going to give me the next number, which is 6.75. 6.75 again give me 11.75. That becomes one more number, 16.25. So I need one number less. So divided by 3, that will be the gap. 6.33 is the gap that I would require. Start with 2. The next number is going to be 8.33. The third number is going to be 14.66, and then I will have the last number. The gap will remain same. If you do not agree, you can look at this example. I can write down np.linspace, and I ask it that start from 2 end it 20, and I need 4 numbers. You will see the first number being 2, second number being 8.33, third number being 14.66, and so on. So 2, 8, 14, 20, gap of 6. Why did I put 19? Oh, that should be 18 by 3. Correct. 6, gap of 6 will be accepted. Make sense? Between two consecutive values, the gap remains same, and we have the result. Thank you. That's the use of linspace. It has a utility in real world. It has a meaning in the real world. It has a purpose. But as of now, we are only concentrating on the syntax part. Okay. So as of now, try to understand, team, the objective is not to know when and what is the relevance. As of now, the objective that I'm trying to fulfill is to know that we can do this. Good. Next is a random submodule. Random submodule of numpy is a module that is used. It is a submodule or subpart of library, right? Submodule of numpy that is used to generate arrays with random numbers. Good. So if I have to create an array with the random numbers, I can use that. The first function that I have is called as rand. Right? Rand function. What is the utility of it? It is used to generate it is used to generate any dimensional array of random floating point numbers. Floating point numbers means numbers with a decimal point notation. Floating point numbers between half open interval of the other way around. So open on 0 side, right? So that should be good. 0, 1 close interval. Half open interval of 0, 1. Now, I'll ask a very basic question. Read the statement that I've written down and tell me if there is something you cannot comprehend. I'm okay if you cannot comprehend even generate, dimensional, array, random, floating, half open, anything. But tell me. I'll explain. Somebody? No one? 0, 0.5, 1. What does that mean, Kunal? I've not yet talked about the syntax, Kunal. So it does not find that message that you put up relevant with rand. You may have that relevance for linspace. You may have that relevance for arange, but not with respect to rand. Half open interval of, so I guess I am assuming you're trying to talk about half open interval means dividing that into half part. Is that what you're trying to say? So 0, 0.5 and 1. What does it mean? Half open interval. Mathematicians in the house. Let me just check. I have mathematicians in the house. Let me just check with them first. They will help me. See team, I'm only looking forward today. to complete numpy if I can. So I have all the time in the world to discuss. Mathematicians in the house? Narendra says half open means 0.0 less than equal to x less than 1.0. Great. Here 0 should be excluded and 1 should be included. Open means inclusion and closed means exclusion. Abhinetri. So I tend to agree with the definition that Narendra has given. You are right on target, but slightly different. The word excluded and included needs to be replaced. So when you talk about half open interval, essentially that means that wherever you have the round bracket, whichever side, that value is inclusive, and you have a square bracket that is exclusive. Essentially, what does that mean? That the data can go up to a value where it is open, but will not reach to the value which is closed. Good? Closed is a square bracket. Round bracket means it's a mere representation in mathematics. I am not even bothered about it. Just to give you little jargons. I talked about that word. Right? So rand is a function which has a by default range of 0 to 1. It has a range of 0 to 1. Its objective is to generate a random data of floating point decimal point notation numbers between the range of 0 to 1, with a limitation that 0 may appear up because it's random, so we cannot guarantee that 0 will come, but it may come up, but 1 will never come. That is what half open interval means. So when you mention an interval in brackets like this, if you mention two round brackets on either side, that means this is inclusive, this is inclusive. If you mention a square bracket on any side, so whichever side has a square bracket, that is exclusive. That means that value is not available, but other value is available. Good? If there is a round bracket, value available. If a square bracket, not available. Thank you. So let's try to generate some random array. Now, I mentioned any dimensional array. So let's try to create up a 1D array of random data. So I'll try to use print. I'm not saving that to a variable. NumPy has a random submodule which has a rand function, and I need an array of a shape of 5 data points. Now I've mentioned one data, 5. That means I need 5 random points between 0 to 1. That will become a 1D array. Can you see that? Is it 1D? You will not have the same values as I have. It will be different. Good. If I need 2D, into the same parenthesis, I will mention the shape. Let's say I need 5 rows and 3 columns. Look at this output. 5 rows, 3 columns. If I need 3D, I will mention 3 different shapes, 3 different, dimensions. When I mention single value, single number, 1D. When I mention 2 numbers, 2D. If I mention 3 numbers, let's say 2, 2, 2, 2 rows, 2 layers, 2 rows, and 2 columns. I am putting W. Good. What did I miss? Another bracket. So here you can see it's 3D. Sensible, not sensible? Yes, no, maybe. Now, similar to that, we have another function similar to rand. We have another function called as rand, not rand, but random. Name of the function is random. Not something wrong copied. Name of the function is random. It is used to generate any dimensional array of random floating point numbers between the half of 2 to 0, 1. Requires the shape to be given as a tuple for 2D or more dimensional arrays. So the ideology between random and rand is the same, right? It is going to generate random floating point numbers of specified shape within the interval of 0 to 1, half open interval. Good. 0 inclusive, 1 not inclusive. But the only difference is, if I just talk about, is look at this part, right? I am using rand function in this example right now. If I write down the word random here, I write down the same random word over there and random over there. For the first one, it will work well, no problems, right? It works well for the first one. I can see this is the output coming in. For the second one onwards, it says there is an error. What is that error? That here I have told it that I need 5 rows and 3 columns. It knows to know that as a tuple. So I need to give that as a single entity. So I need to include 5, 3 into brackets and include that shape, 2 rows, 2 layers and 2 columns into a shape. It works well. Good. So essentially the difference between random and rand is in terms of the syntax and not in the nature. Are we good? Nature of the value is being generated by random, nature of the value is being generated by rand or same. Ask if, where is the question? Confusion, rather. You can unmute if you want to. Let me just give you that access.
Hello.
Yeah, Ashish.
Good day, sir.
Well, good day.
Yeah. So actually, here my question is, so here random dot random, two
Mhm.
columns, two rows, and two. What exactly is this? I didn't get
See
this.
the last, this one,
Yeah.
right here. I'm trying to generate a 3D array
Okay.
that consists of something like this, right? This is first layer containing 2 rows and 2 columns. Then
Correct.
I have a second layer consisting 2 rows and 2 columns, and I have a third layer consisting 2 rows. So look at this. This is the data. I have a depth of 2, number of
Mhm.
rows 2, number of columns 2. That's what we have mentioned over there. The
Oh,
shape. Remember, I talked about the shape property in the
yeah.
history.
Yeah. Yeah. Yeah.
Right? It's the same thing. What shape of the array that I want? In rand function, I do not have to mention that shape as a tuple.
Uh-huh.
Right?
Okay.
In random, I need to mention that as a tuple. That's the only difference. Syntactical difference, no
Okay.
difference in the nature, no difference in the kind of values being generated.
So here it's two rows, two columns, and like
A
two.
depth, or the whatever you want to say it as depth, height, whatever you want.
Okay. Fine. Okay, sir. Makes sense.
Thank you.
Yeah.
Anybody else? Any other question? Or you can mute yourself. So rand function, random function does the same job, but slight difference in terms of syntax. Then comes the next function. People ask me that in best question, why only in the numbers in the range of 0 to 1? What if I want a numbers, floating point numbers in a different range? So here it is. That is called as a uniform function. What is the role of it? It is used to generate random floating point numbers, random floating point number array of specified shape. So shape is under my control, right? Within a specified interval, within the specified interval. But the only concern is which follows uniform distribution. Now, in a very simple terms, I'm not pretty much sure how many of you know what is uniform distribution, but I'll talk about that in a short while. Let's try to look at the syntax of this uniform function first. Good. So, friends, let's say I want an array of 5 numbers from the range of 2 to 20 in such a manner that all those 5 numbers are a floating point number representation in the range of 2 to 20. Any random number. Good. So between print, I'll let it as numpy. Please use your random submodule. And random module has a uniform functionality. Use that. I wanted to generate numbers between 2, 20 and comma. I need 1D array. So size is equal to is the parameter. I want, let's say, 5 numbers. So 5 comma. So look at that. What did I mention? A shape with the term size over there. I can avoid the word size as well. Good. And that's how it looks like. Great. Look at this. If you look at all the floating point numbers that are being generated over there, are those numbers between the range of 2 to 20? I have used a word in the definition that I've given, which follow a uniform distribution. Now, when I talk about in terms of numbers, whenever there is a data, right, a data in a particular range, see, I have used a range of 2 to 20, right? So I have tried to understand it. I'm not talking about in terms of mathematics right now, but trying to give you a layman definition. Mathematically, I'll talk about it later on. But suppose this is my minimum number 2. There is a maximum number 20. Good. Now, in between 2 and 20, how many numbers are possible? Let me ask it. How many numbers are possible? 18? No, Asif. If I would have put that question as how many whole numbers are possible, then you would have said 18. Infinite numbers. There is infinite numbers which are possible. Thank you, Abhinetri. Or someone else was there. Now, in between the combination of those infinite numbers, I am looking for certain numbers whose probability of coming up, whose probability of being there is same. Let's say there is a number x1, there is a number x2, there is a number x3, there is a number x5, or so on. The probability of finding x1, the probability of getting x2, probability of getting x3, or probability is same, right? The probability of appearance is same. Then I will say those numbers as uniformly distributed. Make sense? Every single number within that range, if used, has equal probability. Are we good? Can you explain the same with our example code output? No, I cannot, Abhinetri, right now. Why? Because here I am just showcasing you the output. I can give you the formula. It's a formula with respect to the probability distribution. I am not pretty much sure whether you will understand it or not. So the formula is for this to find out the probability is given by 1 upon b minus a, where b is the maximum value and a is the minimum value. So 1 by 18 in my case, that will be my probability term. So any term in my entire data that follows, that part, it will be termed as this, right? Now, how did it reach to 8.744? Because I need to talk about, a lot of probability distribution before this, because I need to talk about what is Gaussian distribution. I need to talk about what is binomial distribution. I need to talk about what is Poisson distribution. What do you talk about? What is CDF, the cumulative distribution function? I need to talk about what is, the probability density function. And then and only then I will be able to make some sense with this data. It's random. You may not get the same numbers. Because the idea is to get 5 numbers that has an equal probability. There can be infinite possibilities. It is selectively choosing 5 ones. I can choose up infinite numbers. Let's say I put upon 1000. It gives me the list of 1000 numbers. So it's not that I only have 5 numbers available. There can be infinite different possible numbers that follows the same problem. The idea is with the uniform distribution is that every single number will have a probability which is equal. So whatever the probability is 2.41, same probability is held by 6.62. We'll stick to 10 numbers only. Good. That's the idea behind the uniform function. Essentially, use it for the purpose of generating random floating point numbers between given a specified interval. That's it. Right? Do not go into the distribution part. In a similar fashion, I have another function which is for randint. Generate random integer number array of specified shape within a specified within a specified interval. Now with integer array, there is nothing called as probability distribution. The same functionality, no changes at all. I'll just copy the same formula, same piece of code, but instead of uniform, I'll write down the word randint. It has generated a random array of data points between 2 to 20, 2 inclusive, 20 exclusive, and 10 points. I re-execute that, I'll get a different set of numbers. You would have done it at your end, you would have a different set of numbers. Can you check that? Now, do you want me to fix it? Fix means when I execute a piece of code and when you execute a piece of code, we get the same numbers. That means fixing the randomization. Should I do it? Should I not do it? Think about a problem. Suppose you are solving a problem P. Good. That problem in its solution wants a random number to be utilized, right? A random number. So you will, thank you. So that is the ideology. It is happening because of this seed number. If I put my seed number as any different number, 11, let's say, I and you will have a different thing. Now, many people do not understand what is seed. So I give give them this example. Suppose this is your garden, right? This is your garden. If you plant a wheat seed, suppose a seed of wheat, what you will get is a wheat tree. If you plant a seed of rice, you will get a rice plant. If you plant a seed of, let's say, pomegranate, you will get a pomegranate. If you plant a seed of sunflower, you will get a sunflower, correct? It is not going to happen that if you plant a seed of mango, you will get an oranges out of it. Is that going to happen? Essentially not. Same thing is happening over there. Python has a particular seeds. Python has defined certain seeds, right, which is used for random value generation. These seeds are starting from 1, going till 2 raised to 32 minus 1. That number. That will come out somewhere around 42 million. Okay. So I can use 1, 2, 3, 4, 5, 6, 7, up to that number, 2 raised to 32 minus 1. Any number in between. And it has a specified sequence of numbers. Floating point numbers, it has integer numbers. Again, these are not, actually written down, these are calculated based upon the random algorithm. There is an algorithm that we study of the randomization. I will not get into that part because it's subject that I studied in 6 months and I'm still not very much comfortable with that subject. We call that as design analysis of algorithm in the field of computer science. Not to bother about it. It does not make a difference. But you can think of, there is some brain that is trying to generate random numbers. That brain has been told, okay, if I tell you number 11, generate these numbers. If I tell you number 111, generate a different set. Make sense? And no coming from the last. I was looking more of yes, not no's. Yes, Narendra, Abhinetri, confirm. If your question is long, you want to get unmuted, you want to discuss, ask me to unmute. Just put the word unmute in the chat. We can talk. That is easier as compared to typing. But seed is really important for me to you guys to understand. Very important for me. It's not a part of your standard curriculum. It will not be into your documentation anywhere. It's something definitely different from what is given. But you will find it relevance later on. So I can see certain number of no's, like coming from Akshay, Abhinetri, Narendra, or anybody in the house. Till now, any questions, any concerns with any of the topics, any of the functions, any of the methodologies, any of the examples, anywhere? Please ask it. There are 2 persons who have given me a rating to reduce down my pace out of 50. Is it possible to change the random numbers for the same seed? See, Preeti, to answer the question, the answer is yes. You can alter them, but that is not going to be universal. For example, let me just talk about, let's say your name, you write down as Prwthy. Good. You can write it down as Prwthi. You can change it yourself. For yourself, you can do it. But when you talk about your standard documentation, can you change it in your high school mark sheets or any other documentation? You cannot. Right? It's fixed over there. So similarly, this thing, it is the seed values are fixed. These are already fixed, and these are saved into the Python memory. Python already, any Python version that we have, right? Python by default generates those numbers the moment we start using Python into my memory. It generates all those sequences. Those are loaded into my memory directly without me asking for it. These are all default sequences that Python knows, which are predefined. For example, Narendra, we have 206 bones predefined, clear. Irrespective whether we are a male, we are a female, does not make a difference. Whatever kind of value, 206 is fixed. We can alter that number manually. It is possible. We can get a one bone out of our body and put it up with an iron rod or something. Possible. We can get an earlobe bone removed. That does not make a difference in the normal human lifestyle, right? Possible. You can get a bone removed from your finger, or you can add up an additional bones onto your body. Possible. But we don't do it because there are certain standards. Good. Again, I'd just like to talk about a little bit on the feedback that I have on the break part at the time of break, which is a poll activity. I have 2 people out of 15 who said that I am running at a very fast pace. There's one person rating 6. The rest of the people have rated as 8, 9, and 10. 18 people rated second question. So people are saying I'm going at a fast pace. Can you let me know where things which are being taken up in a fast-paced manner? I would like to take a pause. I would like to wait and then answer your queries and concern if you have any, and then move on. It is possible. I completely agree that I may have taken up certain topic in a little bit fast-paced way because that's kind of very human. I know about those things in depth, so I may have got exaggerated and maybe went on with the emotions and may have talked about that in a quick, fast-paced manner. Thank you very much for that input. But if you can just let me know things which are not clear for you, I will repeat it with slower space, with more examples, so that you guys are clear on that. Someone has drawn a green line. Jiva Raghava was the name. Yes, Jiva, if you have something to say. Jeev Raghavan. Quickly, team. Thank you very much. Now, I got a line from you, your end on my screen, so that's the only one reason I asked it. Great. So, till now, no questions. Hope so. Everybody's okay with the random part that I wanted to convey. It's fine, Jiva. See, my objective is to make sure nothing gets unnoticed. No need to be sorry about it. I'll try to notice every single thing. Yes, Asif. Random.random used to generate random integer array. Asif, Can you give me 5 integer values? I want you to give me a 1D array with 5 numbers of integer data in a range of 2 to 20. So your all 5 values needs to be between either equal to 2 or less than 20. Less than greater than or equal to 2, less than 20. Any 5 numbers. You can choose 2, 10, 12, 4, 7. All are integers which are between 2 to 20, where 2 can be inclusive, but 20 is not there. Great. That is random integer function. Could be any randomized thing. If you talk about how many options or choices it has, 2 raised to 32, 4294967295. I can use up to that value for the seed term. I cannot use 6 over there. 6 will be denied. Seed must be between 0 to 2 raised to 32 minus 1. The idea is, if I use a seed value, the seed value will always give me back the same result. For seed number 10, remember, for seed number 10, if I want to get a random integer value in the range of 1 to 20, and I need 10 values, I will have the same 10 values always. If I change my range, the set of values will change. If I change the size, let's say keep the same range, I want 5, let's say 3 values. Only 3 values will be shown up. So for every possible combination, for every possible scenario, there is a given defined set, not only with the random integer. I gave an example with the random integer because it is easier to comprehend. Otherwise, for any random number generation, you can use seed. If you want to fix the randomization, suppose for example, if I use np.random.rand, I did not mention any how many count I want. It is going to give me one floating point number. Good. Look at this. I'm executing it multiple number of times, and I'm every time getting different results. Good. But if I put up just below before that np.random.seed, and I tell it that let's say seed value 10, fixed 0.77 this. So it has specified if my seed value is 10, rand will always generate this number. Despite how many numbers I executed, I will not have a C difference in the result. Good. So the objective of seed is to fix the randomization, if everybody is okay on that part. Next time we talk about indexing and slicing in arrays. Last topic of the arrays. Then we'll conclude the arrays and move on to pandas. If we can reach to pandas today, well and good. If cannot, we'll move on to the next array. Good. I will try to generate some data. So let's make a data array. So data is equal to np.array. Good. Rather np dot, let's take it up from arange functionality, and I'll ask it to generate let's say np dot random function dot rand integer values between let's say 1 comma 100, and I need the size or the shape as 2 rows 3 columns, so two, first dimension 2, second dimension 3, third dimension 3, fourth dimension 4. Good. That's the 4-dimensional thing that I've got. Good. Great. Unmatched bracket. So I have an extra bracket over there. Let's print data. That's the 4-dimensional data that I have. Good. Why it is 4-dimensional? Because you can look at this. I have 4 brackets right at the beginning, and you can look at this 4 dimensions which tells me right at the right. Are we good? The point arises that if I wish to access any single element, let's say for example, I want to extract this 32 from here, right? Get, I want to talk about this 32. I want to do some actions on that 32. So I want to access that. I want to manipulate that. I want to change that. Could be anything. But now, where is that 32? If you look at that information. So in order to tell that information, I would request you to look at the shape of this data. This is 2334, right? So what it tells me that in the first dimension, there are 2 elements. In the second dimension, I have 3 elements. In the third dimension, I have 3 elements. In the fourth dimension, I have 4 elements. Agreed? Great. Now let's try to number them up. The numbering that I'll try to do is going to start from 0. So I have, in the first dimension, I have 2 elements. So that will start from 0 and 1. Good. 2 elements done. Second dimension, I have 3. That will start from 0 again, 0, 1 and 2. 3 values. Third dimension again, 3 elements. That is 0, 1 and 2. And fourth dimension again, 4 elements, 1, 0, 1, 2, 3. Acceptable? So every dimension, I'm going to start the number with 0. Is that okay? And I'll keep up to a number or integer value on the positive side with a gap of 1. Up to the count of values of in that particular dimension. Now, if you try to look at it in a very simple manner, the outermost bracket, this is your outermost bracket starting. This is the first dimension, right? Which closes down at the bottom. How many elements does it have? The first element it has is this, from here till here. That is your first element. The second element starts from here and goes to the bottom, not visible in one single screen. Let me just try and reduce it down. Okay, now I can get it. So that is your outermost bracket. Look at this one here, closes here. The first element that I have is from here till here, right? The second element is from here till here. Acceptable? Great. Now, if you remember my shape, that was 2, 3, 3 and 4. That is my shape. So first dimension has 2 elements. I gave them numbers 0 and 1. So first element is 0, second element is 1. Good. Acceptable till now? Numbering. Now, let's move on to the second dimension now. The second dimension is starting from this bracket, the second bracket, and it closes over there. Good. It has first element, which is from here till here. First element from here till here. Second element from here till here. Third element from here till here. Good. I'll number them again. This is 0. This is 1. This is 2. Similarly, for the second part as well, in this as well, second dimension starts here, ends over there. I have first element, second element, and third element. This is again 0, 1, and 2. Acceptable? Second dimension done. Let's look at the third dimension now. Change of color. Third dimension, this starts from over there, closes over there. Correct? So I have 1, 2, and 3. Similarly, in this case, 1, 2, and 3. 1, 2, and 3. So does here 1, 2, 3. 1, 2, 3, and 1, 2, 3 over there. Acceptable? Let's number them. So I'm putting that onto the right side. This will be 0, this will be 1, this will be 2. This is 0 again, 1 and 2. This is 0, this is 1, this is 2. This is 0, this is 1, this is 2. 0, 1 and 2. 0, 1 and 2. Acceptable so far, team? The numbering. Please follow the numbering. Great. Let's look at the fourth dimension. In the fourth dimension, this is the fourth bracket starting here and closing here. So I have 4 elements, 1, 2, 3, 4. I will number them as 0, 1, 2, and 3. Good. Let me just copy that. This is 0. Change of pen. This is a 0, this is 1, this is 2, and this is 3. And please assume that I'm writing it down for all the things, right? This is all 0, this is all 1, this is all 2, this is an all 3. Good. Instead of me writing down it for every single data point. Common. Good. Now, I was asking you about 32. Right? This was the number I was trying to extract. Good enough? 32. That was my point of question. Now, tell me, out of all the dimensions that is being mentioned along with the numbering, good, the number 32, see, in your shape, you have first dimension, second dimension, third dimension, and fourth dimension. Acceptable? From the first dimension, which section, which number has the number 32? 0 or 1? There are two possibilities, 0, 1. We have that in 0, correct? So I'll use 0. Now, for the second place, right? Within that 0, the second dimension, I have it in 2. For the third dimension, I have it in 2. For the fourth dimension, 0, 1, 2, I have it in 2, right? First dimension at 0th position, second dimension at second position, third dimension at second position, fourth dimension in second position. Agreed? Thank you. Now I can utilize this information and extract that value. What do I want is, in my data, put up a square bracket. Square bracket is used to extract a value. I want a data which is in the 0th first dimension, number 2 second dimension, number 2 third dimension, and number 2 fourth dimension. Did I get 32? Great. Now, on my screen, let's have a look again. And let me see, I've removed down the numbers. Let me see if you guys can tell me, how can I get 12? This 12. Where it is? See, we need to understand position-wise in terms of numbers, in terms of indices, where the thing is located. So this was 0, this was 1. So I am into 1. Into 1, this is 0, this is 1, this is 2. So I am again into 1. Within 1, I have 0, 1, and 2. So I am again into 1 and 0, 1, 2. So triple 1, 2. That should be the answer. Sensible? Please remember, whenever you have to extract a value, you need to use a pair of square brackets. Within that pair of square brackets, you need to mention in a comma separated form the position of that data, wherever it is, whichever the first shape place, second shape place, third shape place, whatever the dimension you have. If it is 2-dimensional, you will only have 2 values. If it is 3-dimensional, you will have 3 values. If it is 4-dimensional, you will have 4 values. Sensible? I've given you a very generic method. It is applicable to any dimensional array. That's indexing. Next comes is the slicing part. Confused? Okay. Why am I getting an output as np.int 3266-bit? Because you are using a little better version of me than Python. In Python 14. It's a Python version issue. How to find 12? Where is 12? X 0, 1. It is into the zeros place. Within that 0, it is 0, 1, 2 in the first position. Within that 1, it is at 0. And within that, it is again at 0. So it will be at 0th, first space, first, second space, again 0, again 0. Give that a try. You might not have the same numbers. I'll just show it on my screen because it's random data that I've generated. Let's print from my data square bracket 0th on the 4th dimension, then 1 on the 3rd dimension, 0 on the 2nd dimension, 0 on the 1st dimension. You always need to think about the shape. Remember the shape first, because if you concentrate on shape, it is easy. Otherwise, numbering is very, very difficult. Sensible, not sensible, eyes, nose, maybe is confirm. Now, just for the sake of understanding and make it easier to comprehend, the slicing part I'm going to do with the 2D array. Let's create another data is equal to np dot, and I'm going to take out a two-dimensional array, put up 1, 2, 3, comma, let's put up 4, 5, 6, comma, 7, 8, 9. Why I'm doing it with the 2D is because in real world scenario, you are mostly going to deal with the two-dimensional data, not 3 dimension, not 4 dimension, not 1 dimension. Majority of the problems you'll be solving with 2D or 1D. 3D, 4D will come, even if the data comes in that space, you will still redirect that into 2D, usually 2D or 3D. I'm going to print DATA for you. Good. Look at the numbering here. Outermost bracket, 3 elements, 0, 1, and 2. Second bracket, 3 elements, 0, 1, and 2. Acceptable? Now, if I ask you where is 1? 1 is at 0, 0. Where is 6? 6 is at 1, 2. Where is 8? 8 is 2, 1. Now, if I wanted to extract a single number, if I have to extract a single number, let's say it's number 6. I want to extract that. How would I write it? I write it the variable name followed by a pair of square bracket. I tell it where it is present in the first dimension. It's present in 1. Then I tell it where it is present in the second dimension. I get that value. Correct? Good enough? Now, let's change the topic. Let's change the complexity. Now, I do not need a single value. Rather, I need multiple values. For example, I need 1, 3, 7, and 9. Can I extract this? 1, 3, 7, and 9. So I need 4 different values together. So you can say that, okay, 1 is at 0, 0, right? 3 is at 0, 2. This is at 2, 0, 7, and this is at 2, 2. Are we agreeing on this point? Thank you. Now, let's try to concentrate. If I need all those 4 terms, I can use print and I can write down, okay, DADA square bracket at place 0, 0, comma, and I can put up at place 0th row, second column, or second row, 0th column, and I can have second row, second column. Correct? I got 1379. But here, these are not as a single, these are not coming as a single unit. These are separate values extracted separately. I've just printed them together. But what if I need them together? Think about it. So listen to that very carefully. When I'm extracting values from DADA, I use the square bracket to extract it. Right? It was a 2D array. So I mentioned 2 things. Right? The value or the index for the first dimension and index for the second dimension. It extracts me the values, the first dimensional index and second dimensional index together. Right? That brings me 9. Acceptable, eyes, nose, maybes. as an example. Good. Now, but I here require a different scenario. I need the data from row 0 and row 2. And when I'm selecting row 0 and row 2, I am selecting column 0 and column 2 over there. Similarly, column 0 and column 2 over there, isn't it? So essentially, what I'm looking forward to is in my data, use the rows starting 0, colon, ending 3 with a gap of 1. If you remember the range functionality, that would generate 0 and 1, or 0 and rather, give it a gap of 2 rather. 0 and 2 will be generated, isn't it? Start value, stop value, and a gap. Is that going to generate 0 and 2? Great. So that is what I defined for the row, because before the comma, the first dimension. After the comma, the next dimension. In the next dimension again, I need 0 and 2. So same thing can be repeated. Can you see this? Did I get 1379? So what did I do here? I extracted out a chunk of data or chunk of information, not the entire thing individually, but separately a small little chunk, just like pizza. If this is the pizza that is there and it has jalapenos, it has, let's say, a corn, it has, a tomato, it has a capsicum, right? It has, let's say, olives, for example. Let's say it has cheese, some cheese crumbs, whatsoever. Now, instead of talking about jalapenos, cheese crumbs, and all those things one by one, what we're trying to talk about is a slice that will contain anything and everything, could be anything. But it has a starting point, it has an ending point. Make sense? Same thing. A slice. Slice means a uniform set of information which is equally separated or equally spaced in terms of gaps. I can extract that out from the entire array. Good. What I need to make sure that I put up the things in terms of range while extracting. Good. Can you explain the command 116? See, Kotian, for that you need to know range. That is very important. Or do you know a range? Either way around is fine with me. Let's take that into example. What I expected was, this was the given data to me. This was my given array. Good. Now, into this given array, I was looking forward to extract 1, 3, 7, and 9. Good. Great. Now tell me what index or what are the positions of all those 4 numbers. I have 4 numbers, 1, 3, 7, and 9. Where is 1? 1 is at 0 index, 0, 0. Where is 3? 0, 2. Where is 7? It is at 2, 0. Where is 9? It is in 2, 2. Acceptable? Thank you. Now, let's try to concentrate slightly onto this part. Slightly. The data or the information that you are seeking from, the outermost dimension that I have has 0, 1, and 2. And the second dimension also has 0, 1, and 2. Acceptable? The data that you are looking for is in dimension 0, this value and this value, correct? And this value and this value. Is that correct? So what you essentially require is a value at 0, 0, value at 0, 2, value at 2, 0, and value at 2, 2. If you look at this part, what is that? It's a sequence of two numbers, 0 and 2, right? What is on to the right side? Again, that is also a sequence of two numbers, 0 and 2. Good. So I need a mechanism by which I can generate these two numbers. If I can generate 0 and 2, again followed by 0 and 2. So I will have a combination of 0, 0, 0, 2, 2, 0, and 2, 2. Good. What I need to do is I have to now generate a sequence in such a manner that while I'm trying to extract the information, I need to give two dimensions for the first dimension, for the second dimension. In this place, I need to put up a value in such a manner that it is a sequence of numbers 0 and 2, which I can get from 0, colon 3, colon 2. Range functionality. Start from 0, stop at 3 with a gap of 2. So 0, next number is 2, next number cannot be generated. Good. This will generate number 0 and 2. Acceptable? In a similar fashion, on the second index, again, I need zeros and twos. So 0, colon 2, colon 0, colon 3, colon 2. That is also going to generate 0 and 2. So now my machine will get to know that I need to take combination of 0, 0, combination of 0, 2, combination of 2, 0, and 2, 2. So 4 different values have been sorted out, and that will be taken up. Let's try to take that through a different example. Maybe that will help. What if I need, let's say, 1436. On the first side, first index and second index. From the first index, I need 0 and 1. Right? I need the data from 0 and 1. Second index, I need 0 and 2. Acceptable? How can I generate 0 and 1? Start from 0, stop at 2, take a gap of 1. How can I generate 0, 2? Start at 0, stop at 3 with a gap of 2. Acceptable? That's it. Use square brackets and put the data around it. 1436 should be there to showcase. 1346. Good. Thank you. That is called, we call it slicing. Great. That's your file for the day. So we have, almost completed certain line 116 again. Okay. What is the problem with 116? The count. That is notional. I can avoid that. Looks like I went to Siberia or Russia, maybe Eastern Europe. But objective is not to type your name in reverse, print your name in reverse. I have a different objective over there. The code that I've written down over there, is that comprehensible for everyone? Eyes, nose, maybes. 3 has written down 9 colon 0 colon minus 1. 0 to 9. Abhinetri, that would have missed A at the beginning. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that would have missed your first A letter. You would have got IRHTENIHB. A would have been missed. Abhinetri. If we just copy and paste. As a part of just quick revisiting to the things, I'll just quickly walk you through with what we have covered up so far in the previous library, which was NumPy. Very quickly, in the meanwhile, maybe some more people might join in. So we talked about NumPy, as you can see on my screen. What is NumPy? Why NumPy? Then we talked about the arrays. How do we create arrays using the array function? Some properties like endim, shape, size, dtype, and item size. Then we also talked about few things with respect to how to create multi-dimensional arrays. We looked at some basic functionalities like reshape functionality. We'll talk about the flatten function. Then we have talked about transpose. We have talked about some statements from arithmetical and statistical functions, addition, subtraction, and all. Then we talked about statistical functions like mean, median, standard deviation, variance, percentile, range, and interquartile range. I have talked about all of them. Hopefully you guys can remember and recall all those. Then we talked about the implementation of string functions on an NumPy arrays. We worked on that part. Then we looked around some miscellaneous important functions, not all of them, just some important functions of relevance, like arange, linspace. Then we talked about some random functions like rand, random. I've talked about uniform. I've talked about randant. I have also given you information about the seed. What is seed and what is the role of seed? We have talked about indexing and slicing. How do I take out a single value from an array or multiple set of values from the arrays? That's what we completed at, and maybe this was the one question that we did it at the end. Good. Today we're going to start off with another library called as Pandas. So let's have some discussion on Pandas first. Let's see how many of you has what kind of opinion about Pandas. Tabular data, rows and columns, data analysis and statistics. Great. So let's talk about Pandas. Very simple library. We'll start with the word Pandas. Right. So Pandas is another library which is built on top of NumPy. A library, I'll say that. It is a library built on top of NumPy. So when I say on the word top of NumPy, what does it mean? That it uses NumPy as its base, as a base library, and using that base, it is going to process a lot of things, right? So it is built on top of NumPy and is useful for data analysis, is useful for data manipulation. It is also useful for, let's say, data visualization. We can create data visualizations from it. When I say visualization, it essentially means that we can create graphs and charts. We'll talk about some more libraries on graphs and charts. That's a separate thing, right? So data manipulation, data visualizations. Well, data exploration, you can say that. Data analysis and data exploration. Let me put that up together. Data exploration and analysis. Now, what is the problem? Now, why we need another library, right? So why we required Pandas was one of the very basic reasons. Now, for all this purpose, NumPy is also good. NumPy was effective for, you can say that it is effective for the numerical information, numerical data. However, it lagged in the data exploration and manipulation facilities, right? And manipulations. So the solution was this, which is the Pandas library. Now, what is the advantage? Why do we, use Pandas? Is one of the prominent reasons. Pandas makes the Pandas allows to explore multiple data forms or explore data in the form of tables. In the form of tables, or we can say that that is like a rows and column structure, a rows column structure. Now, how does it Panda does it? Pandas offers that. Pandas offers these facilities, some basic theory part, right? These facilities or functionalities, I would say that functionalities using two major data structures, right? Two major data structures. Can someone tell me what are the two data structures that are there? And these are, number one, we call it as a series, and the second one is called as a data frame. Two major data structures. However, with Pandas, there are more data structures which are not commercially used, but they are theoretically present. One is called as a panel data, another one is called as panel 4D data. So there is two more categories into this, but panel and panel 4D are not commercially or practically not viable, so they are not used, but they are there, to be very precise, right? Certain scenarios over there. I'll bring into your picture right now. Why we prefer series and not a numpy array? I'm going to import numpy library. And team, I'll like you guys to practice along with me. Numpy as np. And I'm going to import the pandas library too. Import pandas as pd. Those who are using some tools other than Jupyter Lab might not have pandas installed. So how many do you know, guys, how to install pandas? Yes, no, maybe quickly. Or any library. Just a quick note to install. Yeah, you can use pip install. Thank you. To install pandas, I need to just execute. Remove the double quotes. Thank you. So if you do not have pandas installed, just execute this line. That should be good. Great. Let's just import pandas and numpy. Why did I import those? Because I want to create up an array. I'm going to create a very simple one-dimensional array. Okay. And you guys need to listen to that very carefully. I'm going to speak out certain things and I want your full attention onto this. I'm creating an array about my wardrobe. Let's say my wardrobe. Okay. My wardrobe has, let's say, 3 trousers, 4 t-shirts, 2, let's say, 2 ties, 3 pair of socks. I have 2 pair of shoes. I have 1 wallet. I have, let's say, 2 belts, and I have, let's say, 4 handkerchiefs. Did I give you some information? Let's make that as a numpy array. Np.array. Everybody okay with this? I have created a simple array with some data points. Eyes, nose, maybes. Thank you. Let's name that as wardrobe array. Wardrobe underscore ARR. So that we can. Great. Now, can you tell me what was this too? No, I had 3 socks. See, my objective is not that. Hanky was 4. Kunal. I can show that from the transcript of this conversation. There will be transcript available if I'm not wrong. Or maybe after the session, it would be made available. See, objective is not that. I do not want you to remember those things. But point is, with this data, I am not able to remember anything. Now, if I just try to show it up, let's say I'll print that wardrobe ARR. Let me just print that up. Let's print that. Good. Now, these are the numbers. Now, with this array, I also get the facility of index, right? I can also see the index values. Let's print wardrobe ARR again, and I'm going to dot index. I can get the index too, correct? Oh, I cannot get the array index, right? But we know, right? For array, I cannot get the index. Good. We know that there exists an index, right? I can access any element. This is index 0, this is index 1, this is index 2, and 3, 4, 5, 6, 7, up to index 7 we have. Correct? Acceptable? Now the series gives me a better option. What series tells me is that I give you a leverage that you keep this data on, right? Keep this data on, whatever the data that you have. But along with that data, you have the leverage to use the index as a visualization or as a visual look. You can take a visual look at the index too. How will that happen? Let me just try to create up a series first, then I'll come to the syntax. Good. So let's say I want to create up the same series, wardrobe underscore SR, let's say, so that we can remember it's a series. Good. Is equal to same information, the same array I will use, no problems, but I'll say that pd dot series, and I've used the same array. Good. Now let's have a look. How does that series look like? Same piece of information that you have seen before, but onto the left you can see that there is an index 0, 1, 2, 3 up to 7, correct? And onto the right you can see there is a data. Good. So when you look at this data, I'm saying about the look part. If you view that data, you now can see at what index what value is there. And then see with the series, you also get an option that you can manipulate this index. That means this is a default numerical index that is by default, it happens with everywhere. But I have the choice that I can manipulate that too. How? I can tell while creating the series. Okay. So let's say I'll put up SR with index. Same piece of code. No changes. I just change the variable and I'll change few parameters in the series function, series class. Good. I'll put a parameter called as index is equal to, and now here I can pass on a list of values which I want to put up as an index. Let's suppose I wanted to have this as 3, let's say 3 trousers. Good. Let's say I had, what was the number 4? Let's say I had 4 shirts. That's it. 2 socks. What was the next one? Let's say 3, whatever number that is. Let's say 3 shoes. So I'm giving some random things, right? Then I had 2. So let's take up 2 wallets. Let's say 1 belt. Let's say anything else. What else? I have next 2. So it could be anything. Let's say watch. Let's say the 7th one, 8th one is, let's say, hankies or handkerchiefs. Or let's put up something simple. Let's say tie. Randomly chosen. Now, when I create this, look at this. I had 8 values, right? I had 8 different values of different nature maybe, right? All those values are as it is. And I am telling that, okay, first value indicates the trouser, second value indicates the shirt, and so on. Once I do this, look at this. What did I get? I get the same series, right? The same series. On the left side, I still see the index, and on the right side, I see the data. Now, if you look at this data that you see on my screen right now, this series, right? And compare that with the array, that is wardrobe ARR. I'll just print that for you here too. So this is your wardrobe ARR, which is an array. Good. And this is your series, right? Wardrobe series with the index. Can you tell me which one is more informative for you? Carrying the same data information. Data carried is same, right? The series is more informative. Now, if you have to make any decision-making process, or if you have to make any understanding about this data, this is much more convenient for us to explore and analyze data as compared to the series. Correct? As compared to the arrays. That's why Pandas. So Pandas gives me that leverage of using things with names. I cannot do that with the arrays. I can do that with the Pandas. Right? Are we good with the series so far? What is the purpose behind series? So it allows me to use index of my choice. Will we do it later on? I will come to that point as well. Whether we would actually go with that indexing in real world or not, that's a separate issue. Good. I can definitely scroll up. Can I hide the outputs so that you can look at the piece of codes together? And definitely these indices you can manage as per your choice. I've just put them random. Thank you, Yosef. Good. Rest of the team, I hope so fine. Everyone, thank you. So that is the idea. So let's just try to bring down the syntax. Right. So again, as per the standard definition of series, we go with it. It's one-dimensional array. So a series can either be created using the series classes, or could be generated created as the series class object. Let's just put it in correct nomenclature. Or it could be generated through other methods. So there are some more methods which are available, which are series generative methods that directly creates the series for us. We don't explicitly tell them to create using these series function, just like array function, right? You have a function called as np.array that allows you to convert any data structure to array form. In a similar fashion, we have a series class, and I can use that to create a series object. That's fine. Second thing, there are, let's say you have a function called as arange, or let's say a random. Those are the array generative functions where the array is generated from them. The outcome of a particular function, a particular process is an array. Similarly, we have certain functions in series as well, where the outcome is a series. Resultant is going to be a series. Good. There you will not explicitly use a series function, but yes, series will come out. So let's put up the syntax. Create series, or I'll put up the generic syntax. Let's put up the generic syntax. Create series is, and I'll put that here. So I'll put up the word pandas dot The name of the class is series. Within the pair of parentheses, pair of round brackets, I need to put up data, whichever data that we have, and an optional list of index, list of indices. That has to go with index is equal to. There are some more parameters into that. I will not talk about them as of now. We will discuss all of them later on, as and when we require them. Okay. Good, everybody. Simple thing. Here, the data could be anything. It can be a list, it can be an array, it can be a dictionary. I'll talk about all of those options one by one. Good. So let's try to create the series using different methods. Or rather, not different methods, but different inputs, different sort of inputs. Good. Let's create series, creating series using. So do I need to put up another example for arrays? Because we did create one series above with the array. Okay, thank you. No problem. So I'll do that. It's creating series from a list. So I'm not going to make it very complicated here, right? I will try to keep it simple so that we can know about it. We can work around with this at a later stage. Good. So let's try to work around. Let's take up something as data is equal to a simple list 1, 2, 3, 4, 5. Good. A simple list. I'll create my series. Let's say SR1 is equal to pd.series of data. I'm not putting up any index by default. So very simple. SR. Let's take up the same data. Okay. I create another series with specified index. Let's say I want to use some specified indices over there, right? Some specified index. So how will I do that? Let's put up the same piece of code again. SR1, let's say put up with index. Now with index essentially means that I am putting across my own index. Otherwise, the default index is always there. Whenever you create up a series, when I put up a specified word, that means I'm putting up the specified index. I can put up here comma index, and let's take that up as, just wanted to save time. If you want, I can put up index as a separate variable and put up index is equal to something, right? That is my choice. But does not make a difference. Great. Yes, Rosie, I'll do that examples. Don't worry. We'll do the dictionary, we'll do the tuple, we'll take the arrays, everything. With dictionary, there is a slight, variation. So I need to talk about that variation too with dictionaries. So I'll keep that for the end. These are your building blocks of understanding pandas. To be very basic things that I'm talking about, but these things will make you, make your foundations correct. So whenever you deal with a bigger data, these basic concepts will help you a lot to understand that library. Okay, great. I'll just display those two things to you first. Print SR1 so that you can remember. Let's just print print SR1 underscore with underscore index. So team, it might be possible that I might be typing a little bit faster. So ask me to pause. I'll take a pause if you're coding along. Right. So we got the series, right? I have created data 1, 2, 3, 4, 5. When I print and I created a series SR1 and I create another series SR1 with index. With SR1, I did not mention any index parameter, but here I have mentioned an index value that I want A, B, C, D, E. Now, please remember that the number, if you're using index, that means whatever the number of elements I'll have in 1D, that many index are supposed to be given. I cannot make 4 indices over there with the 5 values, or I cannot put up 6 indices with this 5 values. That's not possible. With 6 indices it will work, but 4 indices it will not. Great, good, yes. Thank you. Let's move on to the array example. We'll copy the same information to you. I'm going to just change from list the word to array. Typically, there is no change. With list and array behaves in the same fashion, list, array, and tuple. The only difference is in the terms of the nature of the data. That's the only thing. So I can put up this here, data is equal to np.array. I've just converted that into an array form. Now, is that all created from an array? Do we agree? Thank you. So same output, no changes because it's going to behave in the same fashion. I can put up the same example with the tuple 2. Rosie wanted that. Copy the same example and that will work the same way. No need to put up anything. I can put that through tuple. That should be just a tuple. I just make it as 1, 2, 3, 4, 5. Rest of the things I'll keep it same. Rosie, still get the same results. Now that's not expected, Asif, though I can explain that. Can you tell me very simple thing, Asif? What happens if I put a string A multiplied by 2? What does the multiplication behaves in the form of a string? Since it's 2, you can say duplicate, Sabnetriya. But this multiply sign is the repetition. Essentially, I'm telling it to repeat A 2 times. If I put up 4 here, repeat A 4 times. When I write down a dash multiplied by 50, what do I want? I want dash to be repeated 50 times. Why did I do this? Because there were 2 different series that I was trying to print in. There are 2 series that I'm printing in. This was the output for SR1, and then I used immediately SR1 with index. So I just wanted to segregate both of them so that you can have a clear visualization that this is your SR1 and dated here. This is your SR, the second one with index. That was the only purpose. So I wanted that dashed line in between. So my 2 outputs are separated. That looks a little beautiful. That's it. The outcome looks little kind of, what do you say that? What word should I put it up? Kind of aesthetic. I guess so. Aesthetic is the word. Cosmetic. Thank you. Hope so that's it. Little bit bad throat, please. Okay. So everybody okay till now? There is an issue with the dictionary. So let's take up the same thing that I have taken up earlier. Let's take up a dictionary, dict1. Okay, that's a simple dictionary I want to create. Let's say I have taken up A, okay, key A, value 1, anything of your choice. You can take up any keys. B, colon 2, let's say C, I'll put up :3. This is just for the ease of access and ease of understanding. I'm taking simpler values. Let's say D :4. Let me make it 7, because otherwise you will say that, okay, why are you taking them in sequence? Good. E colon, that is Z :21, or let's say 3, or let's say any number 3. Let's say. Good. Okay, so I have taken A, B, C, D, Z. Let's take any. Okay, that's fine. Now, if I go create a dictionary from here, or let's say create a series from a dictionary, now there is no problem when I create it with the index, without the index. Let's say if I create up this SR underscore with dict, or SR from series from dict, so that we get to know it's a series from the dictionary created. Same function, same class, pd.series, and I will pass on the dictionary dict1. No problem. If I just print that up, there is the problem. Drawing point is, you need to understand it. Here, instead of putting up the manual or the default indices, right? The default indices 0, 1, 2, and so on. Instead of putting these index, what it does is the series will now take the keys of my dictionaries as the index, right? The keys will become the index or the label, right? You can say index or label, anything, right? And the values that we have, they become the data. Do we get this? Just to have a look. You see that A7, the key become the index, and its corresponding value is the data. If that is sensible by any means to you, anyone. I will bring in the catch that is not yet there. Series converts anything to dictionary? No. That is wrong, the wrong assumption, Preeti. Series is a different way of arranging data, different architecture. Dictionary is a different architecture, completely different. They look similar, they appear to be behave similar, but series offers a lot of different functionalities than dictionary can offer. So we can't manipulate the labels now. We can manipulate the labels. The labels can be manipulated. I can change those. I'll talk about those, how we can change the labels. Suppose I do not want a B here. I want something else to be changed. I can do that. But that is something futuristic. I'll talk about those things too. Slowly and gradually. Time will come. How we modify any kind of label. Not even with the rows. Later on, when we talk about the two-dimensional data, you might want to change the column names as well. The column headers in a 2D. So I will tell all those things. Don't worry. Everything is going to come up. Any kind of basic, operations that you might have to deal with any kind of tabular data, you will not feel uncomfortable about it. Split function, where I use that ABCDE there, right, to split that thing. Is that what you're trying to talk, Asif? Here I used it when I wanted to do this. So I will have Asif and Khan as two separate words extracted because there is a white space in between. and that will be given to me back as a list. So I got the result as a split it thing. Good. If I would have, let's say I want to split on, there is no repeated character. You can say that, let's say if I put up, let's say I want to split on a small a, then it gives me two letters. One is Asif and the other is N, because that will be omitted. Whichever character I want to split up, take it off, remaining things will become comma separated values from that junction. So you can split on any character, or you can split on white spaces. Thank you. But this is coming from very basics of Python. Asif, if you have not gone through with the basics of Python, I'll recommend you and request you please go through with that. That will be, easier and convenient for you to follow along. Great. Now let's bring in a problem. The problem is that I want to bring into the picture is a series. Suppose, what if I want to create a series with index? Till now, this is a valid series, correct? This is a valid series. This is a valid, this is a valid dictionary. This is a valid series conversion, right? I'm converting the dictionary to a series form. Acceptable? Let's say I'll put up with index. Good. Now I'm going to put in the index. Let's say index is equal to, I have put in, let's copy of the same index that I've used earlier here, A, B, C, D, E. Good. Let me put up a G there. Let me put up M here, not M. Let's put up a C here. Good. So look at this. What did I do? I have randomly put in a lot of things. Let's put up comma Z also. Great. Okay, that's fine. Now look at this. What is going to, will it work? First of all, think about it. Do not execute. If you're typing along, do not execute. Let me just think about for a moment. Should it work? Kunal says no. That should be the obvious answer. It should not be working. Why? Because we are using a dictionary from 6 or 5 values, and I am creating up, giving index out of bound. Many indexes are given, but that exactly is not going to happen. Now listen to my words very carefully. How does the series class is going to create the object from dictionary? Listen to that very carefully. It is going to create a series object of these index. That means I will have a series that will have index value A, B, G, D, E, and Z. Get? Then, in order to get the values or the data, so this will be my index. In order to get the data, what is series going to do is going to look for that index, whether it is present into the dictionary or not. If the index is present in the dictionary, it's going to take the corresponding value. So A is present, I'll get 7. B is present, I'll get 2. Then I have G. G is not present, I'll get a nan. I'll talk about what is nan in a short while. Good. Then I have D, which is present, I get a value 6. Then I have E. E is present, no. So I'll get a nan again. Then I have a C as per the dictionary. So C has a value 3, I'll get a 3. And then Z have a value 3 again. Do we get this? So series will create the series based upon index and try to fetch the value from the dictionary for those indices. If the value is available, it will take it up. If not, it will put up a nan. What was the word? Nan. Let's just have a look. What did I put? Oh, space. Can you see this? It did create up the series. It was not an error. It did create up a series for me for the index given. Good. But this index will try to fetch the values from here. If the value is available, I will take that value. If not available, I'll put up a nan. What is nan? Nan, those as a term of full form, stands for not a number. It stands for a not a number. That's the basic definition. But do not go by that word. The essential meaning of nan is none or nothing. It is nothing. Nothing means a blank area, not even a white space. I'll come to that, Kunal. Hold on. I have everything in my brain. It was integer here, now it is float. What changed? But did you get this point till now? Everybody? So please be cautious while you're using dictionaries. If you're using dictionaries to create series, please be cautious that are you using an index? If you're using the index, whether it is present, not present, you might land up with the nan values. Nan values means essentially we use the term called as missing data or missing value. Good. So whenever there is a key or there is a label, that particular label does not have a data, then we call that as a missing data. Let's take up another example of understanding what is missing data. Suppose I ask you to fill up a survey, right? At the end of the session, we usually ask you, right? You give a rating on first parameter 1, second parameter 1, third parameter 1, fourth parameter you don't give it, fifth parameter again 1. Right? Now this parameter will always be there, right? But I will have nothing over there, no input. That nothing will still be a part of my data, correct? Though it is blank. So that nothing will be represented as nan. Now, why nan? Why the float question, right? So essentially, now listen to that very carefully. Do you know the type of precedence in arrays? Did I talk about that? No. Type precedence in arrays. Did I talk about that? No. Okay, thank you. So again, conceptual thing, team. So remember, it's just a conceptual thing about the precedence. So I'm currently talking about array. Now, do we know that in terms of arrays, array have all data elements of same type, right? Array will have all elements of same type. That means if there is an integer array, every element is going to be an integer. If there is a floating array, everything is going to be float, correct? Every element is going to be floating point. That means there will be a homogeneous structure in arrays. Now, what happens is, let me just try to talk about this. Suppose I'm going to create up an array from a list. Okay. So if my list contains, let's say, very simple example, all integers, right? 1, 2, 3. Yet, if my list contains all integer values, the data type or D type of the array is going to be integer. Good. Agreed? Eyes, nose, maybes. If I create up an array that contains one integer, second one is also integer, third one is a floating point number, let's say 3.5. What is going to happen? It is going to convert both the integer values to a floating point representation. So what I'll get is a data type as float. It is going to convert 1 to 1.0, 2 to 2.0, and 3 to 3.5. Correct? 3.5 will remain 3.5. So every element is now in floating form. Good. Agreed. if there is even a single element which is of floating nature, all the elements become float. That is what happens in array. Similarly, if I take the same example of an array, again 3 inputs, I have 1, let's say I have 2.5, and I have 3 as a string. Good. I'm talking about arrays right now. Good. So in this scenario, what is going to happen? If that would have been an array, 1 will become a string, 2.5 will become a string, and 3 will remain as a string. Everything gets converted to string form. Correct? So if there is a single string present, then everything gets converted to string form. If there is a single floating point number present, then everything gets converted to floating form. If all the values are integer, then it remains integer. Correct? Everybody okay on that? Eyes, nose, maybes. Or should I showcase that first? Through example. Nobody? So essentially I can say with the arrays, highest precedence is to the string, then to the float, and then to the integer data. Integer and boolean are same. Bool type structure and integer type structure, scalar data structure. So bool will be given equal precedence to the integer. So if there is a boolean value, boolean will remain boolean, because boolean is a subpart of integer now. Thank you. Now that is what with the arrays, but with the series there is a small little issue, because series supports heterogeneity. It supports heterogeneity. That means if there are different types of data, the type will be maintained. Type will be maintained. Individual data type will be maintained. But there is a small little kind of exception to that, and that is with the integer values. Right? If I'm creating a series with all integers, 1, 2, 3, let's say, right? It is going to be integer type. Good. If I create up a series with 1, 2, 3 and one of the floating point number, let's say 1, 2.5 and 3, it is going to convert everything into float form, and I'll get the floating integer, just like arrays. It behaves in the same manner. So integer and float, these are changeable. Good. How? So integer values will be turned to float if there is a float value. However, if I have the same sequence 1, let's say 2.5 as a floating point number, and I have a 3. Now, had that been an array, the data type of this array would have been string. Agreed? Every individual element has been changed to string. If I create an array out of it, if not, if I do not create an array, I create up a series. What happens is it shows me the D type as object. It will show me the D type of this entire series as an object, and it is not going to convert anything. Integer will remain integer. The floating point will remain floating point. A string will remain string. Individual item will hold to their data structure. Right? But the overall data type will be given as object. Good. So if you see a series showing its D type as an object, very critical point to remember, right? If a series is showing a D type as an object, that definitely means that contains a non-numeric input. The series will somewhere have a non-numeric data. Are we good? Thank you. Now coming to this point, why float? This is float because the default data type of NAND, let's try to check. Can I just Okay, I did not talk about how to access those values, but just to showcase, right? This is the thing. I can put up use a square bracket, and we know in order to access the value, we use the indices. So I can put up the index. What is my index? For NAND is G, right? If you look at G right now, it is NAND value. Good. If I print it up, I should not see. I see NAND word, right? If you try to look at the type of it, that gives you the data type of it, correct? It's a numpy floating point number. Good. So essentially, by default, though it does not acquire any space, it does not have a value inside, there is blank, but there is a default data type given to the missing data or NaN values, and that is floating point. And hence you see that all the values is converted to float form, and the data type has changed to float. Here, right, I told you that I am using 5 elements. I should mention 5 labels. What if I make 6 labels over there? What happens? That's going to happen always. What if I, let's say, take up this example and I put up here another label, another index, F. So there it is not going to accept it. It is only and only going to happen with the series, with the dictionaries. If you try to create that through dictionary, then and only then you will get those things. Good. Or there is another thing. There is called as a scalar data. If I try to create up it through a scalar data, let's say 5, data is equal to 5, a single value, then it should create it 0 value, index 0. And when I put up, so when I printed that SR1, it was okay. If I print SR1 with index 2, you will see the difference. I get A, B, C, D, E, F all filled up with a common value. So the idea remains same, Rosie. The idea is that if it is a scalar data or a dictionary, your series is going to be coming from the number of indices given. Otherwise, if it is a list, it is an array, it is a tuple, you need to put up exact same number of indices as you have the data points. Ask if you would have an unmute option.
Hello. Hi, sir. Sir, actually, see, like A is to 7. Can you please scroll up, sir, please?
Let me just take this example off. Okay, go.
Yeah, yeah. So, a little bit, sir. See, yeah, yeah. Here, A is to 7, like string with the integer, string with the integer, string with the integer, like with ratio, like how you have converted. But see, all of a sudden, why A is 7.0? Why it is especially giving it as float? I'm a bit confused here, sir, in this case.
See, I have a very basic question again. Do you know what dictionary is?
Uh, no, sir. Actually, dictionary, it's like it's a library.
Dictionary as a data type. Dictionary is a data type in Python, because I specifically mentioned you that earlier too.
Yeah, yeah.
Go through the
Go through
Python
it, sir.
basics,
Sure.
right? So dictionary is a simple data type in Python that is created as a key value pair, right? It's a comma separated values, comma separate data structure that contains key and its corresponding value, comma. I can
Okay.
have another key, comma, corresponding value, another key and corresponding value. So where key is some entity and it has a certain value. Let's say
Got it.
name
Okay.
Asif, age
Yeah.
12, organization Google. So I have keys and corresponding values. Good. So that is what we call as a dictionary. So that is why that arrangement. Yeah.
Yeah, yeah,
Good.
that I understood, sir. But here, like,
And why the 7 converted to 7.0?
correct,
If you
correct. That is
talk
my question. Yeah.
it, I explained that because the presence of NaN, because of
Okay.
this presence of NaN, right?
Mhm.
Because NaN is present, so I have a floating element into this. There is a floating point because nan is a floating thing. Good. It's a
Okay,
floating
sir.
point value.
Okay,
Because
okay,
there
makes
is a
sense.
float.
Yeah,
So it has converted all integers to float form.
got it. Makes sense, sir.
Because
Okay, thanks.
7 and 7.0 mathematically does not make a difference.
Yep.
Mathematically, 7 and 7.0 will hold the same value, same meaning.
Yes.
However,
Yes.
in terms of representation, there's a difference, right? Integer 7 and floating point 7 are two different things. Good.
Yes.
So the essential change that will happen into the real world is going to be the place or the memory space that is being allotted. Because in integer, we will have a lesser amount of memory space as compared to the floating point numbers. Floating point numbers will acquire more amount of space. So it's a space consideration that we need to look at. Otherwise, it's fine. Good.
Okay, sir.
Never any sort of Google form, any kind of form, maybe an enrollment form, any kind of form, you must have filled it up. Suppose if there is a field which is not mandatory to be filled in, which is not mandatory, and rest of the team will also tell me if it is not mandatory to fill in that field. Now, team, listen to that very carefully. Many people talk about it in a different way. There are multiple ways by which I can access the elements of the series. But what the answer that I'm going to give you right now, whatever I'm going to talk about, is a futuristic approach. It is a futuristic approach. For example, let's try to, so in order to access any element of an array, how do you do it? You take up the variable name followed by a pair of square brackets, and within that square brackets you mention the index, correct? To access any value. Is that correct? So same thing goes over here as well. Suppose I want to access something. So my series name is wardrobe with SR with index. I'll take that. Put up a pair of square bracket. Within the pair of square bracket, I'll mention my index. Now here, let's say I want to talk about belt, or let's say some other number. Let's say shirts. So I will mention shirts. That gives me the result form. Great, no problems. Everybody okay with that? Simple indexing. Great. I want to make it complicated too. Now, essentially, we also know that this series, had that been a case I did not provided those indices, would have had the numerical index, right? Acceptable? So despite I have given the index of my choice, the default numerical index still prevails. That means I can still use that default numerical index to access the data. I can still use that to access the data. How will I do it? Suppose the same shirts. Shirt will be at index number 1. Agreed? What is the index value of shirt? If I go in 0 to 1 on the from top to bottom, shirt will be at index number 1. Acceptable? Yes or no? Thank you. So let's try to see if I can get the value for index number 1. Good. Now look at this. Here it says that it gives me the output 4, but it also gives me a future values, a warning. It says that future series.get item treating keys as position deprecated in future versions. It will always be treated as labels and considered with the data frame behavior to access so on and so forth. Right. So the ideology is that in futuristic terms, or maybe in the recent versions of Python, I'm using might be a little bit older version. So for me, it is showing the warning. For some of you, it might not be even showing warning. It might be giving an error. Good. So point is, listen to that very carefully, that this approach using with the numerical index is not recommended. So what do I talk about is, do not learn these two methods. Do not learn them. Let us learn what is more standard and more going to be futuristic. Good. So what you have to do is, listen to that very carefully. Whenever you are going to use a user defined label or a user defined index, good. Whenever you're going to use a user defined label or a user defined index, you are going to use a word called as LOC. That is location. Good. If you are going to use a numeric index, you all numbers, then you will use ILOC, that is integer location or index location. Do we get integer keys or it's actually integer location? Can we remember that much? So same piece of codes that I have written down over there, I can write them down again. Only difference is that before putting those square brackets, I need to put in those two words. I did not get the warning. Now, good. So start using LOC and ILOC. LOC stands for location. ILOC stands for integer location. Stands for location and strictly requires user defined labels. Good. And when I talk about ILOC, ILOC essentially stands for integer location and strictly need integer indices or integer index or labels. Good. That is the idea behind. Let me just put it up like this. That will be helpful information. So if you're going to use indexed the user defined index, it should always be LOC. If you're going to use integer values, it should always be ILOC. Can we remember this much? Is that okay? Or is it going above the head? Thank you. Now, the next thing that I like to put up is accessing multiple values. Till now, you have seen only single data point. I have extracted one data point, right? Let's access multiple values. So there are again two ways. For example, I can use lock and ILOC the same way. Same series that I've used before. And here in the index, right, .iloc, I can also provide the list of indices which I want. Let's say I want a shirt data. I want, let's say, a belt data. And I want, let's say, anything. Let's say wallets. Good. So what do you see here? A new series has been given to me, shirt, belts, and wallets. The order could be anything, right? I can put them up in any order. That does not make a difference. So the idea is I can specifically ask for any sort of values, right, based upon the user defined keys using the lock. What do I need to do? I need to put that across as the list. This is a list. Good. This is a list of key, a list of my indices that is used under the outer brackets, outer square bracket. That is for the index operator. Are we good? Or slice operator, you might want to say this. Or I can use these data with iloc2. If I want to do that with iloc, so I had shirts, that is index 1. So I'm going to take the same example. Belt is at index number 1, 2, 3, 4, 5, 6, or 5, if I'm not wrong. And wallets is at 4. So 2, 5, 4. List of indices. Which indices I want? I need 2, then 5, then 4. So I missed out on something. It's index 1. So you can see that here, shirts, belts, and wallets. Good. Extracted the same information. But there is a small little benefit also. Now, why you will say that if I can do it with a user defined, then why do I need that second numeric one? Let's suppose I may not need that sparingly like this. I need a small little chunk, let's say from index number 2 to index number 5. So I can also use it for slicing the integer locations. iloc, and I can, instead of doing this, I can tell it, okay, 1:5. So index 1, 2, 3, 4 are there. Good. Sensible, not sensible, yes, no, maybe. If that works well for you. Thank you, Abhinitri. But there are too many people in the house. Let's just take some confirmation from them too. A blank print statement team, so to segregate the outputs, that looks slightly some gap. Great team till now. Any questions, please ask. I have not yet talked about any kind of. So if you want to print 1, 3, and 4th call values alone, how should we slice? See, I do not have multiple columns. I have multiple rows there. Rows, you can say, if you want to look at that way. So essentially, you can tell me, this is your data. I am putting up the numerical index as well for you. 0, 1, 2, 3, 4, 5, 6, and 7. Now you tell me, what do you want? I'll tell you the way. Whichever way you want. Either you need to tell me index numbers or index values, or that's 2 things. Any of those 2 things. 1, 2, 3. Write down your series name dot iloc square brackets. Within that, put up another pair of square bracket to make a list and mention the index 1, 3, 4. Give that a try. Should I do it? So 1, 3, 4 is shirts, shoes, and wallet. I did it, the same, almost similar example. I did it here. Look at this. I have taken 1, 5, 4 instead of 1, 3, 4. Okay, now let's try to follow up with the basic problems that we have seen before, right? You have seen these basic functionalities in NumPy. So we'll talk about all those basic functionalities one by one. So that is your series. Good. So we have 1, 2, 3, 4, 5, 6, 7 elements or 8 elements into that. These are the indices. These are the values that we have. Great. The first property. Let's print the series name dot endim. Now, I never found out what is the relevance of it, because we know as a matter of fact with the series that it is going to be one-dimensional instrument always. So according to me, endim does not make a sense to me, but yeah, as a part of information you should know. Endim, just like an array, it talks me about the size or the dimension of the data. So I have one dimensional thing. It is one dimensional. Series is going to be one dimensional. Expected answer is 1. Next thing that we have is, let me copy the same thing. Just like series, just like the good. So next thing that we talk about is the shape. What does shape tells us? Shape talks about the number of elements in each dimension as a tuple. That's what the shape meaning is. Isn't it? If you remember it correctly from arrays. Thank you. Then you have the size. Size talks about the total number of elements present. Data points. Then you have D type, right? These are the 4 basic points. Item size does not exist over here because it is a heterogeneous structure. So every data point may be of different sizes, and hence item size is not available. Just like arrays, we do not have item size over here. In arrays, we have an item size property. Here, I do not have an item size. But instead of that, I have 2 more things. I have an index and I have a values. Good. So if you look at this, endim talks about, gives me the shape, gives me the number of dimensions. That is going to be 1. Good. Here, number of elements in each dimension. The shape will hold the same functionality each dimension as tuple. Good. I'm expecting here the output for this particular case. I'm expecting that to be a tuple 8 comma. Good. Then the size. Is total number of elements. Get D type. It gives you the data type of the series object, not of the individual element, but series object. Data type of the series. Right. So if I will have all integer values, I'll get integer. If there is a floating point number, everything gets converted to floating point, and it gives me the data type as float. If there is a string present, it gives me the data type as object. Good. Index gives the, or it gives the array of indices. So whatever the index that we have used, I'll get those indices here. What is values gives me? Gives the data as 1D array. Right. So I can extract the values, I can extract the index separately. Good. If you look at those. So I can see 1, I can see 8 comma, that's my shape. Size, integer 32 is the D type that I have got. Index, is this what we have got is, this is an index type object. Trousers, shirts, socks, and so on. Let's put up a list of indices. Good. And finally, you can see gives the data as 1D array. So my data 3, 4, 2, 3, 1, 2, 1, 2, 4. So whatever my input was, the array that we created the data from, I can extract that array as well. Are we good with these 6 functionalities, team? Quickly. Thank you. Now let's move on to some more basic functions, right? The first function that I'm talking about is head. Right? What does it show me? Returns top n data points. And the value of default is 5. What does that mean? So if I take up a series, right, any series, let's say we have the series water with index here. Let me copy this. Okay. And I put up dot head. I do not put anything inside those parentheses. It shows me first 5 data points. Look at this. Trousers, shirts, socks, shapes, and wallets. Right? It has shown me top 5 data points. Are we good? Or I can control that, and I can also view. Let me put that into print. Let's say I'll put up here, let's say 2. When I put 2, you can see that it only shows me 2 data points. You can see the difference. Let me put up a print in between to differentiate the results. Can we notice that? So I can choose out how many data points I want to look at, because it is not mandatory that you will have 4, 5, 6 one view data. You might have thousands of data inputs. So you might want to choose out, I want to look at top 5, I want to look at bottom 5, or I want to look at wherever I want to look at. Sensible? So if you have to get the top data, use head. Then what could be the bottom part? A tail, right? So tail gives me the returns the last n data points. And again, the default remains the 5. So head, then I can have a tail. The same example. When you look at tail, it shows me the last point. Last 5 here. You can see last 2 over there. Watch and tie. Because I have used 2 here. If you put up a number which is greater than the size, that it is going to show up the entire thing. Are we good? Hold on to that question, okay? I want to talk about 2 more functions, 2 or 3 more functions. Okay, let me explain that first. Because I have a lot of explanation to be done. Great. So Asif has a question, how did I got this shape as 8 comma? Is that correct? Great. Now, if you look at this was your series. Good. This is your series. I printed that up. Now, in this series, we created this series using this index and this array or this data, correct? So if you look at this, this is one dimensional. It is one dimensional info. Because it is one dimensional, I am going to represent that as a tuple. The shape is always in a tuple form, right? And since it is only one dimension, so I will have only one value over there. Since I have to make a tuple, so I need to put up a comma there. A single value tuple is made with a comma. Value followed by a comma. Now, how much value will come over there? That value is the total number of elements. In this particular case, that is the first dimension that I'll have, which you can check from the values. If you look at the values output here, this is the first values. So my values are represented using single pair of brackets. I'm pretty much sure you have attended my array session. And in that dimension, I have 1, 2, 3, 4, 5, 6, 7, and 8 elements. So my shape becomes, in the first dimension, I have 8 elements. There is no second dimension, so it's blank. Good. Had there been second dimension, I would have a second value here. Had there been third dimension, I would have a third value over there as well. If you cannot recall it correctly, revisit the video on the arrays part, NumPy arrays, indexing and slicing. I have explained the shape functionality in detail there. Yes or no, team? Thank you. Moving on. Next important function, same array. Let me bring it again. The next important function that I want to talk about is called as info. It gives me the gives the general summary. We'll talk about general summary, right? Let's have a look. Look at this beautiful summary. What you see here is number one, it talks about what is this? It's a series object, right? So type. Then it talks about the second thing, index. It tells me that there are 8 entries in my index. There are 8 values in my index. Those are starting from trouser to tie. It does not give me the detailed list, but tells me it starts from trousers, goes till tie. So first index is trouser, last index is tie. That's 2 things that is available. Good. Then it's a series name. We'll talk about that functionality later on. What is the series name? Then it says non-null count. Non-null count essentially means out of my index, how many index has a data. That means if there is any blank, that will be considered as null. Make sense? We'll take the null example too. Okay. So I have 8 entries. For all 8 entries, I have 8 non-null values. That means for all the 8 values, the data points or indices, there is a value present. The D type of that particular values is integer 32. Good. And then it says memory usage, how much memory it is acquiring up in my machine. Entire memory that is taken up by that particular information, that particular series. Is that okay? Explainable? Now, just to notice the difference between the non-null count part, right? We created up a series here, which has the missing values or none values here. That was by the name SR from dict with index, correct? So let's have a check for this too. Let's print dot info. Now you see that there are 7 entries. That means I have 7 indices, and for which it says 5 non-null. That means it tells me in this series there are 7 entries, 7 indices are there, out of which only 5 are filled up, 2 are not filled. Are we good? Next function that I want to bring into the table is called as describe. Now that gives me the statistical summary. Okay, it gives me the statistical summary. Now remember in in NumPy, I talked about multiple types of things, right? In statistical functions, you don't have to explicitly calculate them every time manually, right? You need to have something direct. So describe is your go-to solution for that. You just need to put up a series followed by the describe function, and what you get is number one, the count. How many values are there? How many values are present, right? Not exact the count of values, present values. What is their mean? What is their standard deviation? What is the minimum value? What is 25th percentile? What is 50th percentile or the median? 75th percentile and max. So you got all Q1, Q2, Q3, Q4, Q5, up to Q4, everything is available. And then you have the standard deviation and mean. If you have the standard deviation, indirectly you have the variance too, right? Agreeable, non-agreeable, eyes, nose, maybe. Very important thing, team. It has a lot of meaning while dealing with the data. When I'll try to work around with the actual data or the exploration part, when I'll do that, you will see that, or when I'll start with the mathematics, you will see that I'll use this a lot. Describe function. Good. Can I move? Thank you. Next function that I want to put up into the picture is unique. Good. What does unique gives me? Gives the array of unique data points. Unique data essentially means that if my data has repeated values, it will tell me what are the unique values that I have. So I can put up unique. So it says that in your data that I have, right? That is my data. Where it is, here it is. Wardrobe. Yeah. It has unique values either 3, either 4, either 2, then 3 repeated, 2 repeated, 1, then I have 1, and then 2 or 4 repeated. So I only have 3, 4, 2, 1 in that order. Good. Unique values. Are we good with the unique? Next one is n unique. N unique gives me the count of unique data. So how many unique data points are there? Earlier you had unique, that gives me which are the unique values. N unique talks about the count of unique values. How many unique values are there? Good. Sorry, I did not change the function. N unique. So I have 4 unique values. Is that okay till now? Thank you. 5 non-null pot. Explain, please. I guess my questions are getting slower towards Asif. So 5 non-null. Essentially, if you look at SR from dict, it has 1, 2, 3, 4, 5, 6, 7 indices. So that is 7 entries, right? Out of those 7 entries, 1, 2, 3, 4, 5 are not null. These are not null values, or null means nothing, right? There are 2 null values or nothing values. Good. Thank you. I thought that you might be able to recall that list sequence, but no problems. My mistake. So up to n unique, everybody okay? Let's talk about next function. And that is value counts. Now what does value counts gives us? It gives me the count of or the frequency. Let me just put up a frequency of the unique data. So I have 3, 4, 2, and 1. These are my unique data points, right? And then what I want is how many times each data point, each unique point has appeared up. Right? It can be 1, it can be 2, it can be 3, it can be 10 number of times. So how many times each unique data point has appeared up? That is what value count gives us. Are we good? Let's have a look. Now I said some series. You can see that the resultant that you see here is a series again, isn't it? It is a series again. Look at this. I have got 2, 3, 4, and 1. So I have a unique value 2 that has appeared 3 times. I have a unique value 3 that has appeared 2 times. I have a unique value 4 that has appeared 2 times. A unique value 1 appeared 1 time. Do you want to cross check? So 2 appeared 3 times. Thank you. That is what value counts gives us. Next function. I have lot many of those. I can keep on talking about them. Next function I want to put up is sample. Shows randomly selected, shows n random selected random data points. The default value is 1. So when I put up sample, so at times what happens is you might have a lot of data and you want to randomly look at certain data, right? Why do you want to look at a random data points? Any ideas? Why would, let's talk about some real world understanding. Why do we do it? Ever bought grains? Anybody ever bought grains like rice or maybe wheat or something like that? Or maybe pulses? Usually what happens is you take out a random sample from the entire lot and try to judge its quality from that random sample. And based upon that random sample, you take up a decision. Is that what happens? Real time? Right? So same logic here. Maybe if I have, let's say, millions of rows of data, millions of data points are there, I may not be able to walk through with every single data point. It's not possible. Even if I can walk through, I will not be able to recall everything, right? So what do I want to do here is, I want to take out some random data points, check how they look like, and I can try to make up some conclusions about the data from that particular data points. So sample is one of the go-to things that you will use. Right. Another example I'll put up with sample n values. Let's print and let's put up 3. So when I put up, see, earlier I had tie, now I see randomly selected wallet. So it would be every time I'll execute, I'll get a different sample because it's random. Get up to sample. Look at the another function, which is the is null function. So I'll bring the same example again. Not this one. Let's take up SR with index example, the other one, dictionary one. If that has the null values, that will help. Is null or is NA, both are same. Good. It returns true or false. Returns true or false for every data point, or it returns true for every missing data point. Else false. Yeah, that would be the idea. So if a particular series for a particular index has a data which is not present, is null is going to check out and tell, okay, true, it is not null. Is it's null? Yes, true. If it is present, it'll say false. Good. Look at this. So it says that index A value is present, so false. Index B value is present, so false. Index C value is not, index G is not present, so true. Index C is not present, so true. So I do not have data for those 2 data points. The rest of the data points are available, and I can see the true and false values. Good. Clear. Thank you. Now I can also use the function called as isNA. Is null and isNA are interchangeable. They are same functions. They have the same role. They have the same functionality, same methodology. God knows why they have created 2 functions. There are 2 separate entities which are available. They does the same job, exactly same job. Not even in terms of processing speed or anything. There is no difference. So I cannot pinpoint any difference between is null and is NA. They're the same. They're replica of each other. Good. But is that useful information for me? Any ideas? Now I can utilize this information to find missing values. Find the count of missing values. So if my data has a missing value, can I find it out? Missing values. How many missing values are there? Now you could say that we could have also derived it from the earlier information, but that was manual, right? Wherein I can look at the info, find out the index, how many elements are there in the index and subtract with the number of elements, not null count. But here I can do it directly. Now listen to that very carefully. With Python or numerically, false is 0 and true is 1. Correct? Agree to that? So if I think of this as 0, this as 1, 0, this as 1, this is 0, again this is 1, this is 0, this is 0. Good. Now if I take a summation of all this, if I add it up, sum up this data, will I get the sum of trues, or I have 1 and 2? So will I get 2 here? And that exactly is the number of missing values that I have. So if there would be any true present, then I'll get some number. If not, I'll get 0. Correct? So if there is a missing value, I will have a number. If there is no missing value, I'll have a 0. And that's what I can do. So I can extend the same function, right? I can extend it after doing the is null. So to this, now if you look at this, this is also a series, correct? That contains Boolean type values. Right? This is also series. To this series, I want to take the summation. So dot sum. So connecting with that method chaining. And I got 2. A straightforward number. So I was able to find out the missing values. Good. Thank you. Next question arises, how to treat the missing values. That means fill missing values with appropriate data. Now, I have used the word appropriate here, but I have not defined what is appropriate. Right? I have not defined you what is an appropriate thing, because appropriate thing will vary very drastically depending upon the nature of the data. Good. It is going to vary in a huge manner. Now, I am going to make those changes right now on this SR from dict, because my job with the null part is done, right? So how will I do that? What do I want to do is, the name of the function is use fill NA function. Fill NA means fill the NaN values or fill not available values. Good. Fill NA. So how will I do it? See, this is my objective. I have a dictionary. I have a series by the name SR from dict with index. I want to modify it, so I'm going to assign it new values. Good. How? SR from dict with index. Good. Dot fill NA is the name of the function. So what do I want to tell it? In SR dot index, find out the missing null values which are null and fill them up. So this fill NA is going to find out wherever there is a missing value and is going to fill that up, all the missing values with one single data. So let's suppose in my case, I'm putting up here, let's say I'm missing data. So I'm putting up a text over there, missing data. Good. Deliberately putting up a text. Cool, good enough. If that is okay, then this SR from dict index, that should have changed. Let's have a look, friends. Can you now see that instead of NaN, now I'm getting the word which I've mentioned over there. I could have mentioned a number. I could have mentioned a floating point number. I could have mentioned a non-floating point number. I could have mentioned any appropriate value. How do we judge an appropriate value? That's a separate entity altogether. I'll talk about that when we have a real world data. Real world data means as in like we'll look into a tabular data and we'll talk about data frames. Then I'll talk about that too. Good. How does we find out what is an appropriate thing? It's not something that you could put up in random. Here I have put up a random data for now. For example, it is used to apply a function to each element, right? Say, for example, we have this, let's say, for example, right? Let's go back up. We have this wardrobe with index, right? Let's suppose I want to see out squared values, right? So I can put up this series dot apply, and onto that, which function? So I can put up a lambda function over there, lambda, let's say lambda x, taking up the square term, so x double star 2. I've given the function. Good, that's it, done. Now you can see that I can see my series got the values applied with the function. So apply will take out every value from this series, give it to the function. The result of the function will be saved back, will be returned back. Are we good? So I got 4, original data was 4, sorry, 3 here. So 3 came to lambda, lambda processed, calculated the square, gave it back 9. Next one would have been 4, so that would have been 16. Then 2 have been became 4, and so on. Are we good? Apply part. Very beautiful function, very useful function. And many of these functions will be repeated at the time when I'll talk about data frame. Why I'm putting those efforts here? Because with the data frame as well, when you're going to apply these functions, right, you're going to apply that on a series itself, right, at a later stage. Good. Eyes, nose, maybe, yes, please confirm very quickly. That'll help. Thank you. There would be a few more functions which I would like to talk at a later stage. Now, someone wanted to talk about the index change, right? The names, right? A particular series, a particular index, right? Though we have another function called as a rename function, but since it is index, so I'll not use the rename functionality, right? Rather, I will use index. I would have to alter all the index together. I cannot alter a single index. Can't be applied condition inside apply. No, I cannot comprehend that, Narendra. You might be trying to say something. Do you want to get unmuted? If your background is clear, I am okay with that.
Yeah, so my question is like you have mentioned that we can use the apply function to process all the index. So I mean, if we want to process or made some changes for a specific index, then we can do with the help of some condition, like we can do
See,
in other programming languages.
yes, you can see conditional access of the data. I have not yet talked about how will you access a conditional data. You can apply it on any sequence. This can be apply function is specifically a series or a data frame function. So if there is a data frame, if there is a series, you can always use apply. That is the only requisite that it has, right?
Okay.
Apart from that, it contains one value, it contains 10 values, whatever it may have. You have that leverage.
Okay.
So for example, let's say I want to put it up for a particular, let's say in my wardrobe with SR with index. I do not want to do it for all the data points. I only want to do it where the data value is 3. If the data value is 3, I want to perform that action. Is that what you're trying to say?
Yeah, exactly.
We can do that. It is possible. We'll take it that example too. Don't worry. But I have not yet talked about accessing the data point based on condition. I have not yet talked about that because we need to first access the data using the condition and then move on to the application part or modification part. Make sense?
Yeah, makes sense. Thanks.
Thank you.
Yeah.
Okay. So let's move on. That is called as a conditional access. That's the next thing that I want to talk about. accessing elements using a condition. Now, condition based. Till now, you have been accessing the elements using the index, right? Whatever, either you were using lock or ilock to get the data. Now, can I use that with some conditioning? So let's take an example. First of all, I want to apply a condition. I want to put up a condition. So first of all, how will I do it? Very simple thing. Take up your series and put the condition. For example, in my series, I want to find out all values which are greater than, let's say, greater than 3. Good. Just an example. Very simple thing. This is a series and I want to check out the values which are greater than 3. What is going to happen? It is going to check out for every single value, trousers, shirts, socks, every single value. So it is going to check out for every single value, just like is null. Is that condition holds true here? No. It holds true here? Yes. Not here. So these are the two values for shirts and for tie. This value holds true, where it is greater than 3. For rest, it does not. Make sense? Now, suppose now this is showing me a true false thing, but I do not want that. I want to extract that data where this condition is satisfied, right? I want to extract that data where this condition is satisfied. So what I'll need to do is I need to select that data. So I can use this condition, the same condition that I have written down. I can use that as index. I will put that condition as index and I will use the same series. So what I'm trying to tell it, look at this very beautifully. Look at this part. I have used the condition in the index, good, and that is the square brackets. So what I'm trying to tell it now, apply this condition to the series, and for whatever index, wherever you are getting the true value, select those indices and show it here. Show it from here. So what I want those, so you see it has got a shirt and it has got a tie. So shirt and tie, that will be resultant of this, and those shirt and tie values will be displayed now. Let's have a look. Team, please confirm if once it goes beyond head. What did I miss? Oh, P is there. Can you see that? Shirts and tie extracted. Once we extract that, now if you want to apply something, like let's say Narendra had that question about application. So I can take that extracted information, dot apply, and let's say I want to put up any lambda function, lambda x colon, let's say I want to put up anything, let's say x cube, let's say put up cube for that matter. Good. So it applies that function only on that data. Good. I have not yet talked about how to merge certain lists, merge the series, join them, concatenate them. I want to talk about those, but not now. I want to talk about those with the data frames. Everybody okay with this? I guess Narendra, that answers your question too. Conditional access or changing or using the apply method using condition. Any questions, team? And if you find it difficult, let me know. So using lambda here is a must. No, not exactly, not lambda is a must. You can use any function. If you have a predefined function, Abhinitri, then you can use that function too. But the point is that usually these would be kind of actions that's not fixed or permanent for us, right? We want to perform certain modifications in the data for one-time change. So usually, most commonly you will use a lambda function. Let me give you a real world example. It's a common example that I quote up to everyone, but let me give you another example. There is a very famous data set, practice data set. We will talk about that data set at a later stage, which is called as Titanic. Heard about it? Anyone? A Titanic data set. It's a row table data, right? For this is very good data for practice purpose to know about things. I will take the data into picture, which contains 891 rows, and I guess approximately 13 odd columns are there. I don't exactly remember the column numbers. 13 or 11, something like that is there. But I'm not bothered. One of the column in that consists the name of the passengers. Consists the name of the passengers. Good. Now look at this part. That one particular column is a series for me. One particular column is a series that contains name, and names are given in this order. Let's say like the first name I remember is Brown, followed by a comma, then Mr., followed by a dot, then I have Owen, and then I have a Harris. That's how the name is. First name I remember. That's essentially in the format. Suppose this is a string, right? Name is a string. So that individual value is a string, and it is of the format last name, followed by a comma, title, followed by a dot, then the first name, and middle name if there exists. Middle name if is present, I have a middle name too. That's how the data is given. Now the beautiful part is that the entire name may not be of any relevance. Let me just take up some thinking capacity. Everybody in the house is going to give me an answer. Okay. It's coming for the purpose of data understanding. It's my purpose behind asking this question is not to judge you, but to bring onto the table the perspective or the thinking capabilities that we should have as a data scientist or an AI engineer. Good. Great. My expectations for this questions is that you know what Titanic is in real world, you know, or you have seen the Titanic movie, at least either of those things. Good. Anybody who does not know what Titanic is? Okay, great. So my question is, suppose there is a list of some names. There is names given. Okay, that contains many names, right? Exactly 891 names. Good. Now, that also gives me another information on the side, that is the survive status. Let's say I have some survival status, name 1010, where 0 represents that this person was lost in the accident. 1 means the person has survived. Good. Now, think about yourself. Think from your own perspective. Completely your choice. You need not follow my choice. You can have your own option. The name, think about it. Will the name of a person, very clear question, will the name of a person has any impact on the survival or any role to play in the survival? Suppose you're supposed to predict a person is going to survive or not, right? Suppose the 892th person is Narendra. So let's say this is just a random example, good? So let's say that this person name 892nd person, right? His name is given as Shishodhya. So I'm just putting that in, then followed by a comma. Then let's say put up Sir dot, let's say Narendra and some middle name. Good. That's how the name is formatted. Do you think that it is going to make an impact? Will there be any impact of this name? Think very closely. That brings in a lot of concepts, like feature engineering is also a concept that comes out from here. There is a relevance concept. A lot of concepts comes out from this particular problem. But I'll only talk about one thing as of now, the apply method. If not the entire name, can you just think of title for a moment? Considering the Titanic has started as a ship from the then United Kingdom, where people who were living into that country were given certain titles like Mr., Miss, Mademoiselle, Miss, so on. Some people have a title like Sir, or maybe Lord, or something of great, a major, doctor. These could have been titles, right? Now the question is, will the title will have an impact? Rosie says yes, I agree to that point. Title would have may have an impact. I'm not saying it will have, but it may have an impact, right? Certain people with certain titles would have gone, the privileges, maybe. So now may not be the entire column given for me, or entire series that is given for the name is not relevant, but only the title given in that in between is relevant. So I need to extract that title. I need to extract it out, right? From the entire string, can I extract the title? Let me just see if you can help me with this. I'm putting down the one name for your example. Let me see. This is a string. The first name is Brown. Just hold on a minute. So fraud people are calling me. This is a string. Let's just check out your Python skills. What I want you to do is, can you help me to extract this name? I just want to take out Mr. from it. Help me with this. Name one. Let's name that as a variable. Though I don't want to do it. Name of square bracket one. So as per, if I go by the definition of Rosie, so name square bracket one. No, I get R, Rosie. What I need is, and R is this R, not Mr's R. Help me. Someone had asked me that question, not here, but some other batch. Need to split an index. Do it. Or should I do it? I'll do it directly. Dot split. That's going to split on the basis of comma. I'll split on comma. I get two parts. Brown on this side, Mr. Owen Harris on that side. So I'll select that first index. I got Mr. Owen Harris as a string. Again, that string needs to be splitted up. Split. Now I want to split that on dot. So I got two parts. I have a Mr. on this side and Owen Harris on this side. I am not interested in Owen Harris. Mr. at 0th index. I got the MR, but it contains white spaces, so I can put up dot strip. Good. Now this was only for a single string. What if that single, I do not want to do it for single string. I want to do it for the entire series, because that will not have one name, that will have too many names. So I can create this entire thing as a lambda function, lambda x colon str of x, just to make sure it is a string. Good. Dot split. Good. Now this function is capable. I can use an apply function, apply this function, and I can pass on my whatever the series name is, I can put up that onto the before it. Now think about, there was one question coming from someone that essentially we need to use functions or lambdas. Abhinetri had that question, right? So lambda is must. No, it is not must. That was the point where we started this topic, right? So the idea was that I would only require to do that once. Should I need to create up a separate function that will always prevail in my memory? I want to use functions which are use and throw. I did it once, done. I don't want to reuse them. Sensible? Thank you. Where I was. Okay. Apply, done. There is another thing that you can use is a sorting function. So let me just show it up with the sort part. So let's bring up our series once again. That is wardrobe with index. Git. If you look at that, can you find it that my data is my data arranged in a sorted manner? So I have two choices. Listen to that very carefully. Choice number one, whether I want to sort as per this, either in ascending or descending order, right? Or I want to sort on the index, again ascending or descending. Good. Again, please remember, ascending and descending in terms of text means the alphabetical order, right? From A to Z is ascending and from Z to A is descending. So please remember that. Good. So let's try to do this. So we have two types of sorting. Sort a series. Good. One is a series sort with respect to the values. So let me just show you. So if I do this wardrobe with index dot sort underscore values. So name of the function is sort values. Using values. Good. Let's name that as, okay. So name of the function is sort underscore values. That's the name of the function. So sort underscore values will allow me to sort the series in, by default it is ascending. So look at this. I got that into the ascending order, the values 1, 2, 2, 2, then 3, 3, then 4, 4. And corresponding indices have changed, right? Indices have moved, right? So it's not that I have got 1, 2, 3, 4, index will remain consistent. No, it's moved along with the index. Good. What if I want to get that into descending order? So what you need to put up here is, in the same sort values function, put up ascending is equal to false. take up a parameter, ascending, ascending, put that as false. So I'm telling it is not ascending. I want to go into the reverse possible manner. I got descending. Good. So if I'm sorting it up and I want to sort it up in ascending order, I do not have to put that. By default, it is true. So I can avoid that. Or if you want to put that into descending order, put up ascending is equal to false. Are we good? Yes, no, maybe. Thank you. Let's have a same look at the series. Sort a series using index. So I now want to check up the sort values in an index form. Name of the function changes to sort underscore index. That's it. You got them sorted up. The index are now sorted up. You can see that B is on the top, W is at the end. Correspondingly, the values have changed. Shuffled. Good. Same thing goes for the using index, descending order. Sort underscore index is the function. Good. When I put ascending is equal to false, I get the data in descending order of indices. Is that good till now? Thank you very much. Okay, I think so. That's more than sufficient for series. Let me just think of. Asif, keep that pending. Keep that pending. I'll come back to the example again, right? Because when I'll start with the Titanic data set, I will bring into that picture again. And to be very precise, it's happening because the basics of Python is not done. Ease of doing things with regex is quite complicated as compared to doing with pandas. Basic logic. Suppose I have two series. Let's say SR1 is not SR1. Let's put up series 1 is equal to np dot series of 1, 2, 3, 4, 5. Good. And I have another series 2, that contains 1, 2, 3. Let's say put up 7, 6, 1. Good. 3 elements only. That's series 2. Now, you guys have seen element-wise additions before too, right? So let me just have a quick look. NumPy has no, oh, not np, but pd dot series. My bad. Good. We got two series. Now, can you tell me what could be the expected output if I put up series 1 plus series 2? Essentially, if you look at it, this is one series that you have. Good. It has index 0, 1, 2, 3, and 4. Good. That has a value 1, 2, 3, 4, and 5. Good. You have another series here, right? That has an index 0, 1, and 2, containing value 7, 6, 1. That's the position right now. What is going to happen? Let's give that a look. I have not got any error. It worked. So I'll tell you what is the logic that I want to tell you. Whenever two series are being added, they are not concatenated like arrays. They're not being concatenated like lists. They'll not concatenate like lists. What is going to happen? It will check for the matching indices. I have a 0 here index. I have a 0 index over there. So matching indices will be added up. 1 will be matched up with index number 1. 2 matched up with index 2. For index 3 and 4, there is no match. So since there is no match happening, put up as NaN. It will put up a NaN value over there or a missing term. Are we good? So if there is no matching index, for example, if there is no matching index, what's going to happen? Suppose here, I'll just put up index is equal to, let's say, ABC. Now if I do it, it will take up index 0, 1, 2, 3, 4, 5. No problems. None of the matching terms, zeros. It will fill up with NaN. Again, ABC index will also be considered. So I have indices 0, 1, 2, 3, 4, and as well as ABC. All indices from both the series are included. However, there is no matching indices, so none of all the values are filled up with NaN. If I put up, let's say this index is 2. So AC comes in, 2 value matches up, index 2 matches up, so index 2 has a 6 and index 2 has a 3. 6 plus 3, 9. Good. Last function. Map. What is the role of it? Is data type always float? For NaN, yes. NaN is always float till now. If there are any modifications in the fundamental definition that happens, then I cannot assure you, but because there have been certain updates wherein people have recommended or asked for a PEP, right? Everybody knows what is PEP. PEP is Python enhancement program. It is Python enhancement program. So it's a kind of document that is created whenever there is any kind of update into Python or any Python libraries. So it is all whenever there is a version of Python that is released or any libraries, the PEP is always released with that. So it's a document. So there have been certain thinks about changing the float, the NAND to float, because it's explicitly taking up too much space. But that did not materialize yet. So I was talking about map function. Now, map is used. It is used to alter, right, values using key value pair, using dictionary. Now, essentially, the idea is, listen to that very carefully. We'll take this series 1 into consideration. Good. Let me just print series 1 again. It's important. Good. Now, here you see that I have three values 1, 2, 3, 4, 5. Let me recreate it. I want to change it slightly. So I wanted to keep it as 1, 2, 3, 1, 3. Good. That's how I want it. Now, my objective here is that if in my series a value is 1, I want to change the word from numeric 1, I want to change it to ONE. If it is 2, I want to change it to TWO. And I'm not telling anything for 3. Good. So how can I do that? I can put up my series name dot map, and within the map function, I can write down a dictionary and tell it, if you find 1, please change that to ONE, comma. So my key is 1, value is this. Second key, if it is 2, change it to TWO. So I need to mention the value, the key here as the values of my series, and the value of my dictionary should be the value that I want to change to. Good. Look at the outcome. So wherever I had 1, I can now see ONE. Wherever I had 2, I can now see TWO. But for 3, I did not give any definition. So it is replaced that 3 with NaN. Any advantage of this? Suppose there is a millions of data. Let's say there is a 1 trillion row or data points, right? Out of that 1 trillion data points, there is only, let's say, 30 data points of type, let's say, type A, and 20 data points of type B. Good. Now you do not want to look at remaining things. You are only concentrated onto these 30. So you want to just cut short your data. What you can do is you can use a map function, put up a particular words for them, and convert rest to NaN. Rest NaN means they got missing. Good. And by that you will be able to access the data only with A and B, because when after that, when you run the is null part, it is going to be true only for the values which are present, which you can use as index and check it out. You will get only the data which is containing the values that you're looking forward to. So you can always alter that information and get the information of your relevance, your choice. So map is very beautiful function that you might want to use. You would have used a map function in Python as well. So that map and this map is different. Okay. Python map function is used to map a function to a sequence. This is a map function. This is a map function of series that is used to map values as dictionary. Good. Hopefully. All right. On that note, I'd like to switch to DataFrames. Second data structure. Now, why did I put up too much time onto the series, though it was not supposed to be that long? Okay, so we are talking about data frame. So what is a data frame? Simple definition of Pandas data frame is a two-dimensional. I will not get too much into theory part. Pandas data frame is two-dimensional tabular data structure that contains rows and columns. So no need to mention that, right? Tabular data structure, that means it has a, it is one of the base, or it is the primary data structure that is used to handle and manipulate data. To handle and manipulate the data. Now, to be very precise, if we talk about real world data, essentially you might get or see the data that is being stored into different database servers or different data storage devices in multiple forms. It can be in 2-dimension, it can be in 3-dimension, 4-dimension, or a huge number of dimensions, because they have their own space constraints. They want to efficiently manage the data. That is a separate thing. But essentially, when you have to work on a data, right, you have to do some data handling process. It's quite complicated to do it in more than 2 dimensions. It's quite complicated to apply things, analyze things when it is more than 2 dimensions. Really difficult. So when we need to handle the data, we prefer using it in 2-dimensional measure. At least as a human being, it is easier for us to understand the data which is in 2 dimension rather than 3 or 4 or multi-dimensional data. Good. So that is the idea behind it. That is why we try to extract, or what does the Pandas data frame offers is to work on the data in a tabular form. That means I get a data in the 2D form, 2-dimensional structure. And that is what we can make it up from here. Again, it supports a lot of things. I'll not talk about those. A data frame can be created using the data frame, can be created as an object of Pandas class, and name of the class is data frame, right? Or by reading external data sources. Data sources like CSV files, like CSV or Excel, HTMLs. You can read out XML. You can read out maybe a Parky file. You can read out SQL queries, etc. There are plethora of types that are supported. I will not talk about all of them. Essentially, in this particular course, we are only going to work around with the CSV files. That's the major file that we're going to work around, right? So I will concentrate only on the CSV part. Good, thank you. So let's now quickly run through with this, and we will create up those things from here. Good. So let us create data frame using list. Now, essentially, we do not actually use list anywhere. We always use a dictionary. But I can create up a list too, but that will look really complicated to you guys, right? So I'll create it from the list first, right? Suppose I have 3 employees as an example. Good. So let's put up a data. This is my data list. That is a list. Good. This list contains information about 3 employees. first employee name. So again, a list in the set that her name is Alice, comma. Let's say her age is 25, comma. Let's say her salary is 50,000 USD. That's the first employee. Let's take up second employee. Another list. Let's his name is Bob. Bob is 30 years old and earns $60,000. Minded it's annual. Third employee. Let's take up Charlie. Charlie is 22 and earns 45K. Good. So that's a simple data list. Now, think about how would I like to represent this data. What I would love to do here is, listen to that very carefully, that I have a table like this, wherein I have a column header called as name, let's say age and salary like this, column headers. Then I have row number, some row number 0, row number 1, row number 2. And I have Alice, then Bob, and then Charlie, 25, 30, and 22. And let's say 50K, 60K, and 45K. Like that, figures like this. And will that look good? So if you look at this, these are the column headers. These are the column headers. If I consider each of them as columns, these are your column headers. And if you just try to concentrate on the thing that I'm putting up in blue, does that by any chance to you looks like a series? Yes or no? Right? So essentially, if you look at this, if I consider this as index and this as data, so this is one series. You can say this along with this is another series. This along with this is another series, correct? Or I can say that every single column in itself is a series. Yes or no? And every column has, I would like to put them a name. So here, just like series, we have the labels, but I have two types of labels now. One is the column label and other one is the index label. Are we good? Great, thank you. So let's just try to create up some labels for the columns. Index, we know we have default. I just want to put up some label names. I can go with the default column labels as well. That is 0, 1, 2. But let me just put up some names for this. So let's put up columns is equal to, let's say the first column name I want is name. The second column I want is age. So I print another list. Third column I want is salary. Good. Let's create up another thing which is IND. Or let's put up as IDX. That is for index. Let's say EMP1. Just wanted to mention EMP1, comma, EMP2, comma, EMP3. Good. We have 3 employees. So I'll take up just that. Now I can create up a data frame out of it. Let's say df1 is equal to pandas dot data frame function or data frame class. So it's constructor being called up. Great. And I'll pass on my data list. Original data, comma. Now, just like series, I have the 2 parameters over there. In series, I had 1 parameter for index. Here I have 2 parameters. One is for index, other one is for column headers. So I can put up columns is equal to columns. Let's name that as, change that name to CLMN. Yes. Why did I change that? So that you guys do not get confused. What is an attribute of the class and what is the variable? So CL11 is the variable and I can use index is equal to IDX. Good. Let's have a look. Done. Now I'm going to show you df1, right, in two forms, right? Let's look at the first try. I'm using the print function and I'm putting print df1. Can you see it? Right? You can see that it looks like a table. I have the column headers name, age, salary, the index emp1, emp2, emp3, and I have the data in between. Correct? Now, the purpose of data frame, right? Okay, let me ask you, what is the purpose of print? To get the output, to display a value. Okay, let me just ask it. A very simple basic question. I usually ask that in interviews. If I write down, let's say, a string, good, and I execute, I have not used print. I am able to display that data. Or if I write down print, and then I write down the same thing, putting that within the print function, I still see the same information. Is there any difference? If yes, what? In both the scenarios, display the value is happening. "93 and 94 are two lines you can mention. There is a huge difference, Abhinitri. It gives data and string. Both are strings, Asif. So output wise, there is no change. Okay. How many of you know about the print function? Comma is main difference. No, that does not make sense. Let me tell you. If you go out and try to look at the syntax of print function, it has few parameters. Look at this. The parameter I want to talk about is file, which is set to none. But if you look at the details, it says file. A file like object or stream defaults to the current STD system standard output. So essentially what is happening, when I use the print function, this thing is going to get saved to my standard output device. That's the default value. And I have the leverage, I can change it. I can pass it on to a printer. I can pass it on to my memory device, wherever. If I want to save that, I can pass it on to my memory as well. Do you want me to show that? Okay. On the left of my screen, I'll just show it very quickly. I'll do that. Do you see this is my latest files that I've created. Last file is your file, which I'm working on Pandas about 1 minute ago, that has been saved. Let me, if you just to showcase, I'm resaving that file. That should change in a short while. Let me refresh. So you can see that 6 seconds ago. So it was saved 6 seconds. So do I have any recent file, any notepad file in here? No. Great. I will just put a few messages above it. Let's say open. Let's name that as you, or let's say the question. Let's say I name that as today's date. Okay, so let's name that as date underscore 07 02/2026 dot txt. So I have opened up a text file, comma, in write mode. So I'm going to write down on this file. That is going to be W plus. Good. Great. And then I'll put a print Jitendra, or let's put up anything else. You might say that you might have pre-formulated that. So any string of your choice. So any string of choice good, deliberately not making it wrong, right? Any string of your choice, good. And comma, now I am redirecting my output. File is equal to, let me open that with a variable name, f is equal to this, good. So file is equal to f. And just wanted, once this print function is done, I want to close that file so that it gets saved. So f dot close. Keep an eye. I execute it. There is no output. The print function is not showing anything on the screen. Why? Because that thing has now been redirected to a file that should be here. Can you see this? I got the file date 07026, and if I double click and open it just to verify, any string of choice, that's what I written down. Now don't lose the context. Why did I come up to this point, right? Don't lose the context. So context was, I'll just remove that file. I don't need it. I have too many files there, highly cluttered. Hold on. All right, so let's come back to the point. Just give me one. Okay, sorry for that interruption, team. My kid just arrived. She wanted my phone. She's just back from the school, so no problems. Thank you. So that was the objective. Now, getting back to the context, what I wanted to convey here is that if I use a print, right, that gives me a different answer. Let me just put that into a comment so that maybe you guys might want to use it later on. So if I use a print, that redirects my output to the output console, whichever output console that I'm putting up. But if I do not use print, the value that I see is actually the last known input. It's just showing me the last information that it remembers. So only the things that is there, right? So if I put up another string below it, let's say ABC, it is not going to show me Jitendra because that's not the last thing. Last thing in the memory event was ABC. So it is only showing me ABC there. Sensible? Thank you. So that is the difference. Now, when I do a print, now this is a very small data frame that we have, right? It's a very small data frame. So it's kind of okay, you can do it up here, no problems. But imagine terabytes of data. For example, consider a file, a data set that is of 1,000 rows, only 1,000 rows containing 3 columns. Let's say I have an employee, 1,000 employee data. Now, if I think of, let's say I'll redirect to a printer, I would redirect that to a printer. What is that going to do? It is going to print out the table, correct? And if that happens, that's a complete wastage of paper. I would say that. Why? Because the purpose of creating the data frame is not to take a paper output, right? It's not to take the paper output or any kind of output. That is not my purpose. My purpose is to analyze that data, to view that data in efficient manner. So essentially, whenever there is a data frame, if you try to view the data frame using print, you would see this kind of structure, right? But if I do not use print, I get this. Now tell me which one is better, the one with print or one without print, right? The second one with print is better for Asif. So if you feel that comfortable, use that, no problems. But essentially, this, according to me and most of the people that I have trained so far, the number would be more than 10,000, maybe 20, approaching 20, maybe. This structure looks much better because it's more tabular, more formatted kind of scenarios that I can see. Great. That looks better. So I will use this formatting. So whenever now onwards, till now you would have noticed, if I have to do any printing or showcase any data, I have always used print, and I will continue doing that. Only with the data frame, I will not do it. Good. And my own reason is that I just wanted to have a look. I do not want to print that out. Great. Thank you very much. So that's how a data frame is created using a list. Or you can create that using a dictionary too. Same information I'm going to take up as dictionary. So you can simply understand that I can convert that to an array form. Let's say using array, I can make that as np.array of this data. Same information, no changes. The rest of the things will remain same. Invalid syntax. Oh, I have this. Good. Let's say make it as df2, and I'll display df2 here as well. So just add that line too. So you can see the same information. Good. That's an array. So list and array wise, there is no difference. Let's go to the dictionary form. There is subtle change. Play data frame using dictionary. Now, and when I'm going to define dictionary, the dictionary formation changes, right? The data dictionary. That will not be like this. It will be like a dictionary. So I'll have a curly brackets at the beginning. I have a curly bracket at the end. Good. And this is not going to look like this. It is going to look something different. Why? Because I would have a key value pairs. The first key that I have is name, right? For name, I have a list of 3 values, right? I have Alice, I have got Bob, and I have got Charlie, right? So first key name that has 3 values, Alice, Bob, and Charlie. Second key, let's put up age, that has 3 values, again colon, 3 values. I'm putting that as a list. So Alice was 25, Bob was 30, and he was 22, comma. Third thing I want to put up is salary. Colon. and let's say I had that 45,000 or whatever the number was, 50,000. So there is just random selection team. You can put up any value, 45,000. Good. Now I do not need these column names. Why? Because these column names are already captured in my dictionary indices or dictionary keys. So essentially, when you were creating a series, the keys of the dictionary were your index. Good. That were your indices. But when you create a data frame, the keys of the dictionary will become column labels. The keys of the dictionary will become the column labels. So I do not have to put up the columns. And I'm going to avoid index 2. I'll explain you why. Good, I got the definition. Now, I'll tell you why did I not use index here. I have used EMP1, EMP2, EMP3 earlier, but now I did not. There is a reason behind it. The reason is this is again a small chunk of data, right? In small data, it is possible for me to put up those names. Let's imagine I'm telling you, just not take up a very small, medium, not even a, take another small data that contains data of 100 employees. Would you like to write down EMP1, EMP2, EMP3, EMP4, EMP100 as a list and then put that as a index? Would you prefer that way? You would not. So when we create a data frame, right, using methods like dictionaries, arrays, or anything else, right, we generally do not put up the keys or put up the indices. Generally do not. If at all there is a requirement to put up the index at all, right, usually what happens is, what we do here is that, because at real time scenarios, what you will get is a data, right? You will have, let's say, a CSV file, right, that contains comma separated values like this, or you have an Excel file, right, that contains row 1, row 2, row 3, row 4, like this data. Good. Let's say this kind of it. You will take this data and one particular column, any particular column, you might want to put up as an index. Correct? I'm still not saying that you will take that as an index, but you might want to. Suppose I have a column already present in my data. I have a particular series which is already present in my data, given data, which is talking about, let's say, employee number. I am not going to create that manually again. Rather, I would like to use that known number as an index if I want to. Sensible? So we have facility, while reading data from an external source, I can choose out which column of my data is going to be the index if I want to make something as index. If not, then I have the choice to remain stick to the default index. Usually we remain stick to the default index unless there is a requirement. Get? Let's keep up for the last topic for the day. Right. So in order to read the data from an external file, right? So Python offers, let me just put up, Python has, not Python, but Pandas has a standard syntax to read any type of, to read rather many types of external files. I'll tell you the list, external files. And that generic syntax is, now understand it, it's generic one. So pandas dot the word read followed by an underscore. Then there is a file type based word followed by pair of round brackets, path to the file. So that is how you can read it up. That's the generic idea. Now, there is a very common question that people ask me. What is that path-based file, so and so forth? So I'll talk about that. Just give me 1 second. Let me complete this piece of code. Something is wrong. Oh, I have an underscore over there. Hmm. No, it's not taking up. No problems. I'll put that as a raw text. Good, that's the way. Great. So now when it comes to what kind of files it could read up, let's have a look. I'm going to show up, first of all, let's say I want to create first data frame, any data frame from an external file. So I am not telling you what type of file I'm reading, just showing you what types of files are available. So pandas.read underscore, and I press the tab key on the keyboard. I press the tab key and you can see that it can read from a clipboard. Let me just redo this. Tab space, okay. I can read it from a clipboard, CSV, Excel, a feather file, an FWF file, GBQ file, STF file, HTML, JSON, then ORC, Parkey, Pickle, SAS, SPSS, SQL, SQL query, SQL table, Stata table, and XML. These are the all possible files that can be read out in Pandas. Are we good? But what we want to read out is a CSV file. So I'm going to use CSV file, and I would have to put a path to the file. Good, here. So let's start up with first file. I'm going to send across a file to you guys into the chat. Okay, I had a one personalized message, so I was responding to that. So here, I was just, okay, I want to put up a file to you guys. So which one would you like to start with? I have 3 major files that I would like to work with you guys as a part of code. One is Titanic. There is a house pricing file, rather 2 different house pricing file, and then there are some more that is relevant to tips, and then there is a lot more files. But let's bring into the content from Titanic perspective. This file may not be available in your standard documentation, so please make sure you have it from here. I am sending a file by the name titanic.csv. Is that into the chat? So click on that folder icon onto the left side. You will have that on Colab environment somewhere bottom, right at the bottom you might have it. Click on that. You will find there is an up arrow, correct? You need to click on that up arrow. It opens up the file browser. From that file browser, find out where did you download that file. So I've got this file over there, Titanic, good, in my downloads. You might have it somewhere. Click on that file, click on open. Now, if your current working pandas file, or the Python file that you have, and your data file that I have just asked you to upload, they are into the same folder, you will they are already present in the same folder, you will see that overwrite message come up, because I'm working in the same folder. I'm working in the downloads folder itself. So I will overwrite it. Not a problem. Otherwise, what you will see here into the list here, you will notice that Titanic.csv has appeared up. Correct? If you're not able to find it, just arrange your data on the modified date. So you will be able to see that. It will come up on the top. Or we'll go reach out of order. Confirm, done. Great. Now, close that folder box so that you have some space. Click on that again. Okay. Now, in this place, I am going to mention full file name since I am reading CSV, so Titanic.csv file. Good. And I'm going to save this as a data frame by the name Titanic. Now, this should work perfectly if your current working file, my current working file is Pandas ADSP B1 jan.ipynb, and my Titanic file, they are in the same folder, same place. You can take a look by clicking on this icon. I can just show you that both of them are in my same drive. This is the Pandas ADSP B1 file, which I'm working on, and this is Titanic. They both are in the same place. So I can directly read that file. Good. Execute it.
Our primary objective today is to empower you with the essential SQL skills required to effectively navigate, analyze, and transform vast datasets. Whether you're aiming to extract specific pieces of information, identify hidden trends, or even make data-driven decisions, the techniques we'll cover will provide you with a robust foundation. This session, you will gain not only just theoretical knowledge but also hands-on experience that you can immediately apply to the real-world data challenges. As we discussed in the introduction, data is being generated at an unpredictable rate across virtual every aspect of our lives and business. However, the sheer volume of this raw data can be incredibly overwhelming. Imagine trying to manually sift through millions of records to find a specific pattern or answer a complex question. It's simply not feasible. This is where the power of structured data management comes into play. The solution involves two key components. First, databases, which are specialized systems designed to store and organize this data in a structured, accessible manner. And second, SQL, the structured query language which acts as a primary tool to communicate with these databases, allowing us to ask precious questions, retrieve relevant information, and transfer raw data into actionable insights that drive informed decisions. To guide our learning journey today, we are structured this masterclass into 7 distinct modules, each building upon the last to ensure a comprehensive understanding. We will bring with the absolute SQL fundamentals covering basic commands and database concepts. Then we'll move on to data aggregation and grouping, learning how to summarize large data sets efficiently. Next, we'll explore joining tables, which is a crucial skill for combining related information from different parts of your database. As queries become more complex, subqueries and common table expression, which is the CTEs, will help us manage that complexity. We will then dive into window functions, which are often advanced analytical capabilities beyond simple aggregation. Following that, we have data manipulation and transformation, which will teach you how to modify and reshape your data. Finally, we'll touch upon advanced SQL techniques that are particularly valuable for data scientists and analysts. This structured approach will ensure a smooth and effective learning experience. Let's jump right into preparing our environment for hands-on practice. Welcome to our first module where we will lay the groundwork of your SQL journey. We'll start by understanding the fundamental building blocks of how data is stored, which is relational databases, and then introduce the very basics of SQL itself. Think of this as learning the alphabet and basic sentences before we write a novel. We'll cover what tables are, rows and columns are, and how SQL allows us to interact with them. This foundational knowledge is crucial because almost all modern data analysis, especially in business intelligence and data science, relies heavily on understanding and querying data stored in relational databases. Getting these core concepts right will make your entire learning process much smoother and more intuitive as we build up more complex topics. Before we dive into SQL, it's crucial to understand what kind of system SQL interacts with. The term you will hear most often is RDBMS, which stands for Relational Database Management System. At its core, an RDBMS is a software system used to create, manage, and retrieve data from relational databases. What makes a database relational is the way data is organized. Instead of storing all information in one giant unstructured block. Relational databases break data down into multiple discrete tables. Each table is a spreadsheet with rows and representing individual records, like a specific customer or a single product, and columns representing attributes of those records, like a customer name, email, or even product's price. The relational part comes from the ability to define relationship between these tables using common fields called keys, which we'll discuss soon. This structured approach ensures data integrity, reduces redundancy, and makes it incredibly efficient to query, manage large volumes of interconnected information. Think of it as a meticulously organized filing cabinet where related information is stored in separately, well-indexed folders rather than a single chaotic file. So if RDBMS is the system that stores and manages our data, then SQL is the language we use to communicate with it. SQL stands for Structured Query Language. Let's break those words down. Structured refers to highly organized way data is stored in relational databases, in tables with rows and columns as we discussed. Query is the act of requesting information from databases, asking specific questions to retrieve the data you need. And language implies set of commands and syntax that both you and your database understand, allowing for precious interaction. Essentially, SQL is standard programming language for managing and querying data stored in an RDBMS. It's the bridge that allows data analysts, developers, and data scientists to interact with these vast repositories of information. Whether you want to retrieve specific customer detail, calculate total sales for a month, update a product price, or even define a new table structure, SQL provides commands to do it all. It's a universal language of data. These slides give you a high overview of different categories and types of commands available in SQL. You can see commands like select, update, insert into, and delete. These fall under data manipulation language, which are commands we will use to interact with the data itself within the tables, retrieving, adding, changing, or removing records. Then you will also notice commands like create database, alter table, drop table, create index, and drop index. These belongs to data definition language, which is DDL, which are commands we use to define, modify, and manage the structure of our databases, such as creating new tables, modifying existing ones, or defining relationships. Don't worry if these seems like a lot right now. We will be covering the most important of these in detail through the masterclass. Specifically, select will be our very next topic, and we'll dive into insert, update, delete, create table, alter table in module 6. This slide serves as a helpful visual roadmap of a powerful tool within the SQL language that we'll be exploring. The select statement is arguably the most frequently used command in SQL, as it's how retrieve data from your database. It's our primary tool for asking the database, show me this information. You specify which column you want to see. If you want all the columns from the table, you can use asterisk. For example, we have select asterisk from customers would display every piece of information about every customer. However, it's often more efficient and practical to select only the specific column you need, like select name, last name, email from customers. The from clause is equally essential as it tells SQL exactly which table you desire data resides in. SQL wouldn't know where to look for columns you have requested. Mastering these two keywords is your big step in communicating with database. An example of both the commands is select asterisk product name, comma price from this product, which is selecting product name column from the product table. Once you know how to select data, the next crucial step is to refine your results to focus only on what's relevant. The where clause allows you to filter rows based on specific conditions, ensuring you only retrieve the data that meets your criteria. You can use various comparison operators like equals, greater than, or less than, and combine multiple conditions using logical operators like and or. For instance, you might want to see sales only for a specific product category and above a certain quantity. After filtering your dataset, you will often want to organize your results in a meaningful way. The order by clause lets you sort your data based on one or more columns, either in ascending order, which is often the default one, or even descending order. This is incredibly useful for quick identifying the highest or lowest values, for seeing data chronologically to observe trends, or simply for presenting your results in structured, readable format. Combining where and order by allows for a very precious data retrieval and presentation. An example of both clause being select asterisk from sales where quantity 5 order by sale data desk implements to select all sales where quantity is exactly 5. Finally, the limit clause is a simple yet incredibly powerful tool for managing the size of your results set, especially when dealing with very large databases. Retrieving all matching rows can be insufficient, time-consuming, and often unnecessary, particularly if you are just looking for a quick overview of the top few entities. Limit allows you to return your query. For example, if you want to find the top 3 expensive products, you would combine select asterisk from products order by. Price decrease to ensure that they are sorted from the highest to the lowest, and then add limit 3. This command is particularly useful in scenarios like implementing pagination of web applications, or when you are performing exploratory data analysis and just want to sample a portion of your data to understand its structure and content without overwhelming your system on your screen. It's a fundamental tool for optimizing query performance and managing output. Before we start doing any practical part, there are 2 ways you can actually run SQL code. One is by downloading the SQL editors such as MySQL, and the second way, which is an online SQL editor. For today, I'll be using Programmis, which is an online SQL editor. So as you can see, this is the window for it, and already they have a few of the datasets which you can practice in. So let me start creating a table, which is a basic, so that we can work upon it. So for creating, the code will be create table. Let's name the table customer, and you can give the values for it or the columns for it. So the columns will be customer ID, and you have to mention the data type too. So customer ID will be my integer data type, and this will also be a primary key in the table, which is going to be a character. And I'm going to limit the characters to 50. And similarly, we have last name, which is also going to be a character. And also I'm limiting this to 50. And let's have email ID too. Email ID is a varchar, which is a character. And let's limit that to 100 characters. And finally, let's have the registration date. And the type would be the date type, which is a series. And then let's close it. So when I run this, it should ideally create a table with customer ID, first name, last name, email, and the registration date as the columns, but it should not have any other table or any other inputs inside it. So when I run it, firstly it shows it successfully run, and you can see here my table is here
with customer ID, first name, last name, email ID, and registration date, and the table is empty. Now, how do you fill in values for this? So the command is insert into. This programming language is not case sensitive, but most of the professional use the keywords as caps and the names or the column names as a small case. So firstly, when you have to insert in any of the name or last name or feed in value, we have to use insert into. And what are the IDs that you're going to insert? I'm going to insert customer ID. Then I'm also going to enter first name, last name, email, and registration date. And what are we entering? We're entering values. So after this, you can just open the braces, and with the separation of quotes, you can enter the customer ID and then their first name with separation of comma. Let's say Alice, comma, and next we have to give his last name. So let's see, Smith. And then we have email ID. Let's say smith@gmail.com. So here I have missed this. So yeah. And then we have to give the registration date, which I'll give it like 23/01/15. This is one of our data that is going in. Let's see if I push only this much, what will be the answer. I ideally have to get this data set over here. So let's just run this. I just erased the previous create table and run this code which was not executed. So here you can see I have entered the value of 1, the first name being Alice, last name Smith, and an email ID being provided, and as well as a registration date. So I'll create 2 more tables with the values inside it. So I've created 3 tables. One is customer, and then we have products with product ID, product name, category, and price. And lastly, I have the sales column or a table, which is sales ID, customer ID, product ID, and sale data. I have some data. I've also added shipping also. But rather than that, we can play with the data sets. So the first query that will be executing is select statement. So it is supposed to select any column, specific column, or the entire table. So for that, we have select asterisk. And say let's select the column of customer, sorry. And let's run this. It should display the entire table. So here you can see all the entire table is being displayed. Now if I want a particular column, for that, here I should add a filter. Instead of asterisk, we have to add what are the things that what columns has to be displayed. So let me display only the first name and the last name. Last name. So let's execute this. It should give me only the first name and the last name column. So as you can see, we have only first name and last name. Similarly, any 2 rows. Then let me filter out using a greater than 100 rupees. Let me select a product name which is 100 and more than 100 rupees. So we have select product name, which is there in the products column, and then we have price. Let me display then from, not from the customers table, from products table. And then the condition is, the where clause is the price should be greater than 100 rupees. So let's run this. Okay, product, check for any errors. So it should give me the product name where the price is greater than 100. So you can see laptop pro cost 1,200 and a desk chair ergonomical cost 250. These are the two products which have a price greater than 100. Now let's go to the next one, which is select the entire table, which is asterisk, and from sales, let's say I need the order by decrease. I want to arrange it in descending order. So we have order by, let's say price. I want to order the price from descending order. So for descending order, by default, it's going to be ascending order. So just give it DESC, which is a short form for descending order. And let's run the code. Such column price. Okay, so I think I have selected the wrong column. We have from sales, no, from products. So the column is in products. So now you can just run the code and you can see here the highest is 12. The highest is 1,200 and then it decreases as we go down. So for ascending, we can use ASC as the command. Now let's create a code which combines everything, that is selecting email of any two newest customers which we want to reach out the latest in the sign up. So we have to basically check which are the two new registrations and we have to add a decreasing order by. So for that we have select the column of email which we are majorly checking for, and also we need registration date. This is from which column, sorry, which table? It is from customers, customer. And then let's order it by registration date. And let me put a descending filter and let me limit it to 2 as well. So let's see the answer. So here you go. This is the 2 registration which is recently registered. Welcome to module 2, where we unlock the power of summarizing data. While selecting individual roles is useful, real insight often comes from understanding patterns across many records. Data aggregations allows us to condense vast amounts of information into meaningful summaries like totals, averages, and counts. This is crucial for answering questions like what was our total revenue last quarter, or even what's the average order value. Instead of looking at every single transaction, we can get a high-level overview that's essential for reporting and strategic decision making. We'll explore the various aggregate functions SQL provides and how to apply them effectively to transform raw data into digestible matrices. This module is all about moving from granular details into valuable summaries. SQL provides a set of powerful built-in aggregate functions that perform calculations on a set of rows and return single summary values. Let's look at the most common ones. Count is used to count the number of rows or null values in a specific column. For instance, count asterisk gives you the total number of records in a table, while count email would count only customers who provide an email address.
Sum calculates the total sum of the values in a numeric column, perfect for adding up quantities sold, total revenue, or even total expenses. Average computes the arithmetic mean or average value of a numeric column, giving you a typical value. Minimum and maximum retrieve the smallest and the largest value respectively from a specific column, which can be useful for identifying outliers or ranges. These functions are your first line of defense against data overload, transferring raw detailed data into concise, digestible matrices that are easy to understand and report on. While aggregate functions gives you grand totals of entire table, the group by clause takes aggregation to the next level, allowing you to apply these functions to groups of rows that share a common value. Think of it as creating subtotals in a spreadsheet where you might sum sales for each product category individually. Instead of getting you total sales of all products across your entire data set, you can group using group by product ID to get total quantities sold for each individual product. This is incredibly powerful for segmenting your data and understanding performance across different categories, regions, customer segments, or even time periods. When you use group by, any column in your select statement that is not part of aggregate function must be included in your group by clause. Ensure that SQL knows how to group the non-aggregated columns to produce meaningful summaries for each distinct groups, providing a much more granular view of your aggregated data. You have learned that where clause filters individual rows before grouping or aggregation takes place. But what if you want to filter the groups themselves based on that results of aggregate function? That's preciously what having clause is for. Having is used to filter the output of a group by clause. For example, if you calculate the total sales of a product category using sum and group by category, you might then want to see those categories where the sum of the sales exceed a certain threshold, say 1,000 rupees. You cannot use where because the aggregation hasn't happened yet at the where clause stage. Having allows you to apply conditions directly to aggregate results, giving you fine-grained control over which summarized groups are included in your final output. This distinction between where and having is a common point of confusion for beginners, but understanding is the key to write effective analytical queries. For example, this is a statement which is select category average price from products group by categories having average price greater than 100. This SQL query retrieves the categories and their average product prices, but only for those categories where the average price of products exceeds 100 rupees. Let's see some practical examples of data aggregation and grouping. So firstly, for data aggregation, the first command that comes to mind is count. So let's use that. So let me use select and count. What we have to count from the entire table. So entire table is asterisk, and then from which table? From sales table. So this is going to count how many times we have made a sale. So the count is 20. Similarly, what if you have to do a sum? Sum of the quantity. Sum of the quantity. So it will be sum quantity ka table, quantity ka column, and we have put a condition as total items sold. And it is from which table? It is from sales ka table. So this should ideally give individual items which have been moved. So which is 25. This is the total items sold. So how do you name this column? Just add as and whatever name you want to give the table as. Next, we'll explore average. So for average, we have AVG
Now let me take the average of the price. Now price is from, let me give me a name as average product price. This is what I'm going to name it. And price is from which table? Price is from products table. So it will be product. And let's execute this. So this is the average price of each product, which is 202.2211 or so. Next, we'll explore minimum and maximum, which is the cheapest product and which is the highest product. So let's IN, this is for minimum. We are calculating in which column? Price. And this, let us name it as cheapest. And then for maximum, again from the column price, let's name it as expensive. And these both are from which column? It is from sales column. Close it and run it. So here there is no such column named price. So check with the, okay, so product, under products we have price. So let's rename the table name. It should be products. Now let's run the SQL code. And here you can see I have made a spelling error. So let's rectify it and run it. So we have cheapest being 20 rupees and expensive being 1200 rupees. Next, how do you use group by? So let us imagine we have to calculate a total quantity sold per unit product ID. So this tells us which products are moving the most. So for that, we need select product ID. We need the product ID to remember which product is selling the most. And then let's calculate the sum of quantity, number of items, and name it as total. Total quantity. And then again, these both are from which table? Sales. And then I'm grouping them by product ID. Let us see if this will work. So here you go, product ID. So 101, the product ID is sold the most with 3 in number, and there are 8 in number also. So you can add a increment or a decrement function to see which product ranks number 1 and number 2. Now, how is having function used? So suppose you have to find a product category where average price is over 100 rupees. So how do you do that? Which category tends to have the higher period item? So for that, I'll write a query which is select category and the average price. Let me name this column as average category price. And then this is from which table? It is products. And I'm grouping them. Sorry. So I'm going to group by category. Also, I'm going to have a having function. So it is having average price. which is greater than 100. Let's say decimal point and close it. Let's run the code. And here you can see the average price of electronics is 288 and furniture is 250. Welcome to Module 3, a critical turning point in your SQL journey. Joining tables, up until now, we have primarily focused on querying data from a single table. However, in the real world, data is rarely confined to one place. Databases are designed to be relational, meaning information is distributed across multiple interconnected tables to avoid redundancy and maintain data integrity. For example, customer detail might not be one table, product information in another, and sales transaction in a third. To answer complex questions that require information from these different sources, like which customer bought which product or what are the most popular products among new customers, we need a way to combine these data. This is preciously what SQL joins allows us to do. Intelligently link related data across different tables to create a comprehensive, ununified view, enabling much richer and more insightful analysis. Before we dive into different types of join, it's essential to understand the concepts of keys in relational databases, as they are very foundation of how tables are linked and how data integrity is maintained. A primary key is a column or a set of columns that uniquely identify each row in a table. Think of it as a unique ID number for every record. No two rows can have the same primary key, and it cannot contain null values. For example, customer ID in the customers table is a primary key, ensuring each customer's record is a distinct one. A foreign key, on the other hand, is a column in one table that refers to the primary key in another table. It establishes a link or relationship between the two tables. For instance, customer ID in our sales table is a foreign key because it refers back to the customer ID in the customers table. This relational design is incredibly powerful because it prevents data duplication, ensures consistent across related tables, and allows us to efficiently query interconnected data without storing the same information repeatedly, which saves space and reduces errors. Now let's explore most common frequent use types of SQL join. The inner join is the most fundamental and acts like an intersection. It returns only the rows where there are matching values in a specified join columns in both of the table being joined. If a record is in one table doesn't have a corresponding match in the other, it simply excludes from the result. Next, we have the left join. This join is designed to return all rows from the left table and only the matching rows from the right table. If there is no match in the right table for a row in the left table, the columns from the right table will simply show null. This is incredibly useful when you want to see everything from your primary table and enrich it with data from another. Even if the same records don't have a direct match, the right join is the symmetrical opposite of the left join. It returns all rows from the right table and only matching rows from the left table, with null values or non-matches on the left side. While less commonly used, that left join in practice, it serves specific purposes when you analytically focus on primary on the right table data. For example, the above SQL query would retrieve the sale ID, quantity sold, product name, and price of all sales by linking each sale record to its corresponding product record. Beyond the basic inner, left, and right joins, SQL offers more specified join types for complex scenarios. The full outer join, which is the most inclusive join, it returns all the rows from both left and right table, regardless of whether there is a match in the other table. If a row from the left table doesn't have a match in the right side columns will be null. Similarly, if a row from the right table doesn't have a match in the left side columns will be null. This is practically useful when you want to see all the data from both the sides and identify any mismatches or records that exist exclusively in one table but not the other. Note that the exact syntax of full order join can vary slightly between different database systems. and sometimes it's simulated using a union or left and right joins. Lastly, a self-join is a fascinating concept where you can join a table to itself. This might sound communicative, but it's incredibly powerful for analyzing hierarchical or self-referencing data within a single table. A classic example of the employee table, where each employee has a manager ID that refers to another employee ID with the same table. By self-joining, the employee table is itself, you can easily retrieve an employee's name alongside their manager's name from the same data set without needing to separate manager's table. This technique is invaluable for organizational charts, bill of material structures, or any data with a parent-child relationship with a single entity. For example, the above query retrieves pairs of employees and their corresponding managers from a single employee table. It does this by joining the table to itself, matching an employer's manager ID with another employee's employee ID to identify the manager. The output will show you two columns, one for the employee's name and one for the manager's name. So talking about inner join, let's execute inner join. We'll see what will be the output. So when do you use inner join? To get the product names from all the sales transaction. If you want to see what product was actually sold in the transaction or not, just the IDs. So for that we have select s dot sale ID and let's say p dot product name, and also s dot quantity and s dot unit price. And this is from which table? We have sales and then s, and we want inner join, so let's mention that from products p on s dot product ID, which will be equal to p dot product ID. So this should give us an inner join. So yeah, so this will be your inner join. Similarly, you can perform a right join and a left join. But here I'll just show you how to create a self join to demonstrate a simple employees table. Okay, so for here I'll create a fresh table, which is create table, and let the name be employee. And let's give the column name as employee. Table name is employee, and the column names being employee ID, and which is which type? Int, and I'll make it as primary key. And then we have, let's have employee name, which is in character format, and let me give the value as 10. And what else can we add? We can add manager ID, which is in int. So this is a table. So here you could have seen employee, here employee ID, and we have employee name, and also we'll have manager ID. This is created here. So I've added few values over here and also inner join. By creating a temporary employees table, alongside their manager pulling both pieces of information from the same table, showcasing how to analyze hierarchical data. So let me just execute this. So let us run this code. And here you can see I've added few of the inner join items here in the columns. Welcome to Module 4, where we tackle the art of managing complexity in SQL queries using subqueries and common table expressions, or known as CTEs. As your data analysis questions become more sophisticated, a single select statement with a simple where and join clause might not be enough. You'll often find yourself needing to perform intermediate calculation, retrieving a specific set of data that then feeds into another part of your query, or break down a multiple step analytical process. This is where subqueries and CTEs become indispensable tools. They allow you to break down complex problems into small, more manageable and often more readable pieces, making your SQL code more organized, easier to understand, and significantly simpler to debug. We'll explore how each of these powerful features help you write more efficient and maintainable SQL. A subquery, also known as inner query or nested query, is simple select statement embedded within another SQL query. Think of it as asking a smaller specific question first and then using answer to make smaller question to help resolve a larger one, more complex one. Subqueries are incredibly versatile and can be used in several parts of SQL statements. A very common use case is where clause. Where is the subquery can generate a list of values that are outer query and then uses for filtering, often with an operator like in or exist. For example, if you might want to all your customers who have purchased a specific product, which involves first finding the customer IDs from the sales table for the product and then using those IDs to retrieve customer details. You can also place subqueries in the select clause to return a single aggregated value for each row of the outer query, or even in the form clause, where the result of the subquery acts as a temporary virtual table, sometimes called derived table, that you can then query further. While powerful, deeply nested subqueries can sometimes become hard to read and debug, which leads us to our next concept of CTEs. Common table expression or CTEs are a modern and highly recommended feature in SQL, defined using the with clause. They allow you to create a temporary named results set that you can reference within a single select, insert, update, or delete statement. The primary benefit of CTE is significantly improvement in readability and maintainability of complex queries. Instead of nesting multiple subqueries, which can quickly become difficult to follow and debug, CTEs lets you break down your logic into distinct, named, sequential steps. Each CTE can build upon the previous one, making your thought process explicit in your code. For instance, you might define one CTE to calculate total sales per product and then another CTE to find average of those totals. And then you will find query selects from second CTE. While CTEs are temporary and only exist for a duration of the query in which they are defined, they are incredibly powerful for multiple step calculation, recursive queries, and simply making your SQL code cleaner, more understandable, and more modular for yourself and others who might read or maintain it. They promote a more organized and logical approach to writing advanced SQL. Welcome to Module 5, where we introduce one of the most powerful and versatile features in SQL for advanced analytical tasks. Windows function, while aggregate function like sum, average, collapse rows into single summary window, functions allows you to perform calculations across a set of related rows without collapsing them. This means you get to aggregate value alongside each individual row, providing crucial context that simply group by statements cannot. For example, amount of their running total of sales in all the same result set. The capability of invaluable for tasks like ranking items with a category, calculating running totals over time, or comparing a row's value to a previous or next row, which are common requirements for financial analysis, trend identification and performance monitoring, understanding window function will significantly elevate your data analysis capabilities and allow you to answer more complex business questions. The core syntax of any window function involves a function name followed by over clause. The over clause is where you define the window or set of rows over which the function will operate. This is magic behind window function as it tells SQL which row are considered related for the current calculation. Within over, you can use two option but powerful subclauses, which is partition by and order by. Partition by divides your data into separate independent groups, similar to how group by works, but crucially, it doesn't. So with collapsing the rows, the window function then performs its calculation independently with each of these partitions. For example, if you're calculating a running total of sales, you might partition by customer ID to get a separate running total for each customer rather than one grand total. Order by within over clauses specifies the logical order of rows within each partition. This is absolutely crucial for function that depends on sequence of data such as ranking function or calculating cumulative sums, ensuring the calculation is performed in the correct order. Within order by, the results of some window function might not be deterministic. Ranking function is one of the most common and intuitive application of window function, allowing you to assign a rank to each row within specified partition based on given ordering criterion. There are three primary ranking functions, each handling ties slightly different. Row number assigns a unique sequential integer of each row within its partition starting from 1. If there are ties in ordering criteria, the row number two products the row number assignment along the tied rows are attributary but unique. Rank assigns a rank to each row, but if there are ties, all tied rows receive the same rank. And next rank skips numbers. For example, if two items are tied for the first place, they both get ranked 1 and the next item gets ranked dense rank. Is similar to rank. It assigns consequently ranks without any gaps even in the presence of ties. So if two items are tied for the first place, they both get rank number 1 and for the next item gets rank 2. Choosing the right ranking function depends on how you want to handle ties, whether you need to consciously sequence the ranks for your analysis, such as finding the top end performers or identifying the order of the events. Beyond ranking, window functions are incredibly powerful for various analytical calculations that involve looking at preceding or succeeding rows. Lag and lead are value functions that allows you to access data from preceding or succeeding row within you to identify window respectively. Lag, which retrieves the value from the column from a row of offset rows before the current row, and default value is used if no such row exists. Lead does the opposite, fetching from a row offset after the current row. These are invaluable for time series analysis such as comparing current sales to yesterday's sales or analyzing sequential events like a customer's current purchase compared to their last ones. Furthermore, window functions are perfectly suited for calculating running totals and moving averages. A running total achieved with sum over order by cumulative sums values as you progress through the ordered data, showing the accumulation of a metric over time. A moving average, typically calculated with average over, smooths out daily over period to period fluctuations by averaging values over a specified window of rows, which helps to identify underlying trends more clearly by reducing noise. These analytical capabilities are fundamentals in financial analysis, sales forecasting, and many other data-driven fields where understanding trends and comparison over time is crucial. Welcome to Module 6, where we shift our focus from merely retrieving and analyzing data to actively changing and structuring it. This module covers data manipulation language, which is DML, and data definition language, which is DML, allows you to add new records, modify existing ones, and delete unwanted data. which are fundamental operations in any database system, essential for keeping your data current and accurate. DDL, on the other hand, gives you the power to define and alter the very structure of your database tables, such as creating new tables from scratch or adding new columns to existing ones as your data requirements evolve. We'll also touch upon data type conversion, a common task when data needs to be presented or used in a different format for calculation or integration. These skills are crucial for maintaining the accuracy and relevance of your database, as well as preparing data for specific analytical needs or ensuring compatibility with other systems. Data manipulation language or DML consists of commands that allows you to interact directly with the data stored within your tables. The insert into statement is used to add new rows or records into a table. This is how new customer signups, new product entities, or new sales transactions are recorded in your database. You specify the table name and the values for the columns, ensuring the data types match. The update statement is used for modifying existing data in one or more rows. This is incredibly powerful for collecting errors, reflecting changes in status, or updating information like a customer's email address or product's price. However, it comes with a critical warning. You must always use where clause with update to specify exactly which row you want to change. Without it, you could inadequately modify every single record in your table, leading to massive data corruption. Similarly, the delete statement is used to remove rows from a table. Just like update, it's absolutely vital to use a where clause to target specific rows for permanent deletion. Without it, you could wipe out your entire table's data. In many professional environments, soft deleting, which is marking a record as inactive with a status flag rather than permanently removing it, is often preferred for auditing and data recovery processes, offering a safer alternative to a full delete. Beyond manipulation, the data itself, SQL provides data definition language, which is DDL, commands that allow you to define, modify, and manage the structure of databases. The create table statement is how you initially define a new table, specifying its name and the names of its column and data type for each column. Data types are crucial because they dictate what kind of information a column can hold, how much storage it requires, and how it behaves in queries. The alter table statement is used to modify the structure of an existing table after it has been created. This can include adding new columns, dropping existing ones, or changing the data type of a column. This flexibility is essential as your data requirements evolve over time. For instance, you might decide to add a phone number column to your customer table. Finally, we have the cast function. While technically a function rather than a DDL command is often used to conjunction with data transformation, it allows you to explicitly convert a value from one data type to another. For example, converting a string that represents a number into an actual numeric type so you can perform mathematical operations on it, or formatting the data into specific string representing for reporting or display purposes. Understanding DDL and data types is fundamental for designing and maintaining robust database schemas. Welcome to our final module, Module 7, where we will delve into some more advanced SQL techniques that are particularly valuable for data scientists, analysts, and anyone working with complex data sets. While the previous modules covered the core functionalities, these advanced tools allow more sophisticated data cleaning pattern, matching, and abstraction, enabling you to extract deeper insights and streamline your analytical workflows. We'll explore powerful functions for working with different data types like dates and strings, touch upon regular expression for flexible patterns matching, and introduce concepts like views and stored procedure with the help of creating reusable and efficient database objects. Mastering these techniques will truly elevate your SQL proficiency and open doors to more intricate data challenges, preparing you for the real-world data science problems. In the real-world data, you will constantly encounter various data types, and SQL provides a rich set of functions to manipulate them effectively, which is crucial for data cleaning and preparation. For dates and times, you can extract specific components like the year, month, or the day using the functions that vary slightly by database systems such as strft time and sqlite year, month, or mysql extract in PostgreSQL. This is crucial for time series analysis, identifying seasonal trends, or grouping data by specific time periods for reporting. You can also calculate difference between dates, for example, to determine how long a customer has been registered or the duration between two events. For strings, SQL offers between powerful manipulation function, which is upper and lower converted text to uppercase or lowercase, useful for standardizing text data to ensure consistent comparison. Strings allows you to extract a portion of a string, which is handy for passing codes or identifiers, while length returns its length concat, combines multiple text columns into a single string, such as creating a full name from a separate first and the last name columns for display. These functions are indispensable for data cleaning, formatting, and preparing text data for analysis. To wrap up our advanced techniques, let's briefly discuss these powerful concepts that enhance your SQL capabilities. First, regular expression, often abbreviated as regex, offer an extreme flexible and powerful way to search for or manipulate complex patterns within the text data. While basic can handle simple wildcard, regex allows you to define intricate patterns such as validating email formats, extracting specific codes or number from long unstructured text fields, or finding words that match a specific structure. The exact function or operator varies by database system. Second, views are virtual tables created from the result set of a SQL query. They don't store data themselves, but rather provide a simplified, predefined window into your data. You can query a view just like a regular table, which can excellent from simplifying complex join or aggregates that you can use frequently, for a less providing a controlled abstraction layer of users who only need to see a specific subsets of data without understanding and underlying complex queries. Finally, we have stored procedures, which are pre-compiled collections of SQL statements that are stored in the database server. They encapsulate complex business logic, can accept parameters, and offer significant benefit like improved performance, enhanced reusability, and improved security. While their syntax is highly database specific, understanding their purpose is key for advanced database interactions, automating and building robust data solutions. The skills you have gained today is not merely technical. They are foundation for critical thinking and problem solving in the domain that relies on data. SQL isn't just a language for databases, it's a superpower for anyone who wants to make sense of information, drive impact. With SQL, you now have the ability to precisely extract specific information, no matter how deeply buried it is. Your datasets allowing you to answer very targeted questions. You can identify crucial trends and patterns that are often hidden in raw, unstructured data, enabling you to uncover valuable insights into performance, behavior, and anomalies. You can summarize vast amount of data into concise, actionable reports and dashboards, transferring overwhelming number into clear native that stakeholders can understand. Ultimately, mastering SQL empowers you to make truly data-driven decisions, impacting everything from business strategy and operational efficiency to significant discovery and public policy. This proficiency will serve you as a cornerstone of your analytical career, opening doors to countless opportunities.
Companies around the world are generating vast volumes of data every hour. This data could be in the form of log files, web server and transactional data, as well as various customer-related data. Also, data is being generated at a rapid rate from social media websites and applications such as Facebook, Instagram, Twitter, and WhatsApp. Companies want to use this data to derive value out of it and make business decisions. That's where data analytics comes into use. Data analytics is the process of exploring and analyzing large data sets to find hidden patterns, unseen trends, discover correlations, and valuable insights to make business predictions. Data analytics improves the speed and efficiency of your business. A few years ago, a business would have gathered information manually, performed statistical and complex analytics, and unearthed information that could be used for future decisions. But today, that business can identify insights on the fly for immediate decisions. Most organizations have big data, and many understand the need to harness that data and extract value out of it. So, they use a lot of modern tools and technologies to perform data analytics. Some of the tools I will discuss in detail later in this tutorial. Now that we have looked at what data analytics really is, let us understand the ways in which you can use data analytics.
What's in it for you? And we're going to go over what is numpy, installing and importing numpy array versus Python list, basics of numpy, finding size and shape of any array, range and arange functions, numpy string functions. And then in part 2, I'll move on to cover axes, array manipulation, and much more. So let's start with what is numpy. Numpy is the core library for scientific and numerical computing in Python. It provides high-performance, multi-dimensional array object and tools for working with arrays. And I'll go a step further and say there are so many other modules in Python built on numpy. So the fundamentals of numpy are so important to latch onto for the Python so that you can understand the other modules and what they're doing. Numpy's main object is a multi-dimensional array. It is a table of elements, usually numbers, all of the same type, indexed by a tuple of position integers. In numpy, dimensions are called axes. Take a one-dimensional array, or we have, and remember dimensions are also called axes, so you can say this is the first axis, 0, 1, 2, 3, 4, 5. And you can see down here it has a shape of 6. Why? Because there's 6 different elements in it in the one-dimension array. And they usually denote that as 6 comma with an empty node on there. And then we have a two-dimensional array where you can see 0, 1, 2, 3, 4, 5, 6, 7. And in here we have 2 axes or 2 dimensions, and the shape is 2, 4. So if you were looking at this as a matrix or in other mathematical functions, you can see there's all kinds of importance on shape. We're not going to cover shape today, but we will cover that in part 2. Did you know that numpy's array class is called NDArray for numpy data array? Now we're going to take a detour here because we're working in Python, and 2 of my favorite tools in Python is the Jupyter Notebook, and then I like to use that sitting on top of Anaconda. And if you flip over to jupyter.org, that's jupyter.org, you can go in here. You can install it off of here if you don't want to use the Anaconda Notebook, but this is the Jupyter setup, the documentation on the Jupyter. Jupyter opens up in your web browser. That's what makes it so nice, is it's portable. The files are saved on your computer. They do run in IPython or IronPython, and you can create all kinds of different environments in there, which I'll show you in just a minute. I myself like to use Anaconda. That's www.anaconda.com. If you install Anaconda, it will install the Jupyter Notebook with the Anaconda separate. And you can install Jupyter Notebook and it'll run completely separate from Anaconda's Jupyter Notebook. And you can see here I've now opened up my Anaconda Navigator. What I like about the Navigator, and this is a fresh install on a new computer, which is always nice, I can launch my Jupyter Notebook from in here. I can bring other tools, so the Anaconda does a lot more. And under environments, I only have the one environment, and I can open up the terminal specific to this environment. This one happens to have Python 3.7 in it, the most current version as of this tutorial. And then you open a terminal if you're going to do your pip installs and stuff like that for different modules. You can also create different environments in here. So maybe you need a Python 3.6, Python 3.5. You can see we're having a nice framework like Anaconda really helps. So you don't have to track that on your own in the Jupyter Notebook and your different Jupyter Notebook setups. We'll go ahead and launch this Jupyter Notebook. And then I've set my browser window for a default of Chrome. So it's going to open up in Chrome. And you can see here, this opens up a folder on my computer. We have a couple different options on here. Remember, I set the environment up as Python 3.7. You would install any additional modules that aren't already installed in your Python on this. And it keeps them separate, so you do have to, for each environment, install the separate modules so they match the environment on there. And in here we have a couple things where you can look up what's running. You have your different clusters. Again, I just installed this on a new machine, so I just have a couple things in here that were run on here recently. And where we go on here is we then have on the upper right new, and from the pull down menu you'll see Python 3, and this will open up a new window. And now we're in Jupyter Python, so this is a Python window. We'll just do a print, and this of course is, let's go hello world, and we'll run that and it prints out hello world in the command line. There's a couple special things you have to know what we're not going to do today, which is on graphics. If you've never seen this, one of the things you can do is you can also do a equals hello world, and if you just put the a in there, now if you do a bunch of these where you have a equals hello world, b equals goodbye world, and you put a, b, a, then return b, it'll only run the last one. But you can see here, if you put the variable down here, it will show you what's in that variable. And that has to do with the Jupyter Notebook inline coding. So that's not basic Python, that's just Jupyter Notebook shorthand, which you'll see in a little bit. So back to our NumPy array versus Python list. Python list being the basic list in your Python. Why should we use NumPy array when we have Python list? Well, first, it's fast. The NumPy array has been optimized over years and years by multiple programmers, and it's usually very quick compared to the basic Python list setup. It's convenient, so it has a lot of functionality in there that's not in the basic Python list. And it also uses less memory, so it's optimized both for speed and memory use. And let's go ahead and jump into our Jupyter Notebook. Since we're coding, best way to learn coding is to code. Just like the best way to learn how to write is write, and the best way to learn how to cook is cook. So let's do some coding here today.
But before we move on, let's understand first what is Jupyter Notebook. So guys, as you can see all over here, that Jupyter Notebook is a popular open source tool that basically allows you to create and share documents which contains codes, equations. You can have visualizations also. Basically, it is used for data analysis, machine learning, and scientific research, which makes it a very essential tool for developers like data scientists and researchers alike. Now, before installing Jupyter Notebook, I request you that you have Python installed in your system. So the requirement should be Python 3.6 or greater. So now let us officially navigate to the Python's website. So guys, as you can see all over here, so on python.org, if I click on download Python, so we're going to see that all over here, download Python 3.125. So as I already told you that the requirement of Python should be greater than 3.6. So just you can click all over here and you can see the download had started. So guys, as you can see all over here that we have installed the Python. Now let us open the file. So you can see the given software is going to install on this directory. Okay. So just click all over here. So guys, as you can see all over here, the Python installation of 3.125 is in progress. Let's wait for some time till it gets installed. So as you can see guys all over here that we have successfully installed our Python. Now let us open our terminal and let us check whether Python is correctly installed. So we are going to type python/version. So as you can see all over here, we have successfully installed our Python. So guys, that was our prerequisite. Now, there are two ways to install Jupyter Notebook. The first one can be pip. Okay, pip is a package manager, or using Anaconda distribution. So let us see with pip first. So guys, pip is a package manager which is used to install and manage software packages, libraries written in Python. So you can see all over here that the Python with version greater than 3.6 have default pip installed in them. Okay, so we can use pip command to install our Jupyter Notebook. So guys, as you can see all over here, we have come to the official documentation of Jupyter.org, and it is saying that installing Jupyter Lab with pip command. So what you can do guys, you can just copy all over here. You can go right all over here and click on this. Now, as you can see all over here, it has started downloading the Jupyter Lab. So guys, we are going to install our Jupyter Lab with the pip command. So this is the official documentation of Jupyter Notebook. Okay, and just all you have to do is copy this and type on your terminal. So as you can see all over here, it has started downloading the packages which is required to download the Jupyter Notebook. Let us wait for some time. Okay guys, so we have successfully completed this step. Now let us move on to our next step. So as you can see all over here, so we have installed, okay. Then what we have to do, then you can type this, you can launch the Jupyter Lab with this command on the terminal. Now let us wait. So as you can see all over here guys, we have successfully installed our Jupyter notebook. So you can go all over here and just create a new notebook, and you can also choose your kernel and you can start working on your Jupyter notebook. Suppose I'll show you one snippet. So 3 plus 5, let us try to run this notebook. So as you can see, it is giving us the 8 as answer. So it is following the Python syntax, and in this way we have successfully installed our Jupyter notebook using the pip command. So now, as you can also see all over here, you can also install Jupyter notebook with this command, pip install notebook, and then you can just open it. This is also another alternative. Similarly, you can install with Viola also. Same command and just open the Viola. Now, if you are using any other operating system like macOS or Linux, then you can install by brew install Jupyter Lab. So Homebrew will be the package manager for macOS and Linux. So I hope so you are pretty clear with how to install Jupyter Notebook with the pip command. Now, I have downloaded Anacondas from this official website. So as you can see all over here, this is the official website of Anaconda. Okay. Now just type your email and you can just download it. So similarly, as you can see, after installing, I'm going to launch my installer and let us click next. Okay. Let us click agree. Okay. And let us install this on the given directory. Let us wait for some time till the installation gets complete. So guys, as you can see all over here, we have completed our installation of Anaconda. So just click on finish and you can say we have successfully installed our Anaconda. Now let us open our Anaconda navigator. So just click on So as you can see all over here, just right click on this and our Anaconda navigator will be opened. So as you can see all over here, this is our Anaconda navigator and it is loading the packages. And for us to install the Jupyter notebook, so as you can see all over here, just click on launch. So guys, if you click on launch, it is going to open our Jupyter notebook. So as you can see all over here, it is saying launching the Jupyter notebook and it is hosted on localhost 8889. So this is our hosted Jupyter notebook. And similarly, you can create a new notebook all over here. And in this way, you can start working.
And just like any modules, we have to import numpy. We almost always import it as np. That is such a standard. So you'll see that very commonly. We can just run that. And now we have access to our numpy module inside our Python. And then the most common thing, of course, is to go ahead and create a numpy array. And in here, we can send it a regular list. And so we'll go ahead and send this a regular array. Let's go 1, 2, 3 to make it simple. And then I'm just going to type in A, and we'll run this. And so you can see down here, the output is an array of 1, 2, 3. And we could also do print, just a reminder that this is an inline command, so that wouldn't work if you're using a different editor. You can see that it's an array 1, 2, 3. But we'll go ahead and leave it as A. Kind of a nice feature so you can see what you're doing really quick in the Jupyter Notebook. And just like all your other standard arrays, I can go A of 0, which is going to be a value of 1. Of course, we do A of 1. You go all the way through this. A of 1 has a value of 2 in it. So whether you're using the numpy array or the basic Python list, that's going to be the same. That should all look pretty familiar and be pretty straightforward. Remember, the first value is always 0. And when we set on there. So let's take a look why we're using numpy, because we went over the slide a little bit, but let's just take a look and see what that actually looks like. And what we want to look at is the fact that it's fast, convenient, and uses less memory. So let's take a glance at that in code and see what that actually looks like when we're writing it in Python and what the differences are. And to do this, I'm going to go ahead and import a couple other modules. We're going to import the time module so we can time it. And we're going to import the system module so that we can take a look at how much memory it uses. And we'll go ahead and just run those, so those are imported. And so we'll do b equals, range of 1, yeah, 1,000 is fine. And so that's going to create a list of 1,000, 0 to 999. Remember, it starts at 0 and it stops right at the 1,000 without actually going to the 1,000. And let's go ahead and print. And we want system.getSize of. And we'll pick any integer, because we have, 0 to 1,000. We'll just throw one in there, 5. It doesn't matter, because it's going to, whatever integer we put in there is going to generate the same value, because we're looking at the size of how much memory it stores an integer in. And then we want to have the length of the b. That's how many integers are in there. And if we go ahead and execute this and run this at a line, we'll see, oops, I did that wrong, comma. If we multiply them together, we'll see it generates 28,000. So that's the size we're looking at, is 28,000. I believe that's bytes. That sounds about right. So let's go ahead and create this in numpy. And we'll go with c equals np. And this is arange. So that's the numpy command to do the same thing that we were just doing in a list. And we'll also use the same value on there, the 1,000. And then once we've created the value of c for np.arange, let's go ahead and print. And we can do that by doing c.size times c.itemSize. And that's very similar to what we did before. We did get the size of, so the c size is the size of the array, and each item size, just reversed. So it's the size of an integer 5, item size is going to be the integers, and c size. And let's just take a look and see what that generates. And wow, okay, we got 4,000 versus 28,000. That's a significant difference in memory, how much memory we're using with the array. And then let's go ahead and take a look at speed. Let's do size. We tried this with lower values, and it would happen so fast that the NP array kept coming up with 0 because it just rounded it off. So size, and let's create an L1 equals range of size, and we'll do an L2. We'll just set up to the same thing. It's also range of size on there. There we go. And then we can do on A1 equals np dot arange size. And then let's do on A2 equals np dot arange. We'll keep it the same size. And what we're going to do is we're going to take these two different arrays and we're going to perform some basic functions on them. But let's go ahead, actually let's just load these up now. We'll go ahead and run this so those are all set in memory. Except for the typo here. Quickly fix that. There we go. So these are now all loaded in here. And let's do a start equals time.time. So it's just going to look at my clock time and see what time it is. And then we'll do result equals, and let's do, let's say we got an array, and we're going to say, let's do some addition here. X plus Y for X comma Y. And we'll zip it up here. Two different arrays. So here's our two different arrays. We're going to multiply each of the individual things on here. L1, L2. There we go. So that should add up each value. So L1 plus L2, each value in each array. And then we want to go ahead and print. And let's say Python list took. And then we'll do time dot time. We'll just subtract the start out of there. So time, whoops, I messed up on some of the quotation marks on there. Okay, there we go. Time minus the start. And we'll convert that to seconds. So we'll go, because that's in milliseconds, so times 1,000. And let's hit the run on there. This is kind of fun because you also get a view while we're doing this of some ways to manipulate the script. And as you can see also my bad typing. There we go. Okay, so we'll go ahead and run this. And we can see here that the Python list took 34 Actually, I have to go back and look at the conversion on there, but you can see it takes roughly 0.34 of a second. And we can go ahead and print the result in here too. Let's do that. We'll run that just so you can see what kind of data we're looking at. And we have the 0, 2, 4, 6, 8. So it's just adding them together. It looks pretty straightforward on there. And if we scroll down to the bottom of the answer, again, we see Python list took 46. A little different time on there depending on what core, because this is on an 8-core computer, so it just depends on what core it's running on, what else is pulling on the computer at the time. And let's go back up here and do our start time. Paste that into here. And this time we're going to do a result equals, and this is really cool. Notice how elegant this is. It's so straightforward. This is a lot of reason people started using numpy is because I can add the two arrays together by simply going A1 plus A2. It makes a lot of sense, both looking at it, and it's just very convenient. Remember that slide we're looking at? Fast, convenient, and less memory. So look how convenient that is. Real easy to read, real easy to see. And I don't know if we don't need to print the result again, so let's just go ahead and print the time on here. And we'll borrow this from the top part because I really am a lazy typer. And this isn't the Python list, this is the numpy list, or numpy array. And let's go ahead and see how that comes out. And we get 2.99. So let's take a look at these two numbers, 46 versus 2.99. So we'll just round this up to 3. That's a huge difference. That's like more than 10 times faster. That's like 15 times roughly at a quick glance. I'd have to go do the math to look at it. And it's going to vary a little bit depending on what's running in the background on the computer, obviously. So we've looked at this, and if we go back here, we found out it's much faster. Yes, there's going to be different speeds depending on what you're doing with the array. Very convenient, easy to read, and it uses less memory. So that's the core of the numpy. That's why a lot of people base so many other modules on numpy and why it's so widely used. So we did glance at a couple operations while we were looking at speed and size. Let's dive into a little bit more into the basic operations. And these are always nice to see. I mean, certainly you want to go get a cheat sheet if you're using it for the first time. Look things up. Google is your friend. We did this for the most basic numpy.array or np.array. And we'll go ahead and create an array. Let's do pairs, 1, 2. And then let's do 3, 4. And if we're going to do that, let's do 5, 6. There we go. And if we go ahead and take this and run this, I can go ahead and do our A down here so it's in line and it'll print that out. You can see it makes a nice array for us. So we have A, and if you look at that, we have 3 different objects, each with 2 values in them. And hopefully you're starting to think, well, how many dimensions or indexes is that? And you'll see 3 by 2. So let's go ahead and take a look, and let's go, how about A.nDimensions? Speaking of which, we'll run that, and we have 2 dimensions for each object. And then we can do the item size, so A dot. We saw this earlier, where we looked up how many items. It was up here, where we wanted to multiply item size times the actual size of the object. So the memory is being used versus the item size. And we should see 4 there. Memory is compressed down. That's always a good thing. And then the shape. The shape is so important when you're working with data science and you're moving it from one format to another. So we have our shape. We just talked about that. We have 3 by 2. 3 rows by 2 objects in each one. Generally, I don't look too much at the size, but the dimensions I'm always looking up. And this is nice, you can automate it. So you might be converting something, you might need to know how many dimensions are going into the next machine learning package so that you can automatically just have it send that information over. So we looked at A shape. Let's go ahead and create a slightly different array, np.array. Let's go ahead and just do as our original setup here. And one of the features we can do, which is really important, is we can do dtype equals. In this case, let's do np float 64. And so what we've done is we're converting all of these into a float. And we type in A. And now instead of having 1, 2, 3, 4, 5, 6, you see they're all float values. 1.0, there's no actual 0 in there, just there's a 1 dot. Or the 1 period, 2, 3 period, 4 period, 5 period, 6 period. And this, again, data science, I don't know how many times I've had to convert something from an integer to a float so that's going to work correctly in the model I'm using. So very common features to be aware of and to be able to get around and use. And we'll also do, let's just curiosity, item size. We'll go ahead and run that. And we see that it doubled in size. So it's not a huge increase. Well, doubling is always a big increase in computers. But it's not a huge increase compared to what it would be if you're running this in the Python list format. And then we did the shape earlier without having it set to the float 64. Let's go ahead and do a shape with it set to 64. And it should be the same 3, 2. So it all matches. So we've gone through, and remember, if this is all brand new to you, according to the Cambridge study at the Cambridge University, if you're learning a brand new word in a foreign language, the average person has to repeat it 163 times before it's memorized. So a lot of this, you build off of it, so hopefully you don't have to repeat it 163 times. But we did manage to repeat it at least twice here, if not a little bit more. And let's go ahead and take this. We're going to go look at one more setup on here. And let me just take this last statement here on the converting our properties of our data. And instead of float 64, let's do complex. Let's just see what that looks like. And let's go ahead and print that out and run it. And so we now have a complex data set up, and you'll see it's denoted by the 1 dot plus 0 dot j. And if we flip over here and do a basic search for numpy data types, better to go to the original web page, but pull up a bunch of these. You can see there's a whole list of different numpy data types. Shorthand, complex, we have complex, complex 64, complex 128. Complex number represented by 2 64-bit floats, real and imaginary components. One option on there, float 16, float 32. Float, shorthand for float 64, most commonly used. And of course all the different ones that you can possibly put into your numpy array. So we covered a basic addition up there when we were comparing how fast it runs. But some very basic components, how to set up a numpy array, how many dimensions it has, item size, data type, again we went to item size, and there's also the shape. Probably one of the more used. I use a shape all the time, very commonly used. And then down here you can see where we actually created a numpy complex data type. So let's look at some other features in numpy. One of them is you could do numpy dot zeros, and we're going to do 3, 4. There we go. And we'll go ahead and run this, and you can see if I do np.zeros, I create a numpy array of zeros. This is really important. I was building my own neural network, and I needed to create an array where I initialized the weights, and I wanted them all to be the same weight. In this case, I wanted them to start off as 0 for the particular project I was working on. And there's other options, like you can do numpy1s, and we'll do the same thing, 3, 4, we'll run that. And you can see I've created an array of numpy1s. In this case, it comes out as a float array. And then this is an interesting to note, because we have, let's go back to our Python and do lrange 5, and we'll print the L, so that's our list. And if I run that, it doesn't create the range until after the fact, until you actually execute it. That's an upgrade in Python. Python 2.7 actually created the array 0, 1, 2, 3, 4. This one actually creates the script, and then once it's used, it then actually generates the array. And if we do that in numpy arange, remember that from before, and if we do numpy arange 5, and let's do L equals, or we can just leave it as numpy, that's fine. There we go, just run that. You can see there we actually get an array, 0, 1, 2, 3, 4 for the value of the numpy arange 5. It generates the actual array. And for part 1, we're going to do just one more section on basic setup, and we're going to concatenation, do a concatenation example. There we go. We're going to do strings. Let's take a look at strings and what's going on with there. And let's do, let's see, print. Let's do an np character, something new here. And we're going to add, and then here's our brackets for what we're going to add. And let's say, let's do hello, comma, hi, and in the brackets on there, let's create another one, and this one's going to be ABC, and we'll do XYZ. So we're just creating some, randomly making some up on here. And then we'll go ahead and just print this. If we run that, you can come down here, and of course make sure all your brackets are open and closed correctly. And then you can see in here when we concatenate the example in numpy, it takes the two different arrays that we set up in there and it combines the hello with the ABC and the hi with XYZ. And if we can also do something like print, let's do np character dot multiply. So there's a lot of different functions in here. Again, you can look these up. It's probably good to look them all up and see what they are, but it's good to also just see them in action. Now let's do hello space, comma, 3, and we'll run this one and run that without the error. And you'll see it does hello, hello, hello. So we multiplied it by 3. And we can also, and let's just take this whole thing here instead of retyping it. And we can do character center. So instead of multiply, let's do center. And over here, keep our hello going. Take the space out of there. And let's do center at 20. And fill character equals, we'll fill it with dashes. So if we run this, you can see it prints out the hello with dashes on each side. And we keep going with that. We can also, in addition to doing the fill function, we can play with capitalize, we can title, we can do lowercase, we can do uppercase, we can split, split line, strip, join. These are all the most common ones. And let's go ahead and just look at those and see what those look like, each one of them. Here we're going to do the hello world, all-time favorite of mine. I always like to say hello universe. And you can see here we did a capital H with the world, but so we want to capitalize. So capitalize is the first one in the array. So we get hello world on there. And we can also take this and instead of capitalizing, another feature in here is title. And let's just change this to how are we doing? How are you doing? Instead of we, we'll do you. And let's run that. And you can see here, because we created it as a title, it capitalizes the first letter in each word. And in this one, we're going to do character lower. Two different examples here. We have an array. We have hello world all capitalized, and we have just hello. And you can see that one is an array and one is just a string. If we run that, you get an array with hello world lowercase and hello lowercase. And if we're going to do it that way, we can also do it the opposite way. There's also upper. And let's paste those in there. And you can see here we have character.upper opposite there, python.data, and we'll do Python is easy. Hopefully you're starting to get the picture that most of the Python and the scripting is very simple. It's when you put the bigger picture together and starts building these puzzles and somebody asks you, hey, I need the first letter capitalized, unless it's the title, and then you start realizing that this can get really complicated. So numpy just makes it simple, and we like that. And so in this case we did Python data, it's all uppercase, Python is easy, like shouting in your messenger, Python is easy. And then if you're ever processing text and tokenizing it, a lot of times the first thing you do is we just split the text, and we're just going to run this np.character.split, are you coming to the party? If we do that, it returns an array of each of the individual words. Are you coming to the party, splitting it by the spaces? And then if you're going to split it by spaces, we also need to know how to split it by lines. And just like we have the basic split command, we also have split lines. Hello, and you'll see here the scoop in for our new line. And when we run that, if you're following the split part with the words, you should see hello, how are you doing? The two different lines are now split apart. And let's just review 3 more before we wrap this up. Commonly used string variable manipulations. We have strip, and in this case we have Nina, admin, Anita, and we're going to strip A off of there. And let's see what that looks like. And then you end up with nin, demin, nate. It basically takes up all leading and trailing letters. In this case we're looking for A. More common would be a space in there, but it might also be punctuation or anything like that that you need to remove from your letters and words. And if we're going to strip and clean data, we also need to be able to reformat it or join it together. So you see here we have a character join. We'll go ahead and run this. And it has on the first one, it splits each of the letters up by the colon and the second one by the dash. And you can see how this is really useful if you're processing, in this case, a date. We have day, month, year, year, month, date. Very common things to have to always switch around and manipulate depending on what they're going into and what you're working with. And finally, let's look at one last character string. We're going to do replace. If you're doing misinformation, this is good, pulling news articles and replacing is and what. In this case, we're just doing he is a good dancer. We're going to replace is with was. And you can see here, he was a good dancer. Hopefully that's not because he had a bad fall. He just was from 1920s and has gotten old. So there we go. We've covered a lot of the basics in NumPy as far as creating an array. Very important stuff here when you're feeding it in. How do we know the shape of it, the size of it? What happens when we convert it from a regular integer into a float value as far as how much space it takes? We saw that doubled it. Item size, you have your in dimensions, and probably the most used is shape. And we'll cover more on shape in part 2. So make sure you join us on part 2 because there's a lot of important things on shape in there and setting them up. We also saw that you can create a zeros-based array. You can create one with ones. If we do a range, you can see how it is a lot easier to use to create its own range, or a range as it is in NumPy. And you saw how easy it was to add two arrays. We saw that earlier, just plus sign. Then we got into doing strings and working with strings and how to concatenate. So if you have two different arrays of strings, you can bring them together. We also saw how you can fill, so you can add a nice headline, dash, dash, dash. We saw about capitalize the first letter. We saw about turning it into a title, so all the first letters are capitalized. Doing lowercase on all the letters, upper for all the letters, just lower and upper, nice abbreviation. We also covered how to split the character set, how to strip it. So if you want to strip all the A's out from leading A's and ending A's or spaces, you can do that very easily. Also, how to join the data sets. So here's a character join option for your strings. And finally, we did the character replace. Now let's go ahead and dive in there since we're going right into part 2, which is getting some coding going under our belt. And here in our Jupyter notebook, we can go under New and create a new folder, Python 3. I think I forgot to do this last time, but we could just do the Control++, which in any browser enlarges a page, makes it a lot easier to see. Always a nice feature. Another beautiful benefit of using Jupyter Notebook. And let me go ahead and show you a neat thing we can do in Jupyter. This is nice if you're working with people and you're doing this as a demo on a large screen. I'm going to do the hashtag or pound symbol array manipulation, kind of a title of what we're working on. And then I'm going to call this cell type markdown as opposed to code. And you'll see it highlights it here, and then if I run it, it just turns it into array manipulation. And then we're specifically going to be working on array manipulation, changing shape to start with. And we'll go ahead and mark this cell also a markdown, so it has a nice little look there. And then it comes up, and you can see it, just like I said, it just highlights it and makes it in bold print, just making it easier to read. Not a Python thing, but a Jupyter thing that's good to know about, especially if you're working with the shareholders, since they're investing money in you. Of course, the first thing we want to do is import. We're going to import NumPy as in P, and that should be standard by now. By now, you start a Python program, you're doing some data science. NumPy is just something you bring in there. And let's go ahead and create our array, and we're going to do that as the np.arange. Remember, that's 0. Well, we're going to do 0 to 9, and then we'll go print. Put a little title on the original array. We'll just print that array A. Remember from the first lesson, so we have our array which is 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's add a print space in between. Let's create a second array, B, but we want this to reshape array A. And what does that mean? And the command is simply reshape. And then we have 9 items in here, and this is so important right now. So be very aware, if I did some weird numbers in here, it's not going to work. And we want multiples of 9. We know that 3 times 3 is 9. So we're going to reshape our A array by 3 by 3. And then we're going to print, well, let's give it a title. Oops, I had too many brackets in there. Modified array. And then let's go ahead and print our B. And let's see what that looks like. And as we come down here, you can see we've taken this and it's gone from 0, 1, 2, 3, 4, 5, 6, 7, 8 to an array of arrays. And we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And so we split this into 3 by 3. And you can guess that if I tried to reshape this, let's just do a 5 by 3, which is 15, that's going to give me an error. So it's not going to work. You're not going to be able to reshape something unless the shape, all the data in there matches correctly. So we can take this flat 9, and we call it a flat because it's just a single array. And we can reshape it into a 3 by 3 array. And first you might think matrices, which this is used for that, definitely. I use it a lot in graphing because it'll come in that I have an array that's xy, comma xy1, y1, comma x2, y2. And so the shape of it might be 2 by the length of the number of points. And I need to separate that into x flat array and a y flat array. And you can see this can be very easy to reshape the array doing that. And we can of course go back. We can do b, do a print, and we'll do b dot flatten. Remember I said it's called a flatten array? And if we run that, you'll see it just goes back to the original one. It takes this 0, 1, 2, 3, 4, 5, 6, 7, 8 and flattens it back to a single array. And then one other feature to be aware of is if we flatten it, one of the commands we can put in there is order. Let me just go ahead and do that. Order equals F. Strangely enough, F stands for Fortran. The whole Fortran days, I remember actually studying Fortran programming language. In this case, you'll see that it uses the first, like 036 is the order. So instead of flattening it like we had before, 0, 1, 2, 3, 4, 5, 6, 7, 8, it now does 0, 3, 6, 1, 4, 7, 2, 5, 8. And if you go to the numpy array page, you can see here that they have the flatten. I just open up the numpy ND array flatten setup to look it up. And they have 3 different options. They have C, F, and A. And it's whether to flatten in C, which was based on how the C code works for flattening, originally worked, which is row major. Fortran, which is column major, or preserve the column Fortran ordering from A. So whatever it was in, the default is the C version. So the default that you saw, you could put order equals C and it'd have the same effect as we saw there before. You could even do order equals A. That would also have the same effect because that's the default. So really the only other thing you really should change on here is to change it to C if you need it. And you can see right here, or F, I mean, not C. The only thing you really want to change it to is to your F for the Fortran order, which then does it by column versus by row. And let's look at, here we go, reshape. So let's create a range of 12, and let's reshape it. And we'll do 4, 3 for this one. And remember this is numpy. I forgot the np there. np.arange. And we can type in just A for print, or you can do full print A. And of course the Jupyter Notebook even have a little extra print at the beginning. If we run this, we'll see we create a nice array of 0, 1, 2. It's reshaped it. So we have 4 rows and 3 columns, or you could call that 3 columns and 4 rows. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But this one is so important. We'll do np transpose A. And let's go ahead and run that. And it helps if I get all the S's in there and don't leave an S out. And you'll see here we've taken our array. If you remember correctly, we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we've swapped it. So we've gone from a 3 by 4 or a 4 by 3 to a 3 by 4. And this really helps if you're looking at like a huge number of rows and the data all comes in. Like let's say this is your features in row 1, your features in row 2, and this is X, Y, Z. Well, when you go to plot it, you send it all of X in one array, all of Y in one array, and all of Z in another array. And so it's really important that we can transpose this rather quickly. This is kind of a fun thing. I can highlight it and do brackets around it. And if you remember correctly, because we're in Jupyter, it doesn't matter where we do the print or not. It'll automatically print it for us. And you see if I hit the run button, it comes up at the same exact thing. And let's play with the reshape. And you know what, let's zoom this up a little bit here. Make that even bigger so you can really see what's going on. And let's play with the reshape just a little bit more. We'll do b equals np.arange. Let's do 8. And reshape, we'll do 2, 4. Let's go ahead and print B and then run that. And you'll see we have now the 2 rows. This is a bit more like, say we have 4, maybe 2 rows of 4 things. So this might be all of our X components and our Y components. So we can switch it back and forth real easy. Important to note here, whether we do 2, 4, or in the case of 4, 3, this has 12 elements. And so however you split it up, it's got to equal 12. So 4 times 3 equals 12. That's pretty straightforward. Same thing down here. 2 times 4 equals 8. If I change this, and let's say I do 2, 3, let's just run that in, and you'll find we get an error because you can't split 8 up into 2 rows by 3. You have to pick something that it can split up and arrange it in. So let's go ahead and run that. And just for fun, let's go reshape our B again, if I can type. Reshape our B again. And what else goes into 8? Well, we could do 2 by 2 by 2. So we can take this out to 3 different dimensions. And then if we, because this is going to come out as a variable, we can just go ahead and run it. And it'll print it. We could also do a print statement on there, just like we did before. And you'll see we have 2 different groups of 2 variables of 2 different dimensions. So 2 by 2 by 2. And let's go ahead and assign this to a variable. C equals B reshape. And let's do something a little different. Let's roll the axes. Roll axes. And we'll take our C and do 2, 1. And if we go ahead and run this, it's going to print that out. Whoops. Hit a wrong button there. Let's do that one again. And you roll the axis, and you can see that we now have, instead of 0, 1, 2, 3, 4, 5, 6, 7, we now have the 0, 2, 1, 3, 4, 6, 5, 7. So what's going on here? We're taking and we're rolling the numbers around, and let's just simplify this. We'll just do it with C, 1 and run that. And so if we roll a single axis, you got 0, 1, and then it rolled the 4, 5 up, and then we have 2, 3, 6, 7. And if we do 2, let me see what happens there. And this is one of those things you really have to play with and start feeling what it's doing. We've now taken 0, 2, 4, 6, 1, 3, 5, 7. So you can see we've now rolled by 2 digits. Instead of rolling the 1 setup, we now rolled 2 digits up there. And so if we go back and we do the 1, so we've rolled it up, 0, 1, 4, 5. And then we're going to take the 2 in there. And we've rolled the 0, 1, 2, 3, 4, 5, and 6, 7. So we start rolling these things around on here. There's a lot of different things you can do on this. But it's another way to manipulate the numbers on your numpy. And finally, let's go ahead and swap axes. We'll do C. And let's just go ahead and run that. It's going to give me an error on there. That's because it requires multiple arguments. Left out the arguments. So now we can swap them. We get the 0, 2, 1, 3, 4, 6, 5, 7. So you can see everything's been swapped around. So next thing we want to go over is we want to go over numpy arithmetic operations. How can we take these and use these? Let me just go ahead and put this cell as a markdown. There we go. We'll run that so it has a nice thing. All right, nice title on there. That's always helpful. And let's start by creating 2 arrays. We'll do A is an NP range, A range 9. And let's reshape this 3 by 3. So by now you should be seeing this reshape stuff, and this should all look pretty familiar. We have our 0, 1, 2, 3, 4, 5, 6, 7, 8 on there. And let's create a second one, B. And this time, instead of doing A range, let's do NP array. We'll just create a straight up array. And we'll do an array of 3 objects. So it's going to be 3 by 1. And if we go ahead and print B out, we run that. This is actually pretty common to have something like this, where you have a 3 by whatever it is and a 3 by 3 array. When you're doing your math, you kind of have that kind of setup on there. And what we can do is we can go np.add AB. Don't forget, we can always put a print statement on there. So if we add it, you'll see that it just comes in there and it goes, okay, we're adding 10 to everything. And we could actually do something more, make it more interesting. 10, 11, 12. So let's change B's, now 10, 11, 12, and let's run that. And you can see that we have 10, and then you had 1 plus 11 is 12, 2 plus 12 is 14. 13, so 10 plus 3 is 13, 11 plus 4 is 15, and 12 plus 5 is 17, and so on. We'll put this back, since that's how the original setup was. Let's do 10 by 10 by 10, and run that, and get the original answer. And if you're going to add them together, we need to go ahead and subtract A, B, and we run that. We get minus 10, minus 9, minus 8, just like you would expect. So we have our subtraction. 0 minus 10 is minus 10, and so on. And if you're going to add and subtract, you can guess what the next one is. We're going to multiply. And we'll multiply AB. And this should be pretty straightforward. You should expect this. If we multiply 10 times 0, we got 0. 10 times 10 is 10, and so on. And finally, if you're going to multiply, what's the last one we got is divide. What happens when we do divide A by B? And we run this. And we're going to get 0. And this is 0 divided by 10 is 0, 1 divided by 10 is 0.1, 2 divided by 10 is 0.2, and so on and so on. So the math is pretty straightforward. It just makes it very easy to do the whole setup. And again, if we went this, and let's say, let's change this up here. Instead of 10, we do 100. And make this 1,000. There we go. And if we run that, and then we do the add, you can see we got 10 plus 100 plus 1,000. Same thing with the subtract. Same thing with the multiply. And then you can also see the same thing here with the divide. So a lot of control there with your array and your math. Again, let's set this back to 10. Oops, it's right up here, wrong section. There we go, 10. And we'll just go ahead and run these and get back to where we were. And this brings us to our next section, which is slicing. And let's put in our, we'll just make this a cell type, markdown. And then we run that. Of course, it gives us a nice looking slicing there. And the slicing means we're just going to take sections of the array. So let's create an array np arange. Let's just do 20. And if you remember, if we do A, we have a 0 to 19. And then we can do A, and remember we can always print these. This can always be put in a print, but because I'm in Jupyter, if you're doing a demo in Jupyter, it's just so great that you have all these controls on here. So we can slice 4 on, and this should look familiar because this is the same as a Python and a lot of other different scripting languages. If we do 4, it goes 0, 1, 2, 3, that's the first 4 in the thing, and it skips some and starts with this one. The first 4 are skipped, and then from there on. You can also do the opposite and go till the 4th one. If we run that, we get 0, 1, 2, 3. Quite the opposite on there. We can do a single item, so we can pick object number 5 on the list, run that, and 5 happens to be 5, because that's the order they're in. And then this one's interesting, because I can do s equals slice, and let's create a slice here, and let's do 2, 9, let's leave a 2 on there. So we'll create an s slice on here. And then if we take our array and we do an array of s, we're taking our slice in there, and let's go ahead and run that. And let's take a look and see what it generated here. First off, we started with 2, so we have 2 at the beginning. We're going to end at 9, which happens to be 8, so it stops before the 9. Remember when we're doing arrays in Python. And then we step 2, so 2, 4, 6, 8. We could do this as 3. Let me run that, and you can see how that changes, 2, 5, 8. And we could do this as, let's leave this at 3, and if we change this to 10, oops, let's make it 12, there we go. And we run that, we have 2, 5, 8, 11. So that's pretty straightforward. It's a very nice feature to have on here where you can slice it and take different parts of the series right out of the middle. So now that we've access to different pieces of our array, let's get into iteration. And this is interesting because my sister, who runs a college data science division, the first question she asks is, how do you go through data? And she's asking, do you know how to iterate through data? Do you know how to do a basic for loop? Do you know how to go through each piece of the data? And in numpy, they have some cool controls for that. So put this as a markdown. There we go, and run it. And it's called the nd-iter. I'm not sure what the nd stands for, but nd-iter for iterator. So before we do that, though, let's create an array or something we can actually iterate through. We'll call it A equals NP arange. Let's do something a little funny here, or funky. And we'll do 0, 45, 5. I'm not sure why the guys in the back picked this particular one, but it's kind of a fun one. And if I run that, we do this, you can see we get 0, 5, 10, 15, 20, 25, 30, 35, 40. That's what this array looks like. And that's just from our slice. This is just a slice. That's all that is we created a slice of 0 to 45, step 5. And so we can do with this, we can also do A equals reshape. Let's go ahead and take and reshape this. And since there's 9 variables in there, we'll do reshape it 3 by 3. So if we run that, whoops, missed something there. That is the A. That really helps. So if we do the A reshape, and we'll go ahead and print that out. We get 0, 5, 10, 15, 20, 25, 30, 35, 40. And then we simply do 4x in our numpy indicator of A colon, and we'll just go ahead and print x. And let's see what happens here when we run through this and we print each one of those. It goes all the way through the whole array, so it's the same thing we just saw before. We got 0, 5, 10, 15, 20, 25, 30, 35, 40. So it prints out each object in the array. So you can go through and view each one of these. And certainly if you remember, you could also flatten the array and just do for A and that also and get the same result. There's a lot of ways to do this, but this is the proper way with the ND iterator because it'll minimize the amount of resources needed to go through each of the different objects in the numpy array. And hopefully you asked this question when I just did that. And the question is, how can I change this instead of doing each object? So first of all, let's go ahead and take my cell type, and we're going to mark that down and run it. And so we're going to work on iteration order C style and F style. Remember C because it came from the C programming, and F because it came from the old Fortran programming. So let's give us a reminder. We'll do a print A, and we'll do 4xn np iterate A. But we also want to do this in a specific order. And you know what? I'm a really lazy typer, so let's go back up here. This is the ND iterator. I knew I was missing the ND part of A. And let's do order equals C. We'll print X on there. And let's do that again. And this time order equals F. There we go. Order equals F. And let's go ahead and run this and see what happens here. And the first thing you're going to notice, our original array, 0, 5, 10, 15, 20, 25, 30, 35, 40. When we do order C, that's the default. 0, 5, 10, 15, 20, and so on. And then when you come down here, you'll see F, order F, is 0, 15, 30. So it takes the first digit of each of the subarrays, or the second dimension, and then it goes into the second one, 5, 20, 35, 10, 25, 40. So slightly different order for iterating through it if you need to do that. So we've covered reshaping, we've covered math, we've covered iteration, we've covered a number of things. The next section we want to go ahead and go over is going to be joining arrays. So we need to bring them together. Let me go ahead and take the cell and make it a markdown. Cell type markdown. There we go. And run that. So let's work on joining arrays so we can bring them together and what different options we have. And let's do, we'll do an NP array 1, 2, 3, 4. We'll go ahead and print. Let's do, oops, first. And these arrays aren't that big, so let's just go ahead and keep it all on one line, A. So if we run this, first array 1, 2, 3, 4. Whoops, I forgot that it automatically wraps it when you do it this way. So we'll go ahead and keep it separate and print A. There we go. And let's go ahead and do a B. And we'll do 5, 6, 7, 8. And notice I'm keeping the same shape on these two arrays. Depending on what you're doing, those shapes have to match. And let's go ahead and print second array. Do a print B. We'll go ahead and run that. Oops. Missed something up there. Let me fix that real quick. when I was reformatting it to go on separate lines. I messed that up. There we go, run. All right, so we have first array 1, 2, 3, 4, second array 5, 6, 7, 8. And we'll put a carried return on there. And the keyword we use is concatenate. And if you're familiar with Linux, it usually means you're adding it to the end on there. And we're going to do what they call along axis 0. So we have concatenate AB along axis 0. Let's go ahead and run that and see what that looks like. And so we have 1, 2, 3, 4, 5, 6, 7, 8. So now we have an array that is 4 by 2. It has a nice shape of 4 by 2 on here. And if we're going to do it along the axis 0, you should guess what the next one is. We're going to do it along the 1 axis. And let's see how those differ from each other. Let's just go ahead and run that. And again, all we're doing is adding in the axis equals 1. So we have our concatenate, we have AB, and then axis 1. Remember a couple things. One, these are the same shape. So we have a 2 by 2, same dimensions going in there. You're going to get an error if you're concatenating and they're not. If you have something that instead of 1, 2 is 1, 2, 3, 4, 5, 6 with a 5, 6, 7, 8. They'll give you an error on there. In fact, let's take a look and see what happens when we do that. Let me just take this. 1, 2, 3, 3, 4, 5. And let's run that. And if we come down here, oh, we got there. It says all the input array dimensions except for the concatenation axes M must match exactly. So it'll let you know if you mess up. That's always a good thing. Let's go ahead and take this back here, and let's go ahead and run that. And so we have our 0 axes, which is 1, 2, 3, 4, 5, 6, 7, 8. And we bring them together. And you'll see a very different setup here when we do it along the axis 1. We end up with, instead of 4 by 2, we end up with a 2 by 4. 1, 2, 5, 6, 3, 4, 7, 8. And that's just changing which axes we're going to go ahead and concatenate on. What I find is when you're talking about the concatenate or the joining arrays, you really got to play with these for a while to make sure you understand what you mean by the axes. It looks very intuitive when you're looking at it. Axis 0, 1, 2, 3, 4, 5, 6, 7, 8. Axis 1 is then splitting it a different way, 1, 2, 5, 6, 3, 4, 7, 8. When you're actually using real data, you start to really get a feel for what this means and what this does. So if we're going to do that, let's go ahead and look at splitting the array. And do that under Markdown and run it. There we go. So you have a nice little title there. And we'll go ahead and create an array of 9. Let's do NP split. We'll do A, and we're going to split it by 3. Let's just see what that looks like. So if we split it, we get an array 0, 1, 2, 3, 4, 5. We get 3 separate arrays on here. Now remember, we're looking at, let me just print A up here. So we're looking at 0, 1, 2, 3, 4, 5, 6, 7, 8, and then we can split it into 3 separate arrays. And let's take this, we're going to do this right down here, just move the A split down here. Instead of the 3, let's do 4, 5, and put that in brackets. And so when we do it this way, we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And that's kind of interesting. I wasn't sure what to expect on that, but we get, when you split an A by 4, 5, you get a totally different setup on here as far as the way it split the array. And to understand how this works, I'm going to change the 5 to a 7. And this will visually make this a little bit more clear. So we had 4 and 5, it went 0, 1, 2, 3, 4, 5, 6, 7, 8. And you see the markers 4 and 5. When we do 4 and 7, I get 0, 1, 2, 3, 4, 5, 6, 7, 8. And so what you're looking at here is the first markers, this is going to go to 4. So there's our first split at the 4, the marker at 4, and then the second split is going to be at position 7. And this is the same thing here, 4, position 5. That's why we're splitting it in those 2 sections. We could also do it 7. Let's just see what that looks like. Run. And you can see I now have 0, 1, 2, 3, 4, 5, 6, 7, 8. So we can split it in all kinds of different arrays and create a different set of multiple arrays on here and split it all kinds of different ways. And before we get into the graphs and other miscellaneous stuff, let's go ahead and look at resizing the array. We'll go ahead and take this cell and set the cell as a markdown and run it. Give us a nice title there. And we'll do an array, an NP array of 1, 2, 3, and 4, 5, 6 here. And let's go ahead and just print. Let's go print a dot shape. And we'll go ahead and run that. Whoops, hit a wrong button there. Hit the comma instead of the dot. So we have a shape of 2, 3 here. And this is important to note because when we start resizing it, it's going to mess with different aspects of the shape. And so we'll go ahead and do a print. Scoop in for a blank line. There we go. And let's do b equals np.resize. We're going to resize a, and let's resize it with 3 by 2. And then we'll just go ahead and print b and print b period shape, not a comma. We'll run that. Oops, forgot the quotation marks around the end. We'll go ahead and run that, and let's just see what that looks like. So we have 1, 2, 3, 4, 5, 6, our original array, with a shape of 2, 3. And then we want to go ahead and resize it by 3, 2. And we end up with 1, 2, 3, 4, 5, 6, and we end up with the shape of 3, 2. That shouldn't be too much of a surprise. You know, we got 6 elements in there. We can resize it by 2, 3 was the original one, and then we're actually just reshaping it is how that kind of comes out as when you resize it like that. But what happens if we do something a little different? And let's go ahead and just take this whole thing and copy it down here so we can see what that looks like. And instead of doing 3, 2, remember last time I did the, to reshape it, I messed with the numbers and it gave me an error. Well, when you resize it, you don't have to match the numbers. They don't have to be the same dimensions. So we can, instead of going from a 2, 3 to a 3, 2, we can resize it to a 3, 3. So let's take a look and see how it handles that. And when we come down here to 3, 3, we end up with 1, 2, 3, 4, 5, 6, and it repeats 1, 2, 3. So it actually takes the data and just adds a whole other block in there based on the original data and repeating it. All right, now at this point, we've been looking at tons of numbers and moving stuff around. What we want to go ahead and do is get a little visual here, because that certainly you can picture all the different numbers on there. But let's look at histogram. Let's put this into a histogram. Let me go ahead and run that. And to do that, we're going to use the matplot library. So from matplot library, we're going to import pyplot as PLT. And that's usually the notation you see for pyplot. So if you ever see PLT in a code, it's probably pyplot in the matplot library. And then the guys in the back did a nice job, and gals too, guys and gals back there. Our team over at Simplilearn put together a nice array for me, 20, 87, 4, 40, 53, with a bunch of numbers. That way we had something to play with. And what we want to do is we want to do plot the histogram. Now remember, a histogram says how many times different numbers come in. And then we're going to put them in bins. And we have bins 0 to 20 to 40 to 60 to 80 to 100. You might, in here with the matplot library, they call them bins. You might hear the term buckets, where they put them in buckets. That's a really common term. And then we want to give it a title. So the way it works is you do your plt.hist for histogram, your plt title, and your plt show. And we're doing just a single array in here in the numpy array of A. And let's go ahead and run this piece of code. Take it a moment to come out there. So it's figure size, so it's generating the graph. And you can see we have, and let's just take a look at this. Let me go down a size. There we go. Okay, so now we can see what we're taking a look at here. So between 0 and 20, we have 3 values. So we have a 20 here, we have a 4, and a 11, and a 15. 0, 1, 2, 3. It's actually 4 values, but they start at 0. So remember, we always count from 0 up. And from 20 to 40, we got 20. So it's 1, 42, 3, 4, 5, 6. And so you can see in the histogram, it shows that the most common numbers coming up is going to be between the 40 and 60 range, least common between the 80 and 100. This looks like an age demographics, is what this looks like to me. And you can see where they would have put it in the buckets of different age groups, which would be a nice way of looking at this. Histograms are so important and so powerful when you're doing demos and explaining your data. So being able to quickly put a histogram up that shows what's common and how it's trending is really important. And using that with a numpy is really easy. And you know what, let's take the same data, and I want to show you why we do bins, or why we have buckets of data. I'm used to calling it buckets. Why we have bins. Let's do it instead of by 20, let's do it by tens and see what happens. And what happens when you do it by tens is you miss out on you can see a nice curve here on the first one, and on the second one it looks like a ladder going up and a plummet, a ladder going up and a plummet, and a ladder going down. So the first would be more indicative of an age group, and the second one would be what you would get if you divided incorrectly. You wouldn't see the natural trend of, I don't know what this would be, maybe how much food they eat. Hopefully not, because I'm in 50, so I'm right in the middle there, which means I eat a ton of food compared to everybody else. But it's some kind of demographic. Maybe it's mental, maybe it's knowledge, because we hit a certain point and then we start losing, our marbles start leaking out or something. So you start off knowing something, and then as you get older you grow more. But you can see here we lose that. You lose that continuity in the thing if you split the histogram into too many bins or too many buckets. And if you actually plotted this by the individual numbers, it would just be a bunch of dots on the graph and wouldn't mean a whole lot. And we've looked at graphs. There turns out are a ton of useful functions in NumPy. I'm sure there's even new ones that aren't going to be in here. But let's just cover some important ones you really need to know about if you're using the NumPy framework. One of them is linspace function. This is generating data. So you have a linspace, we have 1, 3, 10, and when we do that, we end up with 10 numbers. So if you count them, there's 10 numbers. They're between 1 and 3, and they're evenly spaced. We get 1, 1.222. But these are all, there's a total of 10 here, and it's right between the 1 and 3 range. That can be, there's a lot of uses for that, but they're probably more obscure than a lot of the other common NumPy arrays set up. Then a real common one is to do summation. So we'll do summation where you do, in this case we create a NumPy array of two different arrays, 1, 2, 3, or two different dimensions, 1, 2, 3, 3, 4, 5. And we're going to sum them up under axes 0, which is your columns. And if you remember correctly, columns is the 1 plus 3, 2 plus 4, 3 plus 5, so we have 3 columns. And if we change this, we'll just flip this to 1. We get 2 numbers. So we get 1, 2, 3 all added together, which equals 6, and 3 plus 4 plus 5, which equals 12. We'll set this back to 0. There we go, since we're looking at axis 0. And these probably could have been, some of these could be underneath our math section. Square root and standard deviation, two very important tools we use throughout the machine learning process and data science. And simply we take the NP array, we have again the 1, 2, 3, 4, 5, 6, 3, 4, 5. I don't know why I need to keep recreating it, probably could have just kept it. But we can take the square root of A. So it goes through and it takes the square root of all the different terms in A. And we can also take the standard deviation, how much they deviate in value on there. And there's a rabble function. We can run that. And NP array is x, we're going to do x equals, hey, we changed it from A to x. X equals rabble. And this sets it up as columns. So we have 1, 2, 3, 4, 5. This is all columns on here. Very similar to the flatten function. So they kind of look almost identical. But we also have the option of doing a rabble by column. And then another one is log. So you can do mathematical log on your array. In this case, we have 1, 2, 3. And we'll find the log base 10 for each of those 3 numbers. And there's a couple of them. You can't just do any number here after log, but there is also log base 2. Log base 10 is pretty commonly used on here. We'll go and run that. There we go. Before we go, let's have a little fun. Let's do a little practice session here on some more challenging questions. So you start to think how this stuff fits together. Right now we just looked at all the basics and all the basic tools you have. So let's do some NumPy practice examples. And let's start by figuring out how do you plot, say, a sine wave in NumPy. What would that look like? And so in this project we wouldn't have to do this because I've already run these, but we'd want to go ahead and import our numpy as np and import our matplot library pyplot as plt. So we get our tools going here. And then we'll break it into two sections because we need our x, y coordinates in here. So first off, let's create our x coordinates. And our x coordinates we're going to set to an a range. And we want this a range, since we're doing sine and cosine, it's going to be between 0 and 0.1. And then we use our np, and we actually can look up numpy stores pi. So you have the option of just pulling pi in there directly from numpy. It has a few other variables that it stores in there that you can pull from there. But we have numpy pi, and we generate a nice range here. And let's go ahead and run this. And just out of curiosity, let's see what x looks like. I always like to do that. So we have 0.1, 0.2, 0.3, 0.4. So we're going 0 to, in this case, 9.4, 3 times numpy pi. Remember, pi is like 3 point something, something, something. So that makes sense. It should be about 9. And we're doing intervals of 0.1. So we create a nice range of data. And then we need to create our y variable. And so y is going to simply equal np, or numpy.sign of x. And then once we have our x and y, and if we print, let's go ahead and just print y. See how that, we'll do this. Let's do this so it looks print x, print y. So we basically have two arrays of data. So we have like our x-axis and our y-axis going on there. And this is simply a plt.plot because we're going to plot the points. And we'll do x comma y. And then we want to actually see the graph, so we'll do plot.show. And we'll go ahead and run that. And you see we get a nice sine wave. And here's our numbers 0 through 9. And here's our sine value, which oscillates between -1 and 1 like we'd expect it to. Then for the next challenge, let's create a 6x6 two-dimensional array and let 1 and 0 be placed alternatively across the diagonals. Oh, that's a little confusing. So let's think about that. We're going to create a 6x6 two-dimensional, so the shape is 6x6 two-dimensional array, and let 1 and 0 be placed alternatively across the diagonals. Now, if you remember from lesson 1, we can fill a whole numpy array with zeros or ones or whatever. So we're going to do np, create a numpy zeros, and we're going to do a 6x6, and we'll go ahead and make sure it knows it's an integer, even though it's usually the default. And just real quick, let's take a look and see what that looks like. So if I run this, you can see I get 6x6 grid, so 6x6, 0, 0, 0, 0, 0. Now, if I understand this correctly, when they say 1s and 0 placed alternatively across the diagonals, they want the center diagonal, maybe that's going to stay 0 all the way down. And then the next diagonal will be 1s all the way across diagonally. And then the next one 0s, the next one 1s, and the next one 0s, and so on. Hopefully you can see my mouse lit up there and highlighting it. So let's take a little piece of code here. And we'll do z1 colon colon 2 comma colon colon 2 equals 1. And wow, that's a mouthful right there. So let's go ahead and run this and see what that's doing. And so what we're doing is we're saying, hey, let's look at, in this case, row 1. There's 1. And then we're going to go every other row 2. So we're going to skip a row. So skip here, skip here, skip here. So we're going down this way. And we're going every other row going this way. It's hard to highlight columns. So you can see right here where we're not touching each row, is like this row right here is not being touched. Okay, so we're going to start with row 1, and then we're going to skip a row and another one, and so we're going every 2 rows. And then in every 2 rows, we're looking at every 2, starting with the beginning. That's what this thing blank means. So we're going to start with the beginning, and we're going to look at all of them, but we're going to skip every 2. So starting with row 1, we look at all the rows, but we do it by 2 steps. So we go 1, skip 1, 1, skip 1, 1, skip 1, 1. If you left this out, it'd do every one. This would just be 1s. In fact, let's see what this looks like. If I go like this and run it, you can see that I just get 1s. So this notation allows us to go down each row by row, and we're going to do every other row set up on there. And so if we're going to start with row 1, we also, Control Z, try that. There we go. We'll start with row 0. Again, we're going to go each row, step 2. So we'll start with row 0, and we'll go every other row. And this time we'll start with 1, column 1. And again, we go every other one going down. That's what that step 2 is. Skipping every other one. We're going to set that equal to 1. So let's see what that looks like. And you can see here we get our answer. We get 0, 1, 0, 0. But it has the 1s going in diagonals on every other diagonal and 0 on every other one. A little bit of a brain teaser, that one, trying to get that one to work out. So you can see how you can arrange your rows, and here's your step and your different access on there. And then the next one is find the total number and locations of missing values in the array. The first challenge is to create some missing numbers. So let's create our array Z. We're going to do numpy.random.rand 10, 10. And before we do the second part, let me just take this second part out. And let's just see what that looks like. So let's run that. And there we go. So we have a 10 by 10 random array. It randomly is picking out numbers. And next, we want to go ahead and take our random integer size equals 5. And then we're going to do a random 10 size equals 5. So in the Z, we're going to select a number of random spaces here and set them equal to null value. And let's go ahead and run that so you can see what that looks like. And if we look at the array, we've created 1, 2, 3, 4. There should be a fifth one in here. My eyes may be failing me. So we've created a series of, because 0 to 5, 0, 1, 2, 3, 4. So we got 5, there are different null values on here. And this is kind of a neat notation to notice that we can generate random integers, size equals 5. So this generates 5 by 5 miniature grid inside of this to tell it where to put the nands at. So that's kind of a cool little thing you can do. And then we want to look up and see how many null values are in there. And this is simply just np is nan of z. Simple. So if it is nan, then we want to sum it up. So we're going to sum up all of the different null values on there. Now let's do one more feature in here, which is really cool. Let's go ahead and print the indexes. So np argware np is nan of z. So we're going to create our own another np array. And let's run this, and we'll see here that it comes up with the 4 indexes. So we did count 4 of them up there. It tells you where they are, 1, 9, 2, 0, 4, 6, 5, 4. And then let's go ahead and run this again. Run, there we go. This time I got 5. That's what we get for random numbers. Another fun one that I always like to do is very similar, because we have np is nan z.sum. So we're summing the number of nands. And we can get the indexes, and you can reshape the indexes. But you can also just do, we'll do an INDS where np is nan of z. And let's just print, that. Print INDS. Let's see what that looks like. And it's very similar to we have 0, 1, 3, 0, 6, 3, 8, 6, 9, 3. But I've split it into 2 different arrays. So we have our x and our y kind of coordinates going there. And what I can now do is I can now do z INDS equals, and at this point you can also, instead of getting the sum, you can get the means or all the numbers and that kind of thing, or the average as it is. So that'd be one thing you could do, and you can pick out the average. That's very common in data science, to get the average and just use that for a value. But we'll go ahead and just set it to 0, and then let's go ahead and print our z and run that. And you can see when we come down here, we have wherever there was a null value, it is now 0. And you can set this to whatever you want. This is another way to replace data or help clean data up, depending on what it is you're doing. So, wow, we covered a lot of stuff. So quick rehash going over everything. We went into there, we looked at array manipulation, changing the shape, how to switch that around. We even had the flatten down there, which remember we have another command lower that's similar. We could change the order by F. Remember, F stands for Fortran, very strange connotation, but there's C and F. C is the standard. and F switches it to a different order. To be honest, I usually have to look it up because I almost never use F, but when you need it, you're like, oh my gosh, what was the other order? Just do a quick Google. So we talked about reshape, making sure that the dimensions are the same. You don't want to have like something that has 12 objects in it and reshape it to 11 and 5 because it doesn't work. It doesn't divide into 12. We can transpose, so we can switch them. So we can go from a 4x3 to a 3x4. Oops, I did that the other way around. 3x4 to 4x3. We covered reshaping the array. We did the roll the axes. You can do some weird things with swapping and rolling axes and transposing the numbers. We dug a little bit into the arithmetic. So we talked about adding, we talked about subtracting, multiplying, dividing. And at this point it's so important we just look up the numpy mathematics. And you can see here they have just about everything. Your trigonometry, your hyperbolic functions, rounding, sums, products, differences. There is all your different miscellaneous mathematical connotations. So, Google it, go to the main numpy page and look at the different setups you can do on there. So we covered that. And we did slicing, how to break it apart. We did iterating over the array. We covered joining arrays and how to concatenate. Remember, concatenate just means add on to it. So in this case, how are you adding B onto A is how you'd read that. From Linux, you should catch the concatenate because that's used regularly there. Splitting the array, we talked about how to split the array in different ways. So you can split it in array of arrays, all kinds of different ways to split the array up. How to resize it. And remember, resize does not have to have the same shape, but if you resize it, it will take the data and begin at the beginning and add new rows on if the size is bigger. If it's smaller, it truncates it. It just cuts the end off. We looked at how to do a histogram and how to plot that. We mentioned buckets or bins, as they call them in PyPlot. And then we covered a lot of other useful functions in NumPy. We talked about the linspace setup for doing numbers in a series, how to sum the axes up. Again, that's part of the mathematical formulas there that we looked at. There's a sum, there's also means and median. All of those you can compute in NumPy. And you can also do the square root and standard deviation. The ravel function, very similar to the flatten. To be honest, I almost always just use the flatten, but the ravel has its own kind of functionality that it does. And then we went into some NumPy practice examples. We challenged you to create a sine wave in NumPy and how to do that. We're kind of looking for that arange. Remember how we do the arange, and you can have your beginning value, your end value, which they did as 3 times pi, NumPy pi, and we're going to do intervals of 0.1. And then y just equals the NumPy sine of x. There's our math from the math page we were just looking at. Remember that? It's right at the top. And finally, we went down here. We had this kind of a little brain teaser, how to do diagonal zeros and ones, playing with the different connotations of the NumPy array. And then we did a random size, and we played a little bit with with the null values, playing with null values. If you're doing any data science, null values are like a headache. What do you do with them? Big sets of data, you get rid of them. Small sets of data, you have to factor something in there, like figure out the average or the median there, and then replace it with that. Pandas really is a core Python module you need for doing data science and data processing. There's so many other modules that come off of it. It actually sits kind of on NumPy, so if you've already had our NumPy array, hopefully you've already gone through the NumPy tutorial 1 and 2. So today we're going to cover what is Pandas. We'll discuss series. We'll discuss basic operations on series. And then we'll get into a data frame itself, basic operations on the data frame, file-related operations on a data frame, visualization, and then some practice examples. Roll up our sleeves and get some coding underneath there. And let's start with just some real general, what is Pandas? Pandas is a tool for data processing which helps in data analysis. It provides functions and methods to efficiently manipulate large data sets. Now, this is a step down from, say, using Spark or Hadoop in big data. So we're not talking about big data here, but we are talking about pandas, and there is some connections. There's like an interface going on with that, so there is availability, but you really should know your pandas, because if you're working in big data, you'll know there's data frames. Well, pandas is a data frame primarily. It has a couple different pieces we'll look at here. And if you've never worked with data frames before, a data frame is basically like an Excel spreadsheet. You have rows and columns. You can access your data either by the row or the column, and you have an index and different, that kind of setup. And we'll dig more into that as we get deeper into pandas. But think of it as like a giant Excel spreadsheet that's optimized to run on larger data on your computer. And then I said it that it's a data frame. So the data structures in pandas are series, one-dimensional arrays, and then we have data frame, two-dimensional array. And it really centers around the data frame. The series just happens to be part of that data frame. And here's a closer look at a pandas series. Series is a one-dimensional array with labels. It can contain any data type, including integers, strings, floats, Python objects, and more. So it's very diverse. If you remember from numpy we studied, they had to be all uniform. Not in pandas. In pandas we can do a lot more. And pandas actually kind of sits on numpy, so you really need to know both of those if you haven't done the numpy tutorials. And you can see here we have our index 1, 2, 3, 4, 5, and then our data A, B, C, D, and E. Very straightforward. It's just two columns, and we have a nice index label and a column label for the data. And then a data frame is a two-dimensional data structure with labels. We can use labels to locate data. And you can see here we had, if we go back one, we had our index 1, 2, 3, 4, 5. So in each one of these series, they would share the same index over there, the row index. So you have your row index df.index, and then you have a column index df.columns. And this would look, like I said, this would be really familiar if you've done any work with spreadsheets, Excel. So it kind of resembles that. This does make it a lot easier to manipulate data and add columns, delete columns, move them around. Same thing with the rows, so you have a lot of control over all of this. Now, we're of course going to do this in our Jupyter Notebook. You can use any of your Python editors, but I highly suggest if you haven't installed Jupyter and haven't worked with it, it is probably one of the best ways for easily displaying a project you're working on. I skip between a lot of different user interfaces or IDEs for editing my Python, and it's just simply jupyter.org, jupyter.org. And then I always let mine sit on Anaconda, anaconda.com, and just real quick we'll open that up for you. Oops, offline mode. Don't show me that again. But you can see here that I have different tools that I can actually install in my Anaconda, including the Jupyter Notebook, which comes by default. And then I have access to the environments. And again, that's anaconda.com, named after the very large, one of the world's largest snakes, and then Jupyter Notebook. In this case, jupyter.org. And when we're in I'm going to go in here to our Jupyter Notebook, and we're going to go ahead and just do new and a Python 3. And this will open up a Python 3 untitled folder. So diving right in, let's go ahead and give this a title, Pandas Tutorial. And we'll go up to cell, and we'll change the cell type to Markdown so it doesn't execute it as actual code. One of those wonderful tools when you have Jupyter Notebook so you can do demos with this. And let's go ahead and import Pandas, and usually people just call it PD. That has become such a standard in the industry. So we'll go ahead and run that. Now we have our Pandas has been imported into our Jupyter Notebook. And then, we can go ahead and let me do the Control Plus. Since it's Internet Explorer, I can enlarge it very easily so you have a nice pretty view. Whoops, too big. There we go. And whenever you're working with a new module, it's good to check your version of the module. In Pandas, you just use in this case, pd.__version__. That's actually pretty common in most of our Python modules. There's different ways to look up the version, but that's one of the more common ones. And we'll go ahead and run that. We get 0.23.4, and if we go to the Pandas site, we see 0.23.4 is the latest release. And of course, a reminder that if you're going to your environment, you need to install it. So you'll need to do pip install pandas if you're using the pip installer. We'll go and close out of that. And the first thing we want to do is we're going to work with series. A lot of the stuff you do in series you can then do on the whole data set. We need to do what? Create one. We need to manipulate it. Take pieces of it, so query it. Delete, so you can delete different parts of it. So we want to do all those things with the series. And we'll start with the series, and then almost all the code, in fact all the code does transfer right into the actual data table. So we go from a series of a single list of one column, and then we'll take that and we'll transfer that over to the whole table. And we'll start by creating, let's put a, there we go, creating a series from list. And let's just call this ARR equals, and we'll do 0, 1, 2, 3, 4. If you remember from our last one, we could easily do R equals range of 5, which would be 0 to 4. But we'll do R equals 0 to 4, and we'll call this S1, and we'll go PD, and series is capitalized. This one always throws me, is which letters do you capitalize on these modules? They're getting more and more uniform, but you got to watch that with Python. And we're just going to go ahead and do ARR. So we're just going to take this Python list and we're going to turn it into a series. And then because we're in Jupyter, we don't have to put the print statement. We can just put S1 and it'll print out this series for us. And let's go ahead and run that and take a look. And you'll see we have 2 rows of numbers. So the first one is the index. Now it automatically creates the index starting with 0 unless you tell it to do differently. So we get 0, index row 0 is 0, 1, 1, 2, 2, 3, 3, 4, 4. And because it's a series, it doesn't need a title for the column. There's only one column, so why title it? And this also lets you know that it's a data type of integer 64. So we print this out. This is our series, our basic series we've just created. And let's do a second series, PD, and we'll use the same data list. And let's go ahead and do order. We'll give it an order equals, let's do it this way. Let's go index equals order. And it helps if we actually give it an order. So we'll do order equals, and let's do 1, 2, 3, 4, 5. So instead of starting with 0, we're going to give it an order starting with 1. We're going to run that, and we'll go ahead and print it out down here, S2. And we'll see that we now have an index of 1, 2, 3, 4, 5, and that represents 0, 1, 2, 3, 4 in the series. And we're still data type integer 64. And very common as you're messing with numpy arrays is we can import our numpy as NP. Remember that from our numpy tutorials. We can go ahead and create a numpy out of random with the random numbers of 5. And let's just see what that n looks like, so we can see what our numpy looks like. So we have some nice random float values here, 2.33, so on. And that's from our last tutorial, the numpy tutorial 1 and 2. And instead of calling it order, let's call it index. And we're going to set our index equal to A, B, C, D, and E. I want to show you that the index doesn't have to be an integer, so it can be something very different here. And then let's go ahead and create our, we'll just use S2 again. And here's our NP for numpy, series, capital S, and N is our NP for numpy. PD for pandas, there we go, switching my anachronisms. So we have pd.series of n, and we want to do our index equals our index we just created. And then let's go ahead and see what that looks like. S2 to print it, and let's run that. And we can see here we have a nice series going on. A, B, C, D, and E for our indexes. So instead of it being 0, 1, 2, 3, or 4, we can make this index whatever we want. And you can see the numbers here going down that we randomly generated from the numpy array. So we used numpy to create our Pandas series right here. And so continuing on with creating our series, this one I use so often, we create a series from a dictionary. So we have our dictionary. In this case, we went ahead and did A of 1, B is 2, C of 3, D 4, E of 5. So each one of those is a key and then a value. And then we're going to use, let's use S3 equals PD for pandas, series, and then we want to go ahead and just do D in here. Print out S3 here, and let's go ahead and run this. And you can see we got A is 1, B is 2, C is 3, D is 4, E is 5. And it's still of integer 64 because the actual data is 1, 2, 3, 4, 5, and it's all integer 64, type 64. And the last thing we want to do in the creating section of our series is to go ahead and modify the index, because we're going to start modifying all this data. So let's start with modifying the index of the series. And if you remember, let's do a print this time, S1. I'll go ahead and run this. And the reason I did print is because it only prints out the last variable. So if I put S1 up here and we're going to do another variable back down lower, it won't print the first one, just the last one. And we're going to go ahead and take S1 the index, and we're just going to set it equal to a new index. And obviously, the number of objects in our index has to equal the number of objects in our data. And then because it's a last variable, we can go ahead and just do an S1. And let's run that, and you can see how we went from 0 to 0, 0, 1, 2, 3, 4 as our index. We've now altered it to A, B, C, D, and E. So this would be much more readable, or might be representational of a larger database you're working with. So cool tools. We've covered creating a database based on a basic array, Python array. We've showed you how to reset the index. Then we showed you how to use a numpy array. So you can put a numpy array in there. It's all the same, pd.series, a numpy array, and then we can set the index on there. And the same thing with the dictionary. So it's very versatile how it pulls in data. And you can pull in data from different sources and different setups and create a new series very easily in the Pandas. And then we looked on changing your index. So now we have a new index on here. And then we want to go ahead and do some selection. Let's do some basic slicing. Most common thing you'll probably do on here. And we'll just do S1. This notation should start to look really familiar. Again, this is going to put an output. So it doesn't change S1. This just selects it. So we might do A equals S1 and then print A. And you'll see that it just looks at the first three, 0, 1, 2. And we can do the same thing by not having the A in there. I'll go ahead and take that out. But it's just a reminder that it's not actually changing S1. It's just viewing S1. So simple slicing on here. And we can likewise do an append. Oops, before we do append, let's just do a quick kind of fun one. We'll do to -1. And you'll see it covers everything but the E. Of course, you can do -2 on this side. So another way to select it is to go how far from the end. And likewise, we can do a 2 here, a CDE to the end. So it starts at the second one. And another way we can do this is we can do a -2 over here. And that looks at just the last 2 in the slice. So you can see how easy it is to slice the data. And of course, there's no reason to do this, but you could select all of them if you wanted to view all of them on there. Oops, 32. There's not 32, so it's just going to show the first 3. There we go. And then we can also append. So I can take and, let's create another series and append one to it. And if you remember, we had S3. There's our S3. And we have our S1. We'll go ahead and do S1. And let's go ahead and do, let's call it S4 equals S1 append S3. So we're just going to combine those two into S4. And if we go ahead and print S4 on here, you'll now see that we have A, B, C, D, E, A, B, C, D, E, 0, 1, 2, 3, 1, 2, 3, 4, 5, because we started the data at 1. So very easy to append one series to the next. And if we're going to append one series to the next, we need to go ahead and drop or delete one. And drop is the key word for that. And let's just do E, or index E. And so if I run this, you'll see that it'll print it out, and A, B, C, D, there's no E. And remember, all these changes, if I type in S4 again, you'll see that S4 still has E in it. So this change does not affect the series unless you tell it to. So I'd have to do like S4 equals S4.drop E. And there's another way to do that, which we'll show you later on. Let me just cut this one out. There we go. All right, so we've covered all kinds of cool tools here. We have appending, we have slicing, we did all the creating stuff earlier. So you can see here on the setup how easy it is to manipulate the series. So next, what we want to get into is we want to get into operations that happen on the series. Let me go ahead and change this cell to Markdown. There we go, and run that. So series operations, what can we do with a series? And let's start by creating a couple arrays. We'll call it array 1, and we'll do 0 through 7, and array 2, 6 through 6, 7, 8, 9, 5. I don't know why we threw the 5 on the end. Let's go ahead and run those so those load up into Jupyter. And we'll do this a little backwards. We're going to do S5 equals a Pandas series of array 2. So I'm doing this in reverse. And then when we do S5, you'll see that we have 0 to 4. It automatically assigned the index. 6, 7, 8, 9, 5 for our series. And let's go ahead and do the same. And we'll call this S6. And we'll set this equal to PD series for our first array. And if we do an S6 down here to print it out, we'll see something similar. I got 0 through 6, 0, 1, 2, 3, 4, 5, 7 for the data. So those are two series we just created, series 6, 5, and 6. And one of the first things we can do is we can add one series to the next. So I can do s5.add s6. And let's see what that generates. And just a quick thing, if you've never used Pandas, what do you think is going to happen with the fact that this only has 5 different values in it, and this one has 7 values? So let's see what that does. And we end up with 6, 8, 10, 12, 9, and it goes, oh, I can't add this, there's nothing there. So it gives us a null return. Very different than the numpy that would have given you an error. This instead tells you there's no value here because we couldn't generate one. So we can easily add s5.add s6, and likewise we can do s5.sub for subtract s6, and we'll run that. And on the add, the subtract, and you guessed it, we're going to do multiply and divide next. Again, you can see there's the null values where it can't subtract the two because there's no values there to subtract. We can also do s5 multiply, MUL. They're all 3 letters on these. That's one of the ways to remember how they figured out the code for this. So remember, these are all 3 letters, mul. We'll go ahead and run this, and you can see how they're multiplied together. And then we can also do the s5 div, 3 letters again, s6, and run that. And you'll see here, this goes to infinity because we have 0 in the wrong position. So it actually gives you a whole different answer here. That's important to notice. And then in the null values, because there's no data and it can't actually produce an answer off of missing data. And since we're in data science, let's do S6 median. So let's look up the median data, which is simply median. Sorry for those who are following the 3 letters, because median is not 3 letters. And you can see in S6 is 3.0. And let's do a print here. And we'll do median or average. S6. And let's print max, comma S6. And just like median, there's max value. And if we're going to have a max value, we should also have a minimum value. So let's pop in minimum. We'll go ahead and run this. And you're starting to see something that would be generated like, say, in R, where you're starting to get your different statistics. We have a median value of 3, max value of 7, and a minimum value of 0. And what it does when it hits these null values, if there is null values in there, because we could still do that, we could actually, you know what, let's go up here and do, let's pick this one where we multiplied. Let's go S7 equals, I'll go ahead and print the S7 just so I keep it nice and uniform, so I still have my S7 down there, and run it. And then I want to take the S7, because S7 now has null values and an infinity value, and let's see what happens. This is going to be interesting because I want to see what it does with infinity. And we end up with a median of 6, maximum of 27, and minimum of 0, which is correct. It drops those values. So when it gets to there and it doesn't know what to do with them, it just drops those values and then it computes it on the remaining data on there. So that's important to know when you're making these computations, you're looking at min and max and median, you're not going to know that there's null values unless you double check your data for the null values. That's a very important thing to note on there. So just a real quick review on there. We've created our PD series, and we've gone ahead and done addition, subtraction, multiplication, division. All of those are 3 letters, so sub, min, div, add. And then we looked at median, maximum, and minimum. So we're going to go ahead and jump into the next big topic, which is to create a data frame. So now we're going to go from series, and we're going to create a number of series and bundle them together to make a data frame. There we go, cell type, markdown. And we go ahead and run that. So we have a nice title on there. It's always good to have a good title. All right, so our first data frame, we'll jump in with some stuff that looks a little complicated, but we'll break it down. First, I'm going to create some dates. And you know what? Let's just go ahead and do this. I want you to see what that looks like, what I'm creating here. I've created a series of dates, PD date range, and we're going to use these for the index. Okay, so when you look at this, you'll see that it's just, basically it comes out kind of like a basic Python list or a numpy array, however you want to look at it, with our different dates going down. And we've generated 6 of them. And it's going to have whatever time it is right now on the thing for the date for the time. That's that time stamp right there. And then you'll see we have 11/19, 2008, 11/20, 11/19, and looking into the future there. So that's all this is generating a series of dates that we're going to use as our index. And this is a Pandas command. So we have a date range, which is nice. That's one of the tools hidden in there in the Pandas that you can use. And next we're going to use numpy to go ahead and generate some random numbers. In this case we'll do the np.random.random in 6, 4. You can look at this as rows and columns as we move it into the Pandas. And of course you could reshape this if you had those backwards on your data. But we want the 6 to match the rows, and we have 6 periods, so our indexes should match along with the rows on there. And then, you know, before we do the next one, let's go ahead and just print out our numpy array so you can see what that looks like. Here we have it, 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6. 4 by 6. So it's a nice little setup on there. And since working with data frames can be very visual, let's give our columns, we have 4 columns, and we're going to give them names, A, B, C, and D. So now we have columns on there also. And then let's put this all together in a data frame, and we can actually, you know what, let's do this. Since I did it with everything else, let's go ahead and do columns, and you can see there's our columns on there. And we'll go ahead and do df1 equals pandas dot data frame. And note that the D and the F are capitalized. Series, it was just the S, and I always highlight this because you don't know how many times these things get retyped when you forget what's capitalized on there. It's a minor thing. You'll pick it up right away if you do a lot of it. And the first thing we want to do is we want to go ahead and take our numpy array, because that's what we're going to create our data frame off of, is the numpy array. And then we want our index equal to our dates. So there's our index in there. And then we also have columns equals columns. And then finally, let's see what that looks like. And remember, we had all that different data that just looked like a jumble of data. We have our column names and everything else. Our numpy array, kind of just a jumble array over there, 4 by 6. You could sort of read it. But look how nice this looks. I mean, this is, you come into a board meeting, you're working with your shareholders. This is pretty readable. This is, you know, this is our date. This is our A, B, C, D, whatever it is. Maybe each one of these dates has your leads, closures, lost leads, total dollar made, you know, whatever it is, if it's in a business. Maybe it's measurements on some scientific equipment, weather searching material, you know, where this is like high of the temperature, low of the day, humidity of the day, whatever it is. So you can see that we can really create a nice clear chart, and it looks just like a spreadsheet. You know, we have our rows, and we have our columns, and we have our data in there. Now this one I use all the time. If we're going to create, we can create it like you saw here with our numpy array. Very easy to do that and reshape it. You can also create it with a dictionary array. So here we have some data, and let me just go down a notch so you can see all the data on there. We have an animal, in this case cat, cat, snake, dog, dog, cat, snake, cat, dog. We have the age, so we have an array of ages. We have the number of visits and the priority. Was it a high priority? Yes, no. And then we're going to take that, we're going to create some labels. We have A, B, C, D, E, F, G, H, I. And what I want you to notice on this is we have a title, animal, and then we have basically a Python list. And these lists, they don't necessarily have to be equal because we can have non-data, you know, np.nan, numpy array, null value. But we want to go ahead and create labels that are equal to the number in the list. So A, the first cat, B, the second cat, C, the snake, D, the dog, and so on. So we'll go ahead and create our labels, which we're going to use as an index. And we'll call this df, let's do it this way. We'll call this df2 equals PD for pandas, data frame, and then we have our data, just like we did before, and then we have our index equals labels. And if we're going to go from there, let's go ahead and print it out so we can see what that looks like, df2. So let's go ahead and run that. Another, again, you have a nice, very clean chart to look at. We've gone from this mess of data here to what looks like a very organized spreadsheet, very visual and easy to read. Animal, age, visits, priority, and then A through J, cats, and all your different animals, so on and so on. And then when you do programming, a lot of times it's important to know what the data types are. So we can simply do df2 dtypes. And if we run that, we can see that our animal is an object, because it's just a string, but it comes in as an object. Age is a float 64, integer 64, and then priority again is just an object. And exploring this one's very popular. Let's go df2 head, and if we print that out, the df2 head returns the first 5. And we can change this. You don't have to do 5. You might want to just look at the top 2. Maybe you want to look at, let's see, let's do 6. So maybe we want to look at just the top 6 in the database, in your data frame. And you can actually, this creates another data frame. So I could have a df3 equal to df2, and this now takes the df2 and just the first 6 values. So if we do df3, run, get the same answer. And if we do the head of the data, we can also do the tail. It's the same thing. df_tail, you can look at the last, we'll just do the tail, which by default does 5, the last 5. And of course you can just look at the last 3 of those real quick just to see what's at the end of the data. And this is the tail. I love doing the tail of 1 because I'll have like the index or something like that, and it will just show me the last, whatever the last entry was. Looking at stock values, and I might want to look at just the last 5 days of the stock values. I can do that with the data frame tail. And some other key things to look up are the index. So we can do df2.index. And I want you to notice that this isn't a call function. So if I put the brackets on the end, it'll give me an error because index is not callable. It's just an object in there. So we do df2.index. There's also columns. So we can go ahead and let's print this. Remember, the first one's not going to show unless I print it, and then df2 columns. So now we can see that we have our indexes and we have our columns listed here, df2.columns, animal, age, visits, priority. It tells you what kind of object it is, or what kind of data type it is, and they're both object. And then finally df2.values. And again, there's no brackets on the end of df2.values. Because this is an actual object, it's not a callable function. So we'll go ahead and run that, and it just displays a nice array. A very easy way to convert this back to a numpy array, basically. So before I go into the next section, let's just take a quick look at what we covered so far with the data frame. We came up here, we created our data frame. We did it from a numpy array first, setting the columns and the index. The index setting it up is the same as when we set up the series, so that should look very familiar. So is the whole format, the numpy array, the index dates, and the columns. And remember, in our numpy array, we're looking at row, comma, column. So 6 rows, 4 columns is how that reads in the data frame. And we went ahead and also did that from a dictionary. In this case, animal was the column name with all the data underneath that column, and then age with that data, visits that data, priority that data. And then, of course, we added our labels in there for our index. So there's no difference in there, but it automatically pulled the column names. Important to know when you're dealing with a data frame and importing a data frame this way. And then we did looking up D-type. We looked at head and tail, looking at your data really quick. We also did index and columns and values. And note, these don't have the brackets on the end. So the next thing we want to do is go ahead, since we're dealing with data science, is we want to go ahead and describe the data. So we have df2.describe to do that, and we're going to manipulate it in just a minute, but let's just see what this generates. And you can see right here we have age and visits. So looking at our data from up above, let me just go all the way up here. Animal, age, visits, priority. And it does a nice job generating your age versus visits, which has all the data. You have your count, your means, your standard deviation, your minimum value, 25% are in this group, 50%, 75%, and your maximum value. So this will look familiar as a data science setup with your describe for a quick look at your data frame data. So let's start manipulating this data frame and moving stuff around, and we'll start with transposing. And it is simply capital T for transpose. And when we run that, it flips the columns and the indexes. So now the indexes are all column names and the columns are all indexes, animal, age, visits, priority. So if we had come in here with our data shaped wrong, up above where we had a 4x6, we can quickly just swap it if we had it backwards. Not a big deal. And we can also sort our data, something that you can't do, which is more difficult to do with a lot of other packages. In the data frame, it's really easy to do. Take our data frame df2 and we're going to sort underscore values by equals age. And so when we run this, you'll see the default is ascending. So we have 0.52, 2.53, and everything else is organized. So if you look at your indexes, they've been moved around because each index, it moves the whole row, not just the one piece of data is not being sorted. So a very quick way to sort by age our different data in the data frame. And in addition to sorting it, we can also slice the data frame. So I could do df2, and this should look familiar from earlier. We'll just do 1 to 3. So we're going to pull out, oops, it does help if I use a df instead of just d. And we're going to pull up just between 1 and 3. So we have not 0, which is A, but we have B, which is 2, or B, which is 1, and C, which is 2. So 1, 2, and then it does not include 3, which is the standard in Python. And we can even do something like this. We can combine them, which is always fun. Because remember, this returns a data frame. So if I take df2 dot sort values, and we'll do by equals age. This is just kind of fun. And then I'm going to slice it. There we go. Double check my typing and run it. And now you should see FA, because FA are now 1 and 2 on there. So you can very quickly create a whole string on here which narrows it, that you can sort it, then slice it, and do all kinds of fun things with your data frame. We'll just go back to the original one. Run. There we go. And if we can slice it by row, we can also query the data frame. So we can do df2. And this is a little different because I'm going to create an array within an array. And in this case, we're going to look at, let's do age, comma, visits. So look at the different format in here. We have 1 to 3. So we've done this by slicing by an integer value. And then on here, I've done df2 age, comma, visits in an array. And when I run this, you can see that we get just these 2 columns on here. We get age and visits. So it's a quick way to select just 2 columns or select number of columns you're working with. And if you saw up there, we did the slicing. Almost identical to slice is iLocation, which uses the integer location 1, 3. There's a push in Pandas to move to this particular setup instead of doing just a regular slice. And that's because this can be confusing when we slice 1 to 3 and then we select age and visits. So there is a push to go ahead and move to an iLocation, which does the same thing. You can see here BC, it's the same as up above. There's also a copy command, so we can do df3 equals df2 copy. We're just going to create a straight copy of it. And of course, if we do df3, it'll be the same as a df2 on there. So df3 equals df2.copy. And then let's do df3.isNull. So we're looking for null values. And this will return a nice map, and you'll see that everything is false, except when you go up here under the cat or H, they had a null there. And so if we go to have a couple up here also underneath of, let's see, the dog. Okay, there's a bunch of nulls in here. There's D up here. So let's look at D down here, and you'll see false, true. There it is. There's our null value. So we can create a quick chart of null values. You can use this to do other things. We can leverage that null value to maybe take an average or something and fill those null spaces with data. And we can also modify the location. So here's our df3 location. And notice this is location, not iLocation. iLocation has I for integer. Location uses the, in this case, the variables on the left. And what we can do on here, and we'll go ahead and just set this equal to 1.5, and then let's pick a spot. Let's go back up here where we had, let's do F age, let's see, what were we looking at? Oh, here we go. Let's do F and age. And up here, F is set to age of 2.0. And we find out that that's incorrect data, so we go ahead and switch to df3 equal, and then we go ahead and print out our df3. And if we go to F and age, it is now 1.5. So we're just changing the value in the df3. And this is changing the actual data frame. Remember, a lot of our stuff, we do a slice, and like it returns another data frame. This changes the actual data frame and that value in the data frame. So we've covered location and iLocation is null. Making a copy, here's our iLocation, which is equivalent of a slice, and also selecting columns. So now we want to just take a little detour here, and let's look at df3 means. And this is kind of nice because you can do this. You can either do this you can select a single column here, by the way. You can just add the column selection right here like we did before. So we could have age, Look up the mean, that just creates a series. If I run that, there's our age. But if I take that out, instead of selecting it, we can do the whole setup, and it has age and visits. So why doesn't it have priority or animal? Well, those are not integers, so it's really hard. They're non-numerical values. So what is the average? I guess you could do a histogram, which probably we'll look at that later on. But the only two things we can really look at is age and visits, and we have the average or the mean on the age is 3.375, and the mean on visits is 1.9. And let's do DF3 visits. We'll go ahead and steal the visits again. And you remember all those different functions we looked at for a series? Well, we can do those here. We can do the sum. So if we run that, we'll see that these sum up to 19. We could also look up minimum. If you remember that from before, the minimum is 1, max. So all that functionality is here. I'll just go back to summing it up and adding it all together. So real quick, we've shown you how to take the series operations and put them into the data frame. And then we can actually, this is an interesting one, we can just do df3 sum, run, and you'll see the different summations on there. It just combines them. I like the way it just combines the strings on there for priority and animal. We've looked at is null. We've also looked at copying, along with the different slices which we talked about earlier. So let's talk about strings. Let's dive into the string setup on there. And let's go ahead and create a string series. String equals PD series. And we just put it right in there. We have A, C, D, A, B, A, C, A. Popped in a null value. Cow and owl. I don't know why they picked cow and owl in the background. Someone must like those animals. And of course we can just do string. If we run that, you'll see, leave the R out, we'll get an error. But if we put it in there, you'll see that we have a simple series. 0A, 1C, 2D. And it automatically indexes it 0 to 8. And then we can go string dot lower. So when we're talking about our data frame, in this case, or our data series string, in this case, we're going to use the string function, str, and we're going to make it lower. And if we go ahead and put the brackets on there, and you'll see that we've gone from capital A, capital C, so on to ABC. And baka, CBA, cow, owl, they were all lowercase already. And of course, if you want to go lower, you can also do upper. And we'll go ahead and run that. And you can see we now have ACD, AAA, baka. Everything's capitalized except for the null value, which is still null. All right, so we looked at a few basic string. You can see that string functions upper and lower. We're going to jump into a very important topic. I'm even going to give it its own header on here because it's such an important topic. What do you do with missing values? Panda has some great tools for that, so we'll dive into those. We'll work with df4, and if you remember the df copy from above, we're just going to make a copy of df3. And let's just take a quick look at the data we're working with. Oops, df3, forgot the 3 on there. There we go. So here we have our cats, snakes, and dogs. Hopefully not all in the same container, because that would be just probably mean to all of them. So we made a copy, we're going to be working with df4. And the reason we made a copy is we want to go ahead and fill the data. And we just simply do fill NA, and then we're going to give it the value we want to put in there. We'll give it the value 4. So I can run in here, and you'll see now that df4 now has where the NA was, it's filled with the value of 4. Same thing down here. A lot of times we'll compute the mean first. So I might do a mean age equals df4, and then we want to go ahead and do age and dot mean, and then I'll do something like this, df4. I only want to select the age, and I want to fill that with the mean age. And I run in there, and you'll see that our df4 age now has the means in there. Just a quick way of showing you how you can combine these. Let me go back to our original one. There we go. And run that. And keeping with good practices, df5 equals df3.copy. And then we'll print our df5, which should be the original one. And then on the df5, we can now drop our missing data. I'm going to simply drop NA, and we're going to use how equals any. So I'm going to drop any row that has missing data in it. And you'll see we had D here with missing data and H. And then let's go ahead and see what df5 looks like when we do that. There we go. And there it is. D is gone, and so is H. So we create a new data frame off of this, missing those values. Now, if you have a lot of data, dropping values is a good way to take care of it because you don't miss some data. If you have not a whole lot of data, you're working with like the iris data set or something like that, or something small, you want to start trying to find a way to fill that data in so you don't lose your computational power of the data you got. So just a quick look at processing null values or missing values. You can fill them, usually with the means. Some people use medium or the mode. There's different ways you can fill it. One way is means. And we can also just drop those rows. Those are the two main things we do with missing data. Here we go. We're going to cover next. I so love DataFrames for this. File operations. It saved me so much time because they have so many different tools for bringing data in and saving data. So when we're looking at the DataFrame file operations, it's really streamlined. I don't know how many times I'll go on to different data downloads and they'll have Panda download standard on there just because it's so widely used. So let's start with the most common file is a CSV. So we have df3 to CSV or animal. And let me just show you the folders going into. Right now I have some untitled, a few things in here, but nothing labeled animal. So we go ahead and run this, and this has now saved the animal to my hard drive. And you can now see the animal folder up here, and if I, let's do edit with a notepad. Oh, let's open it up with just a regular notepad. There we go. Or WordPad. If I open that up, you can see it's comma separated. Our titles, they don't have an index on the categories on the top. And the index, comma, and then all the different data is separated by commas. Standard CSV file on there. And if we're going to send it to CSV, and notice the format is .to_CSV. And it's just the name of the file we're sending it to. You can also put the complete path. By default, it's going to go whatever the active directory this program's running on. That's why those other folders are in there. So we have our df3 to CSV, and then if we're going to put it in there, we want to also get it back out. And we'll call this one df_animal equals pd read_CSV. I always have to remember it's to_CSV and read_CSV. I always want to do like a capital in there and not the underscore. We're going in here again, it's the active directory. So if I now do print out my df animal, and let's just do the head. We only want to look at the first 3 lines. So if I go ahead and run this, we'll see the first 3 lines and they should match up here what we saved to our CSV. So very easy to save and import from our CSV files on here. And it turns out df3 also has a to Excel. They actually have a lot of different formats, but old school Excel was real popular for so long, still is. We can go ahead and save it as animal.xlsx. We're going to call the sheet named sheet 1, and then I can also do df, we'll call it animal2, and this one's going to come from, and the same format on here. There we go. So we still have our animal xlsx, the sheet 1, that's where it's coming from. Index columns equals none. So we're going to suppress the indexing on the columns. NA values, and it'll just assign it's 0 on up on your indexes. So if it says index columns equals none, that's what it does. And then we've added null values because there's null values in here, and we want to just make sure that they're marked as NA. And we'll go ahead and just print out the animal2, there we go. And let's run that. Let's make this, let's just do the whole thing. So we'll go ahead and run that. And it probably doesn't help that I completely forgot the read. So animal2 equals pd.read Excel. There we go, Excel. So now we go ahead and run it. And what we expect is happening here. We have the same data frame on here. And if I flick back to my folder, you can now see that we have the animal. One of these is in Excel, and one of these is a CSV on here. And so there's our 2 file types on there. And they have other formats. These are just the 2 most common ones used, and I don't know how many times I've had stuff from Excel I need to pull out. If you've ever played with Excel, it's a nightmare in the back end because of the way they do the indexing. So this just makes it quick and easy to pull in an Excel spreadsheet. So we looked at 2 different ways to bring data in and save it to files. We've looked at all kinds of different ways of manipulating our data set and slicing it and creating it for our data frame. Let's get in there for your visualization. Always the big thing at the end, because 1, it lets you check to see what you did, make sure it looks right. And then also, if you're going to show somebody else, it makes it very clear what's going on if they see something visual. So this is where a really important part of data science is. So let's go ahead and bring in our tools. We're going to do import numpy as np. We want to make sure we have our ampersand matplot library in line. This just lets Jupyter know that we're going to print it on this page. If you're using a different IDE, you don't really necessarily need that, but this does help it displays correctly in Jupyter Notebook. And if you remember for earlier, we could create a, we're going to call it TS. We're going to create a pandas, which are cute cuddly creatures, versus a pandem, short for pandemonium? No. So we have TS equals PD series, and we're just going to create a random setup of 50. We'll do an index. We'll set it equal to the pandas date range today. Periods equals 50, so the 50 should match. And I want you to notice something here. I did not import the matplot library. Why? Because it's already in there. Pandas already has its built-in connection and interface with matplot library, so you don't have to import it. And we'll go ahead and do TS equals TS dot cumulative sum. We're going to do the cumulative sum. So a little reformatting there, and we'll go ahead and plot it. And let's take a look at what that looks like. So we have a nice graph here. We have the dates on the bottom. We've set this up so we have a nice range between, in this case, -4 to, looks like about 2 maybe, or 1, -4 and 1. So what we've done here, we've plotted a basic series, just a single row of data, and we've set indexes on there. But we can also do the whole data frame on there, and let's see what that looks like. So first, let's go ahead and create the data frame. We have here random numbers, and we're going to do 50 by 4. And then we'll go ahead and create columns A, B, X, and Y, just because we can. Index is a ts.index on there, so we're going to use the same index as before, just to keep it nice and uniform. We've already generated the dates to go with it. And then we can do, just like we did with the series, we can also do with the data frame, df equals df cumulative sum. So we're going to sum the whole data frame. And then we'll do simply df plot. And let's push that in, and let's go ahead and run this. And look how easy and quick that was to generate a nice graph with all the different data on there. So we have our shared index, we have the shared columns, and then we have the different data from each one that we can easily look at and compare. So very quick way of displaying data. You can imagine if you were working in, I think I mentioned stock earlier because I've been doing some analysis of stock lately. So you'd have your date down here, and then you would have stock A, stock B, stock XY, whatever it is. And you can put them all on one chart and see what they look like next to each other. And this isn't too far off from what some of those graphs look like, and this is just randomly generated. So stock has a lot of randomness in it, which is one of the reasons I actually play with it for doing some of my models for testing them out. Now, there are a lot of features in Pandas. So we're going to show you one more thing on here. There's some of the things, like I didn't go too deep. We looked at the top two for importing data from a CSV and from an Excel spreadsheet. Showed you how to quickly plot the data. There's more settings in there you can do. We're going to do one more thing down here, and this is kind of a fun one. Change this to a markdown and run that. So how would you remove repeated data using Pandas? And this is where you have a data set that comes in, and maybe it's feeding from one location, and instead of noting that it's repeated the date, like, let's go back to stocks. That's a good visual. We have the stocks from the 23rd. And it adds another row, and it's the same row. It's importing the 23rd again and again. So now you have that data repeated 3 times, and you need to go back and figure out how to get rid of it. How do you track that down? So let's start by creating a quick database, or data frame. Not a database. I keep saying database. It's a data frame. And we'll just make this data frame using our dictionary going in. This data frame only has one data series in it, which is fine. So if we do df to print it out, you'll see A, 1, 2, 2, 2, 2, 4, 4, 4, 5, 6, 7, and so on. And so how would you remove that? Well, there is a neat feature in data frames called shift, along with another feature that lets us select just certain information. And we'll go with the location function. Put that in brackets. Remember that from above, location. And then in the location, let me just spread this out a little bit so it's real easy to read. In fact, I'm going to go upscale on that since we're doing a little bit more complicated here. What you can see on the location, is I have dfa.shift. So this is going to shift up 1 by default. You can actually change this to 2 or 3. You can even do a -1 and it shifts the other way. But it's going to shift up by 1 by default. And it's going to say if that does not equal df of a, then we want that. And if you look down here, we had 1, 2, 2, 2, 2, 2. When we run this logic on here and we do the shift, it now gets rid of all the duplicates. So we went from 1, 2, 2, 2, 2, 4, 4, 5, whatever it was. Here it is, 1, 2, 2, 2, 4, 4, 4, 5, 5, 5, 6, 6, 6, to 1, 2, 4, 5, 6, 7, 8. And you'll see on the index, it just deletes them out of there so the index stays the same. Obviously, you don't want the dates to change if you're working with an index dated setup. So it just deletes those duplicates out of there. This is just a quick way to introduce you to, 1, the fact that you can add logic gates into here. And 2, the iLocation allows you to use shift. So there's the shift function, and then the iLocation selects that based on true or false. Wow, so we've actually covered a lot today in Pandas. We've really covered into the basics of selecting your different series out of your column, out of your data frame, how to index rows, how to slice, how to plot. Hopefully you'll take this beyond that and start combining these different things, and you can create long strings and really explore your data, generate some nice graphs. If you're in Jupyter Notebook, it's a great demo to show others. And I didn't know this about Jupyter Notebook. You can do this in Jupyter Notebook, and then you can download, and I never really looked too closely at all the downloads, but you can download it as an HTML and post it to your blog. So it's got a neat feature in there. But any of this is really powerful tool. All of this is really powerful tools for doing your data science.
So as you can see, I'm using Jupyter Notebook for the Python. Okay, so here what I will do, I will go to new and the Python 3. Okay, so here first I will rename it to Pandas for data analysis. Okay, then rename it. Okay, so already everyone know Pandas is a Python library that provides extensive means for data analysis, right? Data scientists often work with data sorted in the table formats like .csv, .tsv or XLX. Okay, so Pandas makes it very convenient to load, process and analyze such tabular data using SQL-like queries. Okay, so in conjunction with Matplotlib and Seaborn, Pandas provide a wide range of opportunities for the visual analysis. Okay, you can make charts and all, right? So the main data structure in Pandas are implemented with series and data frame classes. So now let me import numpy first, okay, as np. Then I will write import pandas as pd. Why I'm writing as np and as pd? Because I don't want to write pandas and numpy again and again and again. So I gave the short form, you can say. Okay, so here I will write just pd dot set underscore option display dot precision. Okay, then I will write comma 2. Okay, where are it? Okay, fine. So we have imported pandas and this numpy library. So now what I will do, I will demonstrate the main method in action by analyzing a data set on the churn rate of telecom operator. I have one data set named telecom churn, okay, operator clients data set. So now let's first import it. Okay, so I will write here df equals to, df means data frame, you can give any name. Okay, df pd, as you can see here, pd means pandas dot read underscore csv, then telecom churn dot csv. So you can find this data set from the description box. Okay, in the description box below, right? Then I will write here df dot head. What does this do, df dot head? It will show you the first 5 lines using the head method of the data set. It will show you first 5 lines of the data set head. And if you will use tail instead of head, you can see the last 5 rows of data set. Okay, if I will write here df dot tail, you can see the last 5 rows of the data set. Fine. Yeah, so on our data set we have state, account length, area code, international plan, voicemail, this. Okay, and the churn rate is false. Fine. So now what I will do, I will recall that each row correspond to one client, an instance, and the columns are the features of the instance. So now let's have a look at the data dimensionally, features, names, and the feature types. Okay, so how many columns and rows we have? Fine. So I will write here print df dot shape. Okay, so now we have 3,333 rows and 20 columns in our table, in our data set. Okay, so now let's try printing on the column names using columns. Okay, so for that, what I will do, I will write here print. So these are all the functions used in Pandas. Okay, then df dot columns. Okay, so now you can see here we have 20 columns right here, 20 columns. Okay, so here state is one column, account and 3 4, these are the all columns name, these columns name. Fine. So now let's use another function called info, which will give you some, it will give you some general information about the data frame. Okay, so here I will write print df dot info. Okay, so yes, so now you can see class is Pandas, core frame, data frame, then this much entries. Okay, 0 to this 3,332. Okay, column name and the non-null values, non-null count is 0, and the data types you can see, this is object, this is int64, 64 object, floating type. Okay, so there are 4-5 type of data sets here. Okay, bool is there, float is there, okay, int is there, and the memory usage you can see 498.1 plus KB. Okay, and then bool is 1, float 64 type is 8 columns, then int 64 8 columns, and object is 3, right? So here these bool, int 64, float 64, and object are the data types of features. Already I told you. So we can see that one feature is logical. Okay, that bool one is logical. Where is the bool? Yes, this one. Churn rate is logical. Okay, logical means true false. Okay, and the 3 features are of the object type. You can see this state, these are the object, and the 16 features are numeric. Okay, float is also numeric plus variable, right? So with this same method we can easily see if there are the missing values. So here are none, because each columns contain 3,333 observation. See, every column is same, and you can see null count is non-null. Okay, so here you can see we don't need any cleaning and that type of thing. Okay, so we can change the column type with the as type method. There is one more method, so let's apply this method to the churn feature to convert into int64. Got it? So for that, what I will do, I will write df, then I will write churn. Please note that no spelling mistake while writing the column names. Okay, equals to df churn. Okay, C is capital dot as type int64. Fine. So now we have convert this bool to int64 now. Okay, so now what I will do, I will use one more method. Okay, let me run it first. it's no issues. Now what I will do, I will write here df dot describe. Yeah. So now, so the describe method shows basic statistical characteristics of each numeric feature, int 64 and float 64. Okay. Count is there for the particular column, the mean, standard deviation, minimum value 25%, 50%. This is the max value. Okay. Okay, now you can see the churn 0 and 1 to 1. Okay. So, and the number of non-missing values, mean, standard deviation, range, medium, everything is here. Using describe, you can just find it. Okay. For every column, it will give you. Okay. Count, how much count, and mean of this particular account length and the area code like this. So now, so in order to see the stat of non-numeric feature, so one has to explicitly indicate data types of interest in the include parameter. Okay, I will use the include parameter. So at first I will write df dot describe include equals to object comma bool. Okay. So now you can see the count is 333 and unique values are the 51 and the top is this and the frequency is this. Okay. So I am here seeing the stat of non-numeric features. Okay, this is like state, international plan, and the voice plan like this. Fine. So for categorical data like type, object, and the Boolean type bool feature, we can use the value counts method. So now let's have a look for that also. So I will write df churn dot value counts. Okay, so this is some data, right? So now what I will do, so there are, okay, fine. So now what I will do here, I will normalize it. Churn dot value counts normalize equals to true. Okay. So we have 2850 users out of 3033 are loyal. Their churn value is 0. Okay. And to calculate fractions pass normalize is equals to true, I did that to the value count function. Okay. So here you can see 0 and the 1 value counts. Right. So now let's go for the sorting data. So what is sorting? So a data frame can be sorted by the values of one of the variables like columns. So for example, we can sort this table by total day charges using ascending or in descending, right? So now I will do here df. Okay, first let me write here sorting. Okay, df dot sort values by equals to total day charge ascending equals to false dot head. Dot head means I want to see the top 5 rows. Okay. So now what I did, total day charge. Okay, total day charge I have sorted in this. Ascending equals to false means I have sorted into the descending order. Okay, and the top 5 rows are this. Okay, 59 is the maximum, 59.64. Fine. So now, like, we can also sort by multiple tables in one go. Okay, so let me do it. Df dot sort, same thing I have to write, values by equals to churn. Okay, this. Yeah, churn, comma, then again total day charge, comma, ascending equals to true, comma, false. Then I want to see, okay, let me write the same dot at. Okay, first I will show you this 1 1 1 1 1. Okay, then let me change it. See, it's sorted now. Fine. So these are the top 5 as per these 2 columns, churn and the total data charge column. Okay, so now we will perform some indexing and retrieving data. So a data frame can be indexed in a few different ways. Like to get a single column, you can use data frame name. Okay, and so now let's use this to answer a question about the column alone. So let's take one question like, what is the proportion of churned users in our data frame? Okay, proportion. Okay, df dot, we will do simply, we have to find the mean. I will write churn dot mean. That's it. Okay, so 14.5% is actually a quite bad for a company, such as a churn rate can make the company go bankrupt, right? So Boolean indexing with one column is also very convenient. So the syntax is, I will write here df, then again df churn equals to 1, then dot mean. Okay, so here what I am finding is what are the average values of numerical features for churn user. Okay, see, account length just ignore this warning. Okay, so account length is 102.66, area code is this, right? So now what I will do, I will find one more thing. So like we will find how much time, like in average, do churn users spend on the phone during daytime. Okay, df then churn equals to 1, then total day in minutes. We have this column, right? I hope so. We have this column, total day minutes. Okay, fine. Yeah, dot mean. Okay, so how much time an average churn user spend on the phone during daytime is 206. Okay, almost 207. Okay, so now let's take one more question, like what is the maximum length of international calls among loyal users? Okay, loyal user means where churn is 0, like who do not have the international plan. So here for that I will write df and df churn equals to 0. Here I will write and df, okay, I will, okay, international plan equals to no. because there is, see, you can see the international plan. No, yes, no, yes, no. Okay, no, then total international minutes. Okay, this. Okay, for the confirmation, let me copy it and paste. Okay, no issues. Dot maximum value. Yeah, so 18.9. Okay, so 18.9 is the maximum length of international calls among loyal user, whereas churn is 0, who do not have the international plan. Okay, so indexing. Data frame can be indexed by column name, I told you already, or the row name, or by the serial number, you can say, of a row. So there is one method, LOC. Okay, method is used for the indexing by name, while iloc is another method for indexing by the number. Okay, first I will show you df dot, here I will write indexing, df dot loc comma state, then area code. Okay, so in this first case, we can say I gave the values of the rows with the index from 0 to 5, like inclusive, and the column labeled from the state to area code inclusive. Okay, so this is how you can perform indexing. Okay, using by name. Okay, if you want indexing by the numbers, you have to use iloc instead of this loc. Iloc means location. Okay, don't get confused. 5 comma 0 to 3. Okay, see, you got the same almost, right? Yeah, this is 0 to 5. Okay, and this is 0 to 3. 0 to 5 means 1 2 3 4 5, and 0 to 3 1 2 3. Fine. Yeah, so what if we need the first or the last line of the data frame? So we can also do that. So here simply you have to write simple thing, df -1. Okay, that's it. See, this is the last line, -1, last line. Fine. So if you want to apply something to all the columns, so there is one more function which is apply. So how to do is df dot apply np dot max. Okay, right, it gave me all the maximum values of the particular table, sorry, particular column, not table. Okay, so this is how you can do this. So this apply method can also be used to apply a function to each row, I already told you. So to do this, you have to just specify the axis, or the lambda function are the very convenient in such scenarios. Like for example, let me give you one example, df, then df state, let's use the state. Okay, then dot apply lambda state, and state 0 equals to w, which is starting from w. Okay, then dot, I need only 5 rows, dot it. Okay, so the state is starting from w, here it is. Okay, top 5, right? So yes, so there is one more function, map method, which is used to replace the values in a column by passing a dictionary or the form, right? So map function D equals to no, okay, it is false, then yes is true, right? Then df international plan equals to df international plan dot map d, okay, df dot head. Fine. Okay, there is some international plan. Okay, p is small, that is why I was saying please write it carefully. Yeah, okay, so this is the map function. Okay, so wherever there is no or yes, okay, so I have mapped it to the true false, right? Okay, see here you can see international plan, yes no yes no yes no. I have marked yes to false, and okay, why different? Because the series is different. Okay, here I have performed different thing. The numbers, just check the number. Okay, 0 1 2 3 4, right? Df dot head, let me write this. So now let's compare. Okay, why it's coming? Because I have already performed that thing. So we'll go to here, see no 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 yes yes. Now you can see here false 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 true true. So for no I gave false, and for the true, for the yes I gave true. Fine, this is the mapping. This is how you can do the mapping. Okay, so now let's do df equals to, same thing can be done using replace as well. There is one more function. Okay, let me give you the name, stack replace. Dot replace, then voicemail plan, oh sorry my bad, plan D. Okay, fine. Now yes, then df dot. Okay, so what I took, voicemail plan, right? Same, see, true true false false, because here if you will see I have write d equals to this. Again you have to write no to false and yes to true. Same I used here d, no need to write again and again. Fine. So now let's see how to do grouping. Okay, so first the group by method divides the grouping columns by their values. Okay, first let me write this grouping. Okay, so here I will write columns to show equals to total day minutes, right, comma total if minutes, comma total night minutes. Okay, then df dot group by, then here I will write Chan, then here I will write columns to show dot describe, percentile. Fine. Where is it's empty? Fine. There is error. df.group can DataFrame describe got an unexpected keyword argument percentile. Okay. Fine. It will be percentiles. Yeah. So this is how you can do the group by with a churn. Okay. So what I did, so let me explain the steps. So first, the group by method divides the grouping columns by their value. Okay. Then they become a new index in the resulting data frame. Then column of interest are selected, column to show, this column to show. Okay, so if column to show is not included, all the non-group by classes will be included. Finally, one or several functions are applied to obtain the groups for selected columns. So here what I did, we group the data according to their values of the churn variable and displays that of 3 columns in each group. Right, these 3 columns in each group. Same. Count means standard deviation minimum 50% max. Count means this. Okay. So this is how you can do grouping. Fine. So if you want to summarize the table, okay, suppose we want to see how observation in our sample are distributed in the context or 2 variables, churn and international plan. So to do so, we can build the contingency tables using the cross tab method. I will show you. Okay. So here I will write summary table. ed dot cross tab. Then I will write here data frame df churn comma df international plan. Okay. So this is the true false. The summary. Okay, we have this much true, false, 0 from the international plan, and the 41 are this much. Okay, for one, there are 346 and 137 true. Right. So this is how you can perform the summary table. Right. You can do for the more also. So now let's create the pivot table. Okay. So let's make the tables. Stack pivot tables. Okay, pivot tables. Fine. So I will add df dot pivot table. Okay, then I will write here. Sorry. Yes. So here I will write total day calls, comma, I will take 3 column total eve calls, comma, then total night calls, comma, then area code. Okay, comma, then aggregate function equals to mean. Okay, I'm using mean. Fine. So this is pivot, you got the area code and the mean of particular this thing. Right. So data frame transformation. So let me explain you first this pivot table. Okay, before moving forward. So so now we can see the most of the users are loyal and do not additional services. Okay, international plan or the voicemail. So this will resemble pivot table to those familiar with Excel and non, of course. Okay, so here the values are the list of variables to calculate stat for, and the index, okay, a list of variables to group data by, okay, area code, okay, and the aggregate function is what stat we need to calculate for the groups. Like we can use sum, mean, minimum, maximum, okay, something else. Okay, so here I have used the mean, right? So now let's predict the telecom churn. Okay, so now let's see how the churn rate is related to the international plan feature. So we will do this using, cross tab contingency, already saw, and also through visual analysis with Seaborn. I've already told you with Matplotlib and the Seaborn, Pandas is crazy. Okay, so here I will write predicting telecom churn. Okay, so here I will write pd dot cross tab df churn, okay, C is capital, churn, comma, df international plan, comma, margin equals to true. Okay, sorry, my bad, it's margins. Yeah, okay, we got the pivot table here using cost tab. So I will import here, import matplotlib for the charts. Matplotlib dot pyplot as plt. Then I will import Seaborn. Just remember to install all these libraries. Okay, you can use pip install Seaborn and pip install numpy, pip install pandas before using it. Seaborn as SNS. Then for the graphic retina, I will use config inline backend dot figure format equals to retina. Okay, then here I will write SNS dot count plot, where x equals to x-axis I'm giving, okay, international plan, comma, let's set the hue equals to churn, then comma, data will be df. Okay, see, we have the counting of using international plan, and the hue is churn, okay, 0 and 1. Fine. So we can see that the international plan, the churn rate is much higher, which is an interesting observation. Perhaps the large and the poorly controlled expenses with international calls are very conflict. Okay, so now let's take a look to another important feature, which is customer service call. Let's also use to to make the summary table first. So for that I will do here pd dot cross tab df churn, comma, df customer service calls, comma, margins equals to true. Okay, yes, so again I have made the summary table for the customer service calls. So now what I will create SNS dot count plot x equals to customer service calls where hue is churn, then data equals to df churn. Yes. Okay. So this is how you can create the chart using Pandas and the Seaborn. Fine. So therefore predicting that the customer is not loyal, churn equals to 1 in the case of when the number of calls to the service center is greater than 3 and the international plan is added. Okay. So this is how you can do data analysis using Pandas. Okay.
If you categorize the steps to become a data analyst, these are the ones. Firstly, you need to focus on skills. Followed by that, you need to have a proper qualification. Then, test your skills by creating a personal project, an individual project. Followed by that, you must focus on building your own portfolio to describe your caliber to your recruiters. And then, target to the entry-level jobs or internships to get exposure to the real-world data problems. So these are the 5 important steps. Now let's begin with the step 1, that is skills. So skills are basically categorized into 6 steps: data cleaning, data analysis, data visualization, problem solving, soft skills, and domain knowledge. So these are the tools: Excel, MySQL, R programming language, Python programming language, some data visualization tools like Tableau, Power BI, and next comes the problem solving. So these are basically the soft skill parts. Problem solving skills, domain knowledge, the domain in which you're working, maybe a pharma domain, maybe a banking sector, maybe automobile domain, etc. And lastly, you need to be a good team player so that you can actively work along with the team and solve the problem collaboratively. Now let's move ahead and discuss each and every one of these in a bit more detail. Starting with Microsoft Excel. While advanced tools are prevalent, proficiency in Excel remains vital for data analysts. Excel versatility in data manipulation, visualization, and modeling is unmatched. It serves as a foundational tool for initial data exploration and basic analysis. Data management. Database management skill is indispensable for data analysts. As data volumes soar, efficient management and retrieval from databases is critical. Proficiency in database systems and querying languages like SQL ensures analysts can access and manipulate data seamlessly. Followed by that, we have statistical analysis. Statistical analysis allows analysts to uncover hidden trends, patterns, and correlationships within data, facilitating evidence-based decision making. It empowers analysts to identify the significance of findings, validate hypotheses, and make reliable predictions. Next, after that, we have programming languages. Proficiency in programming languages like Python is essential for data analysts. These languages enable data manipulation, advanced statistical analysis, and machine learning implementations. Next comes data storytelling, or also known as data visualizations. Data storytelling skill is paramount for data analysts. Data storytelling bridges the gap between data analysis and actionable insights, ensuring that the value of data is fully realized in a world where data-driven communication is central to business success. Data visualization skill is a cornerstone for data analysts. As data complexity grows, the ability to present insights clearly and persuasively is paramount. Next is managing your customers and problem solving. Managing all your customers' data and companies' relationships is paramount. Strong problem solving skills are important for data analysts. With complex data challenges and evolving analytical methodologies, analysts must excel in identifying issues, formulating hypotheses, and devising innovative solutions. In addition to the technical skills, data analysts in 2025 will require strong soft skills to excel in their roles. Here are the top ones. Data analysts must effectively communicate their findings to both technical and non-technical stakeholders. This includes presenting complex data in a clear and understandable manner. Next soft skill is teamwork and collaboration. Data analysts often work with multidisciplinary teams alongside data scientists, data engineers, business professionals. Collaborative skills are essential for sharing insights, brainstorming solutions, and working cohesively towards common goals. And last but not least, domain knowledge. Knowledge on domain in which you're currently working is really important. It might be a pharmaceutical domain, it can be an automobile domain, it can be banking sector, and much more. Unless you have a basic foundational domain knowledge, you cannot continue in that domain with accurate results. Now, the next step, which was about the qualification to become a data analyst. Master's courses, online courses, and boot camps provide strong, structured learning that helps you gain in-depth knowledge and specialized skills in data analysis. Master's programs offer comprehensive, academically rigorous training and often include research projects, making sure you're highly competitive in the job market. Online courses allow flexibility to learn at your own pace while covering essential topics, and bootcamps offer immersive, hands-on training in a short period focusing on practical skills. All three paths enhance your credibility, keeping you updated on industry trends and make you more attractive to potential employers.
So as you can see, I'm using Jupyter Notebook for the Python. Okay, so here what I will do, I will go to new and this Python 3. Okay, so here first I will rename it to Pandas for data analysis. Okay, then rename it. Okay, so already everyone know Pandas is a Python library that provides extensive means for data analysis, right? Data scientists often work with data sorted in the table formats like .csv, .tsv, or xlx. Okay, so Pandas makes it very convenient to load, process, and analyze such tabular data using SQL-like queries. Okay, so in conjunction with Matplotlib and Seaborn, Pandas provide a wide range of opportunities for the visual analysis. Okay, for the you can make charts and all, right? So the main data structure in Pandas are implemented with series and DataFrame classes. So now let me import NumPy first. Okay, as np. Then I will write import pandas as pd. Why I'm writing as np and as pd? Because I don't want to write pandas and numpy again and again and again. So I gave the short form, you can say. Okay, so here I will write just pd dot set underscore option display dot precision. Okay, then I will write comma 2. Okay, where are it? Okay, fine. So we have imported pandas and this numpy library. So now what I will do, I will demonstrate the main method in action by analyzing a data set on the churn rate of telecom operator. I have one data set named telecom churn, okay, operator clients data set. So now let's first import it. Okay, so I will write here df equals to, df means data frame. You can give any name. Okay, df pd, as you can see here, pd means pandas dot read underscore csv, then telecom churn dot csv. So you can find this data set from the description box. Okay, in the description box below, right? Then I will write here df dot head. What does this do, df dot head? It will show you the first 5 lines using the head method of the data set. It will show you first 5 lines of the data set head. And if you will use tail instead of head, you can see the last 5 rows of data set. Okay, if I will write here df dot tail, you can see the last 5 rows of the data set. Fine. Yeah, so on our data set we have state, account length, area code, international plan, voicemail, this. Okay, and the churn rate is false. Fine. So now what I will do, I will recall that each row correspond to one client and instance, and the columns are the features of the instance. So now let's have a look at the data dimensionally, features, names, and the feature types. Okay, so how many columns and rows we have? Fine. So I will write here print df dot shape. Okay. So now we have 3,333 rows and 20 columns in our table, in our data set. Okay. So now let's try printing out the column names using columns. Okay. So for that, what I will do, I will write here print. So these are all the functions used in Pandas. Okay. Then df dot columns. Okay. So now you can see here we have 20 columns right here, 20 columns. Okay. So here state is one column, account and 3, 4. These are the all columns name. These columns name. Fine. So now let's use another function called info, which will give you some, it will give you some general information about the data frame. Okay. So here I will write print df dot info. Okay. So yes. So now you can see class is pandas core frame data frame, then this much entries. Okay. 0 to this 3,332. Okay, column name and the non-null values. Non-null count is 0, and the data types you can see. This is object, this is int64, 64 object, floating type. Okay. So there are 4-5 type of data sets here. Okay, bool is there, float is there, okay, int is there, and the memory usage you can see 498.1 plus KB. Okay. And then bool is 1, float 64 type is 8 columns, then int 64 8 columns, and object is 3. Right. So here these bool, int 64, float 64, and object are the data types of features. Already I told you. So we can see that one feature is logical. Okay, that bool one is logical. Where is bool? Yes, this one. Churn rate is logical. Okay, logical means true, false, true, false. Okay, and the 3 features are of the object type. You can see this state. These are the object, and the 16 features are numeric. Okay, float is also numeric plus variable, right? So with this same method, we can easily see if there are the missing values. So here are, none, because each columns contain 3,333 observation. See, every column is same, and you can see null count is non-null. Okay, so here you can see we don't need any cleaning and that type of thing. Okay, so we can change the column type with the as type method. There is one more method. So let's apply this method to the churn feature to convert into int64. Got it? So for that, what I will do, I will write df, then I will write churn. Please note that no spelling mistake while writing the column names. Okay, equals to df churn. Okay, C is capital dot as type in 64. Fine. So now we have convert this bool to int64 now. Okay, so now what I will do, I will use one more method. Okay, let me run it first. Okay, it's no issues. Now what I will do, I will write here df dot describe. Yeah. So now, so the describe method shows basic statistical characteristics of each numeric feature, int64 and float 64. Okay. Count is there for the particular column, the mean, standard deviation, minimum value 25%, 50%. This is the max value. Okay. Okay, now you can see the churn 0 and 1, dual. Okay. So, and the number of non-missing values, mean, standard deviation, range, median, everything is here. Using describe, you can just find it. Okay, for every column it will give you. Okay, count, how much count, and mean of this particular account length and the area code, like this. So now, so in order to see the stat of non-numeric feature, so one has to explicitly indicate data types of interest in the include parameter. Okay, I will use the include parameter. So at first I will write df dot describe include equals to object comma bool. Okay, so now you can see the count is 333 and unique values are the 51 and the top is this and the frequency is this. Okay, so I am here seeing the stat of non-numeric features. Okay, this is like state, international plan, and the voice plan, like this. Fine. So for categorical data like type, object, and the Boolean type bool feature, we can use the value counts method. So now let's have a look for that also. So I will write df churn dot value counts. Okay, so this is some data, right? So now what I will do, so there are okay, fine. So now what I will do here, I will normalize it. Churn dot value counts normalize equals to true. Okay, so we have 2850 users out of 3033 are loyal. Their churn value is 0. Okay, and to calculate fractions pass normalize is equals to true, I have did that to the value count function. Okay, so here you can see 0 and the 1 value counts, right? So now let's go for the sorting data. So what is sorting? So a data frame can be sorted by the values of one of the variables like columns. So for example, we can sort this table by total day charges using ascending or in descending, right? So now I will do here df. Okay, first let me write here sorting. Okay, df dot sort values by equals to total day charge ascending equals to false dot head. Dot head means I want to see the top 5 rows. Okay, so now what I did, total day charge. Okay, total day charge I have sorted in this. Ascending equals to false means I have sorted into the descending order. Okay, and the top 5 rows are this. Okay, 59 is the maximum, 59.64. Fine. So now, like, we can also sort by multiple tables, so in one go. Okay, so let me do it. df dot sort, same thing I have to write, values by equals to churn. Okay, let me write this. Yeah, churn comma then again total day charge comma ascending equals to true comma false. Then I want to see, okay, let me write the same dot at. Okay, first I will show you this 11111. Okay, then let me change it. See, it's sorted now. Fine. So these are the top 5 as per these two columns, churn and the total data charge column. Okay, so now we will perform some indexing and retrieving data. So a data frame can be indexed in a few different ways. Like to get a single column, you can use data frame name. Okay, and so now let's use this to answer a question about the column alone. So let's take one question like, what is the proportion of churned users in our data frame? Okay, proportion. Okay, df dot, we will do simply, we have to find the mean. I will write churn dot mean. That's it. Okay, so 14.5% is actually a quite bad for a company, such as a churn rate can make the company go bankrupt, right? So Boolean indexing with one column is also very convenient. So the syntax is, I will write here df, then again df churn equals to 1, then dot mean. Okay, so here what I am finding is what are the average values of numerical features for churn user. Okay, see, account length just ignore this warning. Okay, so account length is 102.66, area code is this, right? So now what I will do, I will find one more thing. So like we will find how much time, like in average, do churn users spend on the phone during daytime. Okay, df then churn equals to 1, then total day in minutes. We have this column, right? I hope so. We have this column, total day minutes. Okay, fine. Yeah, dot mean. Okay, so how much time an average churn user spend on the phone during daytime is 206. Okay, almost 207. Okay, so now let's take one more question, like what is the maximum length of international calls among loyal users? Okay, loyal user means where churn is 0, like who do not have the international plan. So here for that I will write df and df churn equals to 0. Here I will write and df, okay, I will, okay, international plan equals to no, because there is, see, you can see the international plan, no, yes, no, yes, no. Okay, no, then total international minutes. Okay, this. Okay, for the confirmation, let me copy it and paste. Okay, no issues. Dot maximum value. Yeah, so 18.9. Okay, so 18.9 is the maximum length of international calls among loyal user, whereas churn is 0, who do not have the international plan. Okay, so Indexing. Data frame can be indexed by column name, I told you already, or the row name, or by the serial number, you can say, of a row. So there is one method, LOC. Okay, method is used for the indexing by name, while iloc is another method for indexing by the number. Okay, first I will show you df dot, here I will write indexing, df dot loc comma state, then area code. Okay, so in this first case, we can say I gave the values of the rows with the index from 0 to 5, like inclusive, and the column labeled from the state to area code inclusive. Okay, so this is how you can perform indexing, okay, using by name. Okay, if you want indexing by the numbers, you have to use iloc instead of this loc. Iloc means location. Okay, don't get confused. 5 comma 0 to 3. Okay, see, you got the same almost, right? Yeah, this is 0 to 5, okay, and this is 0 to 3. 0 to 5 means 1 2 3 4 5, and 0 to 3 1 2 3. Fine. Yeah, so what if we need the first or the last line of the data frame? So we can also do that. So here simply you have to write simple thing, df -1. Okay, that's it. See, this is the last line, -1, last line. Fine. So if you want to, apply something to all the columns, so there is one more function which is apply. So how to do is df dot apply np dot max. Okay, right, it gave me all the maximum values of the particular table, sorry, particular column, not table. Okay, so this is how you can do this. So this apply method can also be used to apply a function to each row, I already told you. So to do this, you have to just specify the axis, or the lambda function are the very convenient in such scenarios. Like for example, let me give you one example, df, then df state, let's use the state. Okay, then dot apply lambda state and state 0 equals to w, which is starting from w. Okay, then dot, I need only 5 rows, dot it. Okay, so the state is starting from w, here it is. Okay, top 5, right? So yes, so there is one more function, map method, which is used to replace the values in a column by passing a dictionary or the form, right? So map function d equals to no okay, it is false, then yes is true, right? Then df international plan equals to df international plan dot map d. Okay, df dot head. Fine. Okay, there is some international plan. Okay, p is small. That is why I was saying, please write it carefully. Yeah. Okay, so this is the map function. Okay, so wherever there is no or yes, okay, so I have mapped it to the true false, right? Okay, see here you can see international plan, yes no yes no yes no. I have marked yes to false. And okay, why different? Because the series is different. Okay, here I have performed different thing. The numbers, just check the number. Okay, 0 1 2 3 4, right? Df dot head. Let me write this. So now let's compare. Okay, why it's coming? Because I have already performed that thing. So we'll go to here. See, no 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 no, yes yes. Now you can see here false false false, true true. So for no I gave false, and for the true, for the yes I gave true. Fine, this is the mapping. This is how you can do the mapping. Okay, so now let's do df equals to, same thing can be done using replace as well. There is one more function. Okay, let me give you the name. Stack replace. Dot replace, then voicemail plan. Oh, sorry, my bad. Plan D. Okay. Fine now. Yes. Then df dot. Okay. So what I took, voicemail plan. Right? Same. See, true, true, false, false. Because here, if you will see, I have write D. D equals to this. Again, you have to write no to false and yes to true. Same I used here, D. No need to write again and again. Fine. So now let's see how to do grouping. Okay. So first, the group by method divides the grouping columns by their values. Okay. First, let me write this grouping. Okay. So here I will write columns to show equals to total day minutes, right? Comma total if minutes, comma total night minutes. Okay, then df dot group by, then here I will write Chan, then here I will write columns to show dot describe percentile. Fine, where is it's empty. Fine, where there is error, df dot group by Chan by can DataFrame describe got an unexpected keyword argument percentile. Okay. Fine. It will be percentiles. Yeah. So this is how you can do the group by with a churn. Okay. So what I did. So let me explain the steps. So first, the group by method divides the grouping columns by their value. Okay. Then they become a new index in the resulting data frame. Then column of interest are selected, column to show, this column to show. Okay, so if column to show is not included, all the non-group by classes will be included. Finally, one or several functions are applied to obtain the groups for selected columns. So here what I did, we group the data according to their values of the churn variable and display stat of 3 columns in each group. Right, these 3 columns in each group. Same, count means standard deviation minimum 50%, max count means this. Okay, so this is how you can do grouping. Fine. So if you want to summarize the table, okay, suppose we want to see how observation in our sample are distributed in the context or two variable, churn and international plan. So to do so, we can build the contingency table using the cross tab method. I will show you. Okay, so here I will write summary table ed dot cross tab. Then I will write here data frame df churn comma df international plan. Okay, so this is the true false, the summary. Okay, we have this much true false 0 from the international plan, and the 41 are this much. Okay, for one there are 346 and 137 true. Right, so this is how you can perform the summary table. Right, you can do for the more also. So now let's create the pivot table. Okay, so let's make the tables. Stack pivot tables. Okay, pivot tables. Fine. So I will add df dot pivot table. Okay, then I will write here. Sorry. Yes. So here I will write total day calls, comma, I will take 3 column total if calls, comma, then total night calls, comma, then area code. Okay, comma, then aggregate function equals to mean. Okay, I'm using mean. Fine. So this is pivot, you got the area code and the mean of particular this thing. Right. So data frame transformation. So let me explain you first this pivot table. Okay, before moving forward. So so now we can see the most of the users are loyal and do not additional services. Okay, international plan or the voicemail. So this will resemble pivot table to those familiar with Excel and non, of course. Okay, so here the values are the list of variables to calculate stat for, and the index, okay, a list of variables to group data by. Okay, area code. Okay, and the aggregate function is what stat we need to calculate for the groups. Like we can use sum, mean, minimum, maximum. Okay, something else. Okay, so here I have used the mean. Right. So now let's predict the telecom churn. Okay, so now let's see how the churn rate is related to the international plan feature. So we will do this using cross tab contingency, already saw, and also through visual analysis with Seaborn. I've already told you with Matplotlib and the Seaborn, Pandas is crazy. Okay, so here I will write predicting telecom churn. Okay, so here I will write pd dot cross tab df churn. Okay, C is capital, churn, comma df international plan, comma margin equals to true. Okay, sorry, my bad, it's margins. Yeah, okay, we got the pivot table here using cost tab. So I will import here, import matplotlib for the charts. Matplotlib dot pyplot as plt. Then I will import Seaborn. Just remember to install all these libraries. Okay, you can use pip install Seaborn and pip install numpy, pip install pandas before using it. Seaborn as SNS. Then for the graphic retina, I will use config inline backend dot figure format equals to retina. Okay, then here I will write SNS dot count plot, where x equals to x-axis I'm giving. Okay, international plan, comma, let's set the hue equals to churn, then comma data will be df. Okay, see, we have the counting of using international plan, and the hue is churn. Okay, 0 and 1. Fine. So we can see that the international plan, the churn rate is much higher, which is an interesting observation. Perhaps the large and the poorly controlled expenses with international calls are very conflict. Okay, so now let's take a look to another important feature, which is customer service call. Let's also use to to make the summary table first. So for that I will do here pd dot cross tab df churn, comma df customer service calls, comma margins equals to true. Okay, yes. So again, I have made the summary table for the customer service calls. So now what I will create SNS dot count plot x equals to customer service calls, where hue is churn, then data equals to df churn. Yes. Okay, so this is how you can create the charts using pandas and the Seaborn. Fine. So therefore, predicting that the customer is not loyal, churn equals to 1 in the case of when the number of calls to the service center is greater than 3 and the international plan is added. Okay, so this is how you can do data analysis using pandas.
What are statistics in data science? Now, statistics is the science of collecting, analyzing, and interpreting data. By applying statistical methods, we can uncover patterns in the data and make informed decisions. Now, as we continue, you notice how these essential concepts will form the backbone of many data science practices. Let's explore the key functions of statistics in data science. First, statistics help summarize data using measures like mean, median, and variance. Next, it models uncertainty with probability and distributions, so we can better understand risk and variability in our data. It also tests hypotheses, such as when we use A/B testing to compare different outcomes. Statistics finds relationship through methods like regression and correlation, revealing how variables impact each other. And finally, all these tools enable data-driven decision-making, turning raw numbers into actionable insights. Now let's talk about why does statistics matter in data science. Statistics form the backbone of data science, providing the mathematical framework needed to make sense of data and draw reliable conclusions. Without statistics, it would be impossible to turn raw data into meaningful insights or make confident, evidence-based decisions. Now, let's have a look at the main branches of statistics: descriptive statistics and inferential statistics. So first, let's talk about the definition. Then we have got methods and measures. Now in the case of descriptive statistics, now let's have a look at the main branches of statistics. So basically there are two core branches: descriptive statistics and inferential statistics. Descriptive statistics summarizes and describes data using measures like mean, median, mode, range, and standard deviation. Its purpose is to organize and present data, typically with charts, graph, or summary tables. The scope of descriptive statistics is limited to the sample data itself. Now, on the other hand, inferential statistics makes inferences about populations based on samples. It uses methods like hypothesis testing, confidence intervals, and regression. The purpose here is to draw conclusions and make predictions with common examples including A/B testing and survey analysis. The scope of inferential statistics extends beyond the sample to the larger population. Understanding both these branches is essential for analyzing and interpreting data in any data science project. Now, let's take a closer look at the descriptive statistics, starting with measures of central tendency. The first measure here is mean, which is the average of all the values, simply calculated as the sum of all the data points divided by the total count. Next is the median, which represents the middle value when the data is sorted from lowest to highest. This is especially useful when dealing with skewed distributions. And finally, the mode is the most frequently occurring value in the data set, helping us identify common patterns or repeated outcomes. Let's continue our deep dive into descriptive statistics by looking at the measures of variability. First, we've got the range. This is simply the difference between the maximum and minimum value in a data set, showing us the spread of our data, which measures the average of the squared differences from the mean. This tells us how much the values in our data set differ from the average. Closely related is the standard deviation, which is the square root of the variance. It gives us a more intuitive sense of how much the values typically deviate from the mean. And finally, we've got the interquartile range, or we say IQR. This shows us the range of the middle 50% of our data, helping us understand how data is distributed across the center and avoid the effect of outliers. Understanding these four measures allows us to summarize not just the center of our data, but how spread out and varied our data set is. Now, let's look at some practical applications of descriptive statistics. One major use is the data exploration and summarization, where we quickly get an overview and basic understanding of complex data sets, helping track performance and detect problems early in fields like manufacturing or operations. And finally, they are central to business reporting and dashboards, where concise summaries are essential for managers to review trends and make data-driven decisions. So in short, descriptive statistics help transform raw data into clear, actionable information across many business, scientific, and operational contexts. Let's explore the first type of data in statistics, qualitative or categorical data. This type of data includes descriptive information that cannot be measured numerically, such as categories or labels, and yes or no responses. These are all about qualities or characteristics rather than quantities. Qualitative data can be further divided into two types: nominal, where the categories have no specific order, and ordinal, where the categories do have an order or ranking. Recognizing and classifying qualitative data is very important as it affects how information is analyzed and interpreted in statistics. Now let's discuss the second main type of data in statistics, which is quantitative or numerical data. This type of data includes information that can be measured and expressed with numbers, making it ideal for mathematical analysis. Quantitative data is further divided into two main categories. First, there is discrete data. These are countable values with specific fixed points such as the number of students, cars sold, or website clicks. Second, there is continuous data, which includes infinite possible values within a given range. Examples of continuous data include height, weight, temperature, or time. Understanding the distinction between discrete and continuous data is very important as it determines which statistical methods and visualizations will be most appropriate. Now let's dive into the fundamentals of probability. Probability measures the likelihood of an event occurring, and it's always expressed as a value between 0 and 1. Here are some key concepts. If the probability or P equals to 0, that means the event will never occur. If P is equals to 1, the event will always occur. And if P is equals to 0.5, the event has an equal chance of occurring or not occurring. It's truly a 50-50% scenario. Now, understanding these basic principles help us quantify uncertainty and make informed predictions about future outcomes. Now, let's look at the different types of probability. First, there's classical probability. This is based on equally likely outcomes such as flipping a fair coin or rolling a balanced die. Next, empirical probability, which relies on observed frequency. It's calculated from actual data, such as the proportion of rainy days over the past month. Let's say, for example, the probability of it's raining today given that it's cloudy. Understanding these three types help us choose the right approach for different situations, whether we are predicting outcomes, analyzing data, or making decisions under uncertainty. Now, probability has a wide range of powerful applications in data science. First of all, it is used in predictive modeling and machine learning, where algorithms estimate future outcomes based on existing data. Probability also plays a key role in risk management and decision making, helping businesses and researchers evaluate the likelihood of different scenarios and plan accordingly. Conditional probability, calculating the chance of one event given that the another has occurred. This is crucial in fields like healthcare, fraud detection, and marketing analytics. And finally, probability is foundational in A/B testing and experimental design, allowing us to measure the effectiveness of new strategies or products. These applications show how probability enables smarter, evidence-driven progress in modern data science. Let's look at one of the most common probability distributions, the normal distribution. This distribution is famous for its bell-shaped symmetric curve, which shows that most values cluster around the mean, with fewer and fewer values appearing as you move away from the center. Now, many natural phenomena like heights, test scores, and measurement errors tend to follow this pattern, making the normal distribution a key concept in statistics. It's characterized by two main parameters: the mean, which determines the center of the curve, and the standard deviation, which controls its spread. Recognizing the distribution helps analysts make predictions, calculate probabilities, and apply statistical techniques to real-world data. Next, let's explore the binomial distribution, which is another common probability distribution. The binomial distribution is discrete and is used for situations with binary outcomes like success or failure. It is based on a fixed number of trials where each trial has a constant probability of success, such as flipping a coin a certain number of times or tracking pass-fail rates. Examples of binomial experiment includes coin flips and measuring how many students pass or fail a test. This distribution helps us model and analyze outcomes when only two possibilities exist in each trial. Now, let's focus on the Poisson distribution, another key type of probability distribution. The Poisson distribution is a discrete distribution specifically used to model rare events. It's particularly helpful for modeling events that occur independently over a fixed interval of time or space. For example, it predicts how many times an event, like a customer arriving on a website receiving a visit, might happen in a certain period. Typical examples include customer arrivals at a store, defect rates in manufacturing, or counts of website visits over a set period. This distribution is a great tool for understanding and predicting random independent events that don't happen very often but are important to track. It's a branch that allows us to make inferences, predictions, or generalizations about a larger population using sample data. Here are some key concepts. First is the population versus sample. The population represents the entire group we want to know about, while the sample is the subset we actually collect data from. Next concept is sampling distribution, which refers to the distribution of a statistic across multiple samples from the same population. Standard error measures how much the sample statistic is expected to vary due to random sampling. And finally, margin of error tells us how much we can expect our estimates to differ from the true population value. Together, these concepts form the foundation for drawing reliable insights from sample data in inferential statistics. Let's review some of the main techniques used in inferential statistics. First, we've got hypothesis testing. This method allows us to test claims or ideas about population parameters based on sample data, helping us determine if observed results are statistically significant and reliability of our estimate. Next are confidence intervals. These provide a range of likely values for a population parameter, giving us a sense of possible variation, reliability of our estimate. And lastly, regression analysis is used to model and analyze the relationships between variables, allowing us to make predictions, uncover trends, and understand how changes in one factor might affect another. Now, let's walk through the hypothesis testing process. The first step is to formulate hypothesis. Start with null hypothesis, represented as H0, which states that there is no effect or difference. Then there's the alternative hypothesis, represented as H1, which suggests that an effect or difference does exist. Now, after setting up the hypothesis, the next step is to choose a significance level noted by alpha. Common choices for significance levels include 0.05, 5%, 0.01, 1%, 0.010, which is 10%. The significance level is important because it controls the likelihood of making a type 1 error, also known as false positive, and now each step in the process is critical for ensuring that statistical results are both meaningful and reliable. The next step is to collect and analyze sample data. Ensure the data is represented by choosing a good sample. Then calculate the appropriate and test statistic for your hypothesis test. Once that's done, it's time to make a decision. Compare the p-value to the chosen significance level alpha. Now, if the p-value is less than or equals to alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. And finally, interpret your results. Draw your conclusions with respect to the context and problem at hand, always keeping the bigger picture in mind. Following these steps helps ensure your hypothesis test is robust, clear, and meaningful. Let's review the common types of hypothesis test used in statistics. The one sample test compares the mean of a sample to a known value, and the one sample Z test is used when the population standard deviation is known. Next, we have two sample test. The independent samples t-test compares to the means of two different groups, while paired samples t-test compares before and after measurements for the same subject. For categorical data test, the chi-square test checks for the independence or goodness of fit. And Fisher's exact test is useful for small sample sizes. And lastly, non-parametric tests such as the Mann-Whitney U-test and Wilcoxon-signed rank test serve as alternatives to the t-test when data doesn't meet certain parametric assumptions. Choosing the right hypothesis test depends on your data type and the specific question you want to answer. Let's explore the central limit theorem, or CLT, a foundation for inferential statistics. The central limit theorem states that as the sample size increases, the distribution of sample means approaches a normal distribution, even if the original data isn't normally distributed. This sample works for any population distribution, making it incredibly powerful. Now, for good results, the sample size should typically be 30 or more. What's interesting is the sample mean distribution, which will have the same mean as the population. The standard error, which measures variability by the sample mean, equals sigma divided by the square root of n, and this gets smaller as the sample size grows. And finally, the formula shown here, which is z is equals to x minus nu divided by sigma over the square root of n. Let's standardize and compare sample means. The CLT makes most parametric statistics possible and is the backbone for many statistical tests. Let's review the main types of regression analysis which are used to model and understand relationships between variables. First up is linear regression. This technique analyzes the relationship between a continuous variable and another variable, resulting in a straight line. It's commonly used in predicting sales or prices. Next is logistic regression. Unlike linear regression, this method is used for binary outcomes, helping estimate probabilities such as whether an email is spam or a patient has a disease. Moving to multiple regression, this allows us to account for the effect of several variables at once, modeling more complex relationships like determining house prices. Lastly, polynomial regression, which is used for non-linear relationships. The resulting curve, rather than a straight line, lets us capture growth trends and other patterns that aren't linear. Understanding these types of regression help analysts choose the right model for the data and business's problem at hand. Let's clarify the important differences between correlation and causation. Correlation is statistical measure of how two variables move together. Correlation values range from -10 to +1. But remember, correlation does not imply causation. On the other hand, causation means that one variable actually causes changes in another. Establishing causation requires controlled experimentation and is much stronger relationship than simple correlation. Always be careful when interpreting results. Just because two variables move together doesn't mean one caused the other. Let's look at some common problems with interpreting correlation and causation. First is the third variable problem, which happens when a hidden variable affects both variables in a question, leading to a misleading connection. There's also this directionality problem where it's unclear which variable is causing others to change. But both are actually caused by a third variable, which is the hot weather. This demonstrates that correlation does not mean one variable causes the other, so always look for hidden factors before assuming causation. Let's talk about statistical errors, specifically type 1 and type 2 errors. Type 1 error, also called as false positive, occurs when we reject the true null hypothesis. In other words, we wrongly conclude there's an effect when there actually isn't. The probability of making this error is equal to the significance level alpha. For example, concluding a drug works when it actually doesn't. On the other hand, type 2 error is false negative, means failing to reject a false null hypothesis. That's when we miss a real effect or difference. The probability of type 2 error is beta. For example, missing the real effect of a drug and saying it doesn't work when it actually does. Understanding these errors is key for designing good experiments and interpreting statistical results properly. Let's look at 3 common sampling methods used in statistics. The first one is random sampling. Here, every individual in the population has an equal chance of being selected. Where every nth individual is chosen, random sampling is crucial for ensuring representative sample. Next is stratified sampling. The population is divided onto homogeneous subgroups or strata, and then a random sample is drawn from each group. This approach makes sure all the groups are represented in the sample. And finally, cluster sampling divides the population into clusters, often based on geography. Entire clusters are then randomly selected. It's cost effective and useful for large, spread out populations. Choosing the right method ensures the data truly represents the whole population and strengthens the study's conclusions. So guys, let's wrap up with some real-world applications of statistics. In business analytics, statistics are used for A/B testing to optimize websites, customer segmentation, and targeting, sales forecasting and demand planning, and quality control, and also process improvement. These techniques help businesses make smarter, data-driven decisions every day. Statistics play a vital role in healthcare and medicine as well. They are key for analyzing clinical trial results, conducting epidemiological studies, evaluating treatment, effectiveness, and identifying risk factors. By using these approaches, healthcare researchers and practitioners can improve patient outcomes in public health. From businesses to medicine, statistics transform raw information into actionable insights that create real impact. Statistics has a huge impact in technology, data science, and finance, and power recommender systems that personalize what users see. In finance, statistics help with risk assessment and management, optimizing investment portfolios, determining credit scores, and supporting market research and analysis. Now, these applications show how statistical techniques help make smarter decisions and solve complex challenges across high impact.
So now let's get started. Setting up is simple. Open your terminal and run this command. So if it's already installed in your laptop, then it will show you the requirement already satisfied. So to check the version that you're using in Seaborn, you can go with this command. So as you can see, the version is also shown. Let's understand how Seaborn thinks. The syntax is elegant. Once you get the pattern, you'll be able to use almost any function easily. Every Seaborn function follows a consistent pattern. So these are the 3 key parameters you'll use everywhere. That is data, X and Y columns. And hue is a parameter that is used to map the colors to categorical or numerical data. This is the template for almost every Seaborn chart. And SNS is our Seaborn. Plot is the kind of chart you want, like scatter plot, bar plot, or hist plot. Data takes your Pandas data frame. And X and Y are the column names you want on each axis. Once you understand this pattern, the rest is just remembering which plot type to call. So now let's quickly understand when to use Seaborn and Matplot library. Seaborn is when you want statistical plots fast, when you need automatic aggregation like mean with confidence intervals, or when you want the output without configuring every element manually. And use Matplot library when you need pixel level control or when you're building very custom chart types. And also when you need to fine-tune a Seaborn plot further. Seaborn ships with several classic datasets that is used for learning. So let's load 3 datasets throughout this tutorial. So now when we run it, The tips dataset captures the restaurant bills, and the Titanic has passenger survival data, and Iris contains flour measurements, and this is classic machine learning dataset. Now let's understand about different plots. Univariate means we are looking at one variable at a time. The goal is to understand its distribution and how the values are spread and where they cluster and whether there are any outliers. And his plot is a modern way to plot the distributions. Now let's quickly go through that. So as you can see here, the smooth kernel density evaluation parameter, and it is great for spotting the shape of your data. So it's basically used for smoother distribution visualization. So here in the output, the KD plot, that is kernel density estimation, it draws only the smooth density curve and no bars at all. So the fill equal to parameter shades the entire area under the curve. It makes it easier to see where the bulk of the data is. So the color parameter sets the fill color. So use KD plot when you want a clean, elegant view of distribution, and that is shaped without histogram bars cluttering the chart. Now let's understand about bivariate plots. So bivariate plots explore the relationship between two variables, such as if one thing changes, what happens to the other. So let's talk about this output. Here, each dot on this chart represents one restaurant visit. So its X position shows the total bill amount, and the Y position shows the tip, and the hue equal to smoker, the parameter colors dots differently for smokers and non-smokers. It lets us see if smoking correlates with the tipping behavior. And the style equal to time parameter, it changes the dot shape for lunch versus dinner. That's 4 dimensions of information visualized in a single chart. So if you take a look at the upward trend, bigger bills generally receive bigger tips. So as you can see here, the bill is 50, and here he is a smoker. As you can see, the total bill is larger here, and the tips received is larger as well. Now let's quickly explore line plot. So in the output, the line plot draws a line connecting the average tip for each party size broken down by the day of the week using hue as day. Seaborn automatically calculates the mean for each group, and it adds a shaded confidence interval as well around the line. It shows how certain we are about that average. So it shows us whether larger tables tip more and whether that pattern differs across different days by the week. Now let's quickly understand categorical plots. So in this output, this plots the average total bill for each day of the week, and it is split by the gender using hue. So the black vertical lines here on the top of each bar are 95% confidence intervals. So they tell you how reliable the average data is. And a short confidence interval such as Friday, here, it shows us the data points are confident in that average. A tall one means its variability, and Seaborn calculates all of this automatically. But in Matplot library, you need to compute it manually. So now let's understand about count plot. So this is the output of count plot. So unlike the bar plot, which averages a numeric column, count plot simply counts how many rows fall into that category. So here it counts how many Titanic passengers were in each class, first, second, and third. And hue equal to survived here, it splits each bar to show survivors versus non-survivors. So in this output, we can see that third class by far had the most passengers, but the lowest survival rate. Now let's go through the box plot. So the output here, a box plot is a chart that shows you the summary of your data in one box shape. So the line in the middle of the box is the median, meaning exactly half the tips were above this value and half were below it. So the bottom and the top edges of this box shows where the middle 50% of all the tips fall. So most of the typical tips live inside this box, and the lines stretching above and below this box are called whiskers, and they extend to the highest and the lowest values in your data. Any dots, that is these that are going high and low, are the outliers. So people who tipped unusually more high or more low compared to everyone else are known as outliers. And hue equal to smoker splits each day into two boxes side by side, one for smokers and the other for non-smokers. So you can compare both groups without needing two separate charts. Now let's quickly understand about violin plot. So here a violin plot combines a box plot with a KD curve. So the wider the violin at any point, the more data values exist in that range. The split equal to true parameter is a powerful trick. Instead of drawing two completely separate violins for each hue group, it draws one violin with each half representing one group. So this makes it extremely easy to compare the distribution shapes of the smokers and non-smokers side by side. So as you can see here on Thursday, the smokers are more compared to the non-smokers. So the violin width is larger for smokers compared to non-smokers. This is how violin plot works. So now let's understand about themes and styles. Seaborn has 5 built-in themes that control the overall background appearance. So the syntax for that is, so you're telling the Seaborn to set the style as white grid for the clean background with grid lines. Dark grid can be used with grid lines with dark background. And white is used for minimal white background. And this is used when there is no grid and dark background. Ticks is when you want a white background with tick marks only. So as you can see here, the code is executed. You can call this once at top of your notebook and it applies globally to every chart you draw. So now let's quickly understand about titles, labels, and legends. So when you assign a Seaborn plot to a variable called AX, you get access to the underlying matplot access object. From there, set_title function adds a little title with custom font size and weight. Set_x label function and set_y label function, it replaces the default row columns names like total bill with clean labels including the units. And the legend function customizes the legend title and position upper left. It keeps it from overlapping the data points clustered in the lower right area. So now let's understand about hue, size, and style. These three parameters encode the additional dimensions in one chart. So this is the output. In this single chart, it has 5 variables simultaneously. X and Y gives us the 2 primary axes, and hue is the day that changes the dot color based on the day of the week. Such as Thursday gets one color and Friday another, and so on. And size makes the dots physically larger for bigger dining. For example, 6th table gets higher dots compared to 2nd table. And style equal to smoker, it changes the marker shape, such as circles for smokers and cross mark for non-smokers. That's about the scatter plot here. So now let's quickly analyze about multivariate plots. So pair plot, one of the first things any data scientist runs on a new data set. It plots every numerical variable against every other. So as you can see here, the pair plot automatically creates a pair of scatter plots, one for every combination of numeric columns in the dataset. That is, the IRIS dataset has 4 numerical features, so pair plots creates a 4x4 grid. That's 16 charts generated from a single function call. So the diagonal calls, it is where a variable would normally be plotted against itself. So the hue equal to species colors at every single point by flower species, making it obvious for which feature combination it best separates the 3 species. And this is called exploratory data analysis. Now let's quickly go through the heat map. So here first the tips dot correlation, it calculates the Poisson correlation coefficient between every pair of numeric columns. It produces a table of values between -1. So think of it this way. Imagine asking how similar is my height to my height. So the answer is obviously perfectly identical. So it's comparing a column to itself. So it will obviously be 1. So every single row will match exactly. And this is why the diagonal of every correlation matrix is always 1. So now let's go through the total bill versus tip, that is 0.68. Here the bigger the bill, the bigger the tip is. So when total bill goes up, the tip also tends to go up, and when it goes down, it tends to goes down. Now you might think why it's not 1, because it's not a perfect rule. Some people on big bills tip poorly and some people on small tips are very generous. So the relationship is strong but not perfect. So it's 0.68 and not 1. If we see total bill versus size, it's 0.60. So more people, more orders and bigger bill. That's when 0.60 comes in. So the bigger party size tends to give a bigger bill and smaller party produces a smaller bill. So why it's lower than 0.68? Because party size does not control the bill as directly as you'd think. So 2 people can order steak and wine and spend more than a table of 4 ordering cheaply. So the link exists, but it is a bit looser. Hence it is 0.60. Now let's go through 3 projects. So here the survived column contains 1 for survived and 0 for did not survive. When we use it as a y-axis in bar plot, Seaborn automatically calculates the mean, which equals the survival rate as a proportion. So a bar at 0.75 means 75% of the group is survived. So here the first class passengers, particularly women, had dramatically higher survival rates. So this is the age distribution of survivors versus non-survivors. Here the KD curves on the same chart. That is 1 for survivors and 1 for non-survivors. The common norm equal to false is critical here. It tells Seaborn to normalize each curve independently. So both the curves have equal area, and even though the groups have different sizes. So without this, the smaller group's curve would appear as a tiny bump next to towering curve. So the result clearly shows where the age distributions differed between those who survived and those who did not. Now let's quickly go through the restaurant tip analysis. So here first we create a new column called tip_PCT by dividing the tip by total bill and multiplying it by 100. This converts the tip into a percentage. So this matters because a $5 tip on a $20 bill is generous, but $5 tip on a $50 bill is quite low. So the raw tip amount alone, it doesn't tell the full story. We then plot this percentage by the smoker and non-smoker groups using box plot, which shows us the typical tipping percentage and how consistent it is, and whether any usually high or low tippers exist for each group on each day. So now, as we've seen the restaurant tip analysis, let's understand about the business intelligence dashboard. So as you can see in the output, now we can see histogram plot and bar plot, box plot and scatter plot. So here the plot.subplots of 2 into 2 creates a 2 row by 2 column grid of 4 empty chart areas returning the overall figures as fig and a 2D array of axis slots. So figure size of 14,10 that we've written, it sets the total canvas size in the inches. So the key to placing each chart in the corrected slot is the axis parameter. That is Ax equal to axis of 0 to 0, it goes to top left. That is to the histogram plot. And axis 0, 1, it goes to top right. Axis 1, 0, it goes to bottom left. And 1, 1 goes to bottom right. And the subtitle adds a single title across the entire figure. As you can see here in the output, there's the 0, 0 axis and 0, 1, 1, 0 and 1, 1. So the title layout function, it adjusts the spacing automatically so panels never overlap. So now we have done with the business intelligence dashboard. Let's quickly understand about Seaborn plus Pandas group by and matplotlib integration. So this basically splits the data frame into 2 groups that is based on every unique combination of day and time values. So the tip.mean function, it calculates the average tip for each of these groups. And the reset_index function, it converts the result back into a flat regular data frame that is necessary because Seaborn expects standard column-based data frames, not the hierarchical index structures. So this approach is useful when you need custom aggregations, medians, standard deviations, counts, or beyond what C built-in estimator handles on its own. So now let's quickly understand about how while-in plot works with Seaborn and matplotlib. So in this, here we've written a code in such a way that while-in plot, it sets the title as tip distribution by day, and the split should be equal to true, and the data as tips, and the X column should be named as day and Y as. So we start by creating a matplot figure and axis object with plot.subplots, then pass this axis into the Seaborn while-in plot. So it tells Seaborn exactly which canvas the panel should draw on. So after the while-in shows, the ax.axline function, it draws a horizontal reference line at the overall average tip value. This is pure matplotlib code layered on top of Seaborn chart. So the dashed red line that you see here, it makes it immediately obvious which groups tip above and which fall below average. So this is how Seaborn and matplotlib works together. Now let's quickly save our charts. So here the plot.saveFigure function, it must always be called before the plot.show function because show function clears the figure entirely from the memory. That is DPI equal to 300, sets the resolution to 300 dots per inch, which is the standard for print quality output. So make sure to save it before the show. So the bbox_inches is equal to tight automatically crops the saved image to fit the content snugly. It prevents axis labels and titles from being cut off from the edges. So the SVG saves as a vector file, meaning it scales to any size without pixelation. It's ideal for charts that appear in different sizes across different media. Now let me tell you some visual storytelling tips. First, lead with the insight. Tell your chart with the conclusion and not just the variables. Next, use color purposefully. Every color should communicate meaning and not just the decoration. Next, reduce the chart junk. Remove the grid lines, borders, and legends that doesn't need extra information. Choose the right chart. For distribution, use histoplot, and for comparison, use bar plot, and for relationship, always try to use scatter. And annotate the key points. Use plot.annotate to call out the most important insight directly on the chart. So let's quickly understand what are the common errors you will be facing while working with Seaborn. So this could not convert string to float. This happens when a categorical column is being used when Seaborn expects numbers. Next, when you use the old displot function, Python throws a future warning telling you that this function is outdated and it will be completely removed in a future version of Seaborn. So the fix is simple here. Just replace it with histogram plot of KD equal to true, which does the exact same thing. It draws a histogram with a smooth curve on top. It's just the newer supported version of the same chart, so you can use this. Hue column has too many unique values. Hue works best with 2 to 6 categories, so delete them first using pd.cut function. The next is when a plot appears but shows nothing. This is when you call plot.show before adding all the customization. Always customize first, then show last. So the following are the best practices that you can follow while working with Seaborn. Always set a figure size when you show subplots. Use the theme function at the start of your notebook for consistent style. Always label the axis and add titles. Save the high DPI versions, that is dot per index, to 300 for reports and presentations. Alright, now we're going to write one connected block of code that creates a complete professional 6-panel analysis dashboard using everything we've learned. Let's walk through it. So here we start by creating a large blank canvas that is 16 to 12 inches with the master title on top. Then figure.add underscore subplot, it divides it into 2 or 3 column and a grid of 6 panels. So the panel 1 is a scatter plot. It plots the sepal length versus width colored by the species. It shows whether the species separate by sepal shape alone. The next one here is box plot. It compares petal length across the species. Setosa is immediately visible as having dramatically shorter petals. So here, as we can see, the length of the petal setosa is very less compared to the other species. Next we have is heat map. Here it shows a correlation between the 4 numerical measurements. The species is dropped first because correlation function only works on the numbers. Next here we have KDE plot. It gets a KDE plot of petal width with 3 overlapping filled curves, 1 per species. It shows the full distribution shape and exactly where the species overlap. Next here we have violin plot. Violin plot gets a violin plot of sepal length across the species. It combines the summary statistics of a box plot with the full distribution shape of a KDE. It shows that the sepal length is weaker separator between species compared to petal measurements. And here in the panel 6, that is count plot, here it counts the samples per all the species. It confirms all the species have exactly 50 rows, perfectly balanced data set. So finally, we have type.layout function. It fixes the panel spacing. The save figure, it saves the dashboard to 300 dpi before memory is cleared. And show function, it shows everything on the screen. So here in the code, we've just written the things that it should be shown here. For example, if we take the heat map, the correlation should be true and the C map should be cool warm. And we set the title as feature correlations. And the subplot is 2, 3, 3. That is the rows, columns, and where it should be placed. And the species, the iris dot drop of species axis equal to 1. So we've used a correlation function here, so only numbers will be considered. It is same for all the plots. We've written a code in such a way that where it should appear and how it should appear as the output. So this is about a final project. Feel free to modify according to your requirements and change the figure size and the subtitles and the colors accordingly and try it with your own requirements.
So what is normal distribution? Normal distribution is a continuous probability density that has a probability density function which gives us a symmetrical bell curve. Now data can be distributed or spread out in different ways, but there are many cases where the data tends to be around a central value with no bias to the left or right, which means that it doesn't show any particular spikes towards the left or the right, and it gets close to a normal distribution. Half of the data will fall on the left of the mean and the other half will fall on the right. Now let's take a look at a graph which shows the height distribution in a class. As you can see, the average height is in the middle and the data to the left of the average height represents the short people and the data to the right of it represents the taller people. The y-axis shows us the likelihood of any of these heights occurring. The average height has the most distribution, or it has the most number of cases in the class, and as the height decreases or increases, the number of people who have that height also decreases. This kind of a distribution is called a normal distribution, where the average or the mean is always the highest point and any other point after that or before that is significantly lower. The resulting data gives us a bell curve, and as you can see, there is no abrupt bias or spike in the data anywhere except for the average height. So this kind of a curve is called a bell curve, and it's usually seen in a normal distribution. The reason we call this a normal distribution is because the data is normally distributed, with the average being the highest and all the other data points having a lower likelihood. Now we came across two terms which are associated with normal distribution: continuous probability density and probability density function. What is continuous probability density? Continuous probability density is a probability distribution where the random variable x can take any given value. Because there are infinite values that x could assume, the probability of x taking on any specific value is 0. For example, let's say you have a continuous probability density for men's height. What is the probability that a man will have the exact height of 70 inches? It is impossible to find this out because the probability of one man measuring exactly 70 inches is very low. It is more probable that he will measure around 70.1 inches or maybe 69.97 inches. And it doesn't stop there. The fact is that it's impossible to exactly measure any variable that's on a continuous scale. And because of this, it's impossible to figure out the probability of one exact measurement which is occurring in a continuous probability density. Next, we have the probability density function. It's nothing but a function or an expression which is used to define the range of values that a continuous random variable can take. An example of this would be to gauge the risk and reward of a stock. A probability density function is a statistical measure which is used to gauge the likelihood of a discrete value. A discrete variable can be measured exactly while a continuous variable can have infinite values. However, for both continuous as well as discrete variables, we can define a function which gives us the range of values within which these variables will fall. And that function is known as the probability density function. Now let's take a look at standard deviation. What is standard deviation? Standard deviation is used to measure how the values in your data differ from one another or how spread out your data is. A standard deviation is a statistic that measures the dispersion of a data set relative to its mean. The standard deviation is calculated as the square root of variance by determining each data point's deviation relative to the mean. If the data points are further from the mean, that means that there's a higher deviation within the data set, and then the data is said to be more spread out. This leads to a higher standard deviation too. Let's take an example of income in rural and urban areas. In rural areas, let's say such as farming areas, the income doesn't differ that much. More or less everyone earns the same. Because of this, our bell curve has a very low standard deviation and it has a very narrow peak. However, in urban areas, the wealth distribution is very uneven. Some people can have very high incomes and can be earning a lot, while other people can have very low incomes. Furthermore, the data distribution between these two income points is going to be more spread out because there are a lot more people living there who work in various fields and who have various incomes. Because of this, our standard deviation is more spread out and our bell curve will also have a wider peak. Now, how can we find the standard deviation? Standard deviation is obtained by subtracting each data value from the mean and finding the squared average of these values. Let's look at how we can do this with the help of an example. These values correspond to the height of various dogs. We can find the mean by finding the average of all these values, which is nothing but adding all the values and dividing it by the total number of values. The mean that we get is 394. This means that the average height of a dog is 394 millimeters. To find the standard deviation, first we need to subtract the height from the mean. This will tell us how far from the mean our data points actually are. Next, we will square up all of these differences and add them up and again divide it by the total number of values that we have. This is called the variance. The variance that we get in this case is 21704. Finally, when we find the square root of this value, we will get the standard deviation. The standard deviation here is 147. The standard deviation will tell us how our data points differ from the average. And it gives us a basic value suggesting how spread out our data is from the very middle or from the mean. So when we plot these values, this value 147 will mean that a curve will have a width of 147 points around the mean. Now, what is the standard normal distribution? The standard normal distribution is a type of normal distribution that has a mean of 0 and a standard deviation of 1. This means that the normal distribution has its center at 0 and it has intervals which increase by 1. All normal distributions, like the standard normal distribution, are unimodal and symmetrically distributed with a bell-shaped curve. However, a normal distribution can take on any value as its mean and standard deviation. In the standard normal distribution, however, the mean and standard deviation are always fixed. When you standardize a normal distribution, the mean becomes 0 and the standard deviation becomes 1. This allows you to easily calculate the probability of certain values occurring in your distribution, or to compare data sets with different mean and standard deviations. The curve shows a standard normal distribution. As you can see, again, the data is centered at 0. This does not mean that the data necessarily starts at 0. This means that after standardizing, this point is where our mean will lie. In a standard normal distribution, the standard deviation is 1. So all the data points will increase or decrease in steps of 1. Let's better understand a standard normal distribution with the help of an example. Again, as you can see, the data is centered around 0, which is nothing but the mean. Let's again consider the weights of students in class 8th. The average weight here is around 50 kgs, and the data increases and decreases in steps of 5. The data over here in this curve is evenly distributed along these steps. This is what a standard normal distribution will look like. We already know that the mean of our data is 50, and because the data is increasing and decreasing in equal steps, we can just standardize it and take it to mean that the data is increasing and decreasing in steps of 1. This is what a standard normal distribution looks like, and when you have a data which looks like this, you can always standardize it and convert it into a standard normal distribution. Now, standard normal distribution has a couple of properties which makes calculation comparatively easy. The first one is that 68% of the values fall within the first standard deviation, which means that 68% of all data values on this curve will fall between the range of -1 to 1, or the first interval ranging from -1 to 1. The second property is that 95% of the rest of the values are within the second standard deviation, or from the second negative point to the second positive point. And finally, 99.7% of the values fall within the third standard deviation, or from the third negative point to the third positive point. This makes calculations on standard normal distribution fairly easy. You can compare scores on different distributions with different means and standard deviations. You can normalize scores for statistical decision making using standard normal distribution. You can find the probability of observations in a distribution which fall above or below a given value. And finally, you can find the probability that a mean significantly differs from a population mean. Now let's take a look at z-score. So what is a z-score? A z-score is used to tell us how far from the mean our data point actually is. It is calculated using the mean and standard deviation, so it can be said that the z-score is how many standard deviations below the mean our data is. Basically, by using the z-score, we can get an approximate location of where our data point lies on the graph with regards to the mean. Now the z-score is given by subtracting the data point from the mean and dividing it by standard deviation. This can also be written as x minus mu divided by sigma. Now any normal distribution can be standardized by converting its values into z-scores. The z-score will tell you how many standard deviation from the mean each values lie. While data points are referred to as x in a normal distribution, they are called z or z-scores in the z distribution. A z-score is a standard score that will tell you how many standard deviations away from the mean an individual point will lie. A positive z-score will mean that your x value is greater than the mean, and a negative z-score will mean that your x value is less than the mean. A z-score of 0 will mean that your x value is equal to the mean. And again, to standardize a value from a normal distribution, all we have to do is convert it to a z-score by subtracting the mean from our individual value and dividing it by the standard deviation. Now let's see how we can find the z-score from data points with the help of a solved example. Let's do a case study. In this case study, we'll be taking the summary of daily travel time of a person who's commuting to and from work. All these values are in minutes. And using these values, we have to calculate the mean, the standard deviation, and the z-score. These values are as shown. As we can see, there are 13 values in total. Let's start by finding the mean. The mean is the average, and it can be gotten by adding all of these values and dividing it by the total number of values. This gives us a value of 38.6. The mean tells us the average of all our data points, which means on an average, he travels for 38.6 minutes to reach work. Next, let's subtract the individual values from our mean and calculate the variance and standard deviation. The values on the left give us the values that we get after subtracting it from the mean, and the variance can be calculated by squaring all of these values, adding up all of the squared values, and dividing it by the total number of values. At the end of the day, we get a variance of 140. To calculate the standard deviation, all we have to do is take a square root of the variance, which gives us a value of 11.8. Now, the mean signifies the average of our values, and we already know this. It gives us the average time which is taken to travel. But the standard deviation will tell us the average value of how much our data points differ from the mean. It tells us the deviation within our own data, and it tells us how far away on an average a point is from the mean. Now, the value that we get is 11.8, which means that on an average, a single data point is around 11.8 data points away from the mean. Now let's calculate the z-score. The z-score is given by subtracting individual data points from the mean and dividing it by the standard deviation. We know that we have a standard deviation of 11.8 and a mean of 38.6. Using these values, we can calculate the z-scores for individual x values. Now we know that a negative z-score means that our x value is lower than our mean. But what does the number 1.06 mean? This means that the z-score for 26 is 1.06 standard deviations away from the mean. The negative symbol here means that our x value is less than the mean. And by how less? 1.06 times the standard deviation. Now we know that the negative value of a z-score means that our x value is less than our mean. But what does the number 1.06 mean? This means that the z-score is 1.06 times the standard deviation less than the mean. The same thing can be said for the z-score of 33. It is 0.47 times the standard deviation less than the mean. The z-score of 65 is 2.23 times the standard deviation more than the mean. That means it has to be added to the mean. The reason that we know it's more than the mean is because this has a positive value. So this means that using z-scores, we can know where our data points fall relative to other points on the graph. The z-score will tell us how far away from the mean a point is in steps of our standard deviation.
Basics and terminology. The first one is outcome. Whenever we do an experiment like flipping a coin or rolling a dice, we get an outcome. For example, if we flip a coin, we get an outcome of heads or tails, and if we roll a die, we get an outcome of 1, 2, 3, 4, 5 or 6. Random experiment. A random experiment is any well-defined procedure that produces an observable outcome that could not be perfectly predicted in advance. A random experiment must be well defined to eliminate any vagueness or surprise. It must produce a definite observable outcome so that you know what happened after the random experiment is run. Random events. Consider a simple example. Let us say that we toss a coin up in the air. What can happen when it gets back? It either gives a head or a tail. These two are known as outcome, and the occurrence of an outcome is an event. Thus, the event is the outcome of some phenomenon. The last one is sample space. A sample space is a collection or a set of possible outcomes of a random experiment. The sample space is represented using the symbol S. The subset of all possible outcomes of an experiment is called events, and a sample space may contain a number of outcomes that depends on the experiment. If it contains a finite number of outcomes, then it is known as a discrete or finite sample spaces. Now let's discuss what is random variable. A random variable is a numerical description of the outcome of a statistical experiment. A random variable that may assume only a finite number of values is said to be discrete. One that may assume any value in some interval on the real number line is said to be continuous. Let's see an example. Let x be a random variable defined as the sum of numbers when two dice are rolled. X can assume the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Notice there is no 1 here because the sum on the two dice can never be 1. Now that we know the basics, let's move on to binomial distribution. The binomial distribution is used when there are exactly two mutually exclusive outcomes of a trial. These outcomes are appropriately labeled success and failure. The binomial distribution is used to obtain the probability of observing x successes in n number of trials, with the probability of success on a single trial denoted by p. The binomial distribution assumes that p is fixed for all the trials. Here is a real-life example of a binomial distribution. Suppose you purchase a lottery ticket, then either you are going to win the lottery or not. In other words, the outcome will be either success or failure that can be proved through binomial distribution. There are four important conditions that needs to be fulfilled for an experiment to be a binomial experiment. The first one is there should be a fixed number of n trials carried out. The outcome of a given trial is only 2, that is either a success or a failure. The probability of success remains constant from trial to trial. It does not change from one trial to another. And the trials are independent. The outcome of a trial is not affected by the outcome of any other trial. To calculate the binomial coefficient, we use the formula which is NCR into p to the power r into 1 minus p to the power n minus r, where r is the number of success in n number of trials and p is the probability of success. 1 minus p denotes the probability of a failure. Now, let's use this formula to solve an example. Suppose a die is tossed 3 times. What is the probability of no 5 turning up, 1 5 and 3 5s turning up? To calculate the no 5 turning up, here r is equal to 0 and n is equal to 3. Substituting the value in the formula, we have 3c0 into 1 by 6 to the power 0 into 5 by 6 to the power 3, where 1 by 6 is the probability of success and 5 by 6 is the probability of failure. Calculating this equation, we'll get the value to be 0.5787. In a similar manner, to calculate the probability of 1 5 turning up, we'll replace r with 1 and n will be 3. So px1 will be equal to 3c1 into 1 by 6 to the power 1 into 5 by 6 to the power 2, which will come out to be 0.347. And for 3 5 turning up, we'll substitute r equal to 3 and the formula will remain the same and we'll get the value to be 0.0046. Now that we are done with the concepts of binomial probability distribution, here's a problem for you to solve. Post your answers in the comment section and let us know. A Poisson distribution is a probability distribution used in statistics to show how many times an event is likely to happen over a given period of time. To put it another way, it's a count distribution. Poisson distributions are frequently used to comprehend independent event at a constant rate over a given interval of time. The Poisson distribution was developed by French mathematician Simon Denis Poisson in 1837. A Poisson distribution is used in cases where the chances of any individual event being a success is very small. The number of defective pencils per box of a 6,000 pencil, the number of plane crashes in India in 1 year, or the number of printing mistakes in each page of a book. All of these examples can have use of Poisson distribution. The Poisson distribution can be used to calculate how likely it is that something will happen x number of times. A random variable x has a Poisson distribution with parameter lambda, and the formula for that is e to the power minus lambda into lambda to the power x divided by x factorial, where x can be the number of times the event is happening. The value of e is taken as 2.7182. Let's discuss some application of Poisson distribution. If you want to calculate the number of deaths per day or week due to rare disease in a hospital, you can use the Poisson distribution. In a similar manner, the count of bacteria per cc in blood or the number of computers infected with virus per week. The number of mishandled baggage per 1000 passengers can also have an application for Poisson distribution. Let's discuss one example to see how you can calculate the Poisson distribution. Suppose on an average, a cancer kills 5 people each year in India. What is the probability that one person is killed this year? We'll assume all these events are independent random events. So, by the formula, we have x is equal to 1 because we have to calculate the probability of one person that is killed this year. So, p x equal to 1 will be equal to e to the power minus 5 into 5 to the power 1 divided by 1 factorial, which will come out to be 0.033, which will be near to 3.3%. So, the probability that only one person is killed this year due to cancer is 3.3%. Now, we have one question for you. Do try to answer in the comment section. Suppose the trains arrive at a railway station with an average arrival rate of 4 trains per hour. What is the probability exactly 6 trains will arrive in a 2-hour period? And here are our options. Please do let us know your answers in the comment section. The research hypothesis, which is also denoted by H1, says that the two variables are related in the population. The acceptance of the research hypothesis follows the rejection of the null hypothesis. The null hypothesis, H0, says that there is no association between the two variables and they are statistically independent. The null hypothesis has no bearing on the study's outcome unless it is rejected. Now let's define expected and observed frequencies. Expected frequencies are the value that we would get if the two tables were statistically independent. The expected values are calculated based on our null hypothesis. The observed frequencies are those frequencies that we gather ourselves from our observation. To calculate the expected frequency, we have a direct formula. We multiply the row total by the column total and divide the whole value by the total number of observations. Now let's move on to chi-square test. The chi-square test is a statistical procedure for determining the difference between observed and expected data. This test can also be used to determine whether categorical variables in our data are correlated. It helps to find out whether a difference between two categorical variables is due to chance or a relationship between them. The chi-square test requires no assumptions about the shape of the population distribution from which the sample is drawn. However, like all inferential techniques, they assume the random sampling. The chi-square test do have some limitations. Firstly, the chi-square test does not give much information about the strength of the relation or its significance in the population. The chi-square test is also sensitive to sample size. The calculated chi-square statistics is directly proportional to the size of the sample, which is independent of the strength of the relation between the variables. So, to calculate the chi-square statistics, we have a direct formula. The chi-square statistics, which is also denoted by x square, is equal to summation of expected frequencies minus observed frequencies whole square divided by expected frequencies. The chi-square test statistics follow 5 steps. First, we make assumptions about random sampling and state its research and null hypothesis. Then, we select the sampling distribution and specify the test statistics, and after that, we compute the test statistics. The value we get is used to decide and interpret the results. Degree of freedom. The degree of freedom is a statistical calculation which represents the number of variables that can vary in a calculation. The degree of freedom can be calculated to ensure that the chi-square tests are statistically valid. These tests are frequently used to compare observed data with the data that would be expected to be obtained if a particular hypothesis were true. The formula to calculate degree of freedom is number of rows minus 1 multiplied by number of columns minus 1. So, after knowing the formula, we have a question for you. How many degree of freedom would a table with 3 rows and 2 columns would have? Post your answers in the comment section. Now that we have learned all the theoretical concepts regarding chi-square test, let's understand this more clearly with the help of an example. Let's say we want to know if the gender has anything to do with the handedness of the people. We have the data of 2237 people in a simple random sample to find out if they are left-handed, right-handed or both. The results of the survey are shown in the table below. To see if the gender is linked to handedness, we perform a chi-square test. The first step is to define the null hypothesis. The null hypothesis says that the gender and handedness are independent to each other. The next step is to calculate the expected values. The expected value is calculated using the formula that is shown in the slide, which is row total into column total divided by the total number of observations. For example, the expected value of a right-handed man can be calculated by multiplying 1067 into 2004 divided by 2237, which comes out to be 956. In a similar manner, you can calculate the expected value for each of the cell. After calculating the expected value, we calculate the value of x square. X square is calculated by the following formula: observed frequency minus expected frequencies whole square divided by expected frequency. So, by putting the values in the formula, we get the x square value to be 12. Now, we got our x square, which is chi squared value, to be 12, and the degree of freedom is equal to 2, which is calculated by r minus 1 into c minus 1, where r and c were rows and columns respectively. The alpha value was assumed to be 0.05. We compare our chi square value with the critical values of the chi square distribution with the degree of freedom. So for degree of freedom 2 and alpha level 0.05, the value was 5.991, which was lower than our chi squared value. This states that handedness and gender are not very likely to be independent. Basics and terminology. The first one is outcome. Whenever we do an experiment like flipping a coin or rolling a dice, we get an outcome. For example, if we flip a coin, we get an outcome of heads or tails, and if we roll a die, we get an outcome of 1, 2, 3, 4, 5 or 6. Random experiment. A random experiment is any well-defined procedure that produces an observable outcome that could not be perfectly predicted in advance. A random experiment must be well-defined to eliminate any vagueness or surprise. It must produce a definite observable outcome so that you know what happened after the random experiment is run. Random events. Consider a simple example. Let us say that we toss a coin up in the air. What can happen when it gets back? It will either give a head or a tail. These two are known as outcome, and the occurrence of an outcome is an event. Thus, the event is the outcome of some phenomenon. The last one is sample space. A sample space is a collection or a set of possible outcomes of a random experiment. The sample space is represented using the symbol S. The subset of all possible outcomes of an experiment is called events, and a sample space may contain a number of outcomes that depends on the experiment. If it contains a finite number of outcomes, then it is known as a discrete or finite sample spaces. Now let's discuss what is random variable. A random variable is a numerical description of the outcome of a statistical experiment. A random variable that may assume only a finite number of values is said to be discrete. One that may assume any value in some interval on the real number line is said to be continuous. Let's see an example. Let x be a random variable defined as the sum of numbers when two dice are rolled. X can assume the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Notice there is no 1 here because the sum on the two dice can never be 1. Now that we know the basics, let's move on to binomial distribution. The binomial distribution is used when there are exactly two mutually exclusive outcomes of a trial. These outcomes are appropriately labeled success and failure. The binomial distribution is used to obtain the probability of observing x successes in n number of trials, with the probability of success on a single trial denoted by p. The binomial distribution assumes that p is fixed for all the trials. Here is a real-life example of a binomial distribution. Suppose you purchase a lottery ticket, then either you are going to win the lottery or not. In other words, the outcome will be either success or failure that can be proved through binomial distribution. There are 4 important conditions that needs to be fulfilled for an experiment to be a binomial experiment. The first one is there should be a fixed number of n trials carried out. The outcome of a given trial is only 2, that is either a success or a failure. The probability of success remains constant from trial to trial. It does not changes from one trial to another. And the trials are independent. The outcome of a trial is not affected by the outcome of any other trial. To calculate the binomial coefficient, we use the formula which is NCR into p to the power r into 1 minus p to the power n minus r, where R is the number of success in n number of trials and P is the probability of success. 1 minus P denotes the probability of a failure. Now, let's use this formula to solve an example. Suppose a die is tossed 3 times. What is the probability of no 5 turning up, 1 5 and 3 5s turning up? To calculate the no 5 turning up, here R is equal to 0 and n is equal to 3. Substituting the value in the formula, we have 3c0 into 1 by 6 to the power 0 into 5 by 6 to the power 3, where 1 by 6 is the probability of success and 5 by 6 is the probability of failure. Calculating this equation, we'll get the value to be 0.5787. In a similar manner, to calculate the probability of 1 5 turning up, we'll replace R with 1 and n will be 3. So Px1 will be equal to 3c1 into 1 by 6 to the power 1 into 5 by 6 to the power 2, which will come out to be 0.347. And for 3 5 turning up, we'll substitute R equal to 3 and the formula will remain the same and we'll get the value to be 0.0046. Now that we are done with the concepts of binomial probability distribution, here's a problem for you to solve. Post your answers in the comment section and let us know. A Poisson distribution is a probability distribution used in statistics to show how many times an event is likely to happen over a given period of time. To put it another way, it's a count distribution. Poisson distributions are frequently used to comprehend independent event at a constant rate over a given interval of time. The Poisson distribution was developed by French mathematician Simon Denis Poisson in 1837. A Poisson distribution is used in cases where the chances of any individual event being a success is very small. The number of defective pencils per box of a 6,000 pencil, the number of plane crashes in India in 1 year, or the number of printing mistakes in each page of a book. All of these examples can have use of Poisson distribution. The Poisson distribution can be used to calculate how likely it is that something will happen x number of times. A random variable x has a Poisson distribution with parameter lambda, and the formula for that is e to the power minus lambda into lambda to the power x divided by x factorial, where x can be the number of times the event is happening. The value of e is taken as 2.7182. Let's discuss some application of Poisson distribution. If you want to calculate the number of deaths per day or week due to rare disease in a hospital, you can use the Poisson distribution. In a similar manner, the count of bacteria per cc in blood or the number of computers infected with virus per week. The number of mishandled baggage per 1000 passengers can also have an application for Poisson distribution. Let's discuss one example to see how you can calculate the Poisson distribution. Suppose on an average, a cancer kills 5 people each year in India. What is the probability that one person is killed this year? We'll assume all these events are independent random events. So, by the formula, we have x is equal to 1 because we have to calculate the probability of one person that is killed this year. So, p x equal to 1 will be equal to e to the power minus 5 into 5 to the power 1 divided by 1 factorial, which will come out to be 0.033, which will be near to 3.3%. So, the probability that only one person is killed this year due to cancer is 3.3%. Now, we have one question for you. Do try to answer in the comment section. Suppose the trains arrive at a railway station with an average arrival rate of 4 trains per hour. What is the probability exactly 6 trains will arrive in a 2-hour period? And here are our options. Please do let us know your answers in the comment section. So, what is the central limit theorem? The central limit theorem is a statistical concept that states that the sample means of the distribution of a random variable will approach to a normal distribution if the sample sizes are large, irrespective of the shape of the original population distribution. We take the population and we take the sample out of them. Let's discuss the mean and standard deviation associated with it. Suppose we are sampling from a population with mean mu and a standard deviation sigma. Let x be the random variable representing the sample mean of n independently drawn observations. Then we can say that the mean of the sampling distribution of the sample means is equal to the population mean, which is mu x bar is equal to mu, where mu x bar represents the mean of the sample means and mu represents the population mean. On the other hand, the standard deviation of the sampling distribution will be equal to the population of the total standard deviation upon the under root of sample size. Let's understand this more clearly by taking a real world example. Suppose you are a regional manager of a pharmaceutical company in charge of 200 stores across the region, and you are in charge of weekly medicine restocking at all of them. You need to know how many cases to order weekly for each store in order to reduce the amount of inventory that expires. The plot on the right hand side shows the distribution of all the 200 stores and average medicine cases required by each of the stores in a week. The red line represents the average cases required, which is equal to 34. You know, there has to be a better way to arrive at a reasonable answer that doesn't entail visiting every single store in your area and obtaining their weekly sales figure. You can apply the central limit theorem to this problem now that you understand the concept. We already knew the central limit theorem, when applied to real world problems, aids in balancing the time and cost of gathering the data required to draw the conclusions about the data. So here you can see the plot on the right hand side shows the distribution of sample means of the sufficiently large subsets taken from the population. Sample size greater than 30 will be sufficient enough to get the normal bell curve. The mean of all the samples taken from that population mean is equal to 34, which is equal to the sample mean of the subsets. If you plot the sample means, you will get a normal distribution which is a form of bell curve. If these samples meet the central limit theorem criteria, you can assume the distribution of the sample means can be approximated to the normal distribution. Now you know how to apply the central limit theorem in a real world problem. Let's discuss some assumptions behind the central limit theorem. The first one is the randomization condition. The data must be sampled at randomly and it must adhere to the randomization rule. The second one is the independence assumption. The sample value must be independent of each other. This means that the occurrence of one event has no influence on the next event. Usually, if we know that people or items were selected randomly, we can assume that the independence assumption is met. The third and the last one is the 10% condition. This states that when the sample is drawn without replacement, the sample size, which is n, should be no more than the 10% of the population. Let's now discuss some application of the central limit theorem. Political and election polling is a great example to show how you can use the central limit theorem. These post results are used to estimate the number of people who support a specific candidate. To calculate the confidence interval, which is shown on the news channel, the central limit theorem is very useful in this. One more place where you can use the central limit theorem is the census data. You use the central limit theorem to calculate the various population details such as family income, electricity, consumption, individual salaries, and so on. Now that we have a good understanding of the central limit theorem, its theories and application, let's see a demo in Python to understand it more clearly. Here we are on an online compiler. We'll discuss the CLT by taking a dice example. A dice has a different number on each side, ranging from 1 to 6. Each number has a 1 in 6 chances of appearing on a roll. Given all the equal likelihood, the dispersion of the numbers that come up from the dice roll is uniform. Let's start by importing some necessary libraries. We'll import the numpy first. From numpy.random, we'll import the randit function, which will be used to generate the random integers. We'll also import the mean function from the numpy. We'll set the seed to 1. Now we'll write the function to generate the random numbers. The randit function will generate a number ranging from 1 to 6. We have taken the 100 because the example will print the samples of 100 dice rows along with the mean. Print the rows and then we'll print the mean of the rows. So when you run this code, you'll get the following result. You see we have the 100 numbers and the mean of this number is 3.38. Now we'll repeat the process 1000 times. This will give you the result of 1000 sample means. According to the CLT, the result of these sample means will be Gaussian. So we'll change this code from here. Means will be equal to mean of this random integers. We'll take from 1, 7, 100 and this will be for in range of 1000. Now we'll plot this distribution. We'll use the pyplot function. We'll get the graph as a histogram graph, so we'll plot it in that means and pyplot.show. Let's recheck our code. We have the random integer function, we have the seed. Okay, we have imported the mean. We have not imported the matplot library, so from matplot library we'll import pyplot. Now I think everything is in place and let's try to run this code. Yep, you can see this graph is a histogram graph in the shape of a bell curve, and if you see closely, the mean is closely to 3.4.
So what is regression? Regression is nothing but a machine learning algorithm that helps us determine the relationship between two or more variables. It uses input or independent variables to find the value of the output or dependent variables. Regression is a prediction algorithm, which means that given some variables, we can predict the value of an output variable. The predicted value is not going to be from a set of values, but is going to be a unique value in itself. Now let's understand what exactly regression is with the help of a few independent input variables. In this case, the variables that we'll be looking at is rainwater, fertilizer, and seeds. When we pass these independent input variables through a regression model, we're going to get a predicted output. The output predicted is that a crop will germinate when all three of these components are put together in certain quantities. So with the help of regression, given raw input data, we can find out the dependent output variable that we'll get when all of these input variables are more or less combined. Regression is nothing but a statistical method which is used to determine the strength and character of the relationship between a dependent variable and a series of other variables. Now, using regression, if we have a set of data points, we can use a regression model to fit a line which passes through most of these data points and use it to predict the outcome for new data points. The line is fit using equation of a straight line or a polynomial equation. Now in this graph, consider that we have our dependent variable or the output y and our independent variable or the output x. For a certain value of our independent variable, we are going to get a certain value of our dependent variable or our output. Using the data given here, we can see how our output varies when our input varies. To predict the value of our outcome y, we're going to need to find a relationship between all of these data points. To do this, we're going to plot a straight line through it because, as you can see, all the data points lie more or less along a given straight line. Now, using the straight line, for any value of x, we can find the approximate value of y. So suppose you want to find the value of y at a point x, which is given here, say, then all you have to do is extend a line from this point onto our predicted model, which is this line here. And then we can see where this point on the line coincides with the y-axis and get the approximate value of the outcome. The equation of a straight line is given as y is equal to b0 plus b1x plus e, where b0 is a constant given by the y-intercept of our line, or basically where the line intersects on the y-axis. b1 is the slope of our line and x is the point for which we want to find the output. E in this case is nothing but an error correcting term. So this is basically how regression works, and this is how prediction takes place in our regression model. Next, we will explain the concept of the R-squared error to you. So what is R-squared error? R-squared error is nothing but an error measurement term which calculates how well our regression model fits the data. It determines the amount of variance in a model caused by the input variables. Now, R-squared is a statistical measure that represents the portion of variance for a dependent variable that's explained by an independent variable or variables in a regression model. R-squared is used to explain to what extent the variance of one variable affects the variance of a second variable. So, if the R-square of a model is 0.5, then approximately half of the observed variation can be explained by the model's inputs. In other words, an R-squared of 60% reveals that 60% of our data fits our regression model exactly. Now, in this case, in this graph, if we have a variance of 60%, it means that 60% of our data points fall exactly on our regression line. However, it is not always the case that a high R-squared is good for a regression model. The quality of this statistical measure depends on many factors, such as the nature of the variables employed in the model, the unit of measure of variables, and the applied data transformation. Thus, sometimes a high R-squared can indicate the problems with the regression model. A low R-squared figure is generally a bad sign for predictive models. Now, all this time we've been talking about variance in our model. What exactly is variance? Variance is nothing but a statistical term which determines how spread out our data is and tells us how many outliers are present in it. Basically, it's a measure of how far a set of numbers is spread out from their average value. Using variance, you can basically figure out where your data is centered and how spread it is from the mean, and also you can find out how many outliers it has. Now, how can you calculate the R-squared error? Let's start by considering the data that we have been given, as shown below. Now we can find the relationship between the input and the output variables by plotting a straight line or a regression model that passes through most of the data. To get the perfect fit for our model, we don't necessarily need to have the line passing through as many data points as possible. A true measure of a good model is that we reduce the error which is present in our model. Now, how do you find this error? The error present in our model is given by nothing but the distance between our predicted line and the data points which do not fall on the line. This is what you have to minimize. The distance between our data points and our line can be calculated by subtracting our data point from the point at which it coincides on our regression line. We square this just to get rid of any negative coefficients that may occur due to finding the difference between the 2 points. Now to find the variance in our data, we're going to find the mean and subtract the data points from the mean. This will basically tell us how spread out our data point is from the average value. We can then square these differences and add up the result to get our total variance. This is also known as the sum of squares total, and using this we can find the total variance in our data. The mean is nothing but the average of our data, and using the mean we can find the center of our data. So this is exactly where our data is centered. This is the average value that occurs in our data. Now the variance is nothing but the distance of all of our data points from the mean. If we do this, we're basically going to find out how spread apart our data is from the average value, or how far all of our data points lie from each other. When we subtract the position of our data points from our mean and square it and add all of that up, we get something known as the sum of squares total. Now the R-squared error is the total variance in our input data. It can be obtained by dividing the SSR by the SST and subtracting the results from 1. So the R-squared error totally becomes 1 minus the sum of our squared errors divided by the sum of the squared difference between our data points and the mean. Now this value gives us the variance, and this is why we can say that R-squared is used to find the portion of variation in our data. Now how can you implement R-squared error with Python? To calculate R-squared error with Python, we're going to look at the data which depicts the weather conditions which were present during World War II. And using the variables which are present in our data, we're going to create a model which predicts the daily weather forecast during World War II. And then we're going to use R-squared error to find the accuracy of our model. So this is our R-squared model. So we're going to start off by importing all of our necessary modules. We're going to use the model numpy to perform numerical calculations on our database and arrays. And we're going to use Seaborn and matplotlib to plot our data. So now we've managed to import all of our data sets. Let's also load our data by reading in the CSV file that it is stored as in the form of a data frame. So over here, as you can see, we've read in the CSV file into a variable called weather, and then after that we're changing weather into a Pandas data frame called climate. This is what our data frame finally looks like. So as you can see in our data frame, we have 5 rows because we're only looking at the top 5 rows, and we have 31 columns. So these are values which are not required and which are basically going to increase our error value. So let's drop them and get rid of them. Now let's also drop any empty values which may occur in the remaining columns of our data set and see what the final data set looks like. So this is our final data set. We have at the end, we're only left with max temperature, minimum temperature, and mean temperature. Now let's plot a count plot of our max temperature. A count plot is basically going to go through the entire max temperature column and figure out how many times every temperature value occurs. So it's going to figure out how many, it's going to count how many times 29.44444 has occurred, and it's going to plot that on this graph. And it is going to do that for every unique temperature value which is present in our column. So finally, this is the value that we get. So over here, as you can see, the majority of our temperature values are concentrated within this range. This means that these temperature values are the ones which occur most frequently. The other ones can be considered as outliers because they rarely are seen in our data, and they can further skew the output that we're going to get. Now let's do the same with minimum temperature. Let's plot a count plot for minimum temperature. So for the minimum temperature, we can see a very similar plot to the one that we got for a maximum temperature. Most of the values are concentrated around this region, but the outlier values here are way fewer. Now let's plot a regression plot between our maximum and our minimum temperature. So using the regression plot, we can plot a regression line for the two variables in our x and y axis. So this is our x axis and this is our y axis. This is basically going to plot a straight line which best fits the data that we are getting here. So over here, as you can see, this is a regression line. This thin blue line is a regression line which intersects our minimum temperature at a value which is between -30 and -40. And it passes through our entire data. So for a value of maximum temperature which is 0, using this we can predict the minimum temperature that would have occurred on the same day. So for 0, it will be somewhere around -10 degrees Celsius. So if we saw maximum temperature of 0 degrees on that day, we would have seen a minimum temperature of -10 on the same day. Now let's plot a heat map to see how these values are correlated with each other. So the correlation is basically used to find which values affect each other linearly, or which values when change will also affect the change in other values. So over here, as you can see, minimum temperature and maximum temperature have a correlation of 0.88, which means if minimum temperature changes, then the maximum temperature will also change to 0.88. Now the best correlation is obviously going to be between the mean temperatures and the minimum and maximum temperatures. The mean temperature is nothing but the average temperature value that we have. So this is basically going to lie in the middle of all of our temperature values, which is why we are going to have a better correlation for mean temperature. But minimum temperature and maximum temperature are also pretty well correlated with a correlation value of 0.88. This means that if our minimum temperature fluctuates, our maximum temperature will also fluctuate proportionately. Now let's separate our input and output values. We're gonna predict the maximum temperature given our minimum temperature. Here x is our input variable and y is our output variable. So now we're basically just gonna get all the important values in our x and y data sets. So after that, this is what our x and y data sets are gonna look like. Now let's split our data set into training and testing sets. The training set will be used to train our regression model, and the testing set will be used to predict how well our regression model is performing. The training data is the data which will be visible to our model, or the data which our model is allowed to have access to. Testing data will be data which the model has never seen before or which it doesn't have access to, and hence it will be made to work on completely new data to better test how well we've fitted to our data set. Now we can split our data set into training and testing sets by using the train test split functionality from our sklearn.model selection library. Now finally, from our scikit-learn library, let's import a linear regression model. We're going to initialize a linear regression model to a variable called regressor, and then we're going to fit our linear regression model to our training data set. So we finally got our trained linear regression model. Now let's use this model to perform predictions on our testing data set. So these are the values that we've gotten after running our linear regression model on our testing data set. Let's see how well we've performed. We are going to import the R2 score from our sklearn metric. Now the R2 score will directly perform R-squared error on our prediction and testing dataset and see how well our testing dataset matches our prediction dataset. So now we've gotten an R-squared error of 0.9345, which basically means that 93% of our output values are influenced by our input values. This also means that our model is 93% accurate and that approximately 93% of our observed variation can be explained by the model's inputs.
Let's start by defining what is mean squared error. Mean squared error measures the amount of error in a statistical model. It calculates the average squared difference between the observed and predicted values. In regression line, the mean squared error represents the average squared residual. As you can see in the graph, as the data points fall closer to the regression line, the model has a less error, decreasing the mean squared error. A model with less error produces more precise predictions. Now let's jump to our Excel workbook and discuss it with an example. Here we have a small table with the actual and predicted values. We'll start by finding the error between the actual and predicted value, which will be the difference between the actual minus predicted values. So here 10 minus 7 will become 3, 16 minus 14 will become 2, 13 minus 17 will become minus 4, 19 minus 20 becomes minus 1, and 7 minus 4 becomes 3. Now just calculate the total of the errors. While calculating the total, we'll treat this negative value as a positive value. So here the total of the errors will become 3 plus 2 5 plus 4 9 1 10 and 13. Then we'll calculate the square of the errors. So here 3 square will become 9, 2 square will become 4, 4 square will become 16, 1 square will become 1, and 3 square again is 9. And we'll do the total of the square errors. So this will become 9 plus 4 13, 13 plus 1 14, 14 plus 16 30 and 39. To find the MSE, that is the mean squared error, we'll divide the total of the square error values with the total number of records. So here MSE will be equal to (39) divided by, and we have a total number of records, that is 5, which will be 7.8. Let's name this as model A. Now for the comparison purpose, we'll create another model, that is model B. We'll have all the columns here. And we'll keep the actual values here same. We'll just change the predicted values. So let's take some random values. We'll keep this as 13, we'll take this as 20, we'll take this as 12, 18 and 3. Now to calculate the error, we'll subtract the predicted values from the actual values. So 10 minus 13 will become minus 3, 16 minus 20 will become minus 4, this will become 1, this will be 1 and this will be 4. Now to calculate the square error, we'll just square the error values. So this will be 9, this will be 16, this will be 1, this will be 1 and this will be 16. The total of all the square values will come out to be 43. Now to calculate the MSE, again we'll divide the total square values with the total number of records. So here this will be equal to 43 divided by 5, which will come out to be 8.6. If you observe here, the total of the errors in both model A and model B is same, that is 13. So which model to prefer? Since the mean squared error of model A is lesser than model B, we'll prefer model A because we are okay with a model that has small errors, but in model B there are some significantly large errors. Suppose in this case 16 minus 20, that is minus 4, minus 3 and this here 4. So we do not want a model where the errors, large errors specifically, are more frequent. We can have a model with the small errors that will be okay. So we'll prefer model A over model B.
Now getting into probability theories. So during your school times or college time, you would have learnt about probability theory. What is probability theory? Yeah, as Vishal said, it is actually chance, the chance of getting. For example, if I toss a coin, okay, I'm tossing a coin and what is the probability of getting my head? It is actually 1 by 2. Only one time my head can occur. That is, as Amani said, it is 0.5. So that's what it is represent here. The number of favorable occurrence to the number of possible occurrence. So the number of possible occurrences, if I toss a coin, either I can get a head or a tail. So there are two possible occurrences. But when I toss a coin, only one can be the result. So either I'll get a head or else a tail. So it is divided by 1 by 2. If I'm talking about probability of getting a coin which is head, then I can tell it is 1 by 2, which has equal probability in terms of coin. For an example, if I'm rolling a dice, what is the probability that I get a number called 2? Dice generally has 6 faces. Yes, as Amani said, it is 1 by 6. So only one option can occur, either 2, 3, 4 or 5 or 6. Any one of these numbers can occur, but there are actually 6 spaces. So the probability is 1 by 6. So that's what we're going to look here. And in another way, now for an example, let us look at a case study. Okay. So in this particular case study, I have 100 coins. Okay. I'm going to toss 100 coins. Sorry, I'm going to toss 10 coins. So I have 10 coins and I'm going to toss 10 coins simultaneously. Okay, this is the process. And how many times it is possible to get a head? So if I'm tossing 10 coins, what is the probability of getting no heads? What is the probability of getting one head? What is the probability of getting two heads? And this is actually the thing that I'm going to choose. Yeah, as I'm going to say, it is 0.5 into 10. But I'm going to repeat the process for 100 times. So first time I'm going to toss 10 coins parallelly. Okay. And I'm going to record how many times head had occurred. And the second time also I'm going to toss 100. And the second time also I'm going to toss 10 coins simultaneously, and I'm going to record how many times head had occurred. Okay, I'm repeating this process 100 times. If you're looking at this frequency, see, so what they actually made a survey. So they had tossed 10 coins and they had repeated this experiment 100 times. So don't get confused. So I'll just tell. Okay, I'm tossing 10 coins simultaneously, and I'm going to do this operations 100 times. Okay, 100 times I'm going to repeat the same process. So first time I'll toss 10 coins. Second time also I'll toss 10 coins. The same way I'm tossing the 10 coins 100 times. Okay, and I had recorded the frequency. So I just see that only in this 100 times, only one time I found that no heads turned up. Okay, all the 10 coins were showing me tail. That frequency is only 1. And 2 times it showed only 1 head and 9 tails. And 3 times it showed 2 heads and 8 tails. Okay, this is actually the number of heads which had occurred. So here, just tell me which is the maximum frequency, which is the number which had maximum times which had occurred on looking at this frequency. This is actually, if you're adding all these things, it comes to 100. 100 times the experiment is done. In only one experiment, I found that all my 10 coins are tail. And in only 2 experiments, I find that only 1 head turned up and the rest 9 coins are tail. Okay, as Matthew said, 5 heads 30 times. So in 30 experiments, I find that 5 times I get head and 5 tails I find. So this is having maximum frequency. So according to us, if I toss a coin, if I toss 10 coins simultaneously, the optimum probability, the maximum probability that I get is 5. 5 times 5 heads will occur and 5 tails would occur. That is the maximum occurrence that is here. So that's what we're going to see here. And this would give you the relative frequency for every flips. For an example, if I ask you a question, what is the probability of getting 0 head when I'm tossing 10 coins? What would be your answer? If I toss 10 coins, all the 10 coins are tail. I'm not getting not even a single head. What is the probability? It is 0.001. This relative frequency would tell you what is the probability. This is nothing but 1 divided by 100. Because in 100 experiments, only one time this scenario had occurred. So 1 divided by 100 is 0.01. 2 divided by 100 is 0.02. Because if you're adding up all this frequency, it comes to 100. So individual value divided by 100. And 30 divided by 100 would be 0.3. Clear? If I'm asking a question, what is the probability of getting 5 heads when I'm flipping 10 coins? What is the probability? What is the probability that I get 5 heads in this particular scenario? It is actually 0.3. 0.3 would be the probability. So for 5 times head, 0.3 is the probability. And what is your expected value? So before I toss a coin, okay, we are not talking about this experiment. In a general way, I am asking a question, okay. I am tossing 10 coins simultaneously. What is the probability for me to get head? What would be your answer? Amani said 5. On what basis you said 5? This is actually your expected value, right? You didn't do any experiment, but you are arriving at a particular value. You guess that, okay, whenever I toss 10 coins simultaneously, at least 5 times I can get head. At least 5 coins will turn up head. That's your expected value. That's where this expected value is calculated. So the method to calculate your expected value is nothing but 0 into your frequency. So into your relative frequency. So if you're multiplying 0.01 into 0, it becomes 0. Your relative frequency into the number of heads. So this is 0.02 into 1, it becomes 0.02. 0.03 into 2, it becomes 0.06. And if you are adding up all these values together, 5.14. Yeah. So 5.14 is the expected value. So according to our analysis, initially before doing this experiment, what was our expected value? If I toss 10 coins, 5 is the thing that I'm going to get 5 times. I assume that at least 5 heads would turn up. Even after looking at the expected value, now we are guessing that it is 5.14. So it is closely near to 5. So 5 times head can turn up. That's how the probability works. Okay. And if I'm asking the probability of individual things to occur, for an example, if I ask you a question, what is the probability of 7 times head occurring when I flip 10 coins? What would be your answer? Your answer would be 0.12, right? This is the probability. Clear about probabilities and expected values? Expected is nothing but your assumption. So initially you would have some assumption. What is that overall assumption that it gives, and what is the maximum number which is occurring? This is all about probability distribution. So generally, if you know the probability, it sometimes help you in knowing some business process. For an example, in the same phases, just connect it with customer getting into your company and getting a particular product. Okay. So initially on a particular day, 10 customers are getting into your shop and they're getting chocolate coffee. And in the same way, what is the probability that tomorrow, if there are 10 customers, how many customers would, if I want to check the probability that 5 customers are getting hard copy, I can derive from this probability values. That's what you can also relate the same example with some of the business cases, and you can do it. Okay, this is about probability distribution. And if you're looking at in our slide also, this will be represented. So this is the same way, like they took another example, how many units sold on the first day, like here are different days. For 10 days 0 units sold, for 55 days only 1 unit had sold, for 150 days 2 units has sold. The same example they had given for another business case. So sales data for AC sold in last 300 days. In last 300 days, how many AC is getting sold? So in last 300 days, only 10 days, I found that 10 days there is no sale. In 55 days, I found only 1 unit sold. In 150 days, I found 2 units sold. So this is actually the frequency which is mentioned, and here the probabilities are calculated correspondingly, and which is being plotted. Here you can see at an average level how many units are sold. At an average level 3 units are sold. This would be your expected value, right? Clear everyone? The same thing in terms of business example they had given. Just go through this example and it is also the same process. Next, coming to binomial distribution. So because we will not much get into the statistical part or a mathematical part, so what will is, because some people are from business background and some people are from maths background, so what I'll do is I'll try to put all these things in a simpler way. So that's the reason I created another slide, because generally on looking at a complete slide, it is difficult for you to understand the stats concept. So that's why I had also created some additional slides to represent all these examples. Okay. So for an example, what is binomial distribution? Okay, as Akansha said, it is 2 values. So whenever you have 2 situations like probability of success or failure, or the event happening or not happening, in those sort of situations, only if we have, if your values are like, if you have a fixed number of trial and if we have the trials of independent of each other, then you can go for a binomial distribution, and it has only 2 options, either a success or else a failure. So in those sort of situations, you can go for a binomial distribution. So only one probability of success and the other things would be a failure. So what I'll do is I'll also show the slide that I had created. For an example, binomial distribution, let's not get much into a technical part. Okay. Suppose a die is tossed 5 times. So how many sides a die has? It has 6 sides. And what is the probability of success there? What is the probability of success in a dice? It is 1 by 6. And what is the probability of failure? It is actually 5 by 6. Yeah. So in this case, what I'm going to do is, what is the probability of getting exactly 2 4s? So if I roll a dice and if I'm doing the same process 5 times, what is the probability of getting exactly 2 4s? In this case, it becomes easier. So one thing is you can do, okay, as Amani said, 1 by 36. I'm just, yes, 1 by 36, when you are accounting 5 times, for a single die, it would be 1 by 6, right? Yeah. Yeah, that is option. And Sandhya, you were telling 2 by 5. How it is 2 by 5? What is 2 by 5? Because 2 4s, yeah, it cannot be related in that way. So I'll just tell you how to do this process. This is the process. You are clear about 1 die phases, right? What is the probability? It is 1 by 6. And just make sure that this I'll be taking in terms of formulas, and I'll also tell you how to do this in Excel in an easier way. First, I'll tell you the formula, how to do this process. Okay. The formula to do this is, binomial distribution is, the formula is NCR, N would be capital NCR, P to the power of R into Q to the power of N minus R. This is the formula. This probably you would have learnt in your colleges or school. So here, let me explain. Once I'll put it in a formula basis, and I'll do this process, and again I'll explain you how this is happening in terms of tool very easily. So what is exactly N here? How many times we had repeated this process? What is N? This is the formula to calculate binomial distribution. So it is 5. 5 times I had repeated the process. So 5, the combination of What is R here? How many times 4 should occur? It is 2. So it is 2. And what is P is nothing but the probability of success. What is the probability of success when you are rolling a dice? It is 1 by 6. Yeah. So if you are dividing 1 by 6 in calculator, what is the value? 1 by 6 to the power of, what is R here? It is 2. And in the same way, what is the probability of failure? Q is nothing but your probability of failure. It is pi by 6. If your success is 1 by 6, it is minus of your success, right? So it is pi by 6. To the power of, what is n? What is n here? Pi. Pi minus 2. So can someone tell me what is pi c to the power of pi combination of 2? What is pi combination of 2? What is the value of, someone said it is 3, but basically we will also do pi c to the power of 2. What you will do is, I will also tell you what is the formula for this. This is nothing but n factorial divided by r factorial into n minus r factorial. I'll just put this formula just for your understanding. This is nothing but n factorial. So if you want to calculate manually by hands also you can do it. N factorial divided by r factorial into n minus r, the whole factorial. Okay, and if you are substituting in this formula, what is the answer that you get? Pi c2. What is n factorial here? 5 factorial is nothing but pi into 4 into 3 into 1. Yeah, 5 into 4 into 1 divided by. So only for this I am just giving a detailed explanation. And what is r factorial? What is r factorial here? Okay, I think everyone had did this process. Everyone had given the answer 10. But just for the first process, I will do this. This is actually 2 factorial. 2 factorial into n minus 2 is nothing but 5 minus 2 is 3. 3 factorial. So 3 factorial would be 3 into 2. Right? So this is actually 3 into 2, it gets cancelled and 2 will cancel by 2. So this is actually 10. So 10 would be the result of 5c2. Instead of 5c2, now you can substitute 10. Okay. 10 into what is the result? 1.6, 1 by 6 into 1 by 6 to the power of 2. What is it? What is the result? Yeah, here 1 by 6 would be 0.167. 0.167 to the power of 2 into the failure would be 0.833 to the power of 5 minus 2 is actually 3. And if you are solving this, you would get a result of 0.161, right? This is the probability that you would get. This is the result that you would get using formula. In the same way, if I am doing the same process in Excel, let me see how much time it is. And now it is the probability. So if I ask you a question, what is the probability? What is the probability for me to get exactly 2 4s when I toss 5 times the dice? What is the probability? It is 0.161. The same thing you can do very easily in terms of Excel. So just open your Excel. Here just type what is the operation that we are going to do? What is the distribution that we are going to do now? We are going to do binomial distribution. So just type binomial, you will get binomial distribution option. So in this binomial distribution, you can see the number to specify here. What is the number that we are going to take here? How many times 4 should occur? So the number of time exactly 4 should occur is 2 times. And what is the number of trials? It is 5. And what is the probability of success? What is the probability of success? It is 1 by 6. Okay, I'm putting 1 by 6. And cumulative. Cumulative is something very important to understand. So now we are going to do a point probability. So in terms of point probability, you have to select false as your option. I'll tell you what is cumulative probability and what is point probability. So now we are able to see the result, right? What is the result? Even when manually calculating 0.161, it is 0.16075. It can be accounted as 0.161. It is equal, right? It becomes very simple in terms of Excel. Now in the same way, if I am asking you, okay, Sandhya, repeat again. So what I'll do is, I'll do the same process again. Binomial distribution. Okay, what is this number of S? Number of S represents that how many times that your number should occur. So in our case, exactly 4 times the number should occur, right? I'll show you the question once more. Suppose a die is tossed 5 times. What is the probability of getting exactly 2 4s? So what is the number that you're expecting? Exactly 2 4s. That's what I had mentioned here as 2. First number is actually I'm mentioning I want 2 exact 4s. And how many trials I had made? How many times I had made the trial? 5 times I had made the trial. And what is the probability of getting a success in a dice? 1 by 6. So I'm giving 1 by 6 here. And it is very easy in Excel because it throws you what are all the parameters to pass. And cumulative, here I'll talk about point probability. Then I'll talk about cumulative probability as well. So first I'll talk about point probability, which is exactly 4. Okay. So here I want only on this particular point, what is the probability? So I'll select my operation as false. Okay. I'm clicking it, I'm closing it, I'm clicking enter. So I get the probability value. Clear? Clear, Sandhya? Clear about this process? Okay. Now, what the question that I had framed is exactly 2 numbers. What exactly 2 4s? So what I did is, and also, so the first question what I did is exactly 2 times the number 4 should occur. This is what I did. So here what I can do is the probability of X is equal to 4. This is the X is equal to 2 times it should occur. The same way, if I want to find less than or equal to 2, P of X less than or equal to 2. In this case, what would be my value? What should be my value? So I should calculate the probability of 0, because if it is less than or equal to 2, I should calculate the probability of 0, I should calculate the probability of 1, probability of 2, right? In this situation. In this case, if I take only one probability, that is sufficient. This is called point probability. Because I am doing this operation for only one particular value, which is a pointed value. I want to know exactly 2 4 to occur. But what if I have a question, okay, at least 2 times it occurred. So in that case, what you will do is P of X less than or equal to 2. Here what you want to know is, you want to know the probability of 0 times occurring, and you want to know the probability of 1 time the value getting occurred, and you want to know the probability of 2 times the value get occurred. Clear? This is what you have to do. So first what I'll do is, I'll take a, now instead of false, instead of this particular false, if I give true, the cumulative actually happens. If I give true here, this is actually cumulative distribution. So this is actually the probability of 0, 1 and 2 gets added. So what is the probability of 0, 1 and 2 all together for less than or equal to 2? What is the probability? In another way, what I'll do is, just copy this. So first time 0 times it is occurring. Okay, what is the value? 0.40. And now I'll just put the value here as 1. Only 1 time the value is occurring. Okay. And now I'll put the probability of 2 times the value get occurred. Okay. Now if I add all these things, this is for what? The probability of X is equal to 0. 0. This is actually the probability of X equal to 1. and this is actually the probability of x is equal to 2. This is, all these points are individual probability, right? This is point probability. What is the chance of 0 time occurring? What is the probability of 1 time occurring? What is the probability of 2 time occurring? This is exactly 0, this is the value. Exactly 1, this would be the probability. Exactly 2, this is the probability. So what if I want x less than or equal to 2? What I should do? These are all like point probabilities I had found. Now if I want to calculate the total, I have to sum it up. Yeah. If I sum all these 3 values, what is the value that I get? 0.964506, which is nothing but if you are mentioning as true, the accumulation happened. If you are mentioning as false, the point probability happens. Now is it clear for everyone? One thing is you can take point probability of all the points and you can add, or else directly with the last value you can divide, you can mention your cumulative as true. Then automatically the accumulation happens. Is it clear everyone? Now is it clear for everyone with this example? This is how the binomial distribution works. Either you can calculate point probability and you can add, or else you can mention your accumulation as true. If you are mentioning accumulation as false, it is point probability. If it is true, then it is a cumulative probability. Okay. Next, I'll get into the other distribution. So in the same way, that's what as I gave you an example here they had given. So now can someone tell me with this particular problem? Don't see the answer. Okay. Just tell me what is the probability of updating. First tell me what is the probability of obtaining exactly 45 heads in 100 tosses of a coin. Can someone tell me for exactly 45? First tell me exactly 45. Then tell me the cumulative probability. So for doing this process, what are all the factors that I should consider? Exactly 45 times. I want to know exactly 45 times how it is occurring. I'll also copy this question. In this question, what is the formula that I should put here? What is the, instead of obtaining fewer hits, first consider exactly 45 hits. First the question is, just tell me the point probability of exactly 45 hits. Okay, 0.048. So I'll also check it once. Okay, so equal to binomial distribution. What is the number of parameters that we are fixing? Exactly 45, right? And number of trials, we had made 100 trials. And what is the probability of success here in tossing a coin? It is 0.5. Yeah, 1/2 or 0.5, anything is okay. And what is the parameter that I should mention for point probability? False or true? I should mention false. Yeah, I mention false. This is 0.048. And in the same way, if I want to find what is the probability of less than or equal to 45 or fewer heads of 45, then what I'll do is I can make it true here. I will get a cumulative option. Okay, fine. So this has a probability of heads occurring less than or equal to 45. Here everyone, 18% chance.
So now let's dive into the definition of the probability distribution function. What is probability distribution function? A function which defines the relationship between a random variable and its probability such that you can find the probability of the variable using the function is called a probability density function. In simple words, probability density is the relationship between an observation and their probability. Some outcomes of a random variable will have low probability density and other outcomes will have a very high probability density. Basically, the probability of a variable x happening or occurring will vary, and it can sometimes take on a lower value or it can take on a way higher value. The overall shape of the probability density is referred to as probability distribution, and the calculation of probabilities for specific outcomes of a random variable is performed by a probability density function, or PDF for short. Now consider a variable x with a PDF of f of x. This is what your probability density function will look like. There might be a point where the probability of x occurring is very high. Hence, your probability distribution function or f of x will also be very high. At other points, the distribution or the probability of x happening or occurring is going to be very low. Hence, your f of x is also going to have a very small value. Basically, given the random sample of a variable, we might want to know things like the shape of the probability distribution. This here is something called a normal distribution, where your probability distribution function takes on a bell shape. However, this is not the probability density function that might always occur. There are different probability distribution functions, and all of their graphs look very different from each other. Knowing the probability distribution for a random variable can help you calculate movements of the distribution like the mean and variance, but it can also be useful for other more general considerations like determining whether an observation is unlikely or very unlikely and might be an outlier or an anomaly. Like, consider this graph itself. In this graph, these points over here, which have very less probability distribution, are outliers, which means that the chance of them occurring is very low. And basically, this is not something that you're going to see in your regular scenario for your variable x. Now let's consider 2 points a and b, which are values that our variable x can take. P of A and P of B just represent the probability of A and the probability of B, which can be found out by drawing a straight line and coinciding it with our graphs. The area under the graph over here, which is going to give you your probability of this region occurring, can be written as probability of A less than equal to X, which is the probability that we're searching for here, less than equal to probability of B. What does this mean exactly? This means that this area is always going to be greater than or equal to the probability of A, but less than or equal to the probability of B. This gives us the narrow region of the probability which is present over here. And doing this, we can find the probability of occurrence for any value of x. Suppose you want to find the probability of B happening. For a probability distribution function, the probability of B happening is not simply this point here, but the entire area of the graph which is taking place before this point itself. So if you want to find the probability between these regions, you're going to have to find the entire area and not simply the probability at one point. Now, so far we've been talking about different types of variables, which is discrete random variables and continuous variables. What exactly do these mean? A variable which can only take a value within a certain range is called a discrete random variable. The value is usually within a certain distance of another finite value. An example of this would be the sum of two dices. Basically, values which are well defined are called discrete values, and a variable which has well-defined values will be called a discrete random variable. This variable can only take values which fall within a certain set of values. Let's say you roll a dice. The dice can only give you specific outcomes which range from 1 to 6. This is what you would call a discrete output. On the other hand, a continuous random variable can take on infinite different values within a range of values. For example, the height of a student. The height of a student is not fixed. Even if the height is 1.7 meters, in reality, the height can be 1.77 or 1.765 or 1.789. The exact height is very hard to determine because it's not easy for us to find the precise value of the height of a student. So basically, the height can take on an infinite different range of values. When we're trying to define the values that a continuous random variable can take, we usually say it in the form of a range of values, which means that the value can fall in that range and can take on any value in that range. It's not like a discrete random variable where you can define definitive values. Now let's understand a probability density function with the help of a graph. Consider the graph below, which shows the rainfall distribution in an year in a city. The x-axis has the rainfall in inches, or the amount of rain that we're getting, and the y-axis has the probability density function of getting that amount of rain. The probability of some amount of rainfall is obtained by finding the area of the curve to the left of it. So let's say we have a point 3. If we want to find the probability of 3 inches of rainfall occurring, we would have to find the area of the curve which falls to the left of 3. When we draw a line from 3 which intercepts the graph and further extend it onto the y-axis, we get a value of 0.5. Simply put, this means that the probability of 3 inches of rainfall occurring is going to be lesser than or equal to 0.5. The exact probability can be found out by finding the area of the curve, which falls to the left of 3. How do we find the probability distribution function? The first step is to summarize your density with the help of a histogram. The first step in a density estimation is to create a histogram of the observations in the random sample. Now, what is a histogram? A histogram is a plot which involves first grouping the observation into bins and counting the number of events that fall in each bin. The counts or frequency of observation in each bins are then plotted as a bar graph with the bins on the x-axis and the frequency on the y-axis. The choice of the number of bins is important as it controls the coarseness of the distribution and in turn how well the density of the observation is plotted. It is a good idea to experiment with different bin sizes for a given data sample to get multiple perspectives or views on the same data. At the same time, the number of bins is important as it determines how many bars the histogram will have and their widths. This will change not only the shape of the graph, but also how the graph is read. This will also determine how a density is plotted. Now, let's see how we can summarize our density with histograms using Python. First, let's import all of our necessary modules which we're going to require. We're going to require matplotlib to plot graphs. We're going to need the normal random function so that we can get a normal distribution. We're going to import mean and standard deviation from numpy to use on our graphs. We're also going to normalize our data, so we're going to import the norm function from scipy. We finished importing all of our necessary modules. Now let's generate a sample which has a size of 1000 and it's going to be a normal distribution. And we're going to also plot this with the help of a histogram in bins of 10. So as you can see here, you get a normal distribution, which is nothing but a almost bell-shaped curve. And we have 10 bins here, which are centered at 0 and which extend from -3 to 3. How will our graph look if we change the number of bins though? Let's run it and see. So you still have a normal distribution, but it's not as well defined. Because of how less the number of bins are, you lose a majority of the data which will contribute to your normal distribution. It doesn't look like a proper normal distribution, but it looks more like a discrete data at this point. Now let's take a look at the next step of finding our probability distribution function. The next step is called parametric density estimation. What exactly is parametric density estimation? The probability density function is of many types. The shape of your histogram will help you determine what type of a function it is. We can also calculate the parameters associated with the function to get our density. Now, different probability distribution functions will have different graphs which will have different shapes and which will also have different parameters like mean, standard deviation, etc. associated with them. Using these parameters, we can find important points of our data. Hence, it's very important for us to recognize what type of a distribution it is. Common distributions will occur again and again in different and sometimes unexpected domains. Getting familiar with common probability distributions will help you identify a distribution from a histogram, and once identified, you can attempt to estimate the density of the random variable with a chosen probability distribution. This can be achieved by estimating the parameters of the distribution from a random sample of data. Now, an example of this would be a normal distribution which has two main parameters, the mean and standard deviation. Given these two parameters, we will now know the probability distribution function. These parameters can be estimated from data by calculating the sample mean and sample standard deviation. This entire process is known as parametric density estimation, and it includes identifying your probability distribution function and getting the parameters which are associated with it. Now, once we have estimated the density, we can check if it's a good fit. This can be done in three different ways. One is plotting the density of the function and comparing the shape to the histogram. The next is sampling the density function and comparing the generated sample to the real sample. And the last one is using a statistical test to confirm if the data fits the distribution. Now over here, as you can see, all we've done is taken our data and plotted the density function on top of a histogram, and we've compared the shape. So the density function that we're actually considering here is a normal distribution. And from this graph, we can see that it's almost an exact fit to our histogram. Now let's see how we can perform parametric density estimation using Python. To begin with, let's generate a random sample of 1000 observations from a normal distribution with a mean of 50, which is determined by the LOC parameter, and a standard deviation of 5, which is determined by the scale parameter. Now, just to show you what the distribution looks like, we're going to plot it in the form of a histogram. So this is what the histogram looks like. But this is just to give you a basic idea of our data and what it looks like once plotted. But let's assume that we don't know the probability distribution and we don't know what it looks like as a histogram, and we don't know that it's normal. So now if we just assume that it's normal, we can calculate the parameters of the distribution, specifically the mean and the standard deviation. We would not expect the mean and standard deviation to be 50 and 5 exactly, given the small sample size and the noise in the sampling data. So because of this noise and the small sample size, we have a mean of almost 50 and a standard deviation of a little more than 5. Now let's define the distribution as normal. So now using this, we've defined a normal distribution. We've used the norm method of the SciPy library, and we're doing this with the mean and the standard deviation that we've obtained from our samples. So up until now, we're just assuming that it's a normal distribution, and because of that, the parameters that we've calculated is the mean and standard deviation. And using the calculated mean and standard deviation, we've gotten a normal distribution. And up until now, again, keep in mind, we do not know for certain that it is a normal distribution. So far, all we have is this data. So the next thing that we're going to do is fit the distribution with these parameters and then sample the probabilities for a distribution for a range of values in our domain, which in this case is 30 and 70. So all we're doing is we're calculating probabilities for a range of outcomes, and in this case we've taken 30 and 70 as our domain. So these are the probability distribution values for the normal distribution that we've defined over here, and this is basically gonna give you the outline of your normal distribution. These are the points at which your normal distribution will be plotted. Now what we're basically going to do is we're going to plot our histograms using the samples that we've already generated along with the values and probabilities of the normal function that we defined over here. So as you can see, it's almost a complete fit. The normal distribution that we have here is made using the mean and the standard deviation of our actual samples. The reason we took mean and standard deviation was because we assumed it was a normal distribution. and the parameters associated with the normal distribution are mean and standard deviation. Using the mean and standard deviation, we got the normal distribution. We calculated probabilities for this normal distribution using a random domain of 30 and 70. And we plotted the probabilities and the values on top of our histogram to see if the normal distribution was a fit to our histogram. If it was not a fit, you would have to go and do the same procedure with other common probability density functions until you found a function which was a proper fit to your histogram. Now let's move on to the final step, which is used in the calculation of our PDF. This final step is called non-parametric density estimation, and it's only used when the shape of a histogram doesn't match a common probability density function, or it cannot be made to fit one. In this case, we will calculate the density using all samples in our data using certain algorithms. This is only done when a data sample does not resemble a common probability distribution, or it cannot be easily made to fit the distribution. And this is often the case when the data has two peaks. This is also called a bimodal distribution, or it has many peaks, which is also called a multimodal distribution. In this case, the parametric density estimation will not be feasible, and alternative methods can be used that do not use a common distribution. Instead, you will use an algorithm which is used to approximate the probability distribution of the data without a predefined distribution, which is also referred to as a non-parametric method because we're not using any predefined parameters. The distribution will still have parameters, but these are not controllable in the same way as a simple probability distribution. For example, a non-parametric method might estimate the density using all observations in a random sample, in effect making all observations in the sample parameters. Now consider this graph which has two peaks. This is not a normal distribution or any other sort of distribution that we are familiar with. So for this, we're not going to use a parametric estimation method, but we're just going to calculate the parameters for every single sample point in this. Perhaps the most common non-parametric approach for estimating the probability density function of a continuous random variable is called kernel smoothing or kernel density estimation, or KDE for short. Kernel density estimation is a non-parametric method for using a dataset to estimate probabilities for new points. It uses a mathematical function and smoothing probabilities, so the sum of the resultant probabilities is always 1. Now in this case, a kernel is a mathematical function that returns a probability for a given value of a random variable. The kernel effectively smooths or interpolates the probabilities across a range of outcomes for a random variable such that the sum of probabilities always equals 1, a requirement of well-behaved probabilities. You also have a parameter called the smoothing parameter, which controls the scope or the window of observations from the data samples that contributes to estimating the probability for a given sample. As such, the kernel density estimation is sometimes referred to as your Poisson-Rosenwald window. Now at the end, you also have a basis function, which is a function which is chosen to control the contribution of samples in the data set towards estimating the probability of a new point. This is only done to make sure that you're not learning from a lot of noise and that you're not using a lot of the outliers. Again, let's see how we can perform non-parametric density estimation with the help of Python. So first we'll start by importing all the necessary modules along with the kernel density estimation, which can be imported from sklearn. Now let's create a bimodal distribution by combining two different samples, sample 1 and sample 2. Sample 1 has 300 examples with a mean of 20 and a standard deviation of 5, while sample 2 has 700 examples with a mean of 40 and a standard deviation of 5. We're then going to use hstack to merge both of them together to get a final sample. The means that we've chosen, which is 20 and 40, are chosen close together to ensure that the distributions overlap in the combined sample. So this is what our distribution is. Let's just plot it so you get a basic idea of what our graph looks like. So this is what our graph looks like. Now we already know that none of the various different probability distribution functions fit these graphs. So now we're going to perform non-parametric estimations. So to perform non-parametric estimations, we're going to use the scikit-learn machine learning library, which provides the kernel density class that implements kernel density estimation. First, the class is constructed with the desired bandwidth or window size of 2. And your basis function, which in this case is a Gaussian function. It's a good idea to at least test different configurations to your data. And in this case, we're only going to try a bandwidth of 2 and a Gaussian kernel. But usually there are multiple different kernels that you can that you can play around with, and you can also tweak your bandwidth to exactly fit the distribution that you have. Now let's run this. So now we've gotten our kernel density estimation. Now we can evaluate how well the density estimates matches our data by calculating probabilities for a range of observations and comparing shapes to the histogram, just like we did for the parametric case before. So again, we're gonna just calculate different probabilities using the kernel density function, and we're just gonna plot it on top of our histogram to see how well the kernel density function is estimating for our data. So these are the probabilities that we've gotten finally with the kernel density estimation, and now we're going to plot it on top of our histograms. So as you can see, it's almost a complete fit. It's just left out some of these outlier values, which again are ranging very high, but overall we have a pretty good fit. The only problem is it's not very smooth, and you can again try tweaking the bandwidth to different values. So let's just, in this case, try tweaking it to 3 and see how well it runs. Okay, so now we've gotten new probabilities, and let's run it on top of our bandwidth. So again, using a bandwidth of 3, you can see that we're fitting our data even better, and we're again ignoring a lot of the outliers which are out there. So this is going to give us a better estimation. So let's come to the first topic at hand. What is cumulative distribution function? The cumulative distribution function is used to describe the probability distribution of random variables. It can be used to describe the probability for a discrete, continuous, or mixed variable. Basically, the cumulative distribution function, or the CDF, of a random variable is just another method to describe the distribution of random variables. The only advantage of CDF is that it can be defined for any kind of a random variable, be it discrete, continuous, or mixed. Let's consider the curve which is shown in the figure. Over here, we can see that we're plotting a random variable x against its probability density function f of x. The graph is plotted between two variables a and b. And as we can see, the probability density function for them is a constant line which extends between these 2 points. The probability density function for the graph shown is nothing but the inverse of b minus a. Now we know why we need a cumulative distribution function, but what exactly is a cumulative distribution function? In layman terms, the cumulative distribution function can be defined as the probability that a random variable isn't greater than a given value. In a random trial, the outcome of a random variable will be less than or equal to any specified value of x as a function of x itself. When plotted in a graph, in which the horizontal axis is a variable x and the vertical axis ranges from 0 to 1. The cumulative distribution function of a random variable that is evaluated at point C will take a value less than or equal to the value of C. In basic simple terms, if I'm evaluating the cumulative distribution function for a random point, let's say C over here, the cumulative distribution function that we get will always be a value which is lesser than this value. And why is that? To first understand this, you should know that the cumulative distribution function is calculated by finding the total probability density function for a given value. So consider the point C. When we draw a line from C, it intersects the curve at a certain point. To find the cumulative distribution function, you have to find the total of the probability density function up until this point. Or basically, you have to find the total of the probability density function for the rectangle which is formed between A and C. This can be done by summing up all of the probability density functions. But what happens when you have a large number of probability density function? In that case, all you have to do is integrate the probability density function over the limits or the points that it is being calculated between. Now let's get back to the problem at hand. Over here, you can see that we have this rectangle, and if we basically find the area of the curve which falls to the left hand side of C, or the entire area of this rectangle, we will have the cumulative distribution function. Now for a rectangle, we all know that the area is nothing but the length into the breadth of the rectangle itself. So for this, we can see that the breadth of the rectangle is nothing but the distance between these 2 points, A and C, which is C subtracted from A. As for the height of the rectangle will be the point at which it intercepts the probability density function on the y-axis. For now, because we're not taking a certain value, let's just assume that value to be f of x itself. So at the end of the day, the probability of x being lesser than or equal to c, or the total probability of x being lesser than or equal to c, is nothing but c minus a into f of x. F of x is nothing but 1 divided by b minus a, as seen in the previous slide. Hence, the total probability or the cumulative distribution function for this graph becomes c minus a divided by b minus a. In general, the formula for cumulative distribution function is the cumulative or the total sum of the probability density function over the interval that it is being calculated over. To find the sum of smaller points, all you have to do is integrate that function. In this case, you'll be integrating the PDF. So the cumulative distribution function for a point x calculated over the probability density function p of x, which is lesser than the value of x, is nothing but the total sum of that entire probability density function. This can also be represented in the form of integration as an integration of the PDF. So we already know in the previous slide that the PDF was represented as f of x. So when we integrate f of x over the values that we have to calculate the cumulative distribution function, in this case between the values of a and b, that's when we get the total distribution function or the cumulative distribution function. Now, up until this point, we've talked about various different terms such as the probability density function and mixed variables, discrete variables, etc. But what do these terms mean? So first, let's take a look at the probability density function, a function which basically defines the relationship between a random variable and its probability is called a probability density function. It shows the relationship between a random variable and the probability such that on solving that function, we get the probability distribution for that random variable. A probability density function of a continuous random variable is a function whose value at any given point in the sample space can be interpreted as providing a relative likelihood that the value of the random variable would equal that sample. Next, we've also been talking about various types of random variables. One of them is a continuous random variable. So what is a continuous random variable? A continuous random variable is one which can take off infinite different values within a range of values. For example, rainfall in a month. Basically speaking, a continuous random variable is a random variable where the data can take infinitely many values. For example, the amount of rainfall received in a month. So let's say every day we get a certain amount of rainfall. So consider a day where we got a rainfall of 1.7 centimeters. In this case, the value 1.7 is not exact. In some areas, the rainfall might have been 1.68, while in others it might be 1.71 or 1.70001. In this case, the random variable can take on an infinite different amount of values which are falling within the same range of 1.7. This is called a continuous random value because there's no definitive value. When we plot a graph of all the different values that the variable can take, we get a continuous curve and not multiple different scattered data points. Another type of a random variable is a discrete random variable. A discrete random variable is the very opposite of a continuous random variable. This variable can take a definitive value within a certain range, and the values are usually within a certain distance or a certain range from each another. For example, consider the example of rolling a dice. When you roll a die, there are 6 definitive values that you can get. 1, 2, 3, 4, 5, and 6. When I roll a die and I say that I got the value of 2, I don't mean that I got 1.999 or 1.98 or 2.30. I mean that I got a definitive value of 2. In simple words, a discrete random variable is a variable whose value can be obtained by counting. It has a countable number of possible values, and the number of values that it can take are finite. Next, we come to mixed random variables. A random variable which can take on both discrete and continuous values is called a mixed random variable. The range of values which fall under this random variable are a mixture of discrete and continuous random variables. For example, take a look at this graph. Starting from 0 and extending up unto 0.5, this variable can take on infinite number of values between this range up until the value for y of 1 by 4. After this, it can take on only one value up until infinity, which is the constant value of 1. So in this region, as we can see, we can plot multiple different values for the same variable. So in this region, ranging from 0.5 on the x-axis and 1 by 4 on the y-axis, the random variable behaves as a continuous random variable. And after this point, ranging up unto infinity, it has a definitive value of 1, and hence it behaves as a discrete random variable. So this random variable can be said to be a mixed random variable. Now let's come up to the case study. In this case study, we will be working with the iris dataset. The iris dataset is a dataset which contains information about 3 different species of iris flowers. Each different species has 50 data points assigned to it, and the species included in the dataset are Iris setosa, Iris versicolor, and Iris virginica. For each flower which constitutes a sample in our dataset, the length and the width of the sepals and petals is measured in centimeters, and these are the features that we'll be working with. Now, based on the combination of these 4 features, it becomes easy to classify the different flowers and to figure out which type of flower it is. It is usually used for classification models. So this is what your iris dataset looks like. It has 50 different rows or 50 different data points and 5 columns. The column values describe the sepal length, the sepal width, the petal length, and the petal width. It also has a separate column which details the species that each of these samples belong to. Now, depending on these 4 features, these are the features that we'll be working with, you're supposed to differentiate between the 3 different species of iris flowers. And as you can see, these features are quite little different from each other. For Setosa, in fact, the sepal length ranges around the value of 5, whereas for Virginica, it ranges more around the values of 6, 6.5. So based on these values, you can differentiate between these 3 different flowers. Now, before we start finding the CDF of this dataset, we first have to find the probability density function by using the different features and plotting the histograms. What is a histogram, first of all? A histogram is an accurate graphical representation of distribution of numerical data. It is an estimate of the probability distribution of a continuous variable. To construct a histogram, the first step is to bin the range of values, that is, divide the entire range of values into a series of intervals and then count how many values fall into each interval, and then plot those values in the form of rectangles. The bins are usually consecutive and non-overlapping intervals. Now, because our ultimate aim is to be able to correctly identify the species of iris flowers given its features, the first question that we have to ask ourselves is which among the 4 features is more useful than other variables in order to distinguish between the species of iris flowers. To answer this question, we first plot the probability density function with each feature as a variable on the x-axis and its histogram and corresponding kernel density plot on the y-axis. So as you can see, when we do that, these are the graphs that we get. The first density plot that we see here plots the sepal length values. So in this graph, as you can see, the sepal length for the 3 flowers, Setosa, versicolor, and virginica, have a significant overlap between each other. A huge amount of the data for Setosa, versicolor, and virginica overlap, and even their distribution graphs, as you can see here represented by these curves, have a major overlap. Versicolor is almost entirely taken over by Setosa and virginica. Because of this, it wouldn't be a good idea to consider sepal length as a distinctive feature. Now, coming to sepal width, we can again see that there's a lot of overlap. A lot more than the overlap in sepal length itself. The spread of data is also very high. In sepal length, the data values were ranging from around 4 to around 8, which is around 4 data points. But over here, they range from 1.5 all the way to 5, which is a slightly higher value as compared to sepal length. So it becomes clear after seeing these graphs that we cannot distinguish between our flowers based on the sepal length and the sepal width itself. Next, we come on to the petal length graph. In the graph of petal length, as you can see, most of the different features are very distinctive from each other. There's not much overlap. The only overlap that you can see is between versicolor and virginica, and even that is significantly lower than that of the sepal length and sepal width. Furthermore, the PDF distributions over here also take on a bell shape. This kind of a probability distribution is called a normal distribution. So it will become easier to calculate the CDF for these as the PDF for the petal length is very well defined. Now over here, as you can see, the Setosa species is well separated from versicolor and virginica. The density of the petal width also looks pretty good. The overlap between these 3 flowers is very less, but again there's a little bit of overlap over here between Setosa and versicolor, and obviously you can see the overlap here between versicolor and virginica. The PDF distribution is also not very well defined, and the normal curve is not smooth in this case. After looking at these graphs, it becomes evident that if we have to choose one feature for classification, we will be picking petal length to distinguish between the species. On the other hand, if you're going to select 2 features, then you might as well choose the petal length and the petal width, because these again have the least amount of overlap. Next, we have to find the CDF of our dataset using the petal length feature. Again, this can be done by integrating over the PDF or by finding the cumulative sum of the PDF values. When we do this, the below graph is observed. The bell-shaped curves in this graph represent the probability density function, and the exponential curves represent the CDF. The CDF is nothing but the cumulative sum or the integration obtained after PDF. So this graph is obtained by adding every single value on our PDF graph. After looking at this, there are three main conclusions that can be drawn. From the graph that we see, it is evident that 100% of the Setosa flower species have a petal length which is less than 1.9. How do we conclude this? As you can see, the CDF for the Setosa flower falls just short of 2. We can take, after extending this value onto the x-axis, we get the value of 1.9. And anything below this value will fall under this curve and will definitely belong to the Setosa species. Now coming on to versicolor and virginica. For versicolor, we can see that the range is from just after 3 to a little after 5. So we can say that petal length, which lies between 3.2 and 5, has a good chance of being versicolor. A chance of 95% in fact. Where is that 5% of uncertainty coming from? Again, as you can observe from this graph, there's a slight amount of virginica which overlaps with versicolor below the petal length of 5 centimeters. So because of this, we have a slight amount of uncertainty which comes into the equation. Now looking at the CDF for virginica, we can see that anything which is above 5 has a very good chance of being virginica. A 90% chance in fact. Where are we losing that 10% of accuracy? This is because some of the petal lengths of the virginica flower falls below 5. Also, there's a little bit of overlap above the value of 5 with versicolor. Because of this, the accuracy for virginica is further reduced. But at the end of the day, we can say with confidence that majority of the flowers which have petal lengths of greater than 5 have a 90% chance of being the virginica flower. Now let's take a look at how we can find the cumulative distribution function with the help of Python. So before we start with finding our CDF, we first have to import necessary modules into our Python program. The first module that we'll be working with is the Pandas library. The Pandas library is used to deal with datasets and modify them at ease. Next, we'll be working with two libraries which are used for plotting data and making graphs, Seaborn and Matplotlib. And finally, we'll also be working with the numpy library, which is used to perform numerical computations on our datasets. So let's run this and import our libraries. Next, let's read the pre-downloaded dataset into our program. This is done with the help of pandas.readcsv, which is going to read in a file which consists of comma-separated values and structure them in the form of a dataset. So again, as you can see, this is our iris data set. It has 4 features: sepal length, sepal width, petal length, and petal width, which are used to differentiate between 3 different species of flowers. And it has 150 data points ranging from 0 to 149, with each flower being allocated 50 data points. Let's perform exploratory data analysis on our iris data set. First, let's find the mean and the median of the iris dataset. Now for all the species, the respective values of mean and median of all the features present in the dataset are found to be pretty close. So as you can see here, sepal length for the 3 different species of flowers that we're going to be considering are pretty close to one another. The Setosa has a mean sepal length of 5 and versicolor has a mean sepal length of 5.936. Virginica is even closer to versicolor with a mean sepal length of 6.5. And this is the trend that you can see in every single feature of our dataset. This indicates that the data is nearly symmetrically distributed with very less presence of outliers. Let's see how spread out our data is Now let's see how spread out our data is, or how wide the range that it falls between is, by finding the standard deviation. Again, the standard deviation for various different features of a data set is found to be a very small value. All of the standard deviation values are comparable to each other for all the features. This means that our data isn't spread out very far, and further shows how few outliers are present in our data. Now let's find the violent plots for the different features which are present in our data set. What is a violent plot? A violent plot shows the distribution of data across several levels of one or more categorical variables, in our case flower species. It plots the distribution such that they can be compared. The violent plot also shows the kernel density estimation of the underlying distribution. So once we're done plotting the violent plots, here are some conclusions that you can draw from them. The violent plot for the sepal length has a huge range of values. It ranges from 4 to 6, and also there are a lot more outliers present in this graph, as can be seen from how wide our violent plots are. The same can be said for sepal length. The range of values is even higher for all three different flowers, and the outliers are even more as they're wider also. Now coming to a petal length, we can see that the range of values that the various petal lengths fall under are very small. Further, the outliers are also not a lot, with Setosa having the most outliers in this case. Versicolor and Virginica have relatively fewer outliers. Another thing that will strike you over here for the petal length feature as compared to the sepal length and the sepal width feature is that in this case, there's a lot of overlap in the range where these values fall under. So as you can see for Setosa, it overlaps significantly with a vast amount of the versicolor species data. And the same can be said for Virginica. The same is also observed in the sepal width feature. But in petal length, all of the three different species have very distinctive ranges of values. Now coming to petal width, we can see that again, the range of values is very short and there's not a lot of overlap, but it's significantly more as compared to that of the petal lengths. Also, the outliers for different species in petal width are greater than that compared to the petal length, as can be seen from how much more spread out this data is widthwise. Now let's also plot pair plots for our iris data set. A pair plot basically allows us to see both distributions of single variables and relationship between two variables. Now in our case, we have four features: sepal length, sepal width, petal length, and petal width in our iris data set. In this case, we will have 6 unique plots which plot two different features against each other. The pairs are going to be sepal length versus sepal width, sepal length versus petal length, sepal length versus petal width, sepal width versus the petal length, the sepal width versus the petal width, and the petal length versus the petal width. Now along the diagonals, the plots basically showcase our histogram data. These are univariate graphs which basically plot one single variable, like in this case sepal length, over here sepal width, over here petal length, and over here petal width. These histograms allow us to see the probability distribution of a single variable, while these scatter plots allow us to see the probability distribution of various features. Now again, looking at these various pair plots, we can come to different observations and conclusions. The first one being that petal length and petal width are the most useful features to identify various different flower types. As you can see here, the data falls between different ranges as compared to the other graphs, where there's a lot of overlap in the ranges that the data falls within. Over here in this graph, we've literally separated the Setosa species of flowers from the rest of the data as it's all concentrated between a certain range and has no overlap in the x-axis or the y-axis with the rest of the data. For versicolor and virginica, the data overlap is very small, but we can find lines and if-else conditions to help build a simple model to differentiate between these two flower types. Also, there's not a lot of data overlap in the y-axis along with the x-axis for all of the three different flower species. The same cannot be said for any of the other plots that we've plotted. Over here in this graph, there's a lot of overlap between versicolor and virginica, and even setosa has an overlap along the y-axis with the other two flowers. So using this, we can conclude that if you were to find the CDF using two different features, petal length and petal width would be the best two features to plot against one another to help classify our flowers. Now let's find the probability density function of our data. So again, we're going to be plotting the various different features in the form of histograms. And over here, as explained before, we see the least overlap in our petal length feature, and this is evidently the best feature that we can use to differentiate between our different flowers. Now let's find the CDF of our data by using the petal length feature. First, let's isolate the data that we have available on the different types of flowers into three different arrays and lists. Next, we know that the area under the plot of the PDF over an interval represents a probability of occurrence of random variable in that interval. In our analysis, petal length is the random variable. Mathematically speaking, CDF is an integral of PDF over the range of values that a continuous random variable takes. The CDF of a random variable evaluated at any point x gives the probability that a random variable will have a value less than or equal to x. So now we're going to be plotting the PDF and the CDF for the iris setosa, versicolor and virginica flowers for comparative analysis of the petal lengths on the same graph. To find the PDF, we first take the counts feature and the bin edges of a histogram. The counts feature is going to tell us how many values are present in every single histogram bar. To find the PDF, all we have to do is take every single data value and divide it by the total number of data values. This is going to give us a continuous graph of the PDF. The CDF is nothing but the cumulative summation of the PDF. This can be done by using the numpy.char function on the PDF. Following this, all we do is plot the PDF and the CDF for various different flowers together on the same graph so that it becomes easier to compare them. Let's run this and see what we finally get. So finally, this is the graph that we get. As said again, we can see from this graph that 100% of the setosa flower species fall below 1.9 and 95% of the versicolor flower species have petal lengths less than 5 but greater than 3.2, while about 10% of the virginica flowers will have petal lengths less than 5. So at the end of the day, we can say that the accuracy for finding our virginica flowers is going to be around 90%. Thus, by using the cumulative distribution plots, we get a better picture and robust understanding of distribution leading to formation of simple univariate classification models.
What is a random experiment? Let's say that you roll a fair die and there are 6 possible outcomes. You can get a number from 1 to 6, but it is impossible to accurately predict the outcome. In mathematical theory, we consider only those experiments or observations for which we know the set of possible outcomes. Also, it is important that predicting a particular outcome is impossible. Such an experiment, where we know the set of all the possible results but find it impossible to predict any one particular execution, is a random experiment. Even if a random experiment is repeated under identical conditions, the outcomes or results will fluctuate randomly. Sample space and events. The sample space associated with a random experiment is the set of all the possible outcomes. Suppose you roll a die. So the sample space for a single throw of die will be 1, 2, 3, 4, 5 and 6. An event is a subset of the sample space, or you can say it is an outcome of a random experiment. Getting a heads when we toss a coin is an event. Now we will discuss about the multiplication rule in probability. The multiplication rule says that when two events are independent, the probability of both occurring simultaneously is given by probability of A intersection B will be equal to probability of A into probability of B. Let's understand this with the help of an example. If a coin is tossed twice, what will be the probability of getting two heads? So, in a single throw, the probability of getting a heads is 1 by 2, that is 0.5. So, the probability of getting the two heads in both the coins will be 0.5 into 0.5, which is equal to 0.25. Let's look at another example. Suppose a coin is flipped and a die is rolled at the same time. So, what will be the probability of getting a head on the coin and 4 on the dice? So, the probability of getting a heads, as discussed in the previous example, will be equal to 0.5, and the probability of getting a 4 on a single throw of die will be 1 by 6, since there are 6 sample space and 1 favorable outcome. So, the probability of getting a head on a coin and 4 on a die will be equal to 0.5 into 0.16, which will come out to be 0.80. Now let's move on to dependent events. Two events are said to be dependent if the outcome of the first event affects the outcome of the second event so that the probability is changed. Let's understand this with the help of an example. Suppose you have a deck of cards. The probability of drawing a card from a deck of cards is 1 by 52. Now, if you do not replace the card, the probability of drawing another card changes to 1 by 51. Another example of it can be parking at a no parking zone and getting a ticket. When you park at a no parking zone, the probability of getting a ticket increases. There is a multiplication rule associated with the dependent events. It says that when the two events are dependent, the probability of both occurring is given by this formula, which is P A intersection B is equal to probability of A into probability of B slash A. The slash reads the probability that B occurs given that A has already occurred. Let's look at an example. 3 cards are drawn from a deck and are not replaced. What will be the probability of getting 3 jacks? So in this case, the probability of getting a jack out of 52 cards in the first draw will be 4 by 52. Now after we have drawn the first card, there are 51 cards left. The probability of getting a jack in a second and third draw will be 3 by 51 and 2 by 50 respectively. So according to the formula, the probability of getting the 3 jacks will be P 0.76 into 0.058 into 0.04, which will come out to be 0.00176. Now that we know all the basic concepts in probability theory, we'll move on to conditional probability. Let A and B be the two events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred is called the conditional probability. It is denoted by PA slash B. Thus, we have PA slash B is equal to PA intersection B divided by P of B. PA slash B is read as probability of occurrence of A given that B has already occurred. Similarly, B slash A can be called as probability of occurrence of B given that A has already occurred. Let's look at an example. In the recent study, it was found that the probability of a randomly selected student is a girl is 0.51 and is a girl and plays sports is 0.10. So if the student is a female, what is the probability that she plays sports? In this case, the probability that a student is female and plays sport is 0.1 and the probability that a student is female is 0.51. So the probability that a student plays a sport given that she is a female will be 0.1 divided by 0.51, which will come out to be 0.1961. Now we are done with all the theories related to conditional probability. We'll move on to the demo in Excel. Let's look at this problem statement. Suppose there are a group of 100 buyers out of which 70 purchased football and 40 purchased hockey. However, there are 20 buyers who purchased both football and hockey. Determine the probability that a randomly chosen buyer has purchased football given that he also purchased hockey. So, this is a clear example of a conditional probability. Let's fill in this table. So the probability of purchasing a football is 0.70 and that of hockey is 0.40. It is also given that there are 20 buyers who have purchased both football and hockey. So 0.20 is the probability of PA intersection B. Now if you remember the formula of the conditional probability, the A slash B is equal to PA intersection B divided by P of B, where PA intersection B is the probability of occurrence of both A and B. PB is the probability of occurrence of B. So we have all the values, let's fit in. So this will be equal to, this is cell E7. So we'll divide the cell E7 by cell E6. Probability is a branch of mathematics concerning numerical descriptions of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking 0 indicates the impossibility of the event and 1 indicates certainty. The higher the probability of an event, the more likely is that the event will occur. Let's look at an example. A simple example is the tossing of a fair unbiased coin. Since the coin is fair, the outcome, that is heads and the tails, are both equally probable. The probability of heads equals the probability of the tails, and since no other outcomes are possible, the probability of either heads or tails can be said to be 1 by 2, which is also 50%. The probability of an event can be calculated by number of ways it can happen divided by the total number of outcomes. Now that we know about the probability, let's see if you can answer this question. What is the probability of drawing a jack and a queen consecutively from a deck of 52 cards without replacement? Here are your options. Post your answers in the comment section and let us know. Now let's move on to conditional probability. Let A and B be the two events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred and probability of B is not equal to 0 is called the conditional probability. It is denoted by PA/B. Thus, we can say that PA/B is equal to PA intersection B divided by P of B, where PA/B is the probability of occurrence of A given that B has already occurred, and PB is the probability of occurrence of B. To know more about conditional probability, you can check our previous video which is specifically on conditional probability. Now let's move on to Bayes' theorem. The Bayes' theorem is a mathematical formula for calculating conditional probability in probability and statistics. In other words, it is used to figure out how likely an event is associated on its proximity to another. Bayes' law or Bayes' rule are the other names of this theorem. The formula for the Bayes' theorem can be written in a variety of ways. The most common version is PA/B is equal to P of B/A into P of A divided by P of B, where PA/B is the conditional probability of event A occurring given that B is true, and PA and P of B are the probabilities of A and B occurring independently of one another. Let's solve a problem using the Bayes' theorem to understand it better. There is a cricket match tomorrow, and in recent years it has rained only 5 days each year. Unfortunately, the meteorologist has predicted the rain for tomorrow. Now, when it rains, the meteorologist correctly forecasts rain 90% of the time, and when it doesn't rain, he incorrectly forecasts rain 10% of the time. Let's calculate what is the probability that it will rain on the match day. So, the two sample spaces here are the events that it rains and it does not rain. Additionally, a third event is also there that meteorologist predicts the rain. So the notation for these events appear below. Event A1 is equal to it rains on the match day, event A2 that it does not rain on the match day, and event B is the meteorologist predicting the rain. Now in terms of probability, we know the following. Probability of A1 is 5 by 365 that it rains 5 days in a year, which will come out to be 0.0136. PA2 is 360 by 365, that is no days for 360 days in a year, which will come out to be 0.986. PB/A1 is 0.9. This signifies when it rains, the meteorologist predicts the rain 90% of the time. In a similar manner, PB/A2 is 0.1, that it does not rain, the meteorologist predicts the rain 10% of the time. Combining all this, we can calculate PA1/B, that is the probability it will rain on the given match day given a forecast of rain by meteorologist. The answer can be determined using the Bayes' theorem as shown below. So here's the formula of the Bayes' theorem, and putting all the values that we have calculated in the previous slide, the probability that it will rain on the match day given a forecast of the rain by meteorologist will come out to be 0.111, which will be equal to 11.11%. So there's an 11% chance that it will rain on the match day given that the meteorologist has predicted the rain. I hope this example is clear to you.
So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it. So you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like. So you have an answer for it. And you have labeled data which is used. You have an external supervision and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut. One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors. Used to solve reward-based problems. No predefined data is used. No supervision. Follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works, and this is my reward. Doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. this is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of a different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options, and we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching. And then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that. And it goes, oh, this is also reward based. And so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, that you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was, and then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row, same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3, it just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment, and suddenly a reward system like this is going to be just is going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing. You add weights to it, and so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward, because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game, or even learn something that isn't a game, is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess. I think was a big one where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action. It's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where you self get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state. This is class player. And when we say class player, we're not talking about a human player. We're talking about just the computer players. And this is kind of interesting. So remember I told you depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it. As you try different moves, it gets to the end. The first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action, and this is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position. And then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through. So it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important. This is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2. I probably should have done ABC. This has a step 3. Step 4, and so on until you get to step N, and this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. It just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have our self setup on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here, and feed forward. Again, this is because it's a human. At the end of the game, back propagate and update state values. this part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go, and it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here, and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just 1 round of training, in fact minimal training, and so it puts an X there, and I'm going to go ahead and do row 0, column 1. And you can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, and you can see right here it let me win. Just like that, I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time, instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3 by 3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. So you pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last, whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
Supervised learning uses labeled data to train machine learning models. Labeled data means that the output is already known to you. The model just needs to map the inputs to the outputs. An example of supervised learning can be to train a machine that identifies the image of an animal. Below you can see we have our trained model that identifies the picture of a cat. Unsupervised learning uses unlabeled data to train machines. Unlabeled data means there is no fixed output variable. The model learns from the data, discovers patterns and features in the data, and returns the output. Here is an example of an unsupervised learning technique that uses the images of vehicles to classify if it's a bus or a truck. So the model learns by identifying the parts of a vehicle, such as the length and width of the vehicle, the front and rear end covers, roof hoods, the types of wheels used, etc. Based on these features, the model classifies if the vehicle is a bus or a truck. Reinforcement learning trains a machine to take suitable actions and maximize reward in a particular situation. It uses an agent and an environment to produce actions and rewards. The agent has a start and an end state, but there might be different paths for reaching the end state, like a maze. In this learning technique, there is no predefined target variable. An example of reinforcement learning is to train a machine that can identify the shape of an object given a list of different objects such as square, triangle, rectangle, or a circle. In the example shown, the model tries to predict the shape of the object, which is a square here. Now, let's look at the different machine learning algorithms that come under these learning techniques. Some of the commonly used supervised learning algorithms are linear regression, logistic regression, support vector machines, k-nearest neighbors, decision tree, random forest, and naive Bayes. Examples of unsupervised learning algorithms are k-means clustering, hierarchical clustering, db-scan, principal component analysis, and others. Choosing the right algorithm depends on the type of problem you are trying to solve. Some of the important reinforcement learning algorithms are Q-learning, Monte Carlo, SARSA, and Deep Q network. Now let's look at the approach in which these machine learning techniques work. So supervised learning takes labeled inputs and maps it to known outputs, which means you already know the target variable. Unsupervised learning finds patterns and understands the trends in the data to discover the output. So the model tries to label the data based on the features of the input data. While reinforcement learning follows trial and error method to get the desired solution. After accomplishing a task, the agent receives an award. An example could be to train a dog to catch the ball. If the dog learns to catch a ball, you give it a reward such as a biscuit. Now, let's discuss the training process for each of these learning methods. So supervised learning methods need external supervision to train machine learning models, and hence the name supervised. They need guidance and additional information to return the result. Unsupervised learning techniques do not need any supervision to train models. They learn on their own and predict the output. Similarly, reinforcement learning methods do not need any supervision to train machine learning models. And with that, let's focus on the types of problems that can be solved using these three types of machine learning techniques. So supervised learning is generally used for classification and regression problems. We'll see the examples in the next slide. And unsupervised learning is used for clustering and association problems, while reinforcement learning is reward based. So for every task or for every step completed, there will be a reward received by the agent. And if the task is not achieved correctly, there will be some penalty used. Now, let's look at a few applications of supervised, unsupervised, and reinforcement learning. As we saw earlier, supervised learning are used to solve classification and regression problems. For example, you can predict the weather for a particular day based on humidity, precipitation, wind speed, and pressure values. You can use supervised learning algorithms to forecast sales for the next month or the next quarter for different products. Similarly, you can use it for stock price analysis or identifying if a cancer cell is malignant or benign. Now, talking about the applications of unsupervised learning, we have customer segmentation. So based on customer behavior, likes, dislikes, and interests, you can segment and cluster similar customers into a group.
What is NLP? Natural language processing, NLP, constitutes a sector of artificial intelligence focused on textual and speech data. This technology enables machines to comprehend, scrutinize, and handle human language, extract valuable information in the process. Now, let's understand who is an NLP engineer. A natural language processing engineer or NLP engineer is a professional responsible for crafting and constructing computer systems that can process, assess, and produce human-like language. NLP branches out into numerous captivating domains, including semantic analysis, sentiment analysis, face recognition, machine translation, and speech recognition. Now, the reach of NLP extends across a diverse spectrum of applications, notably featuring virtual assistants, chatbots, sentiment analysis, customer service interactions, and language translation. The task of NLP engineers involves erecting these innovative applications and seamlessly embedding them into existing frameworks. Now, the average salary of an NLP engineer is 10 lakhs per annum in India. In US, the annual wage of NLP engineers is about $120,000 per annum. Now, let us understand the skills required to become an NLP engineer. Becoming a natural language processing engineer entails the acquisition of a diverse set of skills and knowledge. Some of these encompass the first one as Python programming. Mastery of at least one programming language, such as Python, Java, or C++, coupled with solid grasp of data structures, algorithms, and the principles of software engineering is important. Next is grasp of machine learning. Building a strong foundation in machine learning algorithms encompassing both supervised and unsupervised learning is important. Familiarity with advanced techniques like convolutional neural networks, or also known as CNNs, and recurrent neural networks, also known as RNNs, is vital. The third one being NLP techniques. Cultivating a deep understanding of NLP techniques, which encompasses facets like text preprocessing, syntactic and semantic analysis, and the intricate domain of sentiment analysis. Fourth one is NLP libraries and frameworks. Navigate easily through the NLP libraries and frameworks such as the Natural Language Toolkit or NLTK, Spacey, Stanford Core NLP, and Genesim, harnessing their capabilities to streamline your NLP endeavors. The fifth one is data science acumen. Developing a sound grasp of data science principles encompassing facets such as data visualization, statistical analysis, and the art of data manipulation is important. Armed with this multifaceted skill set, you will be primed to embark on a journey as an accomplished NLP engineer who is ready to navigate the complexities of natural language and contribute to the exciting world of NLP innovations. Now, the important point of today's session That is the roadmap to become an NLP engineer. Here is a comprehensive professional strategy or trajectory for those aspiring to become adept natural language processing engineers. The first one is educational foundation. Embark on your journey by pursuing a degree in a pertinent field such as computer science, linguistics, or artificial intelligence. Many accomplished NLP engineers hold advanced degrees, either a master's or a PhD in these domains. Next one is internship or entry level ventures. Consider immersing yourself in practical experience through internships or entry level positions within the industry. These opportunities not only equip you with hands on expertise but also aid in constructing a robust portfolio. Moreover, they facilitate the establishment of valuable professional connections. Next is skills and knowledge acquisition. Develop a comprehensive grasp of the essential proficiencies requisites for an NLP engineer. This encompasses programming prowess, machine learning acumen, NLP techniques, familiarity with pertinent libraries and frameworks, proficiency in data science, and the owning of communication and teamwork competencies. Next is portfolio development. Curate a diverse portfolio teeming with projects that illuminate your capabilities and expertise. Projects like a sophisticated chatbot, a sentiment analysis tool, or a language model can substantiate your aptitude for solving real world NLP challenges and validate your skill set for potential employers. Now, the next one, networking endeavors. Engage in conferences, meetups, and industry events to forge connections with fellow NLP professionals. This affords opportunities to remain abreast of the latest developments in the field and exposes you to an array of NLP applications. Next is specialization consideration. Ponder the prospect of specializing in a specific NLP realm, be it machine translation, speech recognition, or conversational agents. This specialization not only differentiates you in the job market but also enables you to attain expertise within a particular niche. In summation, the path towards becoming an NLP engineer entails a fusion of educational attainment, hands-on experience, and the mastery of an eclectic array of skills and knowledge domains. Now, we will discuss the applications of NLP. Natural language processing boasts an extensive array of applications extending well beyond the following 10 examples. We have chatbots, intelligent replies on chatbot platform, which was email or LinkedIn, virtual assistants in customer care services, spelling check, and grammar correction.
In India, the salary ranges from 2.5 million rupees to 5 million rupees. However, in US, the salary ranges between $60,000 to $90,000 per year. Entry-level NLP engineers typically have background in computer science engineering or a related field and have some experience with NLP but may not have yet worked on large-scale enterprise projects. Moving towards mid-level NLP engineers. These engineers earn 5 million to 8 million rupees per year. However, in United States, they earn between $90,000 to $120,000 per year. Mid-level NLP engineers have few years of experience working on NLP projects and are typically comfortable working on both technical and business-related aspects of NLP projects. They may have some leadership responsibilities and are often responsible for ensuring that NLP projects are completed on time and to spec. Next, we have is senior level NLP engineers. These engineers earn up to 8 million rupees to 15 million rupees in India per year. However, in the United States, they earn between $120,000 to $165,000 per year. Senior level NLP engineers have extensive experience working on enterprise level NLP projects and are often considered authorities in NLP technologies, methods, and tools. They may serve as subject matter experts, lead teams of engineers and other NLP professionals, and be responsible for ensuring the long-term success of NLP project.
So what is deep learning? Deep learning is a subset of machine learning that deals with algorithm inspired by the structure and function of the brain, and which is a part of artificial intelligence AI. Deep learning is widely used to make weather predictions about rain, earthquakes, and tsunamis. It helps in taking the necessary precautions. With deep learning, machine can comprehend the speech and provide the required output. It enables the machines to recognize people and objects in the images fed to it. Deep learning models also help advertisers leverage data to perform real-time bidding and target display advertising. So what is neural network? To understand how an artificial neuron works, we should first understand how a biological neuron works. So this is one of a biological neuron. So dendrites. These receive information or signals from other neurons that get connected to it. The second one is cell body. Information processing happens in a cell body. These take in all the information coming from the different dendrites and process that information. The last one is axon. It sends the output signals to other neuron for the flow of information. Here each of the flank is connected to the dendrite or the hairs on the next one. Now let's see a neural network. So this image shows an ANN. Okay. So the network starts with an input layer that receives input in data form. The lines connected to the hidden layers are called weights and they add upon the hidden layers. Each dot in the hidden layer processes the inputs and it puts on output into the next hidden layer and lastly into the output layer. So here input to a neuron is known as input layer and the actual neuron is called hidden layer and the output to the next neuron is called output layer. A neural network is a system of hardware or software patterned after the operation of neurons. In the human brain, neural network, also called artificial neural network, are a means of achieving deep learning. So this is a Python kernel file. Okay. So here I will change the name deep learning with Python. Here we will do flower recognition using CNN. Okay, so first what I will do, I will import OS and here I will write print os.list directory, then C / users / 09375 / desktop. This is the path of that folder where I have put the images class. Okay, so let's run it. Yeah, so we have 5 categories in flowers like daisy, dandelion, rose, sunflower and tulip. Okay, I will provide you the zip file of this dataset. So now import some major libraries. So here I will write import warnings, then warnings dot filter warnings, then always. Okay, these are just the warnings. When warnings come, it will ignore or it will always. Warnings, then here I will write ignore. Okay, then let's import some libraries for data visualization and manipulation. So here I will write import numpy as np, then import pandas as pd, my bad, import pandas as pd, then import matplotlib dot pyplot as plt, then from matplotlib import style. Don't worry, we will discuss each of the library. Then import Seaborn as SNS. So what is numpy? This one, numpy. So numpy is a Python library used for working with arrays. It also has a function for working in the domain of linear algebra and matrices. It is an open source, means free project, and you can use it freely. NumPy stands for numerical Python. And the second one is Pandas. Pandas is a software library written for the Python programming language for data manipulation and analysis. In particular, it offers data structure and operation for manipulating numerical tables and time series. Then the third one is matplotlib. So for Python and its numerical extension NumPy, matplotlib is a cross-platform data visualization and graphical charting package. As a result, it represents a strong open source substitute for MATLAB. The API's application programming interfaces for matplotlib allows programmers to incorporate graphs to GUI applications. Okay, so matplotlib import style or as PLT. Why we are writing as PLT, as PT, as NP? Because we don't have to write again and again the long sentence, the matplotlib.pyplot. Okay, we can import using short name PLT. Then fourth one is import Seaborn. So Seaborn is a Python data visualization library based on matplotlib. It provides a high-level interface for drawing attractive and informative statistical graph. For a brief introduction to the ideas behind the library, you can read the introductory notes or the paper from the website. Okay. So now let's set matplotlib to inline and display graph below the corresponding cell for the corresponding cell. So for that I will write here %matplotlib inline. Okay. Then here I will write style dot use. This is one of the style. So here I will write 538. Okay, then SNS dot set style equals to white grid comma color codes equals to true. Okay, let's import some major libraries for model selection. So for that I will write here from sklearn dot model selection import train test split. Okay, then I will add from sklearn dot model selection import kfold. Then here from sklearn dot model, sorry, here I will add matrices matrix. Then import accuracy score comma precision score comma recall score comma confusion matrix comma ROC curve comma ROC. Okay, then here I can import ROC AUC curve not score. So now we will import some more, like from sklearn dot model selection import grid search CV. Then from sklearn dot preprocessing import label encoder. So what is train test split? Okay, Okay, this sklearn model selection train test split. So train test split to getting training and test sets. This control the size of subset with the parameter train size and test size. So determine the randomness of your splits with the random state parameter. Obtain specified splits with the stratify method. Okay, then k-fold. K-fold is again a validation technique in which we split the data into k subsets and the holdout method is repeated k times, where each of the k subsets are used as a test and other k1 subset are used for the training purpose. This accuracy score, precision score, recall score, confusion matrix, ROC curve and ROC accuracy curve. So these all are for the accuracy, to check the accuracy, what will the precision score, and the ROC curve graph for making graphs and all. Okay, these are for metrics. Then grid search CV. So grid search CV is a technique for finding the optimal parameter values from a given set of parameters in a grid. It essentially a cross validation technique, so the model as well as the parameter must be entered. So this is after extracting the best parameter values, the prediction are made. Okay, so this label encoder. So label encoding is a popular encoding technique for like handling categorical values, okay, or variables you can say. So in this technique or method, you can say each label is assigned a unique integer based on alphabetical order. Okay, so now for pre-processing I will import something. So here I will write from ks dot utils not pre-processing dot image import image data generator. Okay, yeah. So this is for the pre-processing of the image. So image data generator, what does it? Allows your model to receive new variation of the images at each epoch. Okay, so but do you remember that it only returns the transform images and does not add it to the set of images that you have, like for the, in our data set. Okay, just it is used for the transform in image. Now let's import some deep learning libraries. So here I will write from keras import backend as k. Okay, then another one is from keras dot models import sequential. Then from keras dot layers import pens. Okay, let's write from keras dot optimizers import Adam, SGD. These all are the optimizers. ADA grad, ATA, ADE, ADA delta. Okay, then last one is RMS Pro. Then from keras dot utils import to categorical. Okay. So Keras. Keras is a model level library providing high level building blocks for developing deep learning models. It does not handle itself low level operations such as like tensor products or convolutionals and so on, and this sequential. Okay, so sequential, the core idea of sequential API is simply arranging the Keras layers in a sequential order, and so it is also called sequential API. Like most of the ANN also has layers in sequential order, and the data flows from one layer to another layer in the given order until the data finally reaches the output layer. And this dense. So Keras dense layer is a layer that contains all the neurons that are deeply connected within themselves. This means that every neuron in the dense layer takes the input from all the other neurons of the previous layer. So we can add as many as dense layer as required. So dense is the one of the most commonly used layers in deep learning. And these optimizers, ADAM, SGD, ADA grad, ADA delta. So optimizers are classes or methods used to change the attributes of your machine or deep learning model, such as weight and learning rate, in order to reduce the losses. So optimizer helps to get result faster. Then this keras.utilist. So keras utilist to categorical function will return the binary value matrix which contains the values either 0 or 1. It contains an equal number of rows from the length of the input vector and column number which was equal to the class number which we defined in our code. Okay, so now let's import for CNN. So here I will write from keras dot layers import dropout flatten activation, and then from keras dot layers import conv2d, then max pooling, max pooling 2d, then patch normalization. Okay, so these are some more layers for the CNN, for particularly CNN. Then import TensorFlow as TF, then import random as Rn. Then random is used for finding the random value. Then let's specifically for manipulating zipped images and getting numpy arrays of pixel value of images. Let's import that. So here I will write import cv2, then from tqdm import tqdm. Okay, then I will write import os, give the spaces, then from random import shuffle, then from zip file, okay, import zip file, then from PIL import image. So TensorFlow is an end-to-end open source platform for machine learning and deep learning. TensorFlow is a rich system for managing all aspects of machine learning system. However, this class focuses on using a particular TensorFlow API to develop and train machine learning models. Okay, train or test. So TQDM means like progress, and it is used to create a smart progress bar for the loops. Okay, now let's run this and see any error. Okay, there is one error. Grid search CV. Where is that grid search CV? What is it? Okay, S will be capital here. Okay, a processing. Maybe processing spelling is wrong, I guess. It's pre-processing. See, pre-processing. Okay, this is the spelling mistake, the minor spelling mistakes. Okay, here keras.optimizers import Adam. So what's cannot import name ADA delta. Why? Because A should be capital here. A will be capital here. Okay. Now module name keras.utils. Okay. It's utils. One more, the last one I guess so. Cannot import name zip file. Zip file, import zip file. Okay, these are some spelling mistakes you can say while importing. So now what we will do next, we will prepare the data and make the functions to get the training and validation set from the images. Okay, so here I will write x equals to blank array and z equals to blank array. Okay, then image size equals to 32. Then we will import all the because we have one particular folder named flowers, and on that we have 4 folders or 5 folder, like with one daisy, one sunflower, one tulip, one dandelion, one rose. Okay, so we have to import each of folder one by one. So here I will write flower, daisy from directory. Okay, and the directory is, I can copy from here. Okay, and paste it here. Then I will write here daisy. Okay, so don't worry, I will provide you the zip file drive link. Okay, you can check from the description box below. And here I will write flower, sunflower, directory equals to, then here I will write sunflower. Okay, then here I will write flower, tulip, directory equals to tulip. Okay, say tulip, sunflower, daisy are my folder names. So here I will write flower, then the directory equals to, here I will write dandelion. Then flower, rose, directory equals to, okay, then rows. Okay, so now let's create function assigning label to image and flower type. Okay, then I will write here return flower type. Then what I will do here, I will import some OS, FN match and make train data. Okay, so I will write here import FN match, then I will write import OS, then def making function make train data, then flower type, comma, directory for image in tqdm. For the loop I said os.list directory, list directory from dir. Okay, then here I will write if fn match dot fn match image start.jpg, like anything .jpg, then label equals to assign label to image of flower type. Okay, then path equals to os.path dot join directory images, then image equals to cv2 dot imread path comma cv2 dot imread color. Okay, then I will write here image equals to cv2 dot resize, cv2 is OpenCV file library, image comma img size comma img size. Okay, then here I will write x dot append these x and z, x dot append np dot array image, then x is capital there, z dot append str label, string label. Okay, so now let's run it. Yeah, school. So here we will check all the length of the training data set for particular daisy, that sunflower roll. So here I will make print data, then daisy, comma, flower, daisy directory. Okay, then I will print the length of like how many photos are there. So as you can see, there are total 764. So now like this we'll check for all. So here let me copy this and paste this here. Here I will write rows, and here I will write rows, then run it. So rows has 1584. Okay, make rows like this. So it's flower rows. So now we'll check for sunflower like this only. Sunflower. Here we'll write sunflower. Okay, 3065. Then here I will write for tulip, tulip. So they are 44049. Then last one, dandelion. Dandelion, and here I have to write D and DI. Okay. So first let me tell you about the dataset. So this dataset contains like 442 images of flowers. Okay, 4242. So the data collection is based on the data Flickr or Google Images we took, or Y-index images, and you can use this dataset to recognize plants from the photo. And the picture are divided into five classes like chameleon, tulips, rose, sunflower, and dandelion. And for each class there are about 800 photos. Okay, not like all 800, but 800 photos. Like photos are not that much high resolution, about 320 into 240 pixels are there. So photos are not reduced to a single size, they have different proportion. Okay, so what I will do, I will give space. Now let's visualize some random images. Okay, so here I will write figure comma ax equals to plt dot subplots, then 5,2, then figure dot set size inches 15,15, then for I in range 5, then for j in range 2, like 5 or 2. Okay, 10 images will come. Then what I will write, then L equals to rn dot random input 0 comma length z. Okay, then ax I comma j dot imshow xl ax I comma j dot set title, then flower plus z l. Okay, then plt dot right layout. This is one of the layout of showing photos. Okay, let's run it. So these are some random image of sunflower, that rose. So I already said you these pictures are not that high quality. Okay, that flower, rose is there, then tulip. So moving forward, let's label encoding with the y arrays, like daisy, rose, like daisy equals to 0, rose equals to 1, then 1 out encoding. So for that we'll write here L equals to label encoder then y equals to le dot fit transform z. Okay, then y equals to categorical y comma 5, then x equals to np dot array x, then x equals to x by 255. Okay, there is no y comma 5. X should be capital. Yeah, so now what we will do, we will split into training and testing validation sets. Okay, for that I will write x train comma x test comma y train comma y test equals to train test split. We already discussed what is train test split, x comma y comma test size equals to 0.25 comma random state equals to 42. Okay, so now let's set the random seeds. So for that I will write np dot random dot seed (42), then rn dot seed is again 42, then tf dot random dot set seed 42. Okay, what we will do now, we will do modeling. We will build a ConvetNet model. ConvetNet means CNN model. So for that I will write here like model equals to sequential, okay, then model dot add connet 2D, then filters equals to 128 then kernel size equals to 2,2, then padding will be same, comma activation equals to ReLU layer, then input shape equals to input shape equals to 32, 32, 3. Then here I will write model dot add max pooling 2D, then pool size equals to 2,2. Then I will write model dot add flatten then model dot add dense. Okay, D will be capital here, then 5 and 2, these all are for the layers. Then model dot add activation, that ReLU, then model dot add dense 5, comma activation equals to softmax. Okay, then let me run it. Go on to 2D, D will be capital. Okay, go on to 2D dot is kernel size. Yeah, it's running. So now what I will do using a ln annealer, we will set the batch side, we will set the epochs, and we will do the callbacks or not. Okay, so for that I will write batch size equals to 45, then epochs will be 10, then from keras dot callbacks import reduce LR on plateau. TEAU. Okay, then I will add red LR equals to reduce LR on plateau, then we'll monitor equals to validation score or accuracy, you can say, comma patience equals to 3, comma verbose equals to 1, comma factor equals to 0.1. Okay, so moving forward, what we will do the data augmentation to prevent overfitting. So now let's do the data augmentation. For that I will write here data gen equals to image data generator then here I will write feature wise center equals to false. So what this line will do, this line will do like set input mean to 0 over the data set. Okay, then I will write sample wise center equals to false. Now this set each sample mean to 0. Then I will write here feature wise center equals to false. So what it will do, no, it's feature wise, I will write standard normalization. Standard normalization equals to false. So it divides input by standardization of the dataset. Okay, then sample wise standard normalization equals to false. Then it divide each input by its standardization this time. Then I will write here, let's see a widening equals to false. Applies that ZCA widening, then rotation range and rotation range equals to 10. It will, what it will do, it will randomly rotate images in the range like degrees 0 to 180. Okay, then zoom range equals to 0.1. This is for randomly zooming image. Then width shift range equals to 0.2. Then what it will do, it will randomly shift images horizontally like fraction of total width. Then height shift image range equals to 0.2. It is for randomly shift image vertically like fraction of total height, and this horizontal flip equals to true for randomly flipping images. This is for vertical equals to vertical, no, false. Okay, then data gen dot fit xstring. Some error is there. It is like width shift range 0.2. Okay, so let's debug this error. So let's run this again. Yeah, it's gone. So now what we will do, we will compile the Keras model and see the summary. For that I will write here model dot compile this optimizer. We already know what are the optimizer, equals to Adam LR equals to 0.001. Okay, then loss equals to categorical cross entropy, comma matrix equals to accuracy. Okay, let's run this. First let me give some spaces. Yeah, so here let's see the model summary. So as you can see here, the layer types like con 2D or max pooling 2D. So output shape is 32, 32, 128, and the parameters are given is 1664. Flatten is again the layer, dense is again the layer. Okay, so total parameter use 16, this much, and the trainable parameters are this. Okay, so moving forward, let's do the fitting on the training set and making prediction on the validation set. Okay, so let's write history equals to model dot fit generator datagen dot flow xtrain comma ytrain comma batch size equals to batch size. Okay, comma epochs equals to epochs comma validation data equals to x test comma y test, then comma verbose equals to 1 comma steps per epoch equals to x train dot shape 0 batch size. Okay, so let's run this. So it will take time, like it will run till 10 epochs of 85. Okay, from this we can get the accuracy for the validation. So I hope you understand till here. If you have any question regarding machine learning, deep learning, Python, you can comment, or you can check our course from the description box below. It will take a little bit of time. So after this we will save this model, and from TensorFlow we import. Then we will do some model performance, evaluate model performance. After that we will recreate the exact same model, like including its weight and the optimizer. Then at the last we will visualize our correctly classified flower images predicted one. Okay. So 5 are done, 5 more are remaining. Okay, like 3 more. If you have any problem in like code, in understanding the code, you can comment down below. Or don't forget to check the course from the description box below. Okay, AI/ML courses. The last one is remaining. What we will do, we will save this model into Kaggle only. Okay, so here I will write model dot save to Kaggle working model 12.h5. Okay, this time accuracy scale validation accuracy 6442 0.6442, accuracy is 66. Okay, so now from TensorFlow import keras, then model equals to keras dot models dot load model Kaggle working model 12.h5. Here I will do the save. I will save the model to the disk and load model from the disk. So let me write the code for that and get back to you. So saved model to disk and loaded model from disk. So now let's evaluate the model performance. Okay, for that I will give some space for better visual. So here we will plot plt.plot history of loss. Okay, then plt.plot history validation loss, then plt.tighten, you can say model loss, then plt.ylabel loss, and plt.xlabel epochs, then plt.legend, train, test, plt.show. So as you can see the graph of that, this is a training and this is the testing loss, how much we lost. Okay, so it's quite okay. So now let's see for the accuracy one, plt.plot history dot history accuracy. Okay, then plt dot plot history dot history and validation accuracy. plt dot title then model accuracy, then plt dot y label. Y label should be like accuracy. plt dot x label will be a box. Then plt dot legend. Then I will train comma test. Then plt dot show. So you can see the accuracy. This is the accuracy of the training, and this is for the testing. It's quite okay. So now let's recreate the exact same model, including its weights and the optimizer. Then we will see the summary. Then again we will do the epochs. Okay, model fitting for the better accuracy. Okay, so for recreating the model, I will write here new model equals to tf dot keras dot models dot load model. Kaggle working dot h5. Then new model summary. Okay, now what I will do, I will run again new model dot fit x train comma y train comma epochs comma batch size equals to batch size comma validation data equals to x test comma y test. Okay, model dot fit batch size, new model dot fit x train y train epochs. This time I think we'll get the good accuracy. Okay, after that we can predict. So again this will run till 10. 1 2 3 4 5 6 7 8 9 10. Okay, if you have any doubt till here, you can please comment down below. Okay, if you have any queries related to Python, machine learning, or don't forget to check the course link. It will go till 10. Or if you want this full code, just comment down below for the same. I will provide you the drive link. 5 more left. As you can see here, accuracy is increasing, okay, with the new model. Okay, 2 more left. The accuracy is OP, like 99%. Okay. After this, we will save the model and visualize the prediction on the validation set. Okay. So now let's save the model. Okay, so now we will visualize the prediction on the validation set. That I will write the code and get back to you. Okay, so here now we are doing, we are storing some properly as well as the misclassified indexes. Okay, so here is like the proper classes, that is misclassified classes. Okay, and here we are loading the model predicting. So let me run it. Still 40. Okay, so let's see the correctly classified flower images. Okay, for that I will write warnings dot filter warning. Always. Then warnings dot filter warning, then ignore, then count equals to 0, then figure comma ax equals to plt dot subplots 4,2, then figure set size inches 15,15 for I in range 4, for j in range 2. So let me write that code. Okay, unindent does not match. Okay, spelling is wrong. Okay. Figure. Figure dot. Okay, let me debug the error and get back to you. So as you can see, it's run properly. Okay, see, predicted flower daisy and actual flower is also daisy. Predicted flower sunflower. Okay, the photos are not, high quality. So that's why here you can see the rose is seeing the rose actual. Okay, this rose and dandelion one, then the daisy sunflower. So now what we will do see like some of the flowers which are misclassified. Okay, the same code will be there. Okay, I will write here. Let's run this. So these are some, the actual flower was tulip but predicted rose. So these are some misclassified images.
Imagine a world where machines get smarter with human help. That's the magic of data science. Take ChatGPT for example. It learned from heaps of internet text, but it needed humans to fine-tune and make it reliable. So it's a perfect blend of AI and human wisdom, and that's the power of data science. As companies begin recognizing the pivotal role of data in their operations, the demand for data science expertise witnessed exponential growth across various sectors. Today, data science stands as the cornerstone supporting businesses in diverse areas such as analytics, data mining, natural language processing, machine learning, and artificial intelligence. Consequently, the compensation packages for data scientists have become notably attractive. According to Glassdoor, the average salary of a data scientist is $153,000 in the US, and in India, it's 13 lakhs per annum, serving as a significant incentive for individuals venturing into this domain. However, the journey toward becoming a successful data scientist is far from effortless. It demands a specific skill set that companies actively seek. Finding a suitable job in the field of data science is becoming increasingly difficult. The ideal way to display your skills is through a portfolio of data science and projects. A solid portfolio of projects will illustrate that you can utilize your data science skills in your profile well. Projects like movie recommendation systems, fake news detection, and many more are the best ways to improve your early programming skills. You may have the knowledge, but putting it into use is what keeps you competitive. Here are the 10 data science projects that can increase your portfolio and enable you to acquire a job as a data scientist. That's it. If these are the types of videos you would like to watch, then hit that subscribe button and the bell icon to get notified.
The concept revolves around using machine learning techniques to determine an individual personality. A personal personality has significant impact on both their personal and professional life. Nowadays, many companies are selecting candidates based on their personality traits. Our study aimed to combine ML techniques like SVD, naive-Bayes, and logistic regression to predict a person's personality. Additionally, we utilize the phrase frequency method to forecast their talent. This model or approach enables users to quickly identify their personality traits and technical abilities. To delve deeper into this project, please refer to the link provided in the description box below. So next on the list is time series forecasting. Time series forecasting involves predicting future values by analyzing patterns in historical data. Its applications span various industries including weather prediction, sales projection, stock price forecast. As time series forecasting finds widespread use in diverse fields, it is imperative for every data scientist to possess knowledge of the methods available for its execution. The seasonal SARIMA employs a dual strategy. In its autoregressive component, it leverages weighted previous values, whereas in the moving average component, it assigns weights to the previously estimated time series errors. To delve deeper into this project, please refer to the link provided in the description box below. Next, we have Parkinson's disease prediction. Parkinson's disease prediction is a progressive disorder of the central nervous system that impacts movement and leads to symptoms like tremors and stiffness. It consists of 5 stages and affect over 1 million individuals worldwide annually. In this machine learning project, we aim to develop an SVM, support vector machine, and model using various Python modules such as scikit-learn, numpy, and pandas. We will import the data, extract the features and labels, scale the features, split the dataset, and design the module SVM model and evaluate its accuracy. Ultimately, we will utilize the developed model to assess the presence of Parkinson's disease in an individual. For further details on this project, please refer to the link provided in the description box below. So next we have speech recognition system. Speech recognition system, often known as speech to text, in the capacity of a machine or program to recognize and transform word spoken aloud into readable text. ML, speech recognition, uses algorithms that model speech in the terms of both language and sound. To extract the more essential part of speech such as words and sentences, acoustic modeling is used to identify the phenomena and phonetics in our speech. For this project, we will utilize PyTTSX3. PyTTSX3 is a Python text-to-speech conversion library. Unlike other libraries, it operates offline and is compatible with Python 2 and Python 3. To learn more about this project, check the link in the description box below. So next we have on the list is sentiment analysis. Sentiment analysis, also known as opinion mining, involves the straightforward task of ascertaining the author's emotion or attitudes expressed in a given text. It aims to decipher the underlying intention of the user when they write something. To identify potential personal information, we utilize a range of natural languages processing and text analysis techniques. We aim to detect, extract, and quantify such information from the text, enabling classification and data manipulation. In this project, we will leverage the Amazon customer review dataset from the conducting sentiment analysis. For further insight into this project, please refer to the link provided in the description box below. So next we have on the list is fake news detection. Can you trust everything you encounter on social media? It is a fact that not all news is reliable, right? So how can you identify fake news? Machine learning holds the key. By engaging in this project focused on detecting fake news, you will gain the ability to differentiate between accurate and fabricated information. This machine learning project focuses on discerning between fake and true news. We employ a TF-ID vectorizer from the sklearn library on our dataset. The model is then pre-trained using pre-initialized passive-aggressive classifier. Ultimately, the accuracy and the confusion metrics indicate our model performance. You can find the project link in the description box below for further details. So next we have image classification using CNN. Deep learning is an immensely popular and rapidly growing field in the present times. Numerous projects and problem statements across various domains heavily rely on deep learning. When confronted with a computer vision problem, many of us, including myself, would opt for a conventional neural network as the go-to deep neural network. In this particular project, we will employ CNN convolutional neural network to develop an image processing project and gain insights into its capabilities and the reason behind its widespread popularity. We will dive into each stage of creating our convolutional model and embark on our first remarkable project. For this project, we will utilize the CIFAR10 dataset, which is commonly employed for image classification tasks. To acquire further information about this project, please refer to the link provided in the description box below. At number 2, we have face recognition system. The remarkable technological advancement never cease to astound people, as they continuously introduce incredible inventions that enhance convenience and comfort in our lives. Among these innovations, face recognition has proven to be the least intrusive and fastest form of biometric verification over the years. This project will utilize the OpenCV face recognition libraries to develop a face detection system. OpenCV offers a powerful set of tools, libraries, and hardwares for real-time computer vision application. With OpenCV, we can create awe-inspiring projects in real time. To gain insight into this process to building a face recognition system, please refer to the link provided in the description box below. And but not at the least, we have movie recommendation system. In today's world, the most people rely on technology to stream movies and TV shows. However, deciding what to watch next can sometimes be disheartening. Thankfully, recommendations based on a viewer viewing history and preferences have become complex. These recommendations are powered by machine learning and can be enjoyable and accessible project for beginners. Aspiring programmers can practice coding in either Python or R language using data from the Movie Lens dataset, which more than 6,000 users generated. If you are interested in learning how to create personalized movie recommendation system for yourself or your loved ones, you can find the project links in the description box below. So these were the 10 data science projects you could start your career in data science.
So let's start with the data science interview questions and answers. And the number one problem we would be facing is real world problem solving. And the question one is handling missing data in predictive modeling. So imagine you have given a data set where 30% of the data for a key predictive variable is missing. This variable is crucial for a predictive model. How would you handle this situation to ensure the integrity and performance of your model? And please describe your approach step by step. So starting with the answer, you can start with handling missing data set is a common challenge in data science, and it's important to address it carefully to maintain the accuracy of your model. And here's how you could approach this situation. The number one point could be identify the missing data. So first you need to understand where the missing values are in your data set. You can do this by using a simple code in Python with libraries like Pandas. For example, you can use the data.isNull.sum function that will show you the count of missing values in each column. Then you can analyze the pattern, determine if there's a pattern to the missing data. Is it random or is it missing for a reason? This can affect your approach. If the data is missing at random, the methods you use might be different than if the data is missing systematically. So choosing a method for imputation. Let's see the next method, that is choosing a method for imputation. So if the missing data is numeric, you might replace missing values with the mean or median of that column. This is simple and effective, but can be used primarily when the data is missing completely at random. Then comes model-based imputation. Sometimes you can use other variables in the data to predict missing values using a regression model. This can be more accurate, but is also more complex. Then we'll use the k-nearest neighbors KN algorithm. But before that, we have a code snippet here that could be used for the implementation of imputation. You could use Python or R. And now moving on, we'll see the k-nearest neighbors algorithm. So this method predicts the missing values based on how closely related the data points are to each other. So after imputation, it's crucial to check how your changes have affected the overall dataset and model performance. Sometimes filling in too many missing values can introduce bias. And then we have visualization. To help understand before and after the imputation, you could visualize the distribution of the variable using histograms or box plots. This helps in seeing how the imputation has changed the statistical properties of the data. And by following these steps, you can handle missing data thoughtfully and maintain the integrity of your predictive model. Now moving to the question number 2, that is based on evaluating model overfitting. So the question is, you have developed a predictive model, but you suspect it might be overfitting the training data. How would you test and address the issue? Please explain your steps and the techniques you would use. So you could start the answer by explaining what is overfitting. So overfitting is a common problem where model performs well on training data but poorly on unseen data, indicating it's too closely fitted to the training data's specific details and noise. So now we'll see a step-by-step guide on how to address this. The number one step is cross-validation. So one effective way to test for overfitting is by using cross-validation technique. Cross-validation involves splitting your training data into multiple smaller sets, that is faults, and then training your model on some of these sets and validating it on the others. So this helps you understand if the model's good performance is consistent across different subsets of data. For example, in Python, you can use the cross_value_score function from sklearn.model_selection. So this is the code, and this is the code snippet of Python that you can use for the cross-validation. And here we are importing from sklearn, that is the module, and we are importing cross_val_score. And here we have used the cross_val_score function, and then we have printed the average cross-validation score. And the next step we will do is running cross-validation model. So this is your predictive model that you have already built using scikit-learn. And here's the X train. These are the X input features of your training data, and Y train, these are the output labels of training data. So we are running cross-validation model here. This is your predictive model that you have already built using scikit-learn. So X-train here, that means these are the input features of your training data. And Y-train here means these are the output labels of training data. And CV equal to 5. This parameter tells the function to split the data into 5 parts, that is false, and the model is trained on 4 of these parts, and the remaining part is used for testing. So this process rotates until each part has been used for testing once. And the printing results, that is score.mean. So this calculates the average of the scores obtained from each cross validation fold. This average score gives you an idea of how well your model is likely to perform on unseen data. A consistent score across different folds suggests your model is generalizing well rather than overfitting to the training data. So now moving to the next point, that is training versus validation error. So plot the training and validation errors as a function of training epochs or complexity of the model. A model that overfits will show a low error on training data and a high error on validation data as it trains further. Then we have pruning the model. If you confirm that the model is overfitting, consider simplifying it. This might mean reducing the number of parameters by selecting fewer features, using regularization techniques like lasso or ridge, or choosing a less complex model. After this step, we will move to regularization technique step. So these techniques add a penalty to the loss function used to train the model, which can discourage complex models that overfit. Then we have common methods that include L1, that is lasso, and L2, ridge regularization. And here's how you can add L2 regularization in Python. So this is the code snippet here. And what we have done here is we are creating the ridge model and we have applied alpha equal to 1.0. So this parameter controls the strength of the regularization. A higher alpha value increases the regularization effect, which helps reduce model complexity and combat overfitting. The alpha value can be tuned to find the optimal balance between bias and variance. And now coming for the fitting the model. So model.fit, and in that we have X-train and Y-train that trains the ridge model on the training data. It adjusts the weight of the feature in X-train to predict the Y-train while also considering the regularization term. This helps prevent the model from fitting too closely to the noisy aspects of the training data. And then we are re-evaluating the model. After making adjustments, it's important to re-evaluate the model again using the same cross-validation technique to see if the issue of overfitting has improved. And then we have visualization. To help illustrate overfitting, you could create a plot showing the training and validation errors over the number of epochs or model complexity. So by using these techniques, you can identify if a model is overfitting and take steps to correct it, ensuring it performs well not only on the training data but also on new unseen data. So now moving to the next question, that is question number 3, and it is based on real-time data stream processing. And the question is, you are tasked with building a model to predict stock prices in real time. The data comes in every second and you need to update your predictions accordingly. Describe how you would set up your system to handle this type of data effectively, and what tools and techniques would you use and why. So you could start answering this question with handling real-time data. So handling real-time data, especially for something as volatile and fast-paced as stock prices, requires a robust system that can process and analyze data quickly and accurately. So here's how you could approach this. We will set up such a system and we'll have some steps. So starting with the steps. So the first step is choosing the right tools. The right tool would be Apache Kafka. So this is a popular tool for handling real-time data that streams because it allows you to publish and subscribe to streams of records, that is data. And it can handle high throughput with low latency. Kafka acts as a buffer and manages the flow of data, ensuring that your system doesn't get overwhelmed. And you can also use Apache Spark. Especially Spark streaming is excellent for processing the data. It can process data in real time and perform complex operations like windowing, grouping data into chunks of a specified time period, and aggregating, that is summarizing data. So you can modify it and perform the predicting of stock prices. And then the step is data processing pipeline. And the first step comes here is ingestion. Data first enters the system, typically through Kafka, which collects data sent from the stock market. And then we do the processing. So Spark streaming takes over here. Here you can apply transformations and run your predictive models on the data. For example, you might calculate moving averages or other indicators that feed into your stock price prediction model. And then comes the output. Finally, the predictions are outputted. This could be to a dashboard for traders, an automated trading system, or even stored for further analysis. And then we develop the model. Now comes the model development. You would likely use a machine learning model that can update quickly and incorporate new data as it arrives. Models such as ARIMA for time series forecasting or more complex machine learning models like recurrent neural networks (RNNs) can be suitable. The model should be retrained or fine-tuned periodically with new data to ensure it stays accurate. Now we'll come to scalability and reliability. So ensure your system can scale as data volume increases. This might mean adding more servers or optimizing your data processing code. Implement monitoring to catch any issues early, like delays in data processing or model performance drops. And now we'll see the step that is visualization and monitoring. Consider setting up a real-time dashboard that shows key metrics like prediction accuracy and processing time. This helps in quickly spotting when something goes wrong. By setting up your system with these tools and strategies, you can effectively handle the challenge of predicting stock prices in real time. So now we'll move to the next question, that is question number 4, and this will be based on scalable data analytics. So we have covered 2 questions that were a bit code-based questions, and now we'll see other questions that would be based on scalable data analytics, or they might be on different areas. And with the 13th question, we will start again with the coding ones. So moving with the question 4, that is based on scalable data analytics. And the question is, given a scenario where your organization suddenly needs to scale its data analysis capabilities due to an influx of data that would be 10 times the normal volume, how would you handle this situation to ensure your data analytics processes remain efficient and accurate? What technologies would you consider and what steps would you take? So you can start answering this question with, handling a sudden increase in data volume requires a strategic approach to scaling your analytics infrastructure without compromising on efficiency or accuracy. So we'll see some steps from that you could effectively manage this scenario. That you would start answering the interviewer that we can start by evaluating the current infrastructure's ability to handle increased loads. This includes assessing your databases, servers, and analytical tools to identify potential bottlenecks or limitations. Then you could move to next step, that would be choosing scalable technologies. To manage the increased data volume, consider leveraging cloud-based solutions such as Amazon Web Services, Google Cloud Platform, or Microsoft Azure. These platforms offer scalable resources which can be adjusted accordingly to the data load, ensuring you only pay for what you use. Integrate big data technologies like Apache Hadoop for distributed storage and Apache Spark for fast data processing. These tools are designed to handle massive volumes of data efficiently and can scale up to meet standard increased demands. Now we'll move to the next step, that would be optimizing data processing. So implement data partitioning and indexing strategies to improve the efficiency of data queries. This will help in managing large data sets by breaking them into smaller, manageable chunks and speeding up search operations. And use real-time data processing frameworks like Apache Kafka or Apache Flink, which can handle high throughput and provide timely insights from large data streams. And the next step would be automation and monitoring. Automate routine data processing tasks to reduce the manual effort and speed up the analysis. This can be done through scripting or using workflow automation tools. Set up comprehensive monitoring systems to track the performance of your data processes. Tools like Prometheus for system monitoring and Grafana for analytics and monitoring dashboards are useful here. They help ensure that the system is running smoothly and alert you to potential issues before they become critical. And the next step will be regular evaluation and scaling. Continuously evaluate the performance of your analytics infrastructure. As your data grows, keep adjusting and scaling your resources to maintain optimal performance. Plan for periodic reviews of your technology stack and infrastructure to ensure they remain aligned with your data needs and organizational goals. By following these steps, you can ensure that your data analytics processes are prepared to handle sudden surges in data volume effectively, maintaining the integrity and speed of insights. So this was all for the question 4. Now moving to the question 5, and this is based on integrating machine learning models into production. And the question is, you have developed a machine learning model that performs well in testing environment. Now you need to integrate it into your production environment where it will be used in real-time applications. What steps would you take to ensure the successful deployment and operations of the model in production? So we'll start answering this by successfully deploying a machine learning model into production involves several critical steps to ensure it performs as well in real-time operations as it does in testing. So you would have a clear pathway to make the interviewer understand. We will start with the pathway with the first step, that would be model validation. So before moving anything into production, revalidate your model's performance using a separate validation dataset. This helps confirm that the model generalizes well to new, unseen data. The next step will be preparing the production environment. Ensure that the production environment is ready to handle the model. This includes setting up the necessary hardware and software, ensuring that it can handle the expected load, and that all dependencies are correctly installed and configured. Then the next step comes, that is model wrapping. Wrap your model in an API, that is application programming interface, making it accessible to other parts of your software infrastructure. Frameworks like Flask for Python can be used to create a simple web server that listens for data inputs and provides model outputs. Then comes the next step, that is deployment strategies. Consider using containerization tools like Docker, which can help encapsulate your model and its environment, ensuring that it works uniformly across different development and production settings. And then we'll use deployment strategies like blue-green deployment or canary releases to minimize downtime and reduce the risk of introducing a faulty model into production. And then comes the next step, that is monitoring and logging. Implement logging and monitoring to track the model's performance and health in real time. Tools like Prometheus for monitoring and ELK, Elasticsearch, Logstash, Kibana for logging help in quickly identifying and diagnosing issues in production. And then comes the next step, that is performance tuning. Monitor the model's performance over time. If the model's performance degrades, or if new data shows different patterns, you may need to retrain or fine-tune the model to maintain accuracy. And after this step, there's a step for feedback loop. Set a feedback loop where predictions and outcomes can be compared. This feedback is crucial for continuously improving the model and catching any drift in data or changes in external conditions that affect the model. And after this comes a last step, that is legal and compliance checks. Ensure all the data used by the model in production complies with privacy laws and regulations. This is crucial for maintaining trust and legality, especially when handling sensitive information. So by carefully planning and executing these steps, you can smoothly transition your machine learning model from a testing environment to a fully functional component of a production system. So this was all about the question number 5. Now moving to the question number 6, that would be based on data-driven decision making. And the question is, your company wants to shift towards more data-driven decision making. You have been tasked with developing a strategy to implement this. What steps would you take to ensure that the data at all levels of the organization is utilized effectively to make informed decisions? And what challenges might you face and how would you address them? So you can start answering this by implementing a data-driven decision-making strategy that will require a comprehensive approach to ensure that reliable data is accessible and effectively used across all levels of the organization. And now we can develop and deploy this strategy, and similarly you could tell this strategy to the interviewer. So the number 1 step will be assessing current data infrastructure. Start by evaluating the existing data infrastructure to understand what data is available, how it is stored, and how it is currently used. This assessment will help identify gaps in data collection, storage, and access that need to be addressed. Now we'll move to the next step, that is developing a data governance framework. Implement a data governance framework that defines who can access data, how it can be used, and who is responsible for maintaining its quality. This framework ensures data integrity and security, which are critical for making reliable decisions. Now we'll move to the next step, that is training and empowerment. So train employees at all levels on the importance of data-driven decision making and provide them with the tools and knowledge necessary to analyze and interpret data. This might include training sessions, workshops, and ongoing support to ensure everyone can use data effectively. Now moving to the next step, that is implementing analytical tools. So deploy user-friendly analytical tools that can integrate seamlessly into the daily workflows of employees. Tools like Tableau, Microsoft Power BI, or even advanced Excel techniques can provide powerful data analysis capabilities without requiring extensive technical knowledge. After this, we'll move to the step that would be creating a centralized data platform. Develop a centralized data platform where all organizational data can be accessed and analyzed. This platform should be scalable and secure, providing a single source of truth for the organization. And then we have the promoting a data-driven culture. So foster a culture that values data-driven decision making. Encourage experimentation and learning from data-driven initiatives. Celebrate successes and learn from failures to continually improve the use of data-driven in decision making. And there would be some challenges and solutions for that. So one major challenge we know here is resistance to change, as some employees may prefer traditional decision-making methods. So address this by demonstrating the tangible benefits of data-driven decisions through pilot projects and success stories. So data silos can also hinder effective data use, promote cross-department collaboration, and integrate disparate data sources to overcome this challenge. After that, you can monitor and do continuous improvement. So by systematically implementing these steps, you can transform your organization into one that leverages data at all levels to make informed and effective decisions. And after answering in these steps, you could make the interviewer have a truth and a faith in you that you could make these models. Now move to the next question, that is question number 7, and that is based on handling large data set. And the question is, your project involves analyzing extremely large data sets, potentially exceeding terabytes in size. What strategies would you use to manage and analyze such large data sets effectively? Describe the tools and techniques you might employ. And you could start this with answering that working with large data sets, especially those in terabyte range, presents unique challenges in terms of storage, processing, and analysis. So we'll have a structured approach to handle these challenges effectively. We'll start with the data storage, that would be use distributed file systems. Consider using a distributed file systems like Hadoop Distributed File System, HDFS, or Amazon S3. These systems are designed to store vast amounts of data across many servers, offering high availability and fault tolerance. And then comes the next step, that is data processing. Leverage big data processing frameworks. Tools like Apache Spark are ideal for processing large data sets because they handle distributed computing effectively. Spark can perform data processing tasks much faster than traditional disk-based processing due to its in-memory computing capabilities. And next, we could start with efficient data sampling. So there are many sampling techniques that we can use. So when the data set is too large to handle, even with powerful tools, consider using data sampling techniques to reduce the size to a manageable level without losing significant insights. Ensure that the sample represents the whole data set accurately. And then comes optimization of data queries. Indexing and partitioning. Optimize your data queries by implementing indexing and partitioning. This can drastically reduce the time it takes to perform queries by limiting the amounts of data scanned. And then we can do scalable analytics. And then we'll move to the next step, that is scalable analytics. And in that, we could start with the parallel computing. Use parallel computing capabilities of frameworks like Spark or Dask to analyze data across multiple nodes. This helps in scaling up your analytics operations to handle large data sets effectively. And now we'll move to the cloud-based analytical tools. So consider using cloud services like Google BigQuery or AWS Redshift, which are designed to handle massive data sets and complex analytics with ease. And after this step, we'll move to data cleaning and pre-processing. Here we will automate pre-processing tasks. We'll use automated tools to clean and pre-process data. This includes handling missing values, normalizing data, and removing duplicates, which can be particularly challenging with large data set. And after this step, we'll move to the step that will visualize large data set. So we'll use specialized tools. That tools could be Tableau or Power BI that can handle large data set by aggregating data and using efficient back-end technologies. For more detailed exploration, tools like Plotly or Bouquet can be used as they offer capabilities to interactively visualize large volumes of data. And after that, there would be step for regular maintenance and updates. That could be continuously monitoring the data quality. As new data comes in, you can continuously monitor its quality. And after this step, you could integrate all these strategies and tools into your workflow, and you can effectively manage and extract valuable insights from extremely large data sets, thereby supporting robust data-driven decision making. And you could answer the whole strategy to the interviewer. Now move to the question number 8, that is based on optimizing machine learning models. And the question is, during model development, you have noticed that your machine learning model is underperforming. What steps would you take to diagnose the problem and optimize the model's performance? What techniques and tools would you use? So you can answer this by starting with the optimizing. And optimizing a machine learning model that is underperforming involves several steps to diagnose and improve its accuracy and efficiency. And here we will have structured approach to tackle this issue. And you could start this with the number 1 step, that is diagnosing the problem. Evaluate model metrics. Start by thoroughly evaluating the performance metrics of a model. For classification task, For classification task, look at accuracy, precision, recall, and the F1 score. For regression task, consider R squared, mean squared error, that is MSE, and mean absolute error, that is ME. And then you can move to the next step. That is, use plots like ROC curves for classification models and residual plots for regression to visually assess where the model is going wrong. After that, we'll move to the next step, that is data quality and quantity check. Inspect the data. That is, sometimes the quality and quantity of data can be the root cause of poor model performance. Ensure the data is clean, well pre-processed, and sufficient. Look for issues like missing values, outliers, or imbalanced classes. And after this, we'll move to the feature engineering step, that would be experiment with creating new features or transforming existing ones to provide better predictive power. And then we have the next step, that is model tuning and configuration. After feature engineering, we'll move to the next step, that is model tuning and configuration. So hyperparameter tuning. Use techniques like grid search or random search to find the optimal settings for your model's parameters. Tools like scikit-learn's grid search CV or randomized search CV can automate this process. And there's a cross-validation that would implement cross-validation to ensure that the model's performance is consistent across different subsets of the dataset. And then we have the next step, that is trying different models. So experiment with algorithms here. If initial models are underperforming, try different algorithms that might be better suited for the problem. For instance, if you started with linear regression and it's not performing well, consider more complex models like random forest or gradient boosting machines. And after this, we have ensemble methods that we can use techniques like bagging, boosting, or stacking to combine the predictions of multiple models to improve overall performance. After this step, we have feature selection that includes reduce dimensionality. Use techniques like principal component analysis, that is PCA, to reduce the number of features, which might help in improving model performance by removing noise and redundancy. And then we have select important features. So use model-based technique to identify and keep only the most important features that impact the outcome. And then comes the last step, that is regular updates and retraining. So here you can monitor and update, that could be continuously monitoring the model's performance over time. As new data becomes available, update and retrain the model to adapt to any changes in underlying patterns. And after that, you could have a consultation and collaboration work with the other teams. And by methodically addressing each of these areas, you can diagnose why your machine learning model is underperforming and can take steps to optimize its accuracy and efficiency. So this was all about question number 8. So let's start with the question number 9, and this is based on handling unstructured data. So the question is, you are given a large amount of unstructured data, including text, images, and videos. What strategies would you use to manage and analyze this type of data effectively? Describe the tools and techniques you might employ. So you can start answering this question by describing that dealing with unstructured data can be challenging due to its lack of predefined format or structure. However, with the right strategies and tools, you can effectively manage and analyze it to extract valuable insights, and there will be an approach how you can do that. So we will discuss the approach here, and starting with the steps. So the number 1 step will be data categorization and organization. So the number 1 step in this step will be sorting and tagging. We will begin by categorizing the data into types, that will be text, images, or videos. Use tagging to add metadata, which helps in organizing the data and makes it easier to access and analyze later. Then, and after that, particularly for text data, we'll use natural language processing, NLP. We will employ NLP techniques to extract useful information from text. Tools like NLTK, Spacey, or even more advanced models like BERT can help you perform tasks such as sentiment analysis, entity recognition, and topic modeling. After that, we will do text indexing. We can use Elasticsearch or Apache Solr to index large volumes of text. These tools provide powerful search capabilities and can handle complex queries efficiently. And after that, we'll move to image data. And to structure image data, we'll use image processing. We'll use libraries like OpenCV for basic image processing tasks such as filtering and transformations. For more advanced image analysis, consider deep learning models using frameworks like TensorFlow or PyTorch. And then we'll feature extraction. Apply techniques to extract features from images such as edges, textures, or key points, which can be used for further analysis or machine learning. And then we'll come to video data. And here we'll do video processing, and we'll use the tools like FMPEG that can be used for basic video processing tasks such as format conversion or extracting frames. For analyzing video content, look at machine learning models that can classify or recognize activities in the video. And after this, we'll move to temporal analysis. For videos, temporal components are important. Techniques like sequence modeling or recurrent neural networks, RNNs, can be useful to analyze sequences of frames for activities or events. And then we'll move to data storage and management. Here we'll use the given volume and complexity of unstructured data and use big data platforms like Hadoop or cloud services like AWS S3 for storage. These platforms can scale up to handle large data sizes and provide the necessary infrastructure to store and retrieve unstructured data efficiently. And then we have visualization and reporting. Custom dashboards that we'll create here. We will develop custom dashboards using tools like Tableau or Power BI, which can integrate different data types and provide a unified view of the analyzed data. And after that, we will do data summarization. Tools that provide summarization capabilities can help in considering large volumes of unstructured data into more manageable and interpretable forms. And after that, we'll leverage these strategies and tools and can effectively manage, analyze, and derive insights from unstructured data, which can be crucial for making informed decisions in various applications. And this is the path that you can explore and explain to the interviewer if this question has been asked. Now moving to the question number 10, and that will be based on scaling AI solutions in enterprise. And the question is, your company wants to scale its AI operations from a few initial pilot projects to enterprise-wide implementation. What are the key considerations and steps you would take to ensure the successful scaling of AI solutions across the organization? And what challenges might you face and how would you address them? So you can start answering this question with the scaling AI solutions. You could answer him that scaling AI solutions across an enterprise requires careful planning and strategic implementation to ensure success and alignment with business objectives. And there should be a strategic approach to implement this. So starting with the approach, and the number one step will be strategic alignment. So identify business objectives. Start by identifying the business objectives that the AI solutions are intended to support. This ensures that the AI initiatives are aligned with the company's strategic goals and can demonstrate clear business value. And then comes the stakeholder engagement. So engage stakeholders from various departments early in the process to gather input and build support. This helps in understanding diverse needs and ensures broader acceptance of the AI solutions. And after that comes the infrastructure and technology. So there's an option that is assess and upgrade infrastructure. Evaluate whether your current IT infrastructure can support the expanded use of AI. You might need to upgrade hardware, invest in cloud solutions, or adopt technologies that facilitate AI processing and data handling. And after that, we have standardization of tools. Standardize the tools and platforms used for AI development to ensure compatibility and ease of maintenance across the organizations. And after that, we'll move to data management. So robust data governance, that is to implement a strong data governance framework to manage enterprise data effectively. This includes policies for data quality, security, and compliance, especially important when scaling AI solutions that rely on vast amounts of data. And after that, we will come to data accessibility. So ensure that data is accessible across the organization, but also secure against unauthorized access. This involves setting up secure data lakes or warehouses that centralize data while allowing controlled access. And then we come to the next step, that is talent and training. So build AI competency, that is develop in-house AI expertise through training programs and hiring. So this builds the necessary skills within the organization to develop, manage, and scale AI solutions. And after that, you can also perform cross-functional AI teams. That could be forming cross-functional teams that include data scientists, IT professionals, and domain experts. So this fosters collaboration and ensures that AI solutions are developed with a comprehensive understanding. And after forming these collaborative teams, we'll move to scalable deployment models. So pilot test and phased rollout. Before a full-scale rollout, conduct pilot tests to gauge the AI solution effectiveness and integration capabilities. Based on feedback, adjust, and then gradually deploy the solutions across the organization. And then we have modular and flexible design. So design AI systems to be modular and scalable, allowing for adjustments and expansions as needs. And then we'll monitor and do the continuous improvement. So there will be performance metrics that would establish metrics to regularly assess the performance of AI systems. We will monitor these systems to ensure they met expected outcomes and adapt as necessary. And after that, we have next step, that is addressing challenges. So there could be cultural resistance, that There could be employees that would be resisting to the changes, but we have to address this through continuous education and by showcasing successful AI use cases within the organizations. And by carefully considering these aspects and methodically implementing steps, you can successfully scale AI solutions across your enterprise, driving significant business value and innovation. And that's all for question number 10. Now we'll move to question number 11, and that is based on ethical considerations in data science. So the question is, in your data science projects, how do you ensure that ethical considerations are addressed? Describe the steps you take to identify and mitigate ethical risk in your projects. What frameworks or guidelines do you follow? So you could start answering this question with ethical considerations, that they're crucial in data science to ensure that the solutions and analyses do not advertently cause harm or bias. Here's how you can ensure that. So there are some steps and we will discuss those steps, starting with the number 1, that is educate on ethical standards. So stay informed about the ethical standards in data science, such as fairness, accountability, transparency, and privacy. Organizations like the Data Science Association and the ACM have codes of ethics that we refer to as guidelines. And then we have ethical risk assessment. Identify potential ethical issues. That would be at the beginning of each project, conduct a thorough assessment to identify any potential ethical risk, such as biases in data or impact on vulnerable groups. This involves reviewing the source of data, the methodologies used for data collection, and the intended use of the data analytics results. And then we have stakeholder analysis. Engage with stakeholders to understand the diverse perspectives and potential impact of the project. This helps in identifying ethical issues that may not be apparent from a purely technical standpoint. And then we'll move to mitigation strategies. Implementing bias mitigation techniques, we will use statistical and machine learning techniques to detect and mitigate biases in data. This might involve techniques like resampling, reweighing, or using algorithms designed to be fair. And then we have privacy preserving methods. Employ methods such as data anonymization, encryption, or differential privacy to protect individual privacy when analyzing sensitive data. Then we have other methods, that is transparency and explainability. There we have model explainability, and after that coming to documentation and reporting. So we have to maintain thorough documentation of data sources, model decisions, and methodologies. And then we have continuous monitoring and feedback. There you have to monitor outcomes and the feedback mechanisms should be applied. And then we have the panels, that is collaboration and advisory panels. There we have ethical review boards. So for complex projects, setting up or consulting with an ethical review board can provide oversight and diverse perspectives on the ethical implications of project methodologies. So by proactively addressing ethical considerations through these steps, you can ensure that your data science projects uphold high ethical standards and positively contribute to society while minimizing harm. So this was all about question 11. Now moving to question number 12, that is based on time series forecasting for business decisions. So the question number 12 is, you are tasked with forecasting monthly sales for a retail company using time series data from the past 5 years. What steps would you take to prepare and analyze this data to make accurate forecast? What specific tools or techniques would you use and why? So we can start answering this by time series forecasting. And we could address them that it's a powerful tool for predicting future events based on past data, especially in business context like retail sales. So we will have a structured approach here, and we'll start with data collection and cleaning. First, we will gather data and ensure that you have collected all relevant data, including monthly sale figures from the past 5 years, and also considering including external factors that might affect sales, such as economic indicators, holidays, and promotional activities. And then we'll proceed to clean data. We'll check for and handle any inconsistencies or missing values. And then we have data visualization. Here we will plot the data. We'll use plotting libraries like matplotlib or Seaborn in Python to visualize the data. This will help in identifying patterns, trends, and seasonality. And then we have decomposition of data. So there's a seasonal decomposition, and we'll use statistical techniques to decompose the data into trend, seasonally, and residuals. So this can be accomplished with tools like the seasonal decompose function from the stats models library in Python. And we'll understand these components separately and can improve the accuracy of our forecast. And then the next step is model selection and forecasting. So there are two models, that is ARIMA and SARIMA models. So we have to choose appropriate forecasting models based on data's characteristics. For instance, ARIMA, that is autoregressive integrated moving average. It is effective for non-season data, while SARIMA, that is seasonal ARIMA, that is suitable for data with seasonal patterns. And after choosing the model, we'll move to cross-validation. We'll implement time series specific cross-validation techniques like time-based splitting to evaluate model performance. And this will ensure your model generalizes well on unseen data. And then we have model fitting and diagnostics. We will fit the model, that is by using the Cynimax class from stat models that will fit your model to the data. And then we will carefully select parameters based on AIC, that is Archaic Information Criterion, that scores or thorough grid research technique. And then we can do the diagnostics and forecast and validation. And after forecast validation, we'll move to iterative improvement. So there's a feedback loop that should be mandatory, and there should be a regular update for the model with new sales data and refining the model as needed. So this continuous improvement cycle helps adapt to changing patterns in sales data. And by following these steps and using these tools, you can create robust forecasts that help the retail company plan better and make informed decisions. So this was all about question number 12. Now moving to question number 13, that is based on customer segmentation using machine learning. So the question is, you are given a data set containing demographic and purchasing behavior data for a group of customers. Your task is to segment these customers into distinct groups based on similarities in their purchasing behavior and demographics. So what steps would you take to perform this segmentation, and can you provide a sample Python code snippet to illustrate the initial stages of data handling and model application? So we can start this by explaining customer segmentation, that it's a powerful approach to tailor marketing strategies and improve customer service by identifying distinct groups based on their behavior and characteristics. And here also we have a detailed approach for this task. So we'll start with number one step, that would be data exploration and pre-processing. So there will be initial exploration, that is beginning by examining the data set to understand the features available such as age, income, purchase frequency, etc. Then we'll look for missing values or anomalies and decide how to handle them. That could be using imputation. And then we'll move to feature engineering. We will create new features that might be useful for segmentation, such as customer lifetime value or average transaction amount. We'll also use normalization, that is normalize the data to ensure that one feature doesn't disproportionately influence the model due to its scale. We'll use standard scaling or min-max scaling as appropriate. So then we'll come to the next step, that is choosing the segmentation technique. And here we have k-means clustering. So this is a popular method for customer segmentation. Here we will decide on the number of clusters by using techniques like the elbow method or silhouette analysis to determine the optimal cluster count. And then we have model implementation. And in that we will use data preparation, and we'll prepare the data by selecting the relevant features and applying any final transformations. And then we have model fitting. We'll fit the k-means clustering model to the data and evaluate and interpret analyzing clusters. And after analyzing clusters, we'll move to the next step, that is strategic insights. We'll provide actionable insights based on cluster characteristics such as targeted marketing strategies for each segment. And then we have iterative refinement, that is feedback incorporation, and we'll use business feedback to refine the segmentation. If additional data becomes available, incorporate it to enhance the model. And now we'll see the sample Python code. So for this, first we'll import the libraries and modules. As you can see on the screen, we have imported Pandas, random forest classifier, train test split, standard scaler, classification report. And after that, we'll load the data. And for that, we have used the Pandas to read the data, that is read_ssv. And after that, we are processing the data, that is data pre-processing. We are handling missing values and using the forward fill or FIL to fill missing values in the data set. And then we are featuring scaling, that is normalizing the selected features, that is feature 1, feature 2 and feature 3 using standard scaler. And then we'll move to the next step, that is data splitting. We'll split the data set into training and testing sets. So that test size equal to 0.2 parameters specifies that 20% of the data will be used for testing. And then we'll train the model. We'll initialize and train a random forest classifier with 100 trees and a random state for reproducibility. And then we'll evaluate the model. We'll make predictions on the test set, that is x_test, using the trained model, and print a classification report showing precision, recall, F1 score and support for each class. So this code demonstrates the process of loading, pre-processing, training, and evaluating a machine learning model, that is random forest classifier, for predicting equipment failures in a manufacturing plant. The use of techniques such as data pre-processing and splitting along with the random forest classifier highlights a standard flow for building predictive maintenance models. So this was all about the question number 13. So now moving to the question number 14, that is based on predictive customer churn. And the question is, you are tasked with developing a model to predict which customers are likely to churn from a subscription service. So what steps will you take to build this model, and can you provide a sample Python code to illustrate the data preparation and model training process? So we'll start answering this question about depicting what is predicting customer churn. So predicting customer churn is crucial for businesses to implement retention strategies proactively, and we'll have a detailed approach for building a predictive model for this purpose, starting with data collection and exploration. And in this, we will collect data, and after that, we will perform the exploratory data analysis, that is EDA. We'll perform an initial analysis to understand patterns and trends. And then we have feature engineering. We will create new features and derive new features that might influence churn, such as change in usage pattern or service upgrades. And then we'll handle the missing values if we found any. And then we'll encode categorical variables. We'll use techniques like one-hot encoding or label encoding for categorical variables. And then we have scale features to normalize or standardize numerical features to ensure they contribute equally to the model's performance. And then we'll select the model, that is, we'll choose the appropriate model and start with for the knowing handling binary classification task. That could be with logistic regression, random forest, or gradient boosting machines. And after selecting the model, we'll train the model and evaluate it. So fit your model on the training data, and after that evaluate the model using appropriate metrics like accuracy, precision, recall, F1 score, and ROC to gauge its performance. And then we'll optimize the model using hyperparameter tuning. We'll optimize the model parameter using grid search or random search to improve performance. And then we have feature importance, that is, analyze and rank features by their importance in predicting churn to refine the model further. And then the last step is deployment and monitoring. We'll deploy the model. Once validated, deploy the model into a production environment where it can predict real-time churn. So after deploying the model, regularly monitor the model to ensure it remains effective over time as new data comes in. So now we'll see the sample Python code for this example. So starting with the importing of libraries, we will import Pandas, NumPy, scikit-learn, sklearn, TensorFlow, and the TensorFlow keras and callbacks. And after importing the modules, we'll start with data loading. We'll load the dataset from a CSV file named equipment_data.csv, and that too with the Pandas data frame. And after that, we'll do the data pre-processing. We'll handle missing values, and for that, we'll use forward fill to fill missing values in the dataset. And then we have feature scaling that will normalize the selected features, that is feature 1, feature 2, feature 3 using standard scaler. And after that, we'll use the data splitting. We'll split the dataset into training and testing sets, and the test size will be equal to 0.2. And this parameter specifies that 20% of the data will be used for testing. And after that, we'll start with building the model. First, we'll see sequential model that initializes a sequential model technique. And then we have dense layers that adds 2 dense layers with 64 units and ReLU activation function. Then we have dropout layers that adds 2 dropout layers with a dropout rate of 0.5 to reduce overfitting. After that, we'll do the model compilation. We'll compile the model using the Adam optimizer and binary cross entropy loss function for binary classification. And there will be an early stopping that will define an early stopping callback to stop training when the validation loss metric has stopped improving after 3 epochs. And after training the model, we will evaluate the model, and evaluating the model on the test data and print the loss and accuracy metrics. So this code demonstrates the process of loading, pre-processing, building, compiling, training, and evaluating a deep learning model using TensorFlow and keras for predicting equipment failures in a manufacturing plant. So the use of techniques such as data pre-processing, dropout, regularization, and early stopping helps in building a robust deep learning model for predictive maintenance. So that's all with question number 14. Now I'll start with question number 15, that is based on deep learning and NLP. And your question is, you are tasked with developing a sentiment analysis model using deep learning to understand customer opinions from reviews. So what steps would you take to build this model, and can you provide a sample Python code snippet to illustrate how you would pre-process data and train a simple deep learning model? So we'll start answering this with sentiment analysis. That sentiment analysis using deep learning allows businesses to gauge customer sentiment from text data like reviews or comments effectively. And we'll have a detailed approach for building a sentiment analysis model. We'll start with data collection and cleaning. We will collect the data, gather a substantial data set of text reviews and their associated sentiments, typically labeled as positive, negative, or neutral. And then we will clean the data, pre-process the data by removing noise such as HTML tags, special characters, and stop words. And we'll normalize the text by converting it to lowercase. And then we have text pre-processing. We'll convert text into tokens, words, or phrases. And then we have vectorization that transforms tokens into numerical format using techniques like word embeddings or TF-IDF, that is term frequency in words document frequency. And then we'll use the padding. And then we have the option of model selection. We'll choose a model architecture based on a basic approach and use a RNN or more advanced architecture like LSTM, that is long short term memory, or GRU, that is gated recurrent units, which are effective for sequence data like text. And then we have model training. We'll compile the model, define the model architecture, and compile it with the loss function suited for classification like categorical, cross entropy, and an optimizer like Adam. And then we'll train the model, we'll fit the model on our pre-processed data. We'll evaluate and optimize it. Evaluating model performance, here use the metrics such as accuracy, precision, recall, and F1 score to assess the model. And then we have hyperparameter tuning. We'll optimize the model by adjusting parameters like learning rate, number of layers, and units per layer. And then coming to deployment. We'll deploy the model and integrate the model into the existing review processing pipeline so it can automatically classify new reviews. So let's see the sample Python code, and we'll have a basic approach for that. Here we'll import NumPy, TensorFlow, sequential, embedding LSTM, dense dropout. So embedding converts positive integers, that is indexes, into dense vectors of fixed size. And LSTM, that is long short term memory layer, that is used for learning dependencies in sequence data. And then we have dense, that is a regularly densed connected NN layer. And then we will import pad underscore sequences. And after that we have the data set and the sample text data representing customer reviews that will store in variable text. And then we have labels that has binary labels indicating sentiment, 1 for positive, 0 for negative. And now we'll start with the pre-processing of data. Here we have declared that tokenizer. We will initialize a tokenizer that will help only the top 1000 most frequent words. And then we have fit underscore on underscore text, that is update the internal vocabulary based on the list of text. It essentially creates a dictionary of word to index pairs. And then we have text to sequences that will transform each text in text to a sequence of integers. And then we have pad sequences that will ensure all sequences have the same length by padding shorter sequences with zeros up to the maximum length. And then we'll start building the model. Here we have sequential model that will set up a linear stack of layers. And then we have embedding layer that will map each word index to an embedding vector of size 64. So the input length is set to 10, that is the length of the input sequences. Then we'll start with LSTM layers. So 2 LSTM layers are added. The first one returns sequences to allow the next LSTM layer to process these sequences. And after that we have the dropout layer that applies dropout with a rate of 0.5 of the first LSTM layer to reduce overfitting. And after that we'll come to dense layer that has output of a single scalar that represents the predicted sentiment and using sigmoid activation to output a probability. And now we'll start with model compilation and training. So we'll configure the model for training and we'll use binary cross entropy as the loss function that is suitable for binary classification, and the Adam optimizer and tracks constantly accuracy as a metric. And then we have the fit that trains the model for a specified number of epochs, that is iterations or the entire data set. And then we'll predict the model, that is after training the model can predict the sentiment of the reviews in the data set. This is useful for checking how the model performs on the training data itself. So this breakdown explains each step of the coding process, detailing how the data is prepared and how the model is configured. And then we'll compile it and use for training and prediction. So it's detailed explanation should help in understanding how to implement a simple LSTM model for sentiment analysis in TensorFlow. Now moving to the question number 16. So let's start with question number 16, that is based on anomaly detection in transaction data. So the question is, you are tasked with identifying unusual transactions in a company's financial data that might suggest fraudulent activity. So what steps would you take to develop an anomaly detection model, and can you provide a sample Python code snippet to illustrate how you would pre-process the data and apply an anomaly detection technique? So we'll start answering this with anomaly detection technique. That is, anomaly detection is essential for preventing fraud by identifying transactions that deviate significantly from typical patterns. And now we'll see the structured approach to building an anomaly detection model for transaction data. We'll start with data collection and cleaning, and we'll collect all the compiling transaction data, which should include details like transaction amount, time, user ID, and transaction type. Then we'll move to feature engineering and develop features that capture the essence of transaction, such as time of day and the day of the week. And then we have data normalization. We'll use scaling techniques such as min-max scaling or standardization to ensure that the model is perfectly normalized. And then we have choosing the anomaly detection technique. So here we have to choose the technique which is effective for high dimensional data sets and works for isolating anomalies instead of profiling normal data points. After choosing the anomaly technique, we'll train anomaly identification. We'll fit the chosen model to the data, and the anomalies that would have been chosen will be those transactions that the model identifies. And after this, we come to the last step, that is review and action. Here we have manual review, that is transactions flagged as potential anomalies should be reviewed manually to confirm fraudulent activity. And then we have continuous improvement. That is, we can regularly update the model with the new data and feedback from the review process to improve accuracy. And now moving to the prediction, that is, after training the model, we can predict the sentiment of the reviews in the dataset. And this is useful for checking how the model performs on the training data itself. Now we'll see the Python code to see how you can set up this model for anomaly detection. We'll start by importing the libraries and module, and after that we'll load and prepare data. That is, we'll load transaction data from a CSV file into the Pandas data frame. And after that, we'll convert the transaction time column to date time format, which allows the extraction of additional time-based features. And after that, we'll perform feature engineering that will extract the hour of the day from the transaction time column. This feature can be important as transactions occurring at unusual hours may be indicative of fraud. And then we'll move to the normalization of data. This will apply standard scaling to the amount and hour of the day feature. This normalization process involves subtracting the mean and dividing by the standard deviation for each feature, ensuring that the feature contribute equally to the analysis and improving the performance of many machine learning algorithms. And after that, we'll start with anomaly detection with isolation forest. That's a technique. We'll initialize an isolation forest model with 100 trees, that is n estimators equal to 100, setting the proportions of outliers, that is contamination, to 1% of the data. So this parameter is crucial as it influences the threshold of marking an observation as an anomaly. Then we'll fit the model to the scaled amount and hour of the day data and predict the anomaly status for each transaction. And then we'll start with filter and display anomalies. We'll filter out transactions identified as anomalies, that is anomaly equal to -1. We'll display these transactions which can be reviewed manually to determine if they represent actual fraudulent activity. So this code snippet provides a systematic approach to detecting anomalies in transaction data, leveraging the isolation forest algorithm's ability to handle complex and high-dimensional dataset effectively. So the pre-processing steps ensure that the data is appropriately formatted and normalized for optional model performance. So this was all about question number 16. Now moving to question number 17, and that is based on integrating machine learning models into web applications. And your question is, you have developed a machine learning model to predict real estate prices based on various features like location, size, and amenities. How would you integrate this model into a web application to allow users to get real-time price predictions? Can you provide a sample Python code snippet to illustrate how you would prepare the model for integration and handle user requests? So starting with the approach, that is integrating a machine learning model into a web application, this will involve several steps to ensure the model is accessible and perform well in a live environment. So here's how you can approach this task. We could divide into steps, and we'll start with number 1 step, that is model preparation. We'll finalize and save the model. So once your model is trained and validated, save it using a format that can be easily loaded into a web application. So Python's pickle module or TensorFlow's save model format are commonly used for this purpose. Then we can use web application backend setup. For this, select a suitable web framework. So Flask is popularly known for its simplicity and effectiveness in integrating Python-based machine learning models. And after that, we'll develop the API. After developing the API within your Flask app, that you can receive user inputs for model features, load the model, make prediction, and return the result. And after this, we'll develop the UI. We'll design a user-friendly interface. We'll create a simple and intuitive UI that lets users input the feature like location, size, and submit them for prediction. And after that, we'll move to the deployment phase. We'll use a cloud platform like Heroku, AWS, or Google Cloud to deploy your Flask application. And then we have the maintenance and updates. We'll monitor and update regularly for the performance and use the model as needed based on user feedback. So now moving to the Python code and see how this model can be created. So here we'll start importing the libraries and module, and we are using Flask, Pickle, and JSONify. And we will start with app initialization. We'll initialize a new Flask web application. That would be a special variable which gives Python files a unique name to differentiate between them when they are imported into other scripts. And after that, we'll load the model. So loading a pre-trained machine learning model from the file system. So this model is assumed to be saved in the same directory as this script. So the model is loaded in RB mode, which stands for read binary. And after that, we'll move to API route and prediction function. So we will define an API endpoint at predict that listens for post request. This is the URL that the front end of the web application will call to send data to the backend. And after that, we'll start with predicting the function. And here we have extract features that retrieves data sent into the JSON format from the post request. That is request.get_JSON, and the force we have set it as true here. And forcefully formats the request data into JSON, ensuring compatibility. And then we'll extract the relevant features, that is location, size, and amenities from the JSON object and store them in a list as expected by the model. And after preparing the features, we'll make the prediction. We'll use the loaded model to make a prediction based on the provided feature. And then we have the return prediction method. Here we will convert the prediction result into JSON format using JSONify and send it back to the client, and this will ensure that the response can be easily handled by the client application. So this was all about the question number 17. Now moving to the question number 18, that is based on analyzing. And now we'll move to the question number 18, that is based on analyzing geospatial data. And your question is, you are tasked with analyzing geospatial data to help a city improve its public transportation system. The data includes GPS coordinates of bus stops, ridership numbers, and traffic patterns. What steps would you take to analyze this data, and can you provide a sample Python code snippet to illustrate how you might visualize bus stop location and ridership? So you can start answering this question that geospatial data analysis can provide critical insights into how effectively a public transportation system serves its city and guide improvements. And there's a detailed approach for this, and we can start with data preparation. And in this, we will do data collection and data cleaning. And after this step, we will move to the next step, that is exploratory data analysis. And in this, we will have statistical summary, we will generate descriptive statistics, and then we have correlation analysis. And after moving that, we have geospatial visualization, that is mapping bus stop. We'll plot the locations of bus stop on a map to visually assess their distribution across the city. And after that, we have heat maps that will create ridership data to identify hotspots and areas with potential service gaps. And after geospatial visualization, we'll move with spatial analysis. We have proximity analysis that will analyze the proximity of bus stop to key areas like commercial centers or residential areas. And now moving to the fifth step, that is optimization and recommendation. So we'll have a route optimization that will suggest modifications to route based on traffic patterns and ridership demand. And the policy recommendations that will provide actionable recommendations for improving bus frequencies. Now moving to the sample Python code where we can define this model and use it accordingly. And here we will start importing the libraries and modules. And here we'll start with importing GeoPandas and matplotlib.pyplot. And after importing, we'll start with data loading. So we will declare a variable bus_stops, and load the bus stops data from a shapefile. So shapefiles are popular geospatial vector data formats for geographic information system software. And then we have the ridership that will load ridership data from a CSV file which includes columns for longitude, latitude and ridership levels. And after that we'll create geodata frame that will convert the ridership data frame into a geodata frame. And this step involves creating a geometry column from the longitude and latitude columns. And then we have the plotting one. Here we will plot the graphs that would be figures and axes and create a figure for the single subplot with a specified size that is 10 cross 10 inches. And then we have city underscore map.plot. It is assumed that there is a base map of the city loaded as a geodata frame named city map. This is plotted first with the light gray color to serve as a background for the other layers. So this was all about question number 18. Now moving to question number 19, that is based on predictive maintenance using machine learning. And your question is, you are tasked with developing a predictive maintenance system for a manufacturing plant that relies heavily on automated machinery. So the data available includes machine operational parameters, maintenance history, and failure incidents. What steps would you take to develop a predictive model, and can you provide a sample Python code? So you can start with predictive maintenance that is essential in manufacturing as it helps prevent equipment failures, reducing downtime and maintenance cost. And here you would have a detailed approach or predictive model for this, starting with data collection and integration. Then you can do EDA, that is exploratory data analysis, and then we can perform feature engineering and then move to data pre-processing task, and then the selection model and training. And after that we have model evaluation and deployment technique that we can do for the model using appropriate metrics such as precision, recall and F1 score. So this was all about question number 19. So now move to question number 20, that is based on personalization using machine learning. And your question is, you are tasked with developing a machine learning model to personalize content recommendations for users on a media streaming platform. The data available includes user demographic details, viewing history and ratings. So what steps would you take to build a model for personalized recommendations? And can you provide a sample Python code for that? So you can start answering this with creating a personalized recommendation systems. This would be essential for engaging users by providing content that is relevant to their interest. And there will be a systematic approach or personalized content recommendation. We'll start with data collection and integration. And after that, we'll perform EDA, that is exploratory data analysis. And then we have feature engineering. In this, we'll interact features, and the temporal features will include time-based features to capture trends and seasonality in viewing behavior. And then we'll select the model, that is by collaborative filtering and hybrid models. And then we'll train the model and validation and implement and monitor them. And after that, we'll deploy them.
And with that, we have reached the end of the session on Data Science Full Course for Beginners. If you have any doubts or questions about this video, then let us know in the comment section below, and our team of experts will be happy to help you as soon as possible. Until next time, thank you and keep learning. Stay tuned for more from Simplilearn.